Welcome to Lecture 1. In this introductory lecture, I will outline my teaching philosophy for the course and outline my course objectives. We will then discuss fundamental physical quantities used to define physical systems and review calculus concepts used in the course. This lecture will be broken down into 3 pieces. 2 will be handled by these videos, which includes the course organization and key measurements that we will build on to describe physical systems. The third, a calculus review section, will be presented by selected videos from the Khan Academy. I will break down this course into 3 major sections: thermodynamics, equilibrium, and kinetics. It is interesting to note that the order the material will be presented in is the opposite as in general chemistry. In this course we will start with the foundational concepts and build applications from them. This order is deliberate in the context of my 3 main goals. The first, illustrate the connection between math and science. I don't want you to always fall into a mindset of finding what is the correct equation to solve a problem. Instead, I want you to approach the material from a more intuitive standpoint where you let the math describe the science. 2. Demonstrate when theories are valid and when they fail. Theories are only valid when the assumptions that make them up are true. It is always important to know when these assumptions are no longer valid so that you know when the model no longer applies. 3. Push you to think of physical systems in the context of the foundational concepts and their applications. In this course, we will develop ideas that will then be used on contrived examples in order to illustrate their properties. However, I want you to start looking at the world around you using the concepts used in this course in order to appreciate how far-reaching these principles are. Now, we will turn to fundamental measured quantities that will be used as a starting point to describe thermodynamic quantities. The first is force, which is a directed push used to accelerate a body. What is shown on the slide is Newton's second law, the sum of the forces are equal to the mass times the acceleration, and a typical free body diagram on a block on a ramp. We will not be solving these types of problems, but it illustrates some of the forces that act on everything in our macroscopic world. Work, however, is something that we'll be spending some time on. It is defined as the energy used to apply a force to an object over a distance. Its units are in Newton meters or joules. As one example, suppose you wanted to lift a 1 kilogram box 1 meter. The work that is done is equal to the force necessary to lift the box, being 1 kilogram times the acceleration due to gravity, 9.81 meters per second squared, and that is multiplied by the distance traveled, 1 meter. Therefore, the work done to the box is 9.81 joules. Now, the energy of an object is its capacity to do work. In other words, work is a change in energy. There are 2 types of energy, kinetic or potential. Just like their names suggest, kinetic energy is the energy in a body due to its motion, while potential energy is the energy of a body as a result of its position and forces acting on it. For example, the box in our previous example gained 9.81 joules of potential energy because it was raised 1 meter. That means that it has 1 meter to fall while being pulled by gravity. Energy cannot be created or destroyed. It can only be changed from one form to another. By doing work to a system is one way to convert energy from one form to another. Pressure is a measure of force exerted over a defined area. There are 2 ways to increase the pressure, being increase the force, or decrease the area that the force is applied over. This idea is important in many places, and the conceptual example below illustrates one instance. If you find yourself on thin ice, what is the best way to avoid falling in? It would be to reduce the pressure of your weight on any one spot of the ice to avoid damaging it. When you're standing, the area that your weight acts over is that of your feet. If you lie down, the area goes up, since the force is now distributed over your entire body. Therefore, the pressure you exert goes down. Pressure can be measured in many different units. In SI, the units are pascals, which is defined as a Newton per meter squared. Another common unit for pressure is the atmosphere. When performing calculations with pressure, be careful that you are aware and consistent with your units to avoid making unnecessary mistakes. The work performed by a system can be determined from a variety of inputs. For example, we will soon use the fact that pressure times a change in volume determines the transfer of energy, or work, of an expansion or compression of a gas. This relationship is seen by doing the unit analysis presented on the right. Pressure is in newtons per meter squared, and volume is in meters cubed. We can divide out the meters squared and be left with newtons per meter, or joules. As a physical picture of this is depicted in the figure on the left, the y-axis is pressure and the x-axis is volume. The pressure remains constant as the volume expands from some initial volume to a final one. One could imagine that as the volume expands, it pushes a weight, which is how one might capture the work performed by the expansion. The final quantities related to energy that will be introduced is heat and temperature. Like work, heat is also a transfer of energy. However, heat relies on the chaotic motion of particles as its conveyance of energy. The temperature of an object is a quantity that determines the direction of the transfer of energy due to heat. So if a block at 0 degrees Celsius were to be put in contact with an identical block at 100 degrees Celsius, the difference in temperature indicates that the energy is transferred as heat from the 100 degrees Celsius block to the 0 degrees Celsius block. We will almost exclusively use the Kelvin temperature scale, which is defined as the temperature in Celsius plus 273.15. So the normal body temperature of 37 degrees Celsius converted to Kelvin is 310.15 degrees Kelvin. The final 3 slides are focused on how we quantify the amount of a substance. The two presented here are the molar concentration and the molality, which will both appear in the course. The molar concentration is the amount of a substance in moles per volume of solution. Note that the solution includes both the solute and the solvent. The molality is the amount of a substance in moles per mass of solvent. Molality is a more constant measure of concentration when there are changes in temperature involved in a process. When the temperature changes, the mass of a substance changes very little. However, the volume of a substance can change dramatically with temperature changes, which will affect the molar concentration much more. Another way to quantify the amount of a substance is to express it using its mole fraction. This is the fraction of the moles of a given substance relative to the total number of moles in the mixture. So here's a quick example of which includes molality and mole fraction. And so in this example, what we're trying to calculate is the mole fraction of glucose that's inside a solution of glucose in water, where we note that the units here are given to us in terms of molality. We have 0.14 moles per kilogram of water of glucose inside our solution. So the first thing that we're going to recognize is that we have 1 kilogram of H2O, and inside that we have 0.140 moles of glucose. And so when we calculate the mole fraction, then what we're doing is we're relating then the number of moles of this 1 kilo of H2O to this 0.14 moles of glucose. So part of our solution is already done. We already know if we're going to be calculating our mole fraction of glucose. Well, we know already that we have the number of moles of glucose, and that's going to be on top, and that's just going to be 0.14. So the only thing we need to calculate is total moles to be able to finish this calculation. So let's calculate the number of moles of water that we have in our system. So we know that we have 1 kilogram of water, and inside 1 kilogram of water we have 1,000 grams. We know that the molar mass of water is 18.02 grams for every 1 mole of water. And so if we do this multiplication, then what we're left with is 55.49 grams, or sorry, 49 moles of water in 1 kilogram of water. So now we know, or now we can easily calculate the total number of moles. X of, or the mole fraction of C6H12O6 in our solution. We still have 0.14 moles on top. And on the bottom what we have is 55.49 plus 0.140. So again, we have the total number of moles of the water and the total number of moles of the glucose. So this is total moles on the bottom. And on top we have the number of moles of glucose, because we're trying to find the mole fraction of glucose in the total solution. And so if we solve for this, what we end up with is 2.52 times 10 to the minus 3. Note that there are no units with this because I'm dividing moles by moles, and so in the end I get a unitless quantity. The final quantification of a given substance we will cover utilizing its amount in moles is the molar volume. This is the volume a substance occupies per mole of molecules. The table on the bottom left shows a list of gases with their molar volumes at standard ambient temperature and pressure, being 298.15 degrees Kelvin and 1 bar. Notice that many of them are 24.8 liters per mole, with a couple of exceptions. For example, argon has a molar volume of 24.4, and carbon dioxide has a molar volume of 24.6. We will discuss these differences later. For now, it's okay to simply note what the molar volume is, and that many gases have similar molar volumes. This course will help you understand the macroscopic world around you in relation to the chemistry and physics present in everyday life. In this preparation lecture, we discussed my goals, expectations, and teaching philosophy for the course. Keep in mind that you will get out of this what you put into it, so apply yourself in order to get your maximum benefit. We also defined key concepts such as work, pressure, heat, and temperature, as well as how substances are quantified using measures of concentration and mole fraction. Please read the syllabus for more information on the specifics of the course, and watch the calculus-related material in order to be fully prepared for the preparation assignment. Welcome to Lecture 2. In this lecture, we will examine fundamental properties of gases in order to define the ideal gas law. Then, we will analyze when it fails and how different models might do a better job in quantifying the properties of gases. One everyday application of these models is characterizing weather patterns. Our climate is determined by the pressure and temperature of gases in different regions. The information in this lecture will allow you to better understand how our climate works. This lecture will be broken down into two pieces. In the first part, we will examine the kinetic model of gases. This model is what defines the ideal gas law, which we will use throughout the course. We will also define Dalton's law, which is very important when dealing with mixtures of gases. The second part of the lecture will focus on real gases. When the interactions between gas molecules is important, the kinetic model no longer applies. The van der Waals equation of state and the virial equation of state takes additional intermolecular interactions into account in order to better predict the properties of gases. The learning objective for this lecture focuses on understanding these descriptions of gases, but also analyzing when they fail. It's important to always understand the underlying principles of the model that you are applying so that you know when it is no longer appropriate to use. The first gas model we will examine is called the kinetic model of gases. It is a very simple yet powerful model. It has three assumptions. First, a gas consists of molecules in ceaseless random motion. Second, the size of molecules is negligible in the sense that their diameters are much smaller than the average distance traveled between collisions. And three, the molecules do not interact, except during collisions. This assumption that the molecules do not interact outside of collisions is, of course, not consistent with reality. We will come back to that later when we improve the model. For now, we will adhere to these three assumptions since what is derived from them is the ideal gas law. Gases that we apply the kinetic model to will be called ideal gases. For the majority of systems, it is very reliable, and we will be using it throughout the course. Since we are assuming that the molecules do not interact except during collisions, then there is no potential energy in the system. This means that all the energy is kinetic energy. Therefore, the faster the molecules move, the greater the total energy of the system. This means that knowing the velocity distribution of a sample of gas is very important if we want to know the total energy of the system. This was characterized by Maxwell, where the probability of finding a given gas molecule at a given speed, denoted as being between v and v plus dv, is determined by rho, where rho is equal to 4 pi times m over 2 pi rt raised to the power of 3 halves times v squared times the exponent of negative m v squared divided by 2RT, where capital M is the molar mass, R is the gas constant, and T is the temperature, and V is the velocity. As you can see in the figure, as the temperature increases, the distribution shifts so that it is more likely that a given gas molecule will be traveling at a higher speed. This is what we intuitively would expect, and this tells us that there is a relationship between the temperature of the gas and the total energy of the gas. Now that we have a definition of the velocity that a sample of gas may have, let us now define what is the pressure that that sample of gas will exert on a container. The strategy that we will use to find that pressure is according to the 4 points that I have written here, where the first point is we will first find the change in momentum for one molecule hitting a wall. Then the second one will be we will find the time between each collision with that wall. The reason we're going to find those two quantities is that so we can determine the force that each molecule generates, and the force is calculated by the change in momentum over the change in time. And then once we've determined that force, then what we're going to do is then find the pressure by dividing that force by the area of that wall. So based on these 4 points, we're going to determine what is the pressure of a gas according to the kinetic model of gases. So let's calculate the first point. The first point is we're going to find the change in momentum for one molecule hitting a wall. In this case, to simplify matters, we're going to operate in one dimension. So let's pretend I have a cavity that is of length L, and I have some particle traveling with speed Vx, in this case initially heading to the left. And what it's going to do is it's going to strike this far left wall. When it hits that wall, it's going to rebound elastically, since according to the kinetic model of gases, all collisions are elastic, meaning that no energy is lost. So when it strikes that wall at speed Vx, it's going to rebound, where it's going to travel to the right then with speed Vx. What that means is that my change in momentum is just going to be the final momentum minus the initial momentum. Well, the final momentum is just going to be m times Vx, since Vx is now moving to the right. And from that I'm going to subtract off m times negative Vx. And so what that leaves me in the end is that a change in momentum is going to be equal to mvx minus Vx, or in other words, 2m Vx. Let's now determine number 2. Let's find the time between each collisions with that one wall. So in this case, we're still looking at our one-dimensional cavity with length L, since we're still looking at the case that we just had above. Let's pretend that we have the case where the particle has just struck the wall and it is just rebounded, so it's now traveling to the right with speed Vx. Now the time it takes for it to come back and strike this left wall again is essentially determined by this speed Vx, and so it has to travel all the way to the one end, so it has to travel a length L, and then it's going to travel all the way back again, that same length L. And so what I can write for an equation is that I can say, well, the speed Vx, well, that's going to be equal to 2 times L divided by the time it takes for it to travel 2L. Basically, the time it takes to go from one end of the cavity all the way back to the beginning. And again, that's what's going to give you my speed Vx. And so if I rewrite this, then I can calculate the difference in time it takes for it to travel in between those two walls, or for basically to travel from the wall that it just struck all the way across the barrier and then all the way back again, to be equal to 2 times L divided by its speed, which again never changes because it always deals with elastic collisions. Alright, so now that we have the change in momentum due to one particle, and we have the change in time, or the difference in time it takes for it to strike the same wall again, we can now determine the force that one molecule generates, which is just again delta P divided by delta T. So I can just substitute in these two values that we just calculated, 2mvx divided by 2L divided by Vx. So in this case, my 2's cancel out. My Vx, which is on the bottom, becomes multiplied. So I get m Vx squared divided by L. And so that is the force generated by one particle. Now, of course, a gas isn't just made out of one particle. A gas is actually made up of many particles put together. And so what we're going to do is define this now for n moles of gas. We're still going to do this in 1D for the time being. But there are two things that we're going to change. The first one is that the mass that we have here, when I have for one particle, we're going to rewrite that for n moles of gas. So the mass of the gas, which would be the value that I'd be plugging into there, well, what's that equal to is n, which is the number of moles of gas, times the molar mass of the gas. So m is the molar mass. The second piece of information that I'm going to substitute in is that this Vx squared, well, that's the velocity in one dimension, in this case the x direction, of the one particle of gas. But of course, as we just saw in the previous slide, we know that there's a distribution of speeds that a sample of gases is going to have, and that's according to Maxwell. And so not all the gas particles are going to move at the same speed. So that means that what we need to do is that what we're going to take then is the average of the squares of the speeds. We're going to take essentially, since the forces relied on Vx squared, what we're going to do is we're going to take the average of Vx squared to then define then the average force that is exerted on that of the walls of our chamber. So if we put these two changes into the force expression that we have written above, what we'll get is then the force of a sample of gases is n times capital M times the average of the squares of the speeds divided by L. And the thing again that I want to stress is that the average of the squares of the speeds is not equal to the average of the speeds squared. These are two different quantities. And again, I'm just reiterating that the value that I'm writing in here is that we're taking the average of the squares of the speeds, because when we talked about one particle, it was the square of that speed, and that now when we talk about an ensemble of particles, we have to take the average of that quantity. And so the average of that quantity is the average of the squares of the speeds. So now let's extrapolate this to 3 dimensions. The one thing that we can say is that since the random or the motion of the particles in 3 dimensions and in 1 dimension it was still random, then that means then that if I were to say the average of any of the directions, and really it's that in any direction anyways, we could say that the average in any of the 3 Cartesian directions are going to be all the same. And this is because the motion of particles is random. The second thing that we can say, and this is according to Pythagoras, is that it's of course always easier to measure the total speed than it is to measure any one component of the speed. And that according to Pythagoras, I can also write that the average of the square of the speed is equal to the summation of each of the components. And so with these two expressions, what I can end up writing then is that the total speed, the average of the speed squared, in this case is equal to 3 times any one of the components. And that's just because these 3 components are all the same. And so really I've got the same component plus the same component plus the same component, which gives me 3 times any one of the components. And I'm choosing to write it as Vx simply because in my expression before I have Vx. I have the x component written in. And so what that means is that I can take that expression for force, and since here I have it written in 1 dimension, now I can write it in 3 dimensions. And so really I can write the force is equal to the number of moles times the molar mass of the gas times the average of the speed squared divided by 3 times L. And all I did there was I just took this 3 and just moved it to the other side. I divided both sides by 3. And that's why the 3 is on the bottom. And that's how I get a measurement of force in 3 dimensions. Now this quantity, the average of the velocity squared, this actually has a special name. What I can call this instead is, I can call it the root mean squared. And in this case, since I'm talking about this, the average of this velocity squared, then it's the root mean squared squared. And so the actual absolute definition is VRMS is equal to the square root of the average of the velocity squared. And that's what gives me the root, meaning the square root, the mean being the mean of the value, and the squared, meaning that it's the square of the velocity. And so when I rewrite this expression, then I can rewrite it as the force is equal to the number of moles times the molar mass times the root mean squared divided by 3L. So that finishes point number 3, which is determine the force. And in this case, again, we have that in 3 dimensions now. So our last and our final point that we need to do, or that we were following with our strategy to find the pressure, is to say, well, the pressure is equal to the force divided by the area. Well, now that I have an expression for the force, which is the number of moles times the molar mass times the root mean velocity squared divided by 3 times L, and with that I'm going to multiply by 1 over A, or I'm going to divide by the area. And in this case, if I have the length of my box times the area of the face, and if I were to draw basically a picture of that, then there is the area and what I'm doing is I'm drawing a box. Then the area of that is just the area of that face, where the length of the box is the length, which is what I drawn before as my length. But the area now then defines, basically, if I have an area and I multiply it by a length, that gives me a volume. And so in the end I can combine the L and the A, and basically then I'm just defining the area of, the volume of the box which is containing my gas. And so this completes then the derivation for the pressure of an ideal gas in a box. Now, of course, this solution for the pressure of a gas inside a box is a little bit unsatisfactory because we have this root mean squared, velocity squared term. And so what we'd like to do is to express this in something that's a little bit more intuitive, and we want to try to understand sort of the pressure of a gas in a box. We want to relate it to, in this case, we're going to relate it to the temperature of the gas in the box, which is something that's, like I said, a little bit more intuitive to be able to measure. Now, fortunately for us, we can go back to the Maxwell distribution of speeds, and what we saw in that expression was that there was a relationship, or if we wanted to find the distribution of speeds, that was in relation to the temperature of the gas. So what we can do is we can go back to that Maxwell distribution of speeds, and we can say, well, VRMS squared, or the average of the velocities, or the average of the square of the velocities, well, that can be determined by the Maxwell distribution of speeds. And how that happens is that because the Maxwell distribution of speeds gives us a probability of finding of a particle traveling at a specific velocity, that if we wanted to find the average of that, then what that's equal to is the value itself. So in this case, since we're finding the average of the speed squared, then it's the speed squared times the probability of finding the particle at that speed. And in this case, I'm going to do the integral, because if I'm going to find the average of something, I have to basically sum over all the potential values that this thing can take. And so if I follow through with this integral, I have 0 to infinity. Since I have to calculate all the speeds, I have the value that the speed can take, that's the v squared. The probability that it can be any speed, well, that's 4 pi capital M over 2 pi r times t to the power of 3 halves. I have another v squared times the exponent of negative m v squared over 2RT dV. Now if I were to simplify this expression, the average of v squared, I can pull out a bunch of constants. I would get 4 pi capital M over 2 pi RT to the power of 3 halves. I got my integral of 0 to infinity. What I'm left with is v to the power of 4 times the exponent of negative capital M v squared divided by 2RT dV. And so what I have here is an integral where if I were to do this explicitly, I'd have to do integration by parts to at least with about 4 iterations because of this v to the power of 4 term. And this is something I would never expect you to do on an exam, and so I'm going to turn to Wolfram alpha, and I can basically let it determine the solution to this definite integral. And the solution to this definite integral is actually something very simple. It's just 3RT over capital M. And so what I'm going to do then is I'm going to take this expression, this 3RT times capital M, and I'm just going to plug it right in for my VRMS squared, just because my VRMS squared is the same as the average of the velocity squared. And so what that allows me to do is then to write my pressure as N times capital M over 3 times V. And with that I'm going to multiply by 3RT divided by capital M. And with that I can cross off the capital M's and the 3's, and what I'm left with is nRT divided by V, or in other words I get PV is equal to nRT. And so this astounding relationship that we've just determined is the ideal gas law, and how we found it was simply just by applying the kinetic model of gases, where again we had 3 assumptions. Particles are basically traveling in random motion. We have the fact that their diameters are so small that it takes a long time for them to collide with other things, and that their diameters are much smaller than the distance that they travel before they collide with something else. And finally, the third one is that we have particles where they don't interact with each other until they collide with each other. And based on just on those 3 simple assumptions, as well as understanding the distribution of speeds that a sample of gases can have, we can then determine the ideal gas law. As was just shown, the kinetic model of gases can be used to derive the pressure exerted by a sample of gas. If this is combined by the square of the root mean squared velocity of the gas calculated from the Maxwell distribution of speeds, then we can get the ideal gas law, which is equal to PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, T is the temperature, and R is the gas constant. The gas constant has many values depending upon the units. Pay very close attention to the units of the value of the gas constant you use when performing calculations. Using the wrong value of R is a common mistake when solving problems, and it depends on the units of the other values plugged into the ideal gas law. Pay special attention to the units of the pressure, since it will typically be expressed in either kilopascals or atmospheres, and both have their own gas constant. Frequently, multiple gases will be present in the specified volume. To account for this, we will employ Dalton's law, which states that the pressure exerted by a mixture of ideal gases is the sum of the pressures that each gas would exert if it were alone in the container at the same temperature. This means that we can use the mole fraction times the total pressure in that volume to determine the partial pressure of the specified gas. The figure on this slide is what Dalton's law would look like visualized. This example has a volume with 3 gases in it. The total pressure of this chamber is the same as the sum of the pressures of the 3 gases if they were separated into 3 separate containers with the same volume. Dalton's law is a concept that we will frequently use in this course. So now that we've defined Dalton's law, let's now apply it to a simple example that relates to the real world. We have these 2 problems where the first one is calculate the mole fractions of N2, O2, and argon in dry air at sea level, given that 100 grams of air consists of 75.5 grams of nitrogen, 23.2 grams of oxygen, and 1.3 grams of argon. And then based on those answers, meaning based on the mole fractions of those three constituents of dry air, we're then going to calculate what is the partial pressure of each of those constituents if the total pressure is 100 kilopascals. So let's start with the first point, which is calculate the mole fraction of each of these constituents. So the first thing we need to determine for the nitrogen, the oxygen, and the argon is the number of moles that each of those masses corresponds to. So the moles of N2, well, that's equal to 75.5 grams divided by the molar mass. So 1 mole of N2 is equal to 28.02 grams of N2, and that equals 2.69 moles. The moles of O2, well, we have 23.2 grams of O2 divided by the molar mass, 1 mole of O2 divided by 32.00 grams of O2, and that's equal to 0.725 moles of O2. And then finally for argon, the moles of argon, well, that's equal to 1.3 grams of argon. Divide that by the molar mass, 1 mole of argon, 39.95 grams of argon, and that's equal to 0.033 moles of argon. And so then to determine now the mole fraction, we need to know what is the total moles that exist in this sample of gas. And so that's just the summation of these three pieces. So if I add the 2.69 plus 0.725 plus 0.033, then the total moles is going to be equal to 3.448. Now to calculate the mole fraction, all we need to do is just take any one of these individual numbers. So in this case we've got the 2.69 moles of N2, and we're just going to divide it by the total number of moles, the 3.448. And we do that for each of these cases. So that means the mole fraction of N2 is just simply equal to 2.69 divided by 3.448, and so that's equal to 0.78. The mole fraction of O2, well, that's equal to 0.725 divided by 3.448, and that's equal to 0.21. And finally, the mole fraction of argon, that's equal to 0.033 divided by 3.448, and that's equal to 0.010. So that answers question 1. So now let's tackle problem number 2. Number 2 is just if the atmosphere is 100 kilopascals, or if the pressure of all three gases combined is 100 kilopascals, what is the partial pressure of each of the constituents? Well, we already saw on the previous slide that if we multiply the mole fraction of one of the constituents by the total pressure, then what we end up with is the partial pressure of that constituent. And so I've written this in the context of nitrogen, but I'm going to just replicate this for the other two gases. But in this case, we already know the mole fraction of nitrogen is 0.78. The total pressure is 100 kilopascals. And so what that gives me is then the partial pressure of the nitrogen gas in this sample. And so that means then the partial pressure of nitrogen is equal to 78 kilopascals. I do the same thing for oxygen. So the partial pressure of oxygen is equal to the mole fraction of oxygen times the total pressure. That means then I'm going to multiply 0.21 times 100. So that means the partial pressure of oxygen is equal to 21 kilopascals. And finally, the partial pressure of argon is equal to the mole fraction of argon times the total pressure. That means that I'm going to multiply 0.010 times 100, and that means then the partial pressure of argon is equal to 1 kilopascal. The ideal gas law works very well for many situations. However, it's important to understand when it fails so that improved models can be used in those situations. To do that, we need to better quantify how often molecules collide. Let's start by first defining the collision cross-section, denoted as sigma. This is the area, in meters squared, around a molecule where if the center of a different molecule enters, they will collide. In the image, the blue circles are a region that signifies the space that a molecule occupies. The yellow concentric circle shows the collision cross-section. Since the center of the second blue circle has entered the collision cross-section of the first, then the two have collided. Still within the context of the kinetic model of gases, it is possible to use the collisional cross-section to define two more quantities, the mean free path and the collision frequency. The mean free path is the average distance a particle travels between collisions. It can be calculated by r times t all over root 2 times Avogadro's number times the collisional cross-section times the pressure of the gas. The collisional frequency is simply the average rate of collisions. It's determined by root 2 times Avogadro's number times the collisional cross-section times the average velocity times the pressure of the gas divided by the gas constant times the temperature. If these two quantities are multiplied together, then we get the average velocity. Now that we have these basic quantities relating to collisions, we can quantify when the ideal gas law no longer applies. Contrary to what the kinetic model of gases assumes, which is what the ideal gas law is based on, we know that molecules do interact with each other when they are not in contact with one another. One of the more significant contributions to these interactions are governed by van der Waals interactions, which is based on electronic forces that arise from instantaneous dipoles in the molecules. These become much less significant the further apart molecules are from each other. So, in general, we can treat gas as ideal when the mean free path is much larger than the diameter of the molecule. In other words, if the distance a molecule can travel before it hits another molecule is much, much larger than its diameter, then it means that the van der Waals forces are typically very small at any given time, and can therefore be neglected. When the mean free path is similar to the diameter of the molecule, then these electrostatic forces are much larger, and must be taken into account. Van der Waals forces can both be attractive and repulsive. The curve represents a typical van der Waals potential energy diagram based on the intermolecular separation of two molecules. When the curve is above zero, that means that the molecules repel each other, and when the curve is below zero, then the molecules attract each other. What we see is that when molecules are very close, they repel, and at a certain distance they begin to attract one another. There is a minimum which defines the optimum distance that molecules would like to be away from each other. As the distance increases between the molecules, the intermolecular forces get smaller and smaller until it is negligible, which is what we intuitively would expect. These intermolecular forces become important when the conditions are such that the gas should condense to a liquid or a solid. This means that, depending on the gas, below a certain characteristic temperature, the ideal gas law no longer holds. The figure in this example is a phase diagram for carbon dioxide. There is a gas region, a phase transition region where both liquid and gas are present, and a liquid region. Each line represents the pressure versus volume relationship at a given temperature. These lines are called isotherms, meaning that the temperature is held constant. As the temperature cools to 31.1 degrees Celsius, the ideal gas law accurately describes the system less and less. You will notice that for the isotherms at temperatures less than 31.1 degrees Celsius, the pressure of the gas increases as the volume decreases until they hit the region outlined by the vapor and liquid phase. In this region, the plot, both liquid and gas are present, and as the volume decreases, the gas condenses completely to a liquid. This is denoted as a horizontal line, since as the gas condenses to a liquid, it requires a lot less space, meaning that the volume can drop without the pressure changing. Then, in the liquid region of the plot, the pressure can increase significantly on the liquid without a large decrease in volume. One interesting property of the liquid-gas phase transition is that if one follows a specific temperature-pressure program, the substance does not need to go directly through a phase boundary. As shown in this phase diagram for carbon dioxide, plotted for the pressure of CO2 as a function of temperature, The parabolic-shaped line that denotes the boundary between the liquid and the vapor phase ends at something called the critical point. Pretend that we have a sample of CO2, initially in the liquid phase. If the temperature and pressure are increased, such that it stayed a liquid past the critical point, the CO2 becomes a supercritical liquid. It is neither a gas or a liquid, but a combination of both. We can then lower the pressure so that the CO2 would become a gas. By going around the critical point, a supercritical fluid can be used to dry fragile structures, since no hard phase change occurs. It can also act as a non-toxic, high-pressure solvent which can permeate every pore to extract organic compounds. CO2 is the most common supercritical liquid since the critical point occurs at 31.1 degrees Celsius. Dutch physicist Johann van der Waals proposed changes to the ideal gas law to account for real gas interactions. He accounted for the repulsive interactions on the pressure by specifying that some of the volume of the container is occupied by the molecules themselves. This decrease in volume scales linearly with the number of moles of gas. He also accounted for the attractive interactions with a term that he subtracted from the repulsive pressure term, since the attractive interactions would tend to draw molecules closer together and reduce the pressure of the system. This attractive term is proportional to the concentration of the gas. The van der Waals equation of state is defined by the pressure being equal to nRT divided by V minus NB minus A times N over V squared, where N is the number of moles, R is the gas constant, T is the temperature, V is the volume, B and A are both constants that are dependent upon the gas. If we plot the van der Waals equation of state, we get an image that looks similar to the one we saw for the CO2 isotherms. There are isotherms that are colored in blue. These ones have a temperature higher than the critical temperature of the gas. Recall that the critical temperature is the temperature at which the critical point occurs. As the temperature increases away from the critical temperature, these isotherms will look increasingly ideal. For isotherms with temperatures less than the critical temperature, those drawn in red, there is a decrease in pressure as the volume drops. This is not physical. Instead, we apply the Maxwell equal area rule to denote the phase change. To apply this rule, we draw a straight line across the isotherm, such that the area above is the same as below the line. This is how we regain the experimentally observed pressure versus volume plot seen previously. Regardless of the obvious unphysical prediction by the van der Waals equation of state, it more accurately predicts physical systems than the ideal gas law. The green isotherm is when the temperature is set to the critical temperature. At the critical pressure, denoted at 1, since the pressure and volume are scaled to the critical values, the isotherm goes flat, denoting that the gas went through the critical point. The flat inflection point at the critical point means that the derivative and the second derivative of the van der Waals equation of state can be set to 0. This allows us to determine the constants A and B for each gas based on its unique critical point. In order to simplify this process, the van der Waals equation of state can be rewritten in terms of molar volume. We can then solve the critical volume, temperature, and pressure in terms of the parameters A and B. Of course, this process can also be reversed if the critical values are known in order to find A and B. For both the ideal gas law and the van der Waals equation of state, we have been quantifying how the pressure and volume change at a given temperature. Compressibility is an empirical measurement of how the pressure of a gas changes as the volume changes. For example, the plot illustrates the compressibility of nitrogen gas at different temperatures. Note that the compressibility of an ideal gas is 1 for all pressures. If a gas's compressibility is larger than 1, it means that the pressure is higher than ideal behavior for a given set of conditions, while values less than 1 means that the pressure would be lower than what is predicted by ideal behavior. Remember that ideal behavior means that there are no intermolecular interactions. So, being larger than 1 signifies repulsive forces dominate, and being less than 1 means that attractive forces dominate. Therefore, it should be no surprise that as the pressure increases, gases tend to have compressibilities higher than 1, which reflects that the molecules are being forced very close together and repel each other. Also note that all the lines converge to 1, or ideal conditions, at low pressures, reflecting when all the gases exhibit ideal behavior. The ideal gas law can be rewritten to include compressibility. In this case, Z is equal to P times the molar volume divided by R times T. When Z is equal to 1, the gas is characterized as ideal. When the gas is not ideal, the compressibility is fit according to a series expansion using either the molar volume or the pressure. Using the molar volume, the series goes 1 plus B over the molar volume plus C over the molar volume squared plus D over the molar volume cubed, etc. While for the pressure, the series goes 1 plus B prime times the pressure plus C times the pressure squared plus D prime times the pressure cubed, and so on. This fits a compressibility curve like the ones described in the previous slide. The constants are temperature dependent and are used to accurately fit for a real gas. However, these terms have no physical meaning since they're only meant to precisely fit compressibility curves. They offer no direct description of the underlying forces between molecules. So let's now do an example where we incorporate all three of these equations of state that we've just spent the last 10 minutes defining. So this problem that I have written down here is calculate the molar volume of methane at 300 Kelvin and 100 atmospheres given that the second virial coefficient B prime of methane is negative 0.0017 per atmosphere. Assume that all other coefficients are 0. Let's compare this result to that obtained using the ideal gas law and the van der Waals equation of state. If the critical pressure is 45.4 atmospheres, the critical volume is 0.0990 liters per mole, and the critical temperature is 190.2 Kelvin. So for this problem, I'm going to start with the ideal gas law. And so in this case, since we know the ideal gas law to be equal to PV is equal to nRT, then we can just substitute in these values right away, and we can start to then determine what it is the molar volume for these conditions. So I'm going to do a little bit of rearranging first. I'm going to divide both sides by n, and I'm also going to divide both sides by p. And so what that means on the left-hand side is that I have the molar volume, and that's equal to the gas constant. Since my pressure is in atmospheres, I'm going to use the appropriate gas constant, which has units in atmospheres. The temperature is 300 Kelvin, and the pressure is 100 atmospheres. And so what that leaves me with is a molar volume of 0.246 liters per mole. The next one I'm going to calculate is the van der Waals. Now this one is going to take a little bit of work because we have to calculate the constants A and B, but since we're given the critical volume, pressure, and temperature, this isn't such a challenging thing. And so I know that the critical volume is equal to 3 times B. And so then if I solve for B, then that's just equal to VC divided by 3. I can then substitute in for VC, which is 0.0990 divided by 3, which means that my B is equal to 0.0330. I can also calculate my A constant. In this case, I'm going to use the critical pressure. And I know that that's equal to A divided by 27 B squared. And so at this point, I can rearrange for A. I know A is going to be equal to 27 B squared times PC times the critical pressure. I substitute in those numbers. 27 times B squared, 0.0330 squared, times the critical pressure, which in this case is 45.4 atmospheres. And so then that gives me an A value of 1.335. Now I could have used the critical temperature to calculate either of these two values, A and B. I just chose this way, using the critical volume and the critical pressure. Regardless, I can continue now and I can just directly calculate what is my molar volume based on the van der Waals equation of state. So pressure is equal to RT divided by the molar volume minus B minus A over the molar volume squared. So in this case, I can start substituting in numbers. The pressure is 100 atmospheres. I'm going to use the appropriate gas law constant, 0.08206. The temperature is 300 Kelvin. I have molar volume minus my B constant, which I just calculated, 0.0330. From that, I'm going to subtract off A, which is 1.335, divided by the molar volume squared. Now, the solution to this, if I were to try to solve this analytically, what it involves is that it involves solving a cubic root. And this is something that I would not expect you to do by hand in this course. And so what I did is, or what I would suggest you would do in this case is go to Wolfram Alpha or find yourself a cubic root solver, and you can basically numerically solve for the molar volume. And so what that gives us then in the end is a molar volume that is equal to 0.229 liters per mole. Now the final method we're going to look at, again, of course, is the virial method. And so with the virial method, we have to first calculate the compressibility, the factor Z, at this pressure, and then we can use that and substitute in to the modified ideal gas law, where we take into account compressibility to calculate the molar volume. So in this case, we can calculate the compressibility Z as being equal to 1 plus B prime times the pressure. And in this case, since the problem itself says all other coefficients are 0, like it says up here, then we don't need to go any further in this expansion. So if we substitute in for numbers, we've got 1 plus B prime in this case is negative 0.0017 times the pressure. That's 100 atmospheres. So my Z in this case is going to be equal to 0.83. Now this 0.83, what this tells us is that we have attractive forces at work, because again, the compressibility is less than 1. But at this point we can just substitute in now into the modified ideal gas law, where we take compressibility into account. Z is equal to P times the molar volume divided by R times T. We're trying to solve for the molar volume. So what I'm going to do is I'm going to multiply both sides by RT. And I'm going to divide both sides by pressure. I can then substitute in the numbers. I'm going to have 0.83, which is my compressibility, times my ideal gas constant, using the one with the appropriate units, 0.08206. And that's going to be times the temperature, which is 300, all divided by 100, and that's equal to 0.204 liters per mole. So the final part of this question asks us to compare our results. So one way to do this is that we would just calculate a percent error. And that what we'll do is we'll take the virial equation of state to be the precise value that we should get, and that we will compare it to what we got from the ideal gas law and the van der Waals equation of state. So if we start with the ideal gas law comparison, then what we would write is 0.246 minus 0.204 divided by 0.204 times 100. And we evaluate that, we get a percent error of 20.6%. And if we find out the percent error with the van der Waals equation of state, then with that we're going to write 0.229 minus 0.204 divided by 0.204. In that case, we only get a 12.3% difference. So these aren't insignificant errors. A 20.6% error and a 12.3% error. It's at least good to know that, or good to see that the van der Waals equation of state does do a better job at trying to quantify the molar volume of these conditions for methane than the ideal gas law, principally because it's trying to include repulsive and attractive terms in its formulation. But it's very evident that the ideal gas law does not include any attractive terms or any attractive forces. And I can claim that there's attractive forces at work here with the methane because the molar volume, when we try to include both attractive and repulsive forces, is less. Not to mention that my virial coefficient is less than 1, which implies that there are attractive forces at play. In my percent error calculation, whenever you do any of these, you always do whatever you measured minus whatever you take to be the exact value. And so in this case, because the virial equation of state is supposed to give an empirically exact value, then that's why I'm choosing to compare directly to the virial, or the value calculated from the virial coefficients. And so again, what this tells us is that both the ideal gas law and the van der Waals equation of state don't completely accurately reflect reality. However, for this course, the simplicity of the ideal gas law is going to make it so that we will be using it quite frequently for many gas-based examples. We started this lecture by looking at the kinetic model of gases, which provided an initial framework. Welcome to Lecture 3. In this lecture, we will quantify the internal energy of a gas and discuss how energy is transferred to and from the gas through work and heat. This lecture will be broken down into 4 parts. We will first quantify what is the internal energy of a system. This will include defining the first law of thermodynamics, which states that the internal energy of an isolated system is constant. Changes in internal energy are quantified as work and heat, which we will then look into more closely. Finally, we will examine some specific cases when the internal energy changes. To start off our discussion of the internal energy of a gas, let us examine one of the types of energy that particles in motion all have, kinetic energy. The translational kinetic energy of a molecule of a gas is 1/2 times m times the average of the velocity squared. We saw in the previous lecture that the average of the velocity squared is equal to 3RT divided by m, where capital M is the molar mass. So, substituting that into the expression for kinetic energy gives 3/2 times the Boltzmann constant times the temperature, where the Boltzmann constant, K sub b, is equal to 1.380658 times 10 to the minus 23 joules per Kelvin. In this calculation, we use the fact that the mass of a particle divided by its molar mass is equal to 1 over the Avogadro's number, and that the Boltzmann's constant is equal to the gas constant divided by Avogadro's number. This expression gives us the average energy of one particle in a gas. We can use this expression for the total kinetic energy to determine the energy of other motions of molecules. This can be done using the equipartition theorem, which states that the energy of a molecule is equally divided among all types of motion, or degrees of freedom. There are 3n degrees of freedom in any molecule, and each contributes 1/2 times the Boltzmann constant times the temperature to the total energy. For a mole of gas, each degree of freedom contributes 1/2 times the gas constant times the temperature, because we're multiplying Avogadro's number by the average energy of each degree of freedom, 1/2 kBT. Since Avogadro's number times the Boltzmann's constant is equal to the gas constant R, then we get 1/2 RT. For a mole of a monatomic gas, there are 3 degrees of freedom, since n is equal to 1. These 3 degrees of freedom represent the x, y, and z directions of the kinetic energy. Hence, the internal energy of a mole of a monatomic gas is 1/2 RT plus 1/2 RT plus 1/2 RT, which is equal to 3/2 RT. A one-atom molecule has no rotational degrees of freedom, since a sphere under rotation has no change, and there are no vibrational degrees of freedom, since each atom isn't connected to anything else to vibrate with. For the other 2 types of molecules listed here, linear and non-linear molecules, they have rotational and vibrational degrees of freedom. For a linear molecule, there are only 2 axes that it can rotate around, which change the position of its parts. Rotation about the center of the linear axis causes no change. Again, the 2 axes it can rotate around each contribute 1/2 r times t of rotational energy, for a total of RT. We have now quantified 5 degrees of freedom, 3 translational and 2 rotational. Since there are 3n degrees of freedom, then there are 3n minus 5 remaining as vibrational states. Each vibrational state contributes a kinetic and potential energy component. This means that each vibrational state adds a total of RT. This means that the total contribution is 3n minus 5, the total number of vibrational states, times RT, the total energy of each vibrational state. The nonlinear molecule follows a similar set of logic, only now it can rotate around all 3 axes, so that there is one extra 1/2 RT of rotational energy. As a result, there's one less vibrational degree of freedom. The total internal energy of a mole of gas is quantified by summing across the row of this table. Energy is quantized. What this means is that for a given degree of freedom, it cannot occupy a state with any value of energy along that continuum. Instead, a degree of freedom is only allowed to have an energy with discrete values. Those values are illustrated by the lines in the figure below. Quantization is a topic that will be covered in more detail in 361b. For this course, it is enough to accept that for each degree of freedom, states can only possess energies that correspond to those indicated by the lines. For equipartition to hold, the system must have enough energy to evenly distribute the molecules of the gas between all the states of the different degrees of freedom. As is illustrated, the different degrees of freedom, vibrational, rotational, and translational, all have different gaps between the different states. Translational has by far the smallest gaps, which begin on the order of about 10 to the minus 37 joules, then rotational at about 10 to the minus 23 joules, and then vibrational at 10 to the minus 20 joules. These values are only meant to illustrate the order of magnitude of the spacing. They are not meant to be exact. The order of magnitude of these gaps, however, can be used to estimate the populations of these states. This estimation is calculated using the Boltzmann distribution law. It states that the ratio of the population of two states, n1 and n2, is equal to the exponential of the negative of the difference in energy of the two states divided by the Boltzmann constant times the temperature. Remember that for equipartition to hold, the states of all the degrees of freedom must be reasonably equally occupied. Using the Boltzmann distribution law, the occupation of the states are determined below. At 293 degrees Kelvin, a state and the next state above it are equally occupied, since n2 divided by n1 is about 1, meaning that the number of particles in n2 is the same as in n1. However, for the vibrational states, this ratio is only about 0.084, meaning that n2 is much less populated than n1. The interpretation of this result is that at room temperature, equipartition fails in that the energy is only distributed between rotational and translational degrees of freedom. I include translational here because it has an energy separation much smaller than rotation. It is only when we increase the temperature to about 3000 Kelvin that we see the ratio of vibrational occupations start to approach 1. The takeaway message is that only for high temperatures does all three types of degrees of freedom matter when calculating the internal energy. At room temperature, only the translational and rotational degrees of freedom significantly contribute to the total internal energy. Now that we have an understanding of the internal energy of a system, let us now define the first law of thermodynamics. It states that the internal energy of an isolated system is constant. This is closely related to the law of conservation of energy, and this law essentially states that work cannot be done without consuming fuel. The internal energy is denoted by the letter U. When discussing things in the context of the first law of thermodynamics, we focus on the change in internal energy, which is quantified as the work performed plus the heat transferred. It shouldn't be surprising that a change in energy is related to two values that quantify transfers of energy, being work and heat. We need to define several statements in order to fully utilize the first law of thermodynamics. The first thing to define is what a state function is. A state function is a quantity that is path independent. This means that regardless of how you change a system from one state to another, the change in that quantity remains the same. For example, altitude is a state function. If we were going to determine the change in altitude between the summit of a mountain and the base camp, we only need to subtract one from the other. This difference has nothing to do with the route taken to go from the base camp to the summit. We will see many state functions in this course. The first one that we're defining here is internal energy. This means that to find the difference in internal energy, we only need to determine the initial and final internal energies and subtract the two. The process used to change the internal energy is irrelevant. We also need to define where reactions take place. The surroundings is where we make observations from. It also acts as a very large reservoir, absorbing or delivering pressure, volume, heat, and work while remaining unchanged. The system is the part of the world where we have interest, meaning where the chemistry is taking place. There are three types of systems. The first is an open system, which can exchange both energy and matter with the surroundings. The second is a closed system, which can only exchange energy with the surroundings. And finally, an isolated system, which cannot exchange energy or matter with the surroundings. Recall that the first law of thermodynamics refers to an isolated system. Finally, we will quantitatively define work and heat. These two quantities represent the transfer of energy between the system and the surroundings. Work, denoted as W, is a transfer of energy that causes or utilizes uniform motion of atoms in the surroundings. It is energy used to cause motion against an opposing force. Heat, denoted as Q, is a transfer of energy that causes or utilizes chaotic motion in the surroundings. It is energy in transit as a result of a temperature difference. A note on the sign conventions. Work and heat are positive if energy enters the system, as work and heat respectively. For heat entering or leaving a system, this has a special name. It is a process is exothermic when the system releases energy, and a process is endothermic when the system absorbs energy. Let us now focus on quantifying work. There are many types of work. For this discussion, we will examine expansion work. Many reactions form gases, and expansion work is done to make room for these gases against an external pressure. The work done by the system is quantified as the integral over the initial volume to the final volume of minus P external times dV. This integral is illustrated in the figure on the bottom left, which depicts a before and after scenario of a gas expanding by a certain volume against an external pressure. There are two notes. The first is that the minimum amount of work is done when the external pressure is equal to 0, and this is called a free expansion. The second point is that the maximum amount of work is done when the external pressure is only infinitesimally less than the pressure inside the system. So, when the external pressure is only slightly different than the internal pressure of the vessel during the expansion, then the maximum amount of work is done. This type of process is called reversible. To make this discussion a little easier, we will hold the temperature constant. In other words, we are discussing an isothermal process. The integral presented in the previous slide is illustrated in both images. In the left image, the external pressure, which is plotted on the y-axis, varies gradually where the external pressure is set to be a little less than the internal pressure at each step of the expansion of the gas. The area under this curve, or the integral of the external pressure over small changes in volume, gives the work performed and is shaded in green. The figure on the right illustrates non-reversible expansion. The case described is one where the external pressure is constant and lower than the internal pressure. When the process begins, the pressure inside immediately drops to the value of the external pressure, and then the volume expands from the initial to the final value. The work performed is again the integral of the external pressure over small changes in volume, or the area under the curve. When compared to the reversible process, it is clear that there is less work being done in the irreversible process. We can quantify reversible isothermal work of an ideal gas by doing the following. When the system expands through an infinitesimal volume dV, the infinitesimal amount of work performed is minus P external times dV. At each stage, the external pressure is the same as the internal pressure of the gas. Applying the ideal gas law, we can substitute nRT over V for the external pressure. Then, integrating between Vf and Vi gives minus n RT times the natural logarithm of Vf over Vi. Let's now do two examples where we're going to quantify calculating the work done by an expanding gas. And so in this first example, we're just doing what is the work done by a gas expanding from 3 decimeters cubed to 5 decimeters cubed against an external pressure of 100 kilopascals. And so we'll start with just our generic work expression, where it's just this integral over the initial to the final volume of minus P external times a small change in volume. Now, the one thing you always want to make sure of whenever doing these problems is that you want to make sure that when you're multiplying a pressure by a volume, that the units then work out that you're going to end up with is joules in the end, which is going to be what work is going to be quantified in. And so what we can see here is that the pressure is in kilopascals, and we can see that the units of volume are in decimeters cubed. So let's just look at that really quickly to make sure that when we multiply these two numbers together, we're actually going to get joules in the end. So 1 decimeter, that's equal to 10 to the minus 1 meters. And so if we're going to take or find a decimeter cubed, then we have to take the cube of 10 to the minus 1, which is just 10 to the minus 3 meters. We also know that a kilopascal is equal to 10 to the 3 pascals. And a pascal, as we saw previously, is a Newton per meter squared. What that means is that if we're going to multiply a decimeter cubed by a kilopascal, then what we end up with is 10 to the minus 3 meters cubed times 10 to the 3 newtons per meter squared. And then we can start crossing out terms. 10 to the minus 3 cancels out 10 to the 3. I have meters squared on bottom and I have meters cubed on top. And so that means then the units that I'm left with is a Newton meter or a joule. So this means that when I go through this calculation, I can directly plug in the 100 kilopascals and the decimeters cubed term that I get out of doing this integral, because when I multiply those two numbers together, I will get a joule. So let's perform this integral. Work is equal to, well, my VF and my VI, that's between 3 and 5. My external pressure is 100, and I'm integrating over dV. Here I have a constant inside my integral, so I can just pull that out front. Work is equal to negative 100 times the integral between 3 and 5 dV. Well, the integral of dV is just going to be equal to V. And so then that's going to be evaluated between 5 and 3. I apply my fundamental theorem of calculus. 100 times 5 minus 3. Well, that just gives me 2. That means my work is equal to negative 200 joules. Let's now look at a slightly more complicated example. In this case, we're going to calculate the work done, where we're going to start with 1 mole of argon gas, and is contained in a cylinder starting at 1 decimeter cubed at 25 degrees Celsius. It expands isothermally and reversibly to 2 decimeters cubed. And so again, we're going to start with our generic work expression. Work is equal to the integral between VI and VF minus P external times dV. And so what we're going to first realize is that this process is reversible. And so what that means is that the external pressure, we can then make that equal to the internal pressure. And so then what that means is that the external pressure is then equal to nRT over V, where all of these are the internal properties of the gas. What we're going to do then is we're going to take that value and we're just going to substitute that into our general expression. And so then now we can write work is equal to, well, my initial volume is 1 decimeter cubed, the final volume is 2 decimeters cubed. We have minus nRT over V times dV. What I'm going to do is I'm going to pull out a bunch of constants. So I can pull out the negative sign, I can pull out the R, the N, and I can also pull out the T, because remember we have an isothermal process, so that means that T is constant. So that can also come out of my integral. And so all I'm left with is between 1 and 2, we have dV over V. And as we've seen, if we do the integral of 1 over V, once that's evaluated, that just gives me the natural logarithm of V, and that's evaluated between 1 and 2. So at this point we just apply the fundamental theorem of calculus. W is equal to nRT ln 2 minus, and I'll put these in brackets, minus nRT natural logarithm of 1. And so in this case I can pull out a minus nRT, and what that leaves me with is natural logarithm of 2 minus the natural logarithm of 1. And so then that just becomes the ratio of 2 over 1 inside this natural logarithm, which in the end is just the natural logarithm of 2. So now at this point we're going to start plugging in actual numbers. This N, that's just the moles. This T, well, that's the temperature in Kelvin. And that this natural logarithm, even though I've got a volume over a volume, but since I've got volume over volume, those units cancel out. So this is actually unitless. And the reason why I'm going into this discussion is because our last value that we have to figure out here is our R. And there are many different types of R. The two that are most commonly used is this one gas constant, which is 8.3145, and its units are decimeters cubed times kilopascals divided by moles and Kelvin. And there's this other one, this other R, which is 0.08205, and that's in decimeters cubed, but the pressure is measured in atmospheres, and the bottom is still moles and Kelvin. And so the question here is, which one of these values are we going to put in? Because we know we've only got 1 mole, we've got a temperature in Celsius, which you can easily calculate into Kelvin. And so the R that we're going to choose, in this case, what we're going to look at is, here this R is going to be multiplied by moles and Kelvin. And that means that on the bottom, we're going to, in both cases, delete the moles and the Kelvin. And so really what's important is just the 2 units that are on top. So if we start with this decimeters cubed times kilopascals, well, we know, and we just found in the previous problem, that that's going to equal to joules. And that's exactly what we want this thing to spit out, because that's what work is. We also can see here in this other case, we've got decimeters times atmospheres. This, I actually don't know what this equals to, but I know that it doesn't equal to joules. And so in this case, the value that we're going to choose then to stick in for R is this 8.3145, because that in the end will give us joules. And it's important to always do this unit analysis when you perform these types of calculations, because sometimes it is convenient to use this 0.08205 because this atmosphere unit that's included in this constant is actually useful to have. But this is a case where choosing one number over the other can either give you the correct answer or the incorrect answer, and so it's very important that you do think about this for a minute before you actually start plugging in constants. So now that we've selected our gas constant, let's plug in all these numbers. Work is equal to minus 1.0, the number of moles. The gas constant we're going to use is 8.3145 because it gives us the correct units. The temperature in this case is 25 plus 273.15. And then we have the natural logarithm of 2. And when we multiply all these numbers together, the final value we get is minus 1.72 times 10 to the 3 joules. Heat, which you will recall, is the transfer of energy that causes or utilizes chaotic motion in the surroundings. It can be quantified by taking the integral over the temperature change of the heat capacity, where the heat capacity of an object is the energy required to raise the temperature of a given quantity by 1 Kelvin. For example, if you're heating 2 kilograms of water, then the heat capacity you would use would be for 2 kilograms of water. However, it is convenient to express the heat capacity of substances in more general terms so that they can be written in reference materials. 2 common ones are the specific heat capacity and the molar heat capacity. These are heat capacities of substances divided by the mass or the number of moles of a substance. That way you could look up the specific heat capacity of water in a book, multiply it by the amount you are using, in our example 2 kilograms, and that way you would get the heat capacity specific to our example. Furthermore, depending upon the process, where either the volume or the pressure is being held constant, the heat capacity is different. We will see the importance of this as we move forward in the course. The difference in constant pressure and constant volume processes can be observed in how heat is measured. In our current context, calorimetry is the process of determining the heat transferred by measuring the temperature change of a process. Constant pressure calorimetry can be performed in nested coffee cups to insulate the process from transferring the heat to the surroundings, but it is open to the atmosphere. This is how the pressure remains constant, since the atmosphere's pressure will not change due to what goes on in the calorimeter. Constant volume calorimetry is performed using a bomb calorimeter. The reaction occurs in a rigid, sealed container in the center of the device so that the process occurs at constant volume. In both cases, the process is immersed in a liquid, for example water, and the temperature change of the water is measured in order to deduce the heat transferred. Let's do a quick example to see how some of these ideas on heat work in practice. So in this example, what we're looking at is a system where we're going to input 330 joules of energy, and we're going to be raising 24.6 grams of benzene from 21 degrees Celsius to 28.7 degrees Celsius at constant pressure. And so what we're trying to determine is the molar heat capacity at constant pressure. And so where we're going to start this problem is just at the generic starting point, where we've got Ti, Tf, the heat capacity times a very small change in temperature, and we're going to integrate this over the two temperature changes. In this case, what we're going to assume is that the heat capacity is temperature independent, and that over small temperature changes, we can probably make this assumption. This C, of course, also is the heat capacity specific to 24.6 grams of benzene. And so when we do this calculation, that's what we're going to get out. And then, of course, the second step to turn it into a molar heat capacity is to divide it by the number of moles of benzene that we have. So moving forward, we can actually substitute in this case, our bounds of integration. And we can also take the C outside of the integral, because as we just described, it's temperature independent, so it's not actually going to be a part of the integral. 294.15, and that's when I add 293 or 273.15 to 21 degrees Celsius. This is 301.85, and that's just when I do that conversion to Kelvin. This integral is straightforward. Since we've got the integral of dt, well, that's just going to be equal to t, and this is evaluated between 301.85, 294.15. And so in this case, I can actually start substituting in values, and I can put in or evaluate this using the fundamental theorem of calculus. So as we saw in the problem, we put in 330 joules of energy. I have my heat capacity, and then I have my difference in temperature, or I have basically the fundamental theorem of calculus saying I'm going to write this as a difference of temperature. And so what I end up with in the end is a heat capacity that's equal to 42.86 joules per Kelvin. And so remember, this value is for exactly 24.6 grams of benzene. And the problem asked for the molar heat capacity. So that means we have to take this number that we have right here, and we have to divide it by the number of moles of benzene, so that we can get then the joules per Kelvin per mole, meaning how much energy do we have to put in per mole to raise it by 1 degree Kelvin. So first then we have to find out the number of moles of benzene. And so that means then we're just going to do a quick conversion where I've got 24.6 grams of benzene. And I'm going to multiply that by 1 mole of benzene is divided by the molar mass, 78.11 grams. And so what I have is 0.315 moles. And so then to find the molar heat capacity, and in this case, since the process is at constant pressure already, then I can add that P there as well. And that's equal to the heat capacity that we just calculated divided by the number of moles. So then that's 42.86 divided by 0.315. And in the end, what we get is 136.1 joules per mole Kelvin. We've now seen that depending on the process, the work and heat transferred for a process can change. We will now define what is a path function. For a path function, the path from an initial state to the final state defines their magnitude. Therefore, it is necessary to account for each part of the path to the final state. Using our mountain climbing example again, a person may choose one of 3 paths up the mountain. Regardless of what path the person takes, the starting place and the final place on top of the mountain will remain constant, so the altitude, a state function, remained the same. However, each path will require the hiker to walk different distances. In this case, the distance traveled is a path function. The person may decide to go straight up the mountain, or decide to take a less direct route, requiring them to walk further. There are many different ways to get to the final state, but the final state will remain the same. Let's relate the lecture material to this concept. We saw that if an isothermal expansion of a gas is done reversibly, this will give a different amount of work than if it is done irreversibly. Both cases, however, means that the system will still arrive at the same final state. We'll also see that the heat capacity at constant volume and at constant pressure are different, so depending on the process, the heat transferred can be different for the same change in temperature. Based on this, we can conclude that the work and heat are path functions. Let's now see how path and state functions interact with each other. The first law of thermodynamics combines the change in internal energy, a state function, with the path functions heat and work. If the process occurs at a constant volume, then there can be no expansion work. That means that the change in internal energy is solely based on the heat transferred. As a result, we can directly calculate the heat capacity at constant volume by measuring the change in internal energy with respect to a change in temperature. A bomb calorimeter with its fixed volume reaction chamber is a device that can be used to make this type of measurement. Let's now look at what happens for isothermal processes. Because the internal energy is determined by the temperature of the gas, if there is no change in temperature, then there is no change in the internal energy. For example, let's look at the expansion of 1 mole of a monatomic ideal gas. Monatomic gases only have translational degrees of freedom, where each axis contributes 1/2 RT to the total energy, meaning that the total energy is 3/2 RT. Note that it isn't dependent upon the volume or the pressure, so taking the derivative of 3/2 RT with respect to volume, because the gas is expanding, and we're holding this at constant temperature, then this derivative is equal to 0. The same could be said if we're taking the derivative with respect to pressure. Now using this, we can relate heat to the change in volume, as the gas expands isothermally. Since the change in internal energy is equal to heat plus work, and it's also equal to 0, then we can rearrange this to just write the heat is equal to the negative work. Therefore, if the isothermal process is reversible, then the heat is equal to positive nRT times the natural logarithm of the final volume over the initial volume. What this result tells us is that as the gas expands and does work, heat must go into the system to offset the energy the system is outputting so that the system remains at the same temperature. Let's now look at a couple of examples which illustrate some points covered in this lecture. In this first problem, we're going to examine an idea where nutritionalists are interested in the use of energy by the human body. And so calorimeters have been constructed for people and can measure their energy output. So let's say that a person does 622 kilojoules of work on an exercise bike, and at the same time they lose 82 kilojoules of energy as heat. And so what we're trying to calculate is what is the change in internal energy for the person. And so we would start with our general change of internal energy, which is equal to work plus heat. And what we're going to write, in terms of this, since we were actually given explicitly the work and the heat, we can write those in right away. 622, and to that we're going to add minus 82. So note that there are the two minus signs that I have here. And so in this case, with our sign conventions, when the system does work to the surroundings, then what that means is that the value of the work is negative. And when the system loses heat to the surroundings, that value is also negative. And so basically what we're saying is that as energy leaves the system, either through work or heat, then that ends up being a negative number. And as the system gains energy, either through work or heat, that's a positive number. But what that means in the end is that our change in internal energy in this case is minus 704 kilojoules. In this case, our second problem is a little bit more challenging than the first one, but again, it will show a couple of interesting points that we've discussed in the lecture. What we're doing is we're looking at the heating of 1 mole of a monatomic ideal gas. It's going to be done at constant volume between 293 and 300 Kelvin. And the question is asking find the work, the heat, and the change in internal energy for this process. And so the order that you find these values can sometimes be different. There's more than one way typically to find the solution to these problems. And so the order that I'm going to do this in is that I'm going to get the easy ones out of the way first. And when I say easy, you'll see why in a second. But here I'm just writing down for work, which is the first quantity that I'm going to be calculating, is the generic integral that we use to calculate work for every case. But of course we know that this process is happening at constant volume. And so what that means is that this integral goes to zero. Since there's no change in volume, there can't be any expansion type work that's done. So that means my work is equal to zero. Let's look at the heat transferred next. So the heat that's transferred is the integral between the initial temperature and the final temperature of the heat capacity specific to this system times little tiny changes in temperature. And so in the problem, we're not actually given what this value with this heat capacity for our 1 mole of monatomic ideal gas is, but we can certainly calculate it. And we can calculate it by first looking at the internal energy for 1 mole of a monatomic ideal gas. And we know that that's equal to 3/2 RT. And the thing again I'm going to stress here is that this is per mole of gas. So if we had 2 moles, then we would multiply this number by 2. And so if we want to find the heat capacity, as we've seen just in the previous couple of slides, what we would do is we would then take the partial derivative of this with respect to temperature. We know that this process is happening at constant volume, so we'll specify that. But when we take the derivative of 3/2 RT with respect to temperature, well, the 3/2 R, those are just two constants, and then the derivative of T with respect to T is 1. So this value is just 3/2 times R. And what this gives us then is the heat capacity, or the volume heat capacity per mole. And so then if we want to turn this into the heat capacity C that we have in that integral for our heat, then we just need to multiply this value by the number of moles of the system. And what we can see, or what we know from the problem, is that it's 1 mole, and we're going to multiply that by 3/2 times R. So when I start to sub in numbers, I'm going to get 3/2 times 8.3145, and that means then my heat capacity is then equal to 12.47 joules per Kelvin. Now I'm just going to take a second and just explain why I chose this value for the gas constant. And the reason why I chose it was that this value again has units of decimeters cubed times kilopascals divided by mole divided by Kelvin. And we know that this decimeters cubed, that's equal to joules. And we also know that what we did when we multiplied this 1 in with the R, well, that would cancel out the moles, because this 1 is the number of moles of the system. And again, what this is doing is that it's taking this out from being a molar heat capacity to the heat capacity specific to the system. So it's not per mole anymore, it's actually the value of the heat capacity for our monatomic ideal gas, which is what gives us this 1247 joules per Kelvin, because we'd have joules on top and Kelvin on the bottom. And so this is the number then that goes straight into our integral that we're going to calculate now. So let's do that integral. Q is equal to, I can actually write in, or I will write in the specific temperature range, 293 to 300. The C is 1247 dt. When we evaluate this integral, the 1247 is a constant, so we're just taking the integral of dt. So that means we get 1247 times t, evaluated from 293 to 300. Fundamental theorem of calculus tells me that I'm going to subtract those two numbers, 300 minus 293. And what that leaves me with is a heat transferred of 87.3 joules. So all that's left for us to find now is then just the change in internal energy, and that's equal to the work plus the heat. And what we saw from our two previous calculations was that our work is equal to 0, and our heat, well, that's equal to 87.3. That means then our change in internal energy is equal to 87.3 joules. We covered a lot of ground in this lecture, and here are a couple of points I wanted to reiterate. The internal energy of a substance is quantified by the equal distribution of energy over the occupied degrees of freedom. The first law of thermodynamics states that the internal energy of an isolated system is constant. The internal energy is a state function, meaning that changes in internal energy are independent of the path taken. Heat and work, which are path dependent and are called path functions, can be used to determine the change in internal energy. They represent the transfers of energy between the system and the surroundings. In order to maximize work of an expansion or a compression process, it must be done reversibly. For isothermal processes, meaning at constant temperature, the change in internal energy is equal to 0, And finally, for constant volume processes, the heat capacity at constant volume is just the change in internal energy with respect to temperature at constant volume. Welcome to Lecture 4. In this lecture, we will quantify the heat transferred at constant pressure as enthalpy, and we will apply this idea to chemical systems. This lecture will be broken down into 3 parts. The first part, we will define enthalpy. In the second part, we will examine what enthalpy means in terms of quantifying the heat capacity of a system. And finally, we will apply enthalpy to chemical systems. By doing so, 2 laws will be presented, Hess's law and Kirchhoff's law. We've looked at a lot of reactions at constant volume when discussing the internal energy of a system. However, a lot of chemistry happens when systems are held at constant pressure, like those open to the atmosphere. We will now focus on this more common case so that we have convenient quantities we can measure in order to be able to make predictions as to the properties of these types of reactions. It is convenient to use state functions to quantify systems because of their path independence. Currently, we only have the internal energy as a state function to define the energy of a system. The oxidation of fat is an example reaction where measuring the internal energy with a calorimeter isn't easily accessible. Consider the oxidation of trysterin. It is an exothermic reaction where the surroundings do work on the system. Remember that calorimetry, our primary tool for measuring the energy change, will not directly quantify the internal energy. This is due to the fact that the energy lost from heat transfer is restored due to the work performed on the system. This is not a constant volume process. The main issue with the trysterin example is that it is a process that occurs at constant pressure. Let us now examine the first law of thermodynamics at constant pressure. The first line simply has the first law of thermodynamics written with heat at constant pressure and work at constant pressure. Rearranging this expression so that the heat at constant pressure is on one side and the change in internal energy and work are on the other side of the equation, evaluating the work integral, and then arranging initial and final terms together gives the heat at constant pressure is equal to the final internal energy plus P external times the final volume minus the internal energy at the initial state plus the external pressure times the initial volume. Since the internal energy, the pressure, and the volume are state functions, we will use these to define a new state function. The enthalpy of a system is defined as H being equal to the internal energy U plus the pressure P times the volume V. A change in enthalpy, like a change in anything, is the final state minus the initial state. The definition of enthalpy can be substituted in for both the final and initial cases. If the pressure is held constant between both final and initial states, for instance, set to some constant external pressure, then we get the heat transferred at constant pressure. This is a quantity that is easily measured with calorimetry. For example, the coffee cup calorimeter can easily perform this measurement since it's open to the atmosphere. Recall the problem that we started with. We had a chemical process where both work and heat transfers occur, and we're looking for a convenient way to measure the energy difference between the initial and final states at constant pressure. This wasn't a problem when the volume was held constant since no expansion work is possible, so we can measure the energy change by measuring the change in temperature of a substance with a known heat capacity in thermal contact with the process. What we have done is a simple rearrangement of terms to combine the internal energy and the expansion work into something we call enthalpy. We can write the change in enthalpy in a more general form as delta H is equal to delta U plus delta P times V. If we can assume ideal gas behavior, then we can substitute PV for nRT. This provides an alternative way to quantify the difference between the change in enthalpy and the change in internal energy. For example, the size of nRT for 1 mole of an ideal gas at 25 degrees Celsius is about 2.5 kilojoules per mole. As we will see in the following example, this difference isn't large, however, it is significant when gases are involved. In this first example, we're looking at a 0.4089 gram sample of benzoic acid, and what we're doing is we're looking at the combustion reaction in a constant volume calorimeter. And then what was measured was that we saw a temperature change in the water from 20.17 to 22.22 degrees Celsius. And so if the effective heat capacity of the bomb calorimeter plus the water is 5,267.8 joules per Kelvin, what we're doing is calculating the change in internal energy and the change in enthalpy for the combustion of benzoic acid in kilojoules per mole. And really the purpose of this example is just to look at the difference between the internal energy and the enthalpy change for a given reaction. So first, let's write down our balanced chemical reaction. So in this case, we have the benzoic acid C6H5COOH. That's going to start as a solid. We're going to be combusting it with oxygen, which will be a gas. Combustion goes to completion, and combustion processes, if they go completely to completion, then we form carbon dioxide and water. And in this case, if we balance this chemical reaction, what I have is I have 6 plus 1 carbons on the left-hand side, which means I have to have 7 carbons on the right-hand side. I have 6 H's on the left-hand side, which means I have to have 6 H's on the right-hand side. And then now I have 14 oxygens. I have 17 oxygens on the right-hand side. 17 minus 1, 2 in the benzoic acid means I have 15, which means I have to have 15 over 2 oxygens on my left-hand side. Now let's look at the information that's provided to us. We're told that this is done in constant volume in a bomb calorimeter. So that means that's going to be a constant volume process. We're given the heat capacity at constant volume, and we're given the temperature change. So with that, we can actually directly calculate the heat at constant volume, which we already know is going to give us the change in internal energy. And so in that case, what we're going to do is we're going to get this generalized integral that we've used before, T initial, T final, heat at constant volume times the change in temperature. And so we're going to integrate this value. I'm going to write in all the constants that we know already. QV is equal to the integral over 293.32 to 295.37. I've already substituted in for Kelvin based on these temperatures in degrees Celsius. 5267.8 times dt. Well, since I have a constant times dt, then really this is just an integral of dt. So I've got 5267.8 times t evaluated between 293.32 to 295.37. In this case, I'm just applying my fundamental theorem of calculus, 5267.8 times 295.37, and then I'm going to be subtracting off 293.32. That means my heat at constant volume is just going to be equal to 1.08 times 10 to the 4 joules. And as I said before, this is equal to my change in internal energy, because the heat transfer at constant volume gives me my change in internal energy. I also know that this is going to be in joules because my heat capacity at constant volume was given in joules per Kelvin. And so when I multiplied the 5267.8 times T, which is what I did right here, then that means then joules per Kelvin times Kelvin leaves me with joules. Now I'm not quite done yet because it's asking for the solutions in kilojoules per mole, and right now I've only got it in joules. And basically what that means is that I have to calculate my internal energy, or my molar internal energy. And so in that case now I'm going to define this molar internal energy for the combustion of benzoic acid. And what that's going to be equal to is the negative of the delta U that I just calculated divided by the number of moles of benzoic acid. And where this negative sign comes from is that what we just calculated here was the heat change that was then put into the water. And what that means is then if I want to find out the internal energy change for the benzoic acid, then it's going to be the negative of this value, meaning whatever the benzoic acid gave out, that's what the water and the bomb calorimeter took in, and that's what then ultimately heated it up. And so that's where this negative sign then comes from. So from here I'm just going to start plugging in numbers. I'm going to have on the bottom the number of moles of benzoic acid is 0.4089 grams. And from that I'm going to have 1 mole for every 122.12 grams. So that's just the molar mass. On top I'm just going to have negative 1.08 times 10 to the 4. And so when I start to calculate this, what I end up with is negative 1.08 times 10 to the 4 divided by 3.35 times 10 to the minus 3, and that's the number of moles of benzoic acid. And so then I get negative 3.225 times 10 to the 6 joules per mole, or negative 3.225 times 10 to the 3 kilojoules per mole, since that's what the problem wants me to express this answer in. But what we found now is the change in internal energy, or the molar change in internal energy for the benzoic acid. Let's now look at the change in enthalpy for this process. So as we've seen, the change in enthalpy is equal to the change in internal energy plus the change in P times V. And as we can just guess off the top of our heads, if we're dealing with things that are solids or liquids, then when we do processes, we're probably not going to see huge changes in the volume or the pressure of solids or liquids. So if we're dealing with solids or liquids, then this delta PV term is just going to be very small. However, when we deal with gases, we know that PV is equal to nRT, and we know that we can have very large changes in pressure or volume when we're dealing with gases if we change the temperature, for instance. And so that's why I'm going to substitute in that ideal gas law expression. Since we're not given explicitly pressures or volumes, but we are given a temperature. And we also deal with changes in the number of moles in terms of the number of gases that we create. And so that's how we're going to then utilize this expression to then determine what is the change in enthalpy of our process. This next part is probably the hardest part conceptually to understand. But what I'm writing down is the change in enthalpy is equal to the change in internal energy plus RT times delta N. And the reason why I say this is conceptually the hardest is that we're looking at the problem, and it says, well, the temperature changed from 20.17 to 22.22 degrees Celsius. And the thing is that that's what we measured in the bomb calorimeter in the water, and in the bomb calorimeter itself, we saw that temperature increase. But what that's a result of is an amount of heat that was transferred from the combustion reaction into the water, and that's why we saw this temperature change. In reality, in the process itself, what has actually changed, since we're only counting gases, is that we saw basically 7.5 moles of gas turn into 7 moles of gas. And that's basically the value, the significant part of this delta PV or delta nRT, that's the significant part of this expression, is that change in the number of moles. So based on that, then what we can do is we can write this expression out, and we can say, well, the delta U, we've already seen that get calculated in terms of joules per mole. Then we're going to use negative 3.225 times 10 to the 6. From that, we're going to add on the ideal gas law, or the gas constant rather, 8.3145. The temperature, which in this case I'm going to use the lower temperature since that's what it started at, 293.32. And then this change in moles, where the final was 7 moles of gas minus 7.5 moles of gas. And again, I'm using this version of the gas constant because this value gives me joules per mole Kelvin. I'm going to multiply it by a temperature and by a number of moles, and so then that just leaves me joules. I'm using this value, this times 10 to the 6th value of the internal energy we just calculated, because it's also in joules. And this way I'm not making any mistakes with my units. Change in enthalpy, still minus 3.225 times 10 to the 6th. From that I'm going to be subtracting off 1.22 times 10 to the 3. And so we can see already that this delta PV or delta nRT term is a couple of orders of magnitude smaller than the internal energy of the system, where we've got times 10 to the 3 versus times 10 to the 6. But when we evaluate this, what we see in the end is that we actually get a small change in our enthalpy relative to our internal energy. And granted, it is a small change. However, we can see that it is significant enough that it is measurable. And that's the thing, whenever we're dealing with anything or in terms of any predictive power of any sort of calculation, is that we want to be able to do these calculations so we can make predictions and then be able to observe them. By being able to make these predictions and then again being able to observe these predictions in experiment, we can then actually convince ourselves that we fully understand the system that we have under observation. Since the change in enthalpy is equal to the heat transferred at constant pressure with no non-expansion work, then the heat capacity C sub P, being equal to the heat transfer divided by the change in temperature, is equal to the enthalpy change divided by a change in temperature. Written as a partial differential, this is equal to dH over dt at constant pressure. One thing that hasn't been made explicitly clear yet is that heat capacities change with temperature. For example, the molar heat capacity at constant pressure is typically reported for temperatures around room temperature as A plus B times T plus C over T squared, where A, B, and C are constants fitted for a given substance. At very low temperatures, nonmetallic solids are found to have heat capacities that are proportional to T cubed. In one example, it would be equal to G times T cubed, where again G is fitted. These are just a few examples of how the heat capacity changes as a function of temperature. So here is a simple example just taking this into account that the heat capacities do change with temperature. And so in this example we're looking at molecular oxygen, and it has a molar heat capacity that varies with temperature at constant pressure, where it's equal to 25.7 plus 0.013 T. And so what our question here that we're trying to determine is, what is the change in enthalpy when 1.46 moles of oxygen is heated from 298 to 367 Kelvin? And so I will of course start with my same place when I talk about heat changes or heat transfers. And in this case, I can write that because my change in enthalpy is equal to the heat transfer at constant pressure. And so in that case, I can then use the same starting place for the integral of Ti to Tf, heat transfer at constant pressure, heat capacity at constant pressure times dt. Well, I know that my heat capacity at constant pressure is equal to N times CPm, or the number of moles times the molar heat capacity at constant pressure, and that's the value that I have given to me in the problem. So then I can then write this as delta H is equal to the integral of, and I'll explicitly write in my bounds of my integration, 298 to 367. I have 1.46 moles, and then I have my molar heat capacity at constant pressure, 25.7 plus 0.013 T times dt. Now in this case, I actually have functions of t in my integral. Here my function of t is just equal to 1. Here I've got explicitly a function of t. And so now I need to actually do an explicit integral. When I do this integral, what I'm going to get is 1.46 times 25.7 t plus 0.013 t squared over 2. And that's evaluated between 367 and 298. At this point, I'm just using the fundamental theorem of calculus and just applying algebra. 1.46 times 25.7 times 367 plus 0.013 times 367 squared divided by 2. I'll put this inside square brackets just so I can delineate this a little bit better, because I want to make sure I make my minus sign here explicit. 25.7 times 298 plus 0.013 times 298 squared divided by 2, close bracket, close big bracket. And so then now I'm just going to evaluate some of these numbers. 1.46. This first value is 9431.9 plus 875.5 minus 7658.9 0.6 plus 577.2. Delta H is equal to 1.46. Now doing the inside of these curly or these rounded brackets, I've got 10307.4 minus 8235.8. Now doing explicitly that subtraction, I've got 2071.6. And then finally my delta H, when I multiply that by 1.46, is 3.02 times 10 to the 3 joules. Since there is an intimate relationship between the internal energy and enthalpy, there should therefore also be a relationship between the heat capacity at constant pressure and constant volume. Let's now figure that out. Since the molar enthalpy equals the molar internal energy plus R times T for ideal gases, then when the temperature changes, the enthalpy and the internal energy also change. Written in terms of differentials, dHm is equal to dUm plus R times dt. Substituting in the dHm is equal to the molar heat capacity at constant pressure times dt, and dUm is equal to the molar heat capacity at constant volume times dt, which is just quantifying the heat transferred at constant pressure and volume respectively, then gives the heat capacity at constant pressure, or rather the molar heat capacity at constant pressure times dt is equal to the molar heat capacity at constant volume times dt plus R times dt. If we divide both sides by dt, then we can rearrange, and what we get is the molar heat capacity at constant pressure minus the molar heat capacity at constant volume is equal to R, the gas constant. So the molar heat capacity of an ideal gas is greater at constant pressure than at constant volume. Remember that as heat capacities grow, so does the energy required to change the temperature by 1 degree. So at constant volume, no expansion work is possible, and all the heat remains in the system. This means a larger change in temperature is possible for an equivalent amount of heat transferred. That means that at constant pressure, some of the heat then escapes as work, meaning that less energy remains in the system, and this results in a lower temperature increase. So using this information, we can now calculate the change in internal energy and the change in enthalpy by exploiting this relationship between the molar heat capacity at constant volume and constant pressure. And so in this case, we have this example where we're going to calculate the change in internal energy and the change in enthalpy for 55.4 grams of xenon as we heat it from 300 to 400 Kelvin. And we're going to assume ideal gas behavior and that the heat capacities are independent of temperature, just to make this problem simpler. So the first thing is that xenon is a monatomic gas. So that means we can immediately calculate the heat capacity at constant volume as being equal to 3/2 times R. That means that knowing this relationship between the molar heat capacity at constant pressure and the molar heat capacity at constant volume, we can then calculate the molar heat capacity at constant volume, at constant pressure, because we'll have rearranging R plus 3/2 over R, and that means that the heat capacity at constant pressure is equal to 5/2 over R. The other piece of information that we will need right away is the number of moles of xenon. Let's now turn to using enthalpy to predict the heat transferred at constant pressure for chemical reactions. Consider the generalized reaction where we have some reactants that turn into products. Recall that enthalpy is a state function, which means that it's path independent. That means that the change in enthalpy can either be determined directly or indirectly. In order to ensure that when performing these types of calculations that conditions are all the same, it is necessary to define something called the standard state. This is the pure substance at exactly 1 bar of pressure. Some notes to keep in mind include the temperature is not a part of this definition. It can be defined for any temperature. The phase must also be specified. It can be defined for unphysical phases or conditions, and the standard state is denoted with an O and a horizontal line through it. Since the system is at constant pressure, the sign of delta H will define exothermic and endothermic processes. The standard state at a given, potentially unphysical temperature can be modified by the heat capacity, as will be seen later. The change in enthalpy for a reaction in the standard state can be calculated as the weighted sum of the standard molar enthalpies of the products minus a weighted sum of the standard molar enthalpies of the reactants. One would then combine all the relevant reactions to give an overall reaction enthalpy. Nu is a weight on each term, which is based on stoichiometric coefficients of the balanced chemical equation. This equation is summarized as Hess's law, which is defined as the standard enthalpy of a reaction is the sum of the standard enthalpies of the reactions into which the overall reaction may be divided. This is simply a statement that enthalpy is a state function, and that any path can be chosen to find the solution. Keep in mind that the difference in the weighted sum of the products and the reactants will appear whenever we discuss thermodynamic state functions in this course. This is now going to be an example of the application of Hess's law for a chemical reaction. So what we're given here is the three thermochemical equations, but really what the problem is asking is to calculate the standard enthalpy of the combustion of propene, where propene is C3H6. And so if I were to write down this balanced chemical equation, it would be C3H6 as a gas plus O2 as a gas, and that then leads me to carbon dioxide and water. And if I balance this chemical equation, I have 3 carbons on the left-hand side, so I have to have 3 on the right-hand side. I also have 6 hydrogens on the left-hand side, so that means I have to have 6 on the right-hand side. That means on the right-hand side I now have 9 oxygen molecules, so I have to have 9 atoms of oxygen on the right-hand side, which means I have to have 9 halves oxygen molecules on the left-hand side. Now for this demonstration of Hess's law, I'm going to draw 2 diagrams, where my first diagram is just going to be a direct measurement of this overall chemical reaction, where because it's combustion, I'm going to assume that it's going to be an exothermic reaction, that heat is transferred outside of the system. And so basically I have 2 different positions. I have when I have my propene and my oxygen. And in the final case, I'm going to have my carbon dioxide plus my water. In this case, I'll write this with a red arrow. And I'm going to have my delta H for this reaction. Now, of course, I don't have this information. I don't know this delta H, or I don't know this direct pathway or information regarding this direct pathway. And so what I can instead calculate is this alternative pathway using these other 3 thermochemical equations that I already know the standard change in enthalpy for. So what I'm going to start with is my propene. And then in this case, I'm going to write a couple of extra things in, and the reason why is that I will account for them later, or I will reproduce them later. But the main point is that I want to maintain, and maybe I'll write them into a different color, but I want to maintain that I have basically the exact same chemical reaction going on, even though I'm going to have other things happening around it. So I still have my C3H6, and I still have my 9 halves O2, but now I'm going to write in a mole of hydrogen and half a mole of oxygen. And what I know is that I can take that mole of hydrogen, and then I can convert my propene into propane, which is what this first thermochemical reaction tells me I can do. And if I do that, then what I gain is, the system loses 124 kilojoules per mole, which is what basically this thermochemical reaction is telling us. And what I have at this level is C3H8 plus 9 halves O2 plus, and then I have my 1 half O2 again. And I'll write my C3H8 actually in green to sort of denote that it is not part of the overall reaction that I have. The second piece of information, or the second reaction, is basically the combustion of the propene. And so what happens is that when I combust the propene, I end up again losing about 2,220 kilojoules per mole. And I turn my C3H8 and 5 oxygens into 3 carbon dioxides and 4 waters. Well, here on this line I have 5 oxygens. So that means then I can take my C3H8 and my 5 oxygens, and what I convert that into is, using the blue, I get 3 carbon dioxides and I get 4 waters. Now, of course, the balanced chemical reaction is only looking for 3 waters. And so that's where this final piece of information comes in, or this final reaction where I can take one of those waters and break it back up into hydrogen and oxygen. And so now I'm going to be back at the same level that I was at before. I'm going to be giving back 286 kilojoules per mole from what the system gave off. So the system's going to regain 286. And it basically is going to convert one of those waters into that mole of hydrogen and that 1/2 mole of oxygen. And so in this case, I've still gone from C3H6 plus 9/2 O2 gives me 3 CO2s and 3 waters, but I've just done it in this different pathway where I had the information available to me that I can know or calculate explicitly this pathway, and then I still get to the exact same spot. So if I were to calculate the change in enthalpy for this system, then all that is just the change in enthalpy in the first reaction plus the change in enthalpy in the second reaction plus the change in enthalpy of the third reaction. And so in that case, that's just going to be minus 124 plus minus 200 or 2,220 plus 286. And what that leaves me with is negative 2,058 kilojoules per mole. And so again, the take-home message from this is that Hess's law is just basically a description of enthalpy being a state function, being that we can either calculate this thing directly, which is what this first diagram is meant to show, that I'm just going to do a direct calculation of this combustion reaction, or I can calculate it indirectly, which is what I showed over here in blue on the right, where either method is the same, and because enthalpy is path independent, then I still come to the exact same answer in the end. Another example of using standard states is when calculating phase transitions. The term phase is more specific than state, since there can be many phases in a given state. For example, for steel, whose phase diagram is provided, has many solid phases. For each phase change, there's a change of enthalpy. We will use the following conventions. In terms of notation, the standard enthalpy of vaporization is denoted as delta sub vap of the standard enthalpy, and the standard enthalpy of fusion is denoted as delta fuse of the standard enthalpy. Following our sign convention, when these values are positive, this means that energy is transferred from the surroundings to the system, and the substance is melting or boiling. It is an unfortunate naming convention here that a positive standard change in enthalpy of fusion is the melting of a substance. For the reverse process, meaning condensation and freezing, the standard change in enthalpy is negative, meaning that the system is transferring heat to the surroundings. Also, since enthalpy is a state function, the standard change in enthalpy of vaporization and the standard change in enthalpy of fusion can be combined to get the values for sublimation and vapor deposition. In other words, moving between solid and vapor phases. So let's now calculate the standard heat of sublimation of ice at 0 degrees Celsius. What we're given basically is the standard change in enthalpy of fusion and the standard change in enthalpy of vaporization. And so what we're going to do is we're going to use Hess's law to basically determine what is the standard heat of vaporization of, the standard heat of sublimation. So this process, what it looks like is we're changing H2O solid to H2O gas. And what we're trying to calculate here is this delta sublimation. And what we're going to end up calculating instead, since we're given these two numbers, what we can then instead calculate is here's the H2O solid. We have a small change to get to H2O liquid. And then we have a larger change to get to H2O gas. And so all we're going to do is we're just going to add up these two changes that we know that leads us to the same place, since again enthalpy is a state function. 601, 45.07. And so all that means is that when we do this change in enthalpy calculation, that's just going to be equal to, here we've got delta H1, and here we've got delta H2. We're just going to apply Hess's law. So I've got 601 plus 45.07, which is the standard heats of vaporization and fusion. And then by adding those two numbers together, what we end up with is 51.08 kilojoules per mole. And that again, this is this standard heat of sublimation. One issue with calculating the change in enthalpy is that absolute values in enthalpy are not easily determined. To get around this, the standard method is to use an indirect route. We calculate the change in enthalpy by setting the value of the elemental components to be 0. So the reactants are then broken down into their elemental components, and the products are then built up from the elements. The change in enthalpy from breaking down and building up components from their elements is called the standard heat of formation. We can then calculate the change in enthalpy using the standard heat change for the reaction is equal to the weighted sum of the standard heat of formation of the products minus the weighted sum of the standard heat of formation of the reactants. The standard enthalpy of formation of an element in its reference state, being the most stable form at standard ambient temperature and pressure, which is 1 bar and 25 degrees Celsius, is defined as 0. The idea of enthalpies of formation is similar to the idea of land elevation, that it is relative to sea level. We have just defined sea level to be 0 elevation, and the height of everything is relative to that. Standard enthalpies of formation follow this same idea. Let's now do an example where we're going to calculate the enthalpy of formation, or use the enthalpy of formations to calculate the standard enthalpy of a reaction at 298 Kelvin. And the reaction we're going to look at is the breakdown or the combustion of glucose with oxygen to form carbon dioxide and water. However, where this is actually maybe interesting for us is that this also can be used to calculate the metabolic breakdown of food. And this is because since enthalpy is a state function, it's a path-independent thing. And so if we have the same reactants and products for a given reaction, then it doesn't matter the pathway we use to calculate it. So even though in our bodies it's a very complex metabolic process, in reality we can still derive the amount of energy that we gain, or the maximum amount of energy that's potentially gained through through the digestion of glucose by simply doing this combustion reaction. The values that I'm going to be using for this calculation come from Wikipedia, and I would invite you to use these values in subsequent parts of the course whenever the internet is available, so that you can then draw from this knowledge base to do your calculations. To start off though, we will write down just this general form of the change in the standard heat for the reaction is equal to the weighted sum of the heats of formation of the products minus the weighted sum of the heats of formation of the reactants. And in this case, the products, well, we have carbon dioxide and we have water. And so I'm just going to then just write in the weighted sum. So I have 6 moles heat of formation, or the standard heat of formation of water. Make sure I have my state in there. And to that I'm going to add, since this is a sum, standard heat of formation of carbon dioxide. And from that I'm going to subtract off the weighted sum of all the reactants, which in this case is glucose and oxygen. So I've only got one glucose molecule, C6H12O6, and from that I'm going to add on 6 times the standard heat of formation of oxygen. Now a big thing to take note of is the states. And this is because, and I'm going to use water as an example, is that water could either be formed as a liquid or a gas, and it could of course also be ice, but the typical ones whenever we look at these reactions is going to be liquid or gas. And there's actually a slight difference in the enthalpy of formation for water, like liquid water and gaseous water. So again, in order to get an accurate result, we want to make sure that we have the correct, or that we use the correct phase whenever we do these calculations. And so it's always helpful to write in those phases whenever we start subbing into doing this calculation, so that then we can make sure we keep this straight. So going to the table that I have provided with Wikipedia, then I'm going to substitute in the number. The heat of formation of liquid water is just going to be 6 times negative 285.8. We have the heat of formation of carbon dioxide. That's going to be 6 times negative 393.5. I'm going to subtract off the heat of formation of glucose, negative 1271. And to that I'm going to add 6 times 0. And this is because the heat of formation of oxygen gas at room temperature, well, this is the standard of the reference phase, the reference state, and so then that is just defined as 0. And that's why I've written in a 0 here. That means that term just disappears. From here I can then just start to evaluate. I just have algebra just to complete now. I have negative 1714.8. To that I'm going to add negative 2361. And from that I'm going to add, and the minus minus cancels out, so I get 1271. And that means then that the heat from this reaction is negative 2804.8 kilojoules per mole. And where these units come from is that each of these numbers that I substituted in are in kilojoules per mole. And so hence all of the numbers, when I add and subtract them, they end up giving me kilojoules per mole. Taking a quick step back, just looking at what this result means, well, the negative sign, that tells us that heat was transferred from the system to the surroundings, and this is something that we would expect because again we're doing a combustion reaction, but also in the context of this metabolic process we would hope that we would be transferring heat from the system, which in this case is going to be the glucose and the oxygen, and that heat then gets put into the surroundings, which is the rest of our body, and this is again how we're extracting useful energy out of eating food. The standard enthalpies of formation are typically given for one temperature. Kirchhoff's law allows for the calculation of standard enthalpies of formation at different temperatures. This is the change in standard heat of reaction at a new temperature T prime is equal to the change in standard heat of a reaction at a known temperature T plus the change in the standard heat capacity at constant pressure for the reaction times the difference in temperature, where the change in the standard heat capacity at constant pressure for the reaction is equal to the weighted sum of the change in standard molar heat capacities at constant pressure of the products minus the weighted sum of the change in standard molar heat capacity at constant pressure for the reactants. For small changes in temperature, typically less than 100 degrees Kelvin, it can usually be assumed that the heat capacities are constant. Here is an example of using Kirchhoff's law to determine the enthalpy change of a reaction at a different temperature. What we're given is that we get the standard enthalpy of formation of gaseous water at 25 degrees Celsius is minus 241.82 kilojoules per mole. And what we want to do is find out its value at 100 degrees Celsius. What we're given is these different values, these molar heat capacities at constant pressure for the various pieces of this reaction. And since we're talking about the standard enthalpy of formation, then that's why we have water, hydrogen gas, and oxygen gas. So starting off calculating this reaction, what we're trying to do is trying to find the standard heat at 373.15 or 100 degrees Celsius. And to do that, what we're going to do is take the heat of the reaction at 298.15 Kelvin. And what we're going to do is we're going to add to that the standard heat capacity at constant pressure for the reaction. And we're going to multiply that by the difference in temperature, 373.15 minus 298.15. And in this case, what we have is we know We know that this change in temperature, well, that's just going to be 75 degrees. We know this heat of the reaction at 298.15 because that's negative 241.82 kilojoules per mole. And so what we don't have is this part in the middle, this change in the standard heat capacity at constant pressure for the reaction. And so that's what we're going to then now determine. Now the reaction that we're working with here is, since this is a heat of formation, we've got hydrogen gas plus oxygen gas, and that's going to water, or gaseous water. So that means we can calculate this change in molar, or in heat capacity at constant pressure, and we'll use this sum, or this weighted sum, heat capacities of formation, or the molar heat capacities of formation of the products, minus the weighted sum of the heat capacities of formation of the reactants. And so in this case, we're just going to use the values that were provided in the problem itself. So we have in our reaction, and I should make sure that I balance this, I have to make sure I have a 1/2 in front of the oxygen since I've only got one oxygen in the water. And so in this case, we've got our products, we've got one water, and that the heat capacity for the water is the 33.58 joules per Kelvin per mole. So here's 33.58. And from that I'm going to subtract off. I've got one hydrogen. The heat capacity for hydrogen that I'm going to be substituting in is 28.84. And to that I'm going to be adding on, well, here I've got 1/2 of an oxygen molecule. So then 1/2 of the heat capacity, 29.37. I then do the algebra within the square brackets, 33.58 minus 28.84 minus 14.685. What that leaves me with is negative 9.945 joules per mole Kelvin. And I know it's in joules because that's just what the values that I use to calculate are in joules per mole Kelvin. Now what I'm going to do is that I'm going to just convert it into kilojoules because that's just what this standard heat of formation is written in. So then I can write this as negative 9.945 times 10 to the minus 3 kilojoules per mole Kelvin. And I'm just going to take that number, and that number is going to be the number that I'm going to substitute in for this question mark here that I had before. That means then I can then quickly then do this calculation where I'm at minus 241.82, and to that I'm going to add this negative 9.945 times 10 to the minus 3, and to that I'm going to multiply that by 75. And when I do this calculation, what I end up with is negative 242.6 kilojoules per mole. Now taking a step back again to try to understand what is it that we just calculated, we can see that this value at 100 degrees Celsius is not very different from the value at 25 degrees Celsius. And in this case, we did also assume that the heat capacities didn't change or that they remain constant over this relatively small temperature difference. What can see though is that as this temperature difference gets bigger, in this case it was just 75 degrees, but as this temperature change gets bigger, then that means that this result is going to also deviate more and more. And so the idea behind this is that we can see, or we can start to get a sense of how much these things change over a given temperature that then gives us an idea of how precise we need to be, or if we know the precision that we need to have when we do with our experiment, we can then understand what are the errors that we can then tolerate when doing these calculations. Here's a summary of what was covered in this lecture. The heat transferred at constant pressure is the change in enthalpy of a system. The molar heat capacities at constant volume and constant pressure differ only by the gas constant. Hess's law, which is a statement that enthalpy is a state function, can be used to determine the standard enthalpy of a reaction and is quantified as the weighted sum of the products minus the weighted sum of the reactants. And finally, Kirchhoff's law enables standard enthalpies to be determined at different temperatures depending upon the heat capacities of the species involved. Welcome to Lecture 5. In this lecture, we will quantify processes where no heat is transferred between the system and the surroundings in order to discuss heat engines. This lecture will be presented in two parts. The first part will focus on adiabatic processes, which are processes where no heat is transferred between the system and the surroundings. In the second part, we will discuss heat engines, which are objects that convert heat to work, and vice versa. An adiabatic process occurs when the system is isolated thermally. This means that no heat can transfer in or out of the system. In the context of the first law of thermodynamics, the heat, or Q, is equal to 0. Therefore, when applying the first law of thermodynamics, the change in internal energy is equal to the work. Keep in mind that adiabatic expansions results in changes to the pressure, volume, and temperature. Now that we have determined this direct relationship between work and the change in internal energy, let us quantify the work done by an adiabatic process. Recall that work is defined as the negative of the external pressure times the change in volume. This can be difficult to integrate because the temperature changes in adiabatic processes. However, we can use this to our advantage since work is equivalent to the change in internal energy. Changes in internal energy can be quantified by integrating the heat capacity of a substance at constant volume by small changes in temperature. This means that once the initial and final temperatures are known, this integral can be performed and the amount of work will be determined. The difference between reversible or irreversible processes is that the change in temperature will differ. As you can also see in the figure on the right, that the area under the adiabatic curve would be less than the area under the isothermal curve. This is just one example. It's possible to extract more work from an adiabatic process compared to an isothermal one, using different conditions. One thing that we have to keep in mind is that we've always been using Boyle's law, which is this idea that P1 V1 is equal to P2 V2, to basically describe the relationship between pressure and volume as gases expand and contract. The one thing that you have to remember is that the temperature, it's assumed that the temperature is constant with this. That's what makes Boyle's law hold. And what we just discussed is that adiabatic process, or expansions, well, they don't have constant temperatures. So we can't use Boyle's law to then relate pressure and volume for adiabatic expansions or compressions. And so we just have to take a step back to be able to then reformulate some of this relationship between these two state variables so that then we can then apply it to solving problems that have to deal with adiabatic expansions or contractions. The process that we're going to follow to come to this relationship is going to draw upon this factor, this idea that work is minus P, or the external pressure, times a small change in volume, and then small changes in the internal energy is just equal to the number of moles times the heat capacity at constant volume times small changes in temperature, and the fact that these two quantities for adiabatic processes are equal to each other, and this is because Q is equal to 0. And what we're going to end up with is something that actually looks very similar to Boyle's law with a very minor difference. But we'll get to that when we actually solve for this problem. At this point, though, we're going to continue forward with this. Small changes in work is equal to small changes in internal energy. And we're just going to substitute directly into this expression. So minus P external dV is equal to the number of moles times the molar heat capacity at constant volume times dt. And what we're going to assume here is that we're going to be dealing with reversible processes. So that means then for P external, I can then substitute in the number of moles times R times T over V times dV, and that's still equal to NC times dt. At this point, I can cross off the number of moles on both sides, and then all I'm going to do is I'm just going to integrate. So I'm going to have on this side an integral between V initial and V final times minus RT dV over V. And on this other side, I'm going to have an integral between T initial and T final of the molar heat capacity at constant volume times dt. And in this case, I'm just going to then rearrange just so that I can move this T over here over to the other side. And this is so that I get an integral where I've got solely as a function of V on one side and solely as a function of T on the other side. So I'm going to have minus R integral of dV over V from VI to VF. And on this other side, I'm going to have the molar heat capacity at constant volume, integral Ti Tf dt over T. And so we know these integrals pretty intimately. The integral of 1 over V times dV, well, that's just going to be equal to the natural logarithm of Vf over Vi. And on the right-hand side, I have the molar heat capacity at constant volume times the natural logarithm of T final over T initial. So now there are two things that I'm going to do in this step. The first thing I'm going to do is I'm going to use a substitution for the gas constant, where I know R is equal to the molar heat capacity at constant pressure minus the molar heat capacity at constant volume. And so what that means is that I'm going to be writing in for my R right here, I'm going to be writing in CPM minus CVM. The other thing that I'm going to be doing at this point is I'm going to be taking this minus sign and I'm going to use the natural logarithm property where any value that's out front of a natural logarithm becomes the exponent of that. And so if I have a minus 1 out front, then what that means is that I then have a minus 1, or I can use that or interpret that as a minus 1 for the Vf over Vi. And so what an inverse does is it just reverses that order. So I'm just now going to write this as Vi over Vf. On the right-hand side, it's still going to be the molar heat capacity at constant volume, and then the natural logarithm of the final temperature over the initial temperature. I'm just going to erase these extra markings just not to confuse at the very end when you're looking back over this whole thing. But the next thing I'm going to do right now is I'm going to divide both sides by the heat capacity at constant volume. And I'm going to write that down into the next step. I'm just going to subdivide this a little bit, just so that I can use the full page. But when I accomplish that, well, we can see basically on the right-hand side here that dividing both sides by the constant, or the heat capacity at constant volume, well, that basically gets rid of the term on the right-hand side. And on the left-hand side, well, I can basically divide it into this term that's in the parentheses, and so then it'll cancel out this term on the right, and then I basically just am left with a ratio with the term on the left. And so what we end up with writing is the heat capacity at constant pressure divided by the heat capacity at constant volume minus 1 times the natural logarithm of the initial volume over the final volume, and that's equal to the natural logarithm of the final temperature over the initial temperature. Now at this point, I'm just going to define a new constant just to simplify this expression. So what I'm going to do is I'm going to let gamma be equal to this ratio of molar heat capacities at constant pressure and constant volume. And so that just means I rewrite now this expression as gamma minus 1 natural logarithm of the initial volume over the final volume, and that's equal to the natural logarithm of the final temperature over the initial temperature. And then again, I'm going to reuse the same property that I invoked a little bit earlier, where I have a term that's sitting out in front of a natural logarithm, and so that's the same thing as letting that be what's inside the natural logarithm be raised to the exponent of whatever is out front. So then I can write natural logarithm of Vi over Vf raised to the power of gamma minus 1 is equal to the natural logarithm of T final over T initial. From here, I can just take the exponential of both sides, and what that'll do is that'll get rid of the natural logarithms. And so what I'm going to be left with is Vi over Vf raised to the power of gamma minus 1, and that's equal to Tf over Ti. So remember what we were originally going for. We're trying to find a relationship like Boyle's law to relate the pressure and the volume between two different states in an expansion. Within a single state, though, we can still use the ideal gas law, and this is how I'm going to convert these temperatures on the right-hand side of my expression into pressures and volumes so that then we can get back to a more Boyle's law type relationship. And so if I write down the ideal gas law and then I solve for the temperature, then I get PV divided by NR, and so then I can then write Vi over Vf raised to the power of gamma minus 1, and that's equal to, well, the final temperature is equal to the final pressure divided by times the final volume, all divided by the number of moles times R, and this is going to be multiplied by N times R divided by P initial, V initial. And so we can just cancel out the n times r and the n times r, and what we're left with is p final v final divided by p initial v initial. And then now what I'm going to do is I'm just going to move this volume final and this initial volume over to the left-hand side so I can group all the final and initial volumes together. I'm also going to slightly rewrite this expression on the left-hand side, where I'm going to stop writing it in a parentheses, and I'm just going to write explicitly the initial volume raised to the power of gamma minus 1, and with that I'm going to multiply it by the initial volume. That's the one that I took from over here on the right-hand side. I'm going to divide that by Vf raised to the power of gamma minus 1 times Vf, which is, again, this Vf that I took from the right-hand side. And that's going to be equal to P final over P initial. And then from here, these are supposed to be dots, not minus signs, but from here what I have on the left-hand side is I have a value raised to the power of gamma minus 1 times a value. And so basically what this Vi and this Vf that I have here, what that does effectively is it just cancels out these minus 1s. And we could take this akin to, just as a simplified expression, if I have x raised to the power of n minus 1 and I multiply that by x, well, what that gives me is just x to the n, which is because I've basically, by multiplying these two things together, I add the exponents of the numbers with it, and since this is x raised to the 1, n minus 1 plus 1 gets rid of the minus 1 and the plus 1 and just leaves me with the n. And I can use that exact same thing here with my expression that I've been building. And so in the end what we have is Vi raised to the power of gamma divided by Vf raised to the power of gamma, and that's equal to the final pressure over the initial pressure. And so again, to write this like a Boyle's law type expression, then what we have is Pi Vi raised to the power of gamma is equal to Pf Vf raised to the power of gamma. So the only difference between an adiabatic expansion and then an isothermal expansion, which is what Boyle's law talks about, is that we have to just raise the volumes that we input into our expression to the power of gamma, where gamma again is just this ratio of the heat capacities at constant pressure and the molar heat capacity at constant volume. Let's now apply this result to a problem where we're trying to determine the work done by an expansion of an adiabatic process. And so here in this process we have 0.85 moles of a monatomic ideal gas. It's initially at a pressure of 15 atmospheres and 300 Kelvin, and so it's now allowed to expand until the final pressure is 1 atmosphere. And so what we're trying to find is the work done, knowing that this is done adiabatically and reversibly. And so if we're going to find the work done, we know that the work is equal to the change in internal energy, which is just going to be equal to the integral of the initial temperature to the final temperature of the number of moles times the molar heat capacity at constant volume times dt. And so we can start to fill in values here. We know that this initial temperature is 300 Kelvin. We know that the number of moles here is 0.85. We know that this heat capacity here, well, that's equal to 3 over 2r. And how I know that is that for a monatomic gas, we know that the internal energy U is equal to 3/2 R times T. And if we take the derivative of this guy with respect to T, or temperature I should write, we'll take the partial, and we hold that at constant volume, then that's what's going to give us this 3/2 R. So the only thing that we don't have in this whole expression is what is the final temperature. And from there, once we know that, then we can actually just evaluate this integral and we can determine our work. So that's where we're going to start, is we're going to start looking for what is this final temperature. So then to find the final temperature, what we need to do is define the state variables at the final state. And we're going to use the initial state variables to do that. So the first thing we need to do is to find out what the initial volume is, because we know the initial pressure and we know the initial temperature. And so what we'll do is we'll find what Vi is. And then from this we can just use the ideal gas law, because within a state we can use the ideal gas law on ideal gases to find values. And so in this case, once I write down my ideal gas law, I can solve for VI, and I can substitute in for all the values, 0.850 times 0.08206, and I'm using this version of the gas constant because I'm going to write down my pressure in atmospheres. So I'm going to write my 15 on the bottom, and then I'm going to multiply all this by 300, which is the temperature. And what this gives me is an initial volume of 1.40 liters. Using this, then I can find the final volume. I'm going to use the expression that we just calculated in the previously, just a second ago. Pi times Vi raised to the power of gamma is equal to Pf times Vf raised to the power of gamma. Well, in this case, we know that gamma is just going to be equal to the ratio of the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. We know the molar heat capacity at constant volume, and we just said that that was 3/2 R. We know that the molar heat capacity at constant pressure is just that number plus 1, so that gives me 5/2 R. So that gives me a gamma that's going to be equal to 5/3, because I can cancel out my R's and I can cancel out my halves. And so in this case, then I can just plug in the numbers that I've just calculated that are given to me in the prompt. So that means my initial pressure, I can do this in atmospheres, so my initial pressure is 15. My initial volume, I just calculated 1.4 raised to the power of 5/3. My final pressure is 1. And then I've just got my final volume raised to the power of 5/3. And so if I calculate this thing on the left-hand side, what I get is 26.3. And then what I do is I take it to the square root of the power of 5/3. And then that's what gives me my Vf. So what that gives me is a final volume of 7.1 liters. Finally, since I know now the final volume, I know the final pressure, I can find out what the final temperature is. And from that, I'm just going to use the ideal gas law. P final, V final is equal to NR T final. What I'm going to get is T final is equal to P final V final divided by N times R, which is just going to be 1 times 7.1, all divided by 0.85 times the ideal gas constant. Again, I'm going to use the one that's written in atmospheres, 0.08206. What that gives me as a final temperature is 102 Kelvin. And the one thing I just want to point out real quickly here is that we just did an adiabatic expansion, a reversible expansion, and what that happened is that our initial temperature started at 300 Kelvin, and that this expansion dramatically lowered the temperature to 102 Kelvin. And typically adiabatic expansions lower the temperature of the gas itself, and that's something that's common with these problems. But now we can finally get back to our original problem, because again what we were trying to find was the work of the system, and we can now substitute in the bounds of this integration. Since I know my initial temperature is 300, my final temperature is 102, and then I'm just going to plug in my values, 0.85, the heat capacity at constant volume, 3/2R, and then I'm going to be integrating this over dt. Well, in this case, I still have 0.85. I'm going to have 3/2 times 8.3145, and that this is just going to be T evaluated between 102 and 300. And here I'm using the gas constant 8.3145 because this is the one that's written in liters times kilopascals, which then in the end gives me joules, which is what my value of work is going to be in. From here, though, I can multiply all the numbers that I have up front, and I get 10.6, and that's equal to 102 minus 300, because that's what I get when I evaluate my variable t with respect to the 102 and the 300, so that's just applying my fundamental theorem of calculus. Finally, what I'm going to be left with as an energy is negative 2099 joules. Now that we have defined adiabatic processes, we can now fully examine heat engines. These are devices that exchange heat for work. The schematic for heat engines typically have a high temperature and a low temperature reservoir, which are both connected to an engine. you can continue to imagine this engine as a movable, frictionless piston that allows PV work to be done by or to the gas. The figure as drawn shows heat moving from the high temperature source to the engine to produce work. Some of the heat also goes to the cold temperature source. This is the intuitive direction for heat to flow. Alternatively, however, all the arrows can be reversed so that work is put into the engine and it can draw heat from the cold temperature source and transfer it to the hot temperature source. A common example of a heat engine performing work is how steam is used to spin a turbine and produce electricity. The heat source that creates steam includes coal, natural gas, and nuclear reactors. They all follow the same basic principle. Water is heated to form high-pressure steam. The steam then expands into a turbine to spin it and produce electricity. The steam is then condensed in a heat exchanger and pumped back into the boiler. The high-temperature reservoir is in the boiler that produces the steam. The work output is the electricity generated by the turbine, and the cold reservoir is the condenser that transfers heat away from the spent steam to the cold reservoir. As was stated previously, heat engines can be used in reverse to draw heat from the cool reservoir and transfer it to the hot temperature source using work. Refrigerators and air conditioners use this principle. For example, in a refrigerator, the compressor pressurizes the coolant and pushes it to coils outside of the refrigerator. When this hot gas, heated from the compression, meets the air outside the refrigerator, it cools and liquefies. Now recall that adiabatic expansion cools the substance. This property is used to dramatically cool the coolant by expanding it into the refrigerator. This transfers heat from the interior to the coolant. The coolant turns back into a gas, and it flows back to the compressor for the cycle to restart. The work inputted occurs at the compressor, and heat is transferred from the cooler interior to the exterior of the refrigerator. Air conditioners work on a similar principle, only heat is transferred from air inside a structure to the outside. Let's now look at one idealized heat engine cycle, which represents the maximum efficiency possible for any classical heat engine. It is called the Carnot cycle, and it is a process with 4 steps. The first is a reversible isothermal expansion of the piston. The second is a reversible adiabatic expansion of the piston. These 2 steps represent the work done by the gas. Notice that the adiabatic expansion cools the gas. And the final 2 steps are a reversible isothermal compression of the gas, and finally a reversible adiabatic compression of the gas. The fact that the compressions occur at lower temperatures means that the work put into the cycle is less than the work extracted from the cycle. The difference between the expansion and compression work is the area enclosed. The area enclosed by the forepass therefore represent the total work performed by the process. Let's now determine the work that's done for each step for the Carnot cycle, and then we'll use that basically to calculate the total work produced. Now the thing that we're going to do is we're going to be calculating the work done in the 4 steps, and I'm just numbering these 4 steps, where again we have the first isothermal expansion, we have the first adiabatic expansion, then we have an isothermal compression, and then finally we have an adiabatic compression that leads us right back to the beginning point, which is this point right here, P1 V1 T hot. And through this, we have this region that's basically enclosed by the 4 lines, and that region is going to end up being the work that's generated by this cycle. And so then by calculating what is the area under each of these curves, we can then add that up, and what will end up in the end is the total work of the Carnot cycle. So starting with the first step, this is an isothermal expansion, and so the work that's performed by an isothermal expansion is simply just going to be equal to the integral of V1 to V2, since we've got V1 here and V2 over here, and that's going to be the integral of minus P external times dV. And of course I can write, since we're looking at reversible processes, then this can be minus nRT over V times dV. And since T is constant, and I know T is constant because this is an isothermal expansion, and so then that means that all of these variables, nRT, those can just come straight out front. I get the integral of dV over V. So we know the answer to this is going to be minus nRT natural logarithm of V2 over V1. I also know that the T in this case, this is just going to be T hot. and I know that's T hot because I have an isothermal process where I have T hot and T hot here. So the temperature, like I said before, is constant. I'm just denoting it explicitly here in the expression. For the second step, which is this adiabatic step that I have, well, in that case, I'm going to calculate the work just like we outlined in this lecture, where I know that the work is going to be equal to the change in internal energy, since again this is an adiabatic step, which is just going to be the integral from T hot to T cold of N times the heat capacity, the molar heat capacity at constant volume times dt. And so again, I have two constants, the number of moles and the heat capacity, and so those come straight up front, and so I'm just basically taking the integral of dt, and in the end what I get is a work that's equal to the number of moles times the molar heat capacity at constant volume times T cold minus T hot. Alright, so that takes care of the expansions. Now let's do the compressions. The first compression happens here. This is step 3. This is an isothermal compression. This is done at T cold, and it runs between P3 and V3 and P4 and V4. And so again, I can just write this as, since it's an isothermal compression, then the work is just going to be equal to the integral from V3 to V4 of minus P external dV. I can make the same substitution. I can make P external equal to nRT over V. Since T is constant, then I can then put it all out front. This is now T cold, integral of V3 to V4 dV over V. And again, I get a work that's equal to nRT cold, natural logarithm of V4 over V3. Finally, we have step 4. Step 4 is an adiabatic process, and it runs from P4 V4 to P1 V1, so we end up back at the beginning. The step 4, since it's an adiabatic process, then we know the work performed is the same as the internal energy, which I can calculate by saying the integral from T cold to T hot of the number of moles times the molar heat capacity at constant volume times dt. And I get an exact same answer that I had down here before. The only difference is that I'm just going to have to reverse T hot and T cold, because T hot is now the final state, T cold is now the initial state. So now if I want to find what the total work of the cycle is, I just need to add up these 4 expressions for work, for these 4 parts of the cycle. And the reason why I can just add them up is that some of them are going to be minuses, some of them are going to be pluses, so their sign will determine if I'm going to add and subtract, and that sign comes from essentially the sign convention that we've been using this whole time. If the system does work on the surroundings, it's negative. If the system has work performed on it by the surroundings, then it's a positive. But when I'm adding this up, I can just say, well, work total is equal to work 1 plus work from step 2 plus work from step 3 plus work from step 4. Let's now write in all 4 of those steps. So work 1 is going to be minus nRT hot, natural logarithm of V2 over V1. To that I'm going to add the work from step 2, which is just N times the molar heat capacity at constant volume, T cold minus T hot. From that I'm going to subtract the value from step 3, which is just nRT cold, natural logarithm of V4 over V3. And then finally I'm going to add the last step, which is just N times the molar heat capacity at constant volume times T hot minus T cold. Let's now simplify this expression so that we end up with something that's easily manageable. What we can see if I rearrange this expression, I'm just going to group together the work that's done from adiabatic and isothermal processes. So minus nR T hot, natural logarithm of V2 over V1 minus nRT cold, natural logarithm of V4 over V3 plus N times the molar heat capacity at constant volume, T cold minus T hot. And in this case, what I'm going to do, just to make this simpler in this last step, is that in this final one, if I pull out a minus sign out of this expression right here, then I can write minus N times CVM, And the minus sign that gets pulled out just means that I can reverse the sign or reverse the order of that, of what's inside the parentheses. And what we can see here now is that I have an expression where two of these terms cancel each other out. I have n CVM T cold minus T hot minus n CVM minus, or T cold minus T hot. So that means the work that's done and the work that's done on the system in the adiabatic steps cancel each other out. And so what we're left with is then the work that's performed in the isothermal expansion and then the work that's done to the system in the isothermal compression. So to simplify this further, we're going to have to do a little bit of work on the side. So I'm going to make this little side box so we can do this little bit of work. But we know that for isothermal expansions, then what we can write is P1V1 is equal to P2V2, and we can write P3V3 is equal to P4V4. And this is the generalized thing because we can apply Boyle's law because we have isothermal expansions, which means that there's no change in temperature. We also found in this lecture that for adiabatic changes in pressure and volume, P2V2 times, or raised to the power of gamma, is equal to P3V3 raised to the power of gamma. And so that became the relationship so that we can then describe as things change between different states for adiabatic expansions and compressions, where again this gamma is just going to be equal to the ratio of the heat capacities. We can also write P1V1 raised to the power of gamma is equal to P4V4 raised to the power of gamma. And where I'm getting these expressions from is if I just go back up for one quick sec, we have our isothermal steps, which are up here and down here at the top and the bottom of the pathway. And related to them we have P1V1 and P2V2 for an isothermal expansion, and we also have P4V4 and P3V3. And so that makes up the isothermal relationships that we can write with Boyle's law. And then we have our adiabatic expansion and compression, and the states that relate those two together are P2V2 and P3V3 as well as P4V4 and P1V1. And so that's basically where I'm getting these values from, or these relationships from. It's just basically from that diagram from our curve. In the end, what I want to do is I want to find a way to relate this ratio of V2 over V1 to V4 over V3. Because if I can do that, then that means that I can simplify this expression over here into something that's a little simpler to handle, where I only need to know 2 of the volumes instead of having to know all 4 of the volumes to be able to calculate the total work done by the cycle. And so, as we can see, we're dealing with ratios. So then let's create a ratio of our own. So using the adiabatic parameters, we're going to create our own ratio that we're going to write P1 V1 gamma divided by P2 V2 gamma, and that's going to be equal to P4 V4 gamma divided by P3 V3 gamma. And again, all I've written is P1 V1 is equal to P4 V4, which is something that we already have just right up here. And we've got P2 V2 raised to the power of gamma is equal to P3 V3 raised to the power of gamma. And that's just what we have right here, and we've just taken the ratio of those two things. What I'm going to do now is I'm going to take out of all of these volumes, I'm going to take out just one of them. And what I mean by that is I can write P1 V1 times V1 raised to the gamma minus 1. P2 V2 raised to, or times V2 raised to the power of gamma minus 1. That's equal to P4 V4 times V4 raised to the power of gamma minus 1. P3 V3 times V3 raised to the power of gamma minus 1. And so again, all I'm doing is I'm just taking out a V1, a V2, a V4, and a V3, and what that does to all those terms before when I had them raised to the power of gamma is that they're just now raised to the power of gamma minus 1. This is now where I'm going to use Boyle's law, because in this case I know that these bottom terms, or at least on the left-hand side, this P2 V2, well, I know that that's just equal to P1 V1. So I can write P1 V1, V1 raised to the power of gamma minus 1, all over P1 V1 raised, or V2 raised to the power of gamma minus 1. And so, like I said, I've just changed that P2V2 into a P1V1. I can do the exact same thing over here, only in this case I'm going to convert the P4V4 into a P3V3. So that means on the top I'm going to have a P3V3 V4 raised to the power of gamma minus 1 divided by P3V3 V3 raised to the power of gamma minus 1. And now I can cancel out these terms on the left-hand side and the right-hand side. And so what I'm left with then is V1 over V2 raised to the power of gamma minus 1 is equal to V4 over V3 raised to the power of gamma minus 1. And so what this implies is that V1, the ratio of V1 over V2, is equal to the ratio of V4 over V3. Remember that that's exactly what we were looking for back up here, where we were trying to find a relationship between V2 over V1 and V4 over V3 so that we can simplify this expression further. We have that now down here where we can see that the ratio of V4 over V3 is equal to V1 over V2. Or I can use that in the opposite way. But what I'm going to do is I'm going to then substitute this expression that we just determined back into our work expression, where now I can say minus nR T hot, natural logarithm of V2 over V1, minus nR T cold, natural logarithm of, well, V4 over V3 is equal to V1 over V2. Well then now, since I've got V2 over V1, V1 over V2, I'm going to then flip this V1 over V2, where I'm going to multiply in front of it by negative 1 over negative 1. And what that does is again, is that I'm going to flip the sign of this negative here, but then that means I can also raise this to the power of negative 1. So let me write that in just a little bit more explicitly so that we can see this. Minus nRT hot, natural logarithm of V2 over V1, minus, I've got minus 1 over minus 1, nRT cold, natural logarithm of V1 over V2. So one of these minus 1's cancels out this minus sign, so I get plus, and that one disappears, and I still have a minus 1 that then raises this natural logarithm V1 over V2 to the power of minus 1. Minus nRT hot, ln V2 over V1, plus nRT cold, natural logarithm of V2 over V1. What this leaves us in the end is that we can now simplify this expression. We can distribute out certain terms. I can distribute out an n, an r, and a natural logarithm of V2 over V1. And what I'm left with here now is T cold minus T hot. And since we know that T hot is going to be bigger than T cold, then we know that this will give us a negative number when we have a net amount of work that the system performs, which is what we expect from the Carnot cycle, is that we're supposed to be converting heat into usable work. And that's something where the system is transferring that energy to the surroundings, so the total value should be a negative number. We also now have this problem that's simplified to that we only need to know now two of the volumes, which basically are related to each other through the isothermal expansion, which is V1 and V2. Once we know those two things, where we know the hot temperature and the cold temperature as well as V2 and V1, then we can calculate the total work from a Carnot cycle. The efficiency of any heat engine is based on the usable energy extracted relative to the energy inputted. For a heat energy performing work, the efficiency is equal to the absolute value of the work performed over the heat inputted. We can substitute in the values calculated from the Carnot cycle to get an expression that is generalizable to all heat engines. So the work performed is negative nR times T hot minus T cold times the natural logarithm of V2 over V1. I'm expressing it like this so that when the absolute value is applied later, we still get an expression for the efficiency. The heat inputted occurred in the isothermal expansion. We saw that the work performed in this step was negative nR T hot times the natural logarithm of V2 over V1. Since this is an isothermal process, then the heat transferred is equal to the negative of the work. So the heat inputted into the system is N times R times T hot times the natural logarithm of V2 over V1. So dividing the absolute value of the work by the heat inputted results in T hot minus T cold over T hot. And therefore rearranging this gives an efficiency value which is equal to 1 minus T cold divided by T hot. Let's use this on a real-world example so that we get practice calculating efficiency values for heat engines. So in this, what we have here is at a power plant, we have superheated steam at 560 degrees Celsius, and it's used to drive a turbine for electricity generation. The steam is then discharged to a cooling tower where it's at 38 degrees Celsius. And so what we're supposed to do is calculate the efficiency for this process. And so we know that the efficiency is just going to be equal to 1 minus T cold over T hot. Now, one of the major things that you have to use when you do calculations, that in general, it's always good to do this in Kelvin. And this is no different for these types of calculations, especially if the temperature goes from a positive value to a negative value, because then if you end up having a negative ratio of T hot and T cold, then what that means is that then you get an efficiency that's going to be greater than 1, which is not going to be something that's possible. So you need to always do these things in Kelvin. So if we write these down in Kelvin, we have 560 degrees plus 273.15, and that gives me 833.15. And the other one is 38 plus 273.15, and that's equal to 311.15. So if we write those values into this expression, we get 1 minus T cold, 311.15, divided by 833.15. When we evaluate this expression, what we get is 0.63, or 63% efficiency. Here's a summary of what was covered in this lecture. An adiabatic process means that the heat transferred, or Q, is equal to 0. And so what this results in is that the change in internal energy delta U is equal to the work of the process. This relationship can be used to determine the work done during an adiabatic process, meaning that the work is equal to the integral over T1 to T2 of the number of moles times the molar heat capacity at constant volume times dt. A heat engine is a device that converts heat to work or work to heat. Common examples of these are power generating facilities and refrigerators. And finally, the Carnot cycle provides an upper thermodynamic limit on the efficiency of a classical heat engine. Welcome to Lecture 6. In this lecture, we will step away from thermodynamics briefly to discuss some statistical mechanical concepts. Thermodynamic quantities can be derived from statistical mechanics, and we will demonstrate this point by deriving the internal energy. This lecture will be broken down into 3 parts. First, we will define macrostates and microstates. Second, we will quantify what is a partition function and present the partition functions for translational, rotational, and vibrational types of motion. Finally, we will derive the internal energy of a system based on the partition functions that define it and apply it to a monatomic gas. In thermodynamics, a macrostate is described by properties such as pressure, temperature, volume, internal energy, and enthalpy, and a microstate is described by quantifying the variables associated with the states of the individual atoms or molecules in a system. We'll go over a couple of examples in order to illustrate these 2 points. For now, think of a macrostate as a group of similar microstates. We are generally not interested in individual microstates since it's the macrostate of a system that we measure as a property of the system. One major assumption in statistical mechanics is the principle of equal a priori probability, which states that all microstates are equally probable. This means that the number of different microstates that is a member of the same macrostate determines the probability of the macrostate occurring. These points can be easily seen with an intuitive example, throwing 2 dice. The image shows all possible face value combinations of 2 dice arranged according to their total. A microstate in this case is the face value of the 2 dice. So a microstate would be when one dice reads 1 and the other also reads 1. Since we can distinguish the 2 dice, then a face value of 5 and 2 is different from 2 and 5 and are counted as 2 different microstates. The macrostate in this case is the total from both dice. Since each microstate is equally likely, then the number of microstates in a macrostate determines how likely a given macrostate is. As can be seen in the image, 7 is the most probable macrostate, since there are 6 combinations of microstates that give 7. 2 and 12 are the least likely macrostates since there is only 1 microstate for each. There are a total of 36 microstates and 11 macrostates for this system. An important observation is that as the number of total microstates increases, the number of probable or observable macrostates decreases. In the dice example, increasing the number of microstates means throwing more dice. If we were to throw more dice, say 10 or 100, the broad distribution seen with the 2 dice becomes much thinner. The most likely macrostate becomes very probable relative to all others. This phenomenon is what allows us to average over moles of particles and get predictable, observable quantities, since they tend to be the only probable ones. Consider a second example. Suppose we have 3 identical non-interacting molecules distributed over energy levels where the total energy of the system is equal to 3. How many different ways can we distribute the molecules? Assume that the molecules can be distinguished from one another by their locations. The illustration on the left shows that there are in general 3 ways to distribute the molecules in the energy levels. These are the macrostates. For each macrostate, there are different number of microstates. For macrostate 1, there is only one way to put all 3 molecules into energy level 1. For macrostate 2, there are 6 ways to arrange the 3 molecules on their own in energy levels 0, 1, and 2. Finally, there are 3 ways to distribute the 3 molecules where one is in energy level 3 and the other 2 are in energy level 0. Since there are 10 ways to arrange the molecules so that the total energy is 3, then that means the most probable macrostate is number 2. The general formula for calculating the number of microstates in a distribution W is equal to n factorial divided by the product of ni factorial. And this is where n is the total number of particles, ni is the number of particles in the nth energy level. The exclamation mark is called factorial, where n factorial, or anything factorial, is given by n times n minus 1 times n minus 2 all the way down until it's times 1. As a side note, 0 factorial is also equal to 1. The large pi symbol means the product of all that follows. In this case, it is referring to the product of all ni factorial. Written in a different way, it would be written as n1 factorial times n2 factorial all the way to ni minus 1 factorial ni factorial. Let's use this now in practice to determine the number of microstates in a distribution using the exact same problem that we had already analyzed with our 3-particle system, where what we're trying to do is just have 3 identical non-interacting molecules distributed over energy levels where the total energy is equal to 3. And so what we're trying to do is again just determine how many microstates exist in each of the 3 macrostates. And so the way that we calculate this, as was shown on the previous slide, was that we would then take n factorial divided by the product over I of ni factorial. And so in this case, since we've got 3 particles in our system, that means on top we're going to have 3 factorial. And on the bottom, well, this capital pi sign just means the product of what follows. And I basically is going to be equal to 0, 1, 2, and 3. So that means on the bottom what we're going to have is the number of particles in the 0th energy level factorial times the number in the 1st energy level factorial times the number in the 2nd energy level factorial times the number in the 3rd energy level factorial. And so we're going to use this general expression then based on the original definition to determine how many microstates exist in each of the 3 macrostates that we examined previously. Let's now apply this to each of the macrostates. So for macrostate number 1, we have, starting with the general definition, we have n factorial divided by the product over I of ni factorial. For this system, and like for the other 3, we've got 3 factorial on top. And on the bottom, we're basically, again, taking the product of the number of particles sitting in each of the energy levels. So n0, there are 0 particles in it. n1, there are 3. n2, there is 0. And n3, there is 0. So that means I'm going to write 0 factorial, 3 factorial, 0 factorial, 0 factorial. Now we know that each of these 0 factorials, they're just equal to 1. And so what we're left with is 3 factorial divided by 3 factorial, which means that there is only 1 microstate in macrostate 1, which is an answer that we already showed to ourselves and we can see in the image. Moving on to macrostate number 2, we can start with the general definition. n factorial over the product over I of ni factorial. Well, in this case, we still have 3 factorial on top. The number of molecules haven't changed. On the bottom, well, we have 1 particle in N0, 1 particle in N1, 1 particle in N2, and 0 particles in N3. So that means we have 1 factorial times 1 factorial times 1 factorial times 0 factorial. And that this denominator is 1 times 1 times 1 times 1. So it's just 1. That means we're left with 3 factorial on top, 3 times 2 times 1 over 1, which means that we have a total of 6 microstates in macrostate 2. Let's now determine the number of microstates in macrostate number 3. Here again, n factorial divided by the product over I of ni factorial. What that gives me again, 3 factorial on top. Well, here we have 2 in N0, 0 in N1, 0 in N2, and 1 in N3. So we have 2 factorial times 0 factorial times 0 factorial times 1 factorial. And so in this case, again, the zeros and the 1 factorials, they're just equal to 1. And so what we're left with is 3 times 2 times 1 divided by 2 times 1. And so in the end, what we have is 3 microstates in macrostate number 3. Now, one point I'd like to stress, again, is this fact that each microstate is equally probable of occurring. And so that means that we have, over the sum of all of these different microstates, we have 10 in total. And so if each of these then are equally likely, then the one or the macrostate that has the most number of microstates is going to be the one that we're going to observe the most. It's the one that's most likely. And so that means then that in this case, given this specific system, macrostate number 2 is going to be the one that we're going to see the most, or that we're going to measure the most, because it has 6 microstates. Or in other words, it has the most microstates out of all 3. And then in this case, macrostate number 1 is the one we will least see, since there's only one microstate that makes up this one state. What this says to us also is that if we ended up in macrostate number 1, if we somehow found ourselves in that state, we would tend to then move towards macrostate number 2, since it is more likely that we would find it, or there's 6 possibilities out of 10, as opposed to 1 possibility out of 10. That is, if the system matures or changes into something else, that it would then tend to change into macrostate number 2. Similarly, if we found ourselves in macrostate number 3, again, we would tend to move towards macrostate number 2 when the system changes, simply because it is just more likely that we would end up in macrostate number 2 because there's just more possibilities for macrostate number 2 to occur. Moving forward, we are now going to examine something called a partition function. First, we will re-examine the Boltzmann distribution law, which we have already used. Specifically, n2 over n1 is equal to e raised to the power of negative delta E over kb times T. And what this looks at is the relative populations of 2 energy levels. This expression comes in other forms. For instance, the population of a single energy level, Ni, is equal to n naught times E raised to the power of Ei divided by the Boltzmann constant times the temperature, where Ei is just the energy of a specific energy level. And in this case, we can calculate the total population by taking the sum over Ni, where Ni again is equal to n naught times the sum of E raised to the power of Ei divided by the Boltzmann constant divided by temperature. Now, Ni over n gives the fraction of the population in energy level I, or the probability of being in state I, and can be expressed as Ni over n is equal to E raised to the power of negative Ei divided by the Boltzmann constant times the temperature, divided by the sum over I of E raised to the power of negative Ei over the Boltzmann constant times temperature. Dividing this expression of one energy level by another energy level returns the originally presented form. The sum term in the Boltzmann distribution law has great theoretical importance and is called the partition function, or Q. It is defined as the sum over I of the exponent of negative Ei divided by the Boltzmann constant times the temperature, where E sub I is the energy of state I, and the summation extends over all states. One thing to keep in mind is that Q has no units, it's just a number. It tells us the number of accessible states to a particle at a given temperature. For example, at T is equal to 0, only the ground state N naught is accessible, and we set E naught to be equal to 0. Finally, it can be used to calculate various thermodynamic properties. Let's now apply this definition to a three-level system so that we can calculate its partition function. And so what we have in this example is that we have a three-level system where one level is at 0 joules, the second level is at 2.0 times 10 to the minus 21 joules, and the third energy level is 8 times 10 to the minus 21 joules. And what we want to do is we want to find the partition function Q at 300 degrees Kelvin. So the first thing that we're going to determine in order to do this is we're just going to calculate what is Kb times T, what is the Boltzmann factor times this temperature. And so in this case what we are going to do is multiply the Boltzmann factor, 1.381 times 10 to the minus 23, and we're going to multiply that by 300 Kelvin. And so the units for this are Kelvin, and the Boltzmann factor is joules per Kelvin. And so in the end, in this multiplication, what we're going to end up with is a value in joules. That number is going to be 4.14 times 10 to the minus 21 joules. So now that we have this value ends up being the denominator in the exponent for the partition function, or the definition of the partition function. So in general, the definition is Q is equal to the sum over all the states I times, or E raised to the power of negative EI over KBT. And so we just found this denominator, and all we're going to do now is evaluate the sum, where at each value for I, we're going to sub in for the three energies. Written explicitly, this is E to the negative E naught divided by KBT plus E to the negative E1 over KBT plus E to the negative E2 over KBT. And if I substitute in numbers, well, the energy of the 0th energy level, or of the ground state, is equal to 0, so we can just plug in 0 for that. For the first energy level, that's 2.0 times 10 to the minus 21, so E to the negative 2.00 times 10 to the minus 21. This is divided by KBT, which we found to be 4.14 times 10 to the minus 21. To that, I'm going to add E raised to the power of negative 8.00 times 10 to the minus 21, and that I'm going to divide by 4.14 times 10 to the minus 21. And so if I evaluate all of these, E to the power of 0, well, that's equal to 1, plus E raised to the power of negative 2 times 10 to the minus 21 divided by 4.14 times 10 to the minus 21, that's equal to 0.617. And finally, E raised to the power of negative 8 times 10 to the minus 21 divided by 4.14 times 10 to the minus 21 is equal to 0.145. And so that means then the partition function for this system is 1.76. We are now going to examine how partition functions can be used to derive thermodynamic quantities. To do this, we need to understand how the different expressions of energy, translational, rotational, and vibrational, are accounted for. Given that the total energy of a molecule is simply the sum of all the different types of energy that it possesses, then we can just substitute in this sum into the definition of a partition function. Then, using the property of exponentials, where the sum can be separated into a product of exponential terms, what we are left with is a product of the three partition functions, where each one represents a type of energy. Let's look at the three types. What we will see is that the expressions that are used to quantify the energy of each type are quantum mechanical in nature. It's alright if you have not taken a quantum mechanics course yet, as I only mention where the energy terms come from for interest's sake. The first type we'll look at is for translation. The particle in a box model is used to derive the energy expression. Substituting this into the Q-trans expression and simplifying it gives 2 pi times m times the Boltzmann constant times T raised to the power of 3/2 times the volume V divided by Planck's constant H raised to the power of 3. One thing to note is that the volume of container V is in liters, or in decimeters cubed, and m, the mass, is the mass of the molecule. The second type is rotational motion. The rigid rotator is the model used to derive the energy expression. Substituting this into Q rot expression and simplifying it gives 8 times pi squared times the moment of inertia I times the Boltzmann factor times the temperature divided by sigma times Planck's constant h squared. The sigma is something called the symmetry number, which is the number of indistinguishable orientations that can be produced by rotations less than or equal to 360 degrees. We include this parameter so that we do not overcount states that are the same. For example, for a homonuclear diatomic molecule, say hydrogen, there are two indistinguishable orientations, being at 180 degrees and 360 degrees, so sigma is equal to 2. For a heteronuclear diatomic molecule, say HF, there's only one indistinguishable orientation, being a full rotation to 360 degrees, so sigma is equal to 1. The third type is vibrational motion. The harmonic oscillator is the model used to derive the energy expression. Substituting this into the partition function and simplifying gives 1 over 1 minus e raised to the power of h nu divided by the Boltzmann constant times t, where nu is the frequency of the vibration. If there are several vibrational modes, as for polyatomic molecules, then take the product of all the partition function values, each with their own frequency nu. Also, a partition function or a vibrational partition function equal to 1 indicates that only the ground state is thermally accessible. This is typical at room temperature. Let's now do an example where we calculate the molecular partition functions. In this case, what we're going to do is we're going to calculate it for a CO2 molecule. We're going to calculate basically the three molecular partition functions at 300 Kelvin. We're going to assume our CO molecule is in a box of 1 liter. We're going to say that its moment of inertia is 1.45 times 10 to the minus 46 kilogram meter squared, and the fundamental frequency of vibration for the CO molecule is 6.4 times 10 to the 13 inverse seconds. So the first one that we're going to start with is translation. And that means then Qtrans is going to be equal to 2 pi times m times kBt raised to the power of 3 over 2 times the volume divided by Planck's constant cubed. We substitute in all the numbers. We have 2 pi. In this case, the mass of carbon monoxide, well, if we go to our periodic table, carbon has a mass of 0107 AMUs. Oxygen has a mass of 15.999 AMUs. And then each AMU is 1.66 times 10 to the minus 27 kilograms. So there's the mass of carbon monoxide. We're going to multiply that by by the Boltzmann constant, 1.381 times 10 to the minus 23. We're going to multiply that by the temperature, 300 Kelvin. All of this is raised to the power of 3 halves. Multiply that by the volume, which is equal to 1. And we'll divide this by Planck's constant, 6.626 times 10 to the minus 34, raised to the power of 3. What we get is a numerator of 4.21 times 10 to the minus 68, divided by 2.91 times 10 to the minus 100. And doing this division, what we get is 1.447 times 10 to the 32. And so what we can see is that this is a very large number. And so what this large number means is that there are the energy levels, or the spacing between energy levels is going to be very small. And basically that just means that there's very little energy difference between these energy levels, and hence that's why that there are so many that are thermally accessible. Let's now move on and calculate the rotational partition function. So that means Q rot, that's going to be equal to 8 pi squared times the moment of inertia I times Boltzmann's constant times the temperature. That's divided by sigma times Planck's constant squared. When I substitute in numbers, what we'll get is 8 pi squared times the moment of inertia, which was given in the problem, 1.45 times 10 to the minus 46, times 1.31 or 381 times 10 to the minus 23, times 300 divided by 1 times 6.626 times 10 to the minus 34 squared. And in this case, I substituted in 1 for the symmetry factor sigma because CO, just like HF, has only one identical or rotation, where if we were to spin this thing completely around 360 degrees, we would get the exact same thing back. And so that's why my sigma in this case is equal to 1. When we evaluate these numbers, the final number that we get for Q rotation is 108. And so what this says is that there's 108 accessible energy levels for the system at 300 Kelvin. The final one is vibrational. And so in this case, my Q vibrational, that's equal to 1 over 1 minus e to the negative h nu over kb t. And so as an aside, let's just calculate the minus h nu over kb times t. In this case, we've got negative 6.626 times 10 to the minus 34. That's going to be times 6.4 times 10 to the 13, which was a number given in the problem, being the fundamental frequency for the CO bond. Boltzmann's constant 1.381 times 10 to the minus 23, and that's going to be multiplied by 300. And so then this number is going to be equal to negative 10.24. What that means when I substitute that in is I'm going to get 1 over 1 minus e to the negative 10.24. And so basically this number, this e to the negative 10.24, is going to be very, very, very small. And so in effect, what I'm going to get is 1 over 1. And so my answer is effectively equal to 1, which again isn't something that's surprising. It's very well known that vibrational partition functions are very small, and that in this case around room temperature only the ground state is accessible. So just as a point of comparison, let's just redo this calculation at 3000 Kelvin. So we've got our partition function for vibrational modes, for the one vibrational mode here, 1 over 1 minus e to the negative h nu over kbt. Again, we're going to calculate this h nu over kbt as a separate thing, just as an aside, minus 6.626 times 10 to the minus 34, that's times 6.4 times 10 to the 13, divided by 1.381 times 10 to the minus 23. In this case now I'm just going to substitute in 3000. And what that does is just move this decimal place over one. So it's now negative 1.024 is what this factor is. And so if I were to substitute that in now, 1 minus e to the negative 1.024, well, this exponential is now a number that's comparable to 1, which means that my qviv now is going to be equal to 1.56. And so what this says now is that more than the ground state is actually accessible. But you can see that this number is still very, very small compared to the rotational and the translational. And so you can see how little of an effect the vibrational modes have on the partition function, being how few vibrational states are accessible even at these highly elevated temperatures. Where at 3000 Kelvin we would expect that the CO molecule to probably have decomposed before it actually has any significant contributions from vibrational excitations. Partition functions can be used to find state functions. For example, to find the internal energy, we begin with the energy per molecule, being capital E over capital N, and that's equal to the sum over I of Ni times Ei, divided by the sum over I of Ni. Substituting in the number of particles in state Ni, which is equal to N naught e to the negative Ei over Kb times T, gives E over N being equal to the sum over I of N naught Ei times E to the negative Ei over Kbt, all over the sum of I times N naught E raised to the power of negative Ei over Kbt. In this case, I've also multiplied both sides by capital N, so that I've just got the energy is equal to this expression. We can divide out the N naughts, And also the denominator in this case is equal to the definition of the partition function Q. So in this case we have a final expression for the energy is equal to capital N times the sum over I, EI times the exponent of negative EI over kBt divided by the partition function Q. To simplify this expression further, we must first return to the definition of a partition function and take the derivative as a function of temperature at constant volume. So the partial derivative of the partition function with respect to temperature at constant volume is the same as taking the derivative of the sum over I of E raised to the power of EI over kBt. And when we take that partial derivative with respect to temperature, what we end up with is 1 over kB times T squared times the sum over I of EI times e to the negative EI over kBt. Rearranging this so that we have the sum written onto one side of the equation and everything else to the other side, we get the sum over I times EI times e to the negative EI over kBt, and that's equal to kB times T squared over the partial derivative of the partition function with respect to temperature at constant volume. The left-hand side of this equation is in the numerator of our current expression, presented on the previous slide. Putting this result into our definition gives E being equal to N times the Boltzmann constant times T squared times the partial derivative of the partition function with respect to temperature at constant volume divided by the partition function. Now, we have the partial derivative of Q with respect to T at constant volume divided by the partition function Q. Another way of expressing this is the partial derivative of the natural logarithm of Q with respect to T at constant volume. If the chain rule is applied to this expression, we take the derivative of the outer function first, being the natural logarithm of Q, which is 1 over Q, and then multiply that by the derivative of the inner function Q with respect to T. So substituting in the partial derivative of the natural logarithm of Q with respect to T at constant volume into our expression, and assuming that we are operating on 1 mole of gas, gives the molar energy being equal to R times T squared times the partial derivative of the natural logarithm of Q with respect to temperature at constant volume. If we add heat to the system at constant volume, then no work is being performed. Therefore, this energy expression quantifies the internal energy of the system. The molar internal energy naught is simply the energy at 0 Kelvin and is meant to define a reference energy for the molar internal energy. This expression shows the direct relationship between the partition function and a thermodynamic state function. Statistical mechanics is a powerful model which can be used to quantify many macroscopic observations. So in our final example, what we're going to do is take that expression that we just derived and we're going to calculate the internal energy for 1 mole of a monatomic gas using partition functions. And then once we have that, then we're going to then determine the molar heat capacity at constant volume. So that expression that we just calculated was the molar heat or the molar internal energy minus the molar internal energy naught, and that's equal to RT squared times the partial derivative of the natural logarithm of the partition function with respect to temperature at constant volume. And the thing that we have to remember is that we're dealing with a monatomic gas, like say argon. And so because it's monatomic, then it can translate in any of the 3 Cartesian directions, being x, y, or z. However, because there's only 1 atom per molecule, then there's no rotational degrees of freedom and there's no vibrational degrees of freedom because it's symmetric under rotation and it's not vibrating with anything. That greatly simplifies our expression for our partition function because then we only have to worry about the translational part, or the translational partition function. So let's substitute that directly into our expression. RT squared, we're going to be taking the partial derivative of the natural logarithm of Q trans, which is 2 pi m times kb times t raised to the power of 3/2 times the volume divided by Planck's constant cubed. And for that, then this is this derivative with respect to temperature, all at constant volume. Well, if we take this derivative, when we take the natural logarithm of something, then the first part of this, the derivative of the outer function, is just to take 1 over all of the internal part to the natural logarithm. So that means we have h cubed on top divided by 2 pi mkbt raised to the power of 3/2 times the volume. And then we have times the derivative of the inner function. Well, we're going to get a 2 pi mkb raised to the power of 3/2 divided by h cubed times v, because all of that is a constant, because the only thing that is going to be directly affected by this derivative is just this temperature term. So really all we're doing is we're just taking the derivative of the temperature raised to the power of 3/2. And so when we take that derivative, what we end up with is 3/2 t raised to the 1/2. And that's basically what I'm just writing into here. This is the only part where that derivative of the inner function really changes anything. So now that I have that, I can start crossing off terms. And before I do that, I'm going to just make sure I keep adding in my RT squared at the front. But here now I can cross off Planck's constant cubed. I can cancel off 2 pi. I can cancel out the m. We can cancel out the Boltzmann's factor. And we can cancel out the volume. And so what we're left with then is RT squared, and here I've got a 3/2, and then I've got a t raised to the 3/2 on the bottom and the t raised to a 1/2 on top. So 1/2 divided by 3/2 gives me a 1 over t. Simplifying this expression, well, I can cross off the square on top and the 1 over t, and so what we're left with is 3/2 RT, which is exactly what we had determined previously a couple of lectures ago for the internal energy of a monatomic gas, where each part of the monatomic gas contributed 1/2 RT for each degree of freedom, being motion in the x, the y, and the z direction. So now that we have that, and it's very remarkable that we're able to just calculate this from partition functions, but from that we can now determine what is the molar heat capacity at constant volume. Because to do that, all we're going to do is we're just going to take the partial derivative of the molar internal energy divided by the molar internal energy naught with respect to temperature at constant volume, which is the definition of the molar heat capacity at constant volume. When we substitute in our expression for the molar internal energy minus the molar internal energy naught, we get 3/2 RT. We're taking the partial derivative with respect to temperature at constant volume. And what we end up with is, well, the 3/2 RT comes up front, so we're just taking the derivative of t with respect to t, which just gives us 1. And so in the end, we just get 3/2 R, which again is exactly what we had determined before when we did this from the equipartition theorem. Here is a summary of what was covered in this lecture. A microstate quantifies the state of individual molecules, while a macrostate groups together microstates with similar properties. As the number of atoms increase, the number of likely observable macrostates decreases. This is because each microstate is assumed to be equally likely to be visited, and many microstates tend to fall under a few macrostates for large numbers of atoms. The number of microstates in a distribution is found by calculating W, which is equal to n factorial, where n is the total number of states, divided by the product of ni factorial, where ni is the number in each individual state. This value can serve to represent the probability of a particular macrostate occurring. Assuming that each microstate is equally likely, then the more microstates in a given macrostate means that the more probable that macrostate will occur. The partition function, which quantifies the number of accessible states at a given temperature, is determined as the sum over I of e raised to the power of negative of the energy of the ith state divided by the Boltzmann constant times the temperature. And finally, the partition function is used to determine thermodynamic state functions, such as the internal energy. Welcome to Lecture 7. In this lecture, we will discuss the entropy as well as the second and third laws of thermodynamics in order to apply them to chemical systems to determine if the process is spontaneous. This lecture will be presented in 4 pieces. In the first part, entropy will be defined, as well as what it means for a process to be spontaneous. Next, the second law of thermodynamics will be given, and several examples of changes in entropy will be shown. Then the third law of thermodynamics will be defined, And finally, we will combine the second and third laws to apply standard molar entropy to chemical reactions to determine if a process is spontaneous. Entropy, typically denoted as a capital S, is defined as the Boltzmann constant times the natural logarithm of W, where W is the number of microstates in a given macrostate. A lot of reference material defines entropy as a measure of disorder. A better simile is that it is a measure of uncertainty, since it is not usually known which microstate the system is in. The uncertainty is quantified as the number of states that a system can occupy given a total energy for the system. One example calculating entropy for a system uses our 3-molecule example with a total energy of 3. Since there is one microstate for macrostate 1, then the entropy for macrostate 1 is the Boltzmann's constant times the natural logarithm of 1, which is equal to 0. There are 6 microstates for macrostate 2, so the entropy for macrostate 2 is the Boltzmann's constant times the natural logarithm of 6. And there were 3 microstates for macrostate 3. Thus, the entropy for macrostate 3 is Boltzmann's constant times the natural logarithm of 3. This means that the second macrostate for this system has the highest entropy. It follows that it is the most uncertain since it has the most microstates. On the other hand, there is no uncertainty for macrostate 1, since there is only one microstate. Now, entropy is used to define if a process is spontaneous. This is in contrast to enthalpy, where if a process is exothermic or endothermic, are properties typically used to describe if a process is favorable. This transfer of heat at constant pressure does not, however, indicate if a process will happen or not. That is what it means for something to be spontaneous. In other words, a spontaneous process is a process that has a tendency to occur without work needing to be done. In contrast to this, a non-spontaneous process is one that can only happen by doing work. Bear in mind that the spontaneity of a process says nothing about the rate at which it occurs. We also intuitively know what it means for a process to be spontaneous. One example is a gas expanding to fill a volume. What is not spontaneous is all the gas particles moving to one corner of the box. That won't typically happen unless work is put into the system to move all of the gas particles there. Another example is that of a plate shattering, which can be seen by following the link in the slide. It is not spontaneous for all the pieces of the plate to come back together and form the plate. So here's what we know about entropy and spontaneity. Entropy is a measure of the order of magnitude of the number of microstates in a given macrostate. Each microstate is equally likely. Therefore, the macrostates with more microstates are more probable to be observed. So, systems will tend to move towards macrostates with higher entropy, as they will naturally find these macrostates randomly. This means that spontaneity and entropy are linked, since processes which increase entropy are spontaneous. In other words, entropy is time's arrow, where we associate increasing entropy with time moving forward. This idea is in fact the second law of thermodynamics, which states that the entropy of an isolated system tends to increase. One way to quantify this statement as an equation is to define a change in entropy, since this is the quantity that tends to be positive. It can be written as delta S is equal to Q reversible divided by T, where the heat transfer, or Q, is used, instead of, for example, work, because a quantity that describes chaos should be quantified with a transfer of energy that quantifies random motion. Q reversible means that the heat is transferred in small packets and dispersed evenly. Temperature in the denominator takes into account the entropy already present for a system at a specified temperature. And entropy is a state function, so it's path independent. Let's do a quick example where we calculate the change in entropy using this definition. So in this example, we're talking about a reversible transfer of 100 kilojoules of heat into a large mass of water at 273 Kelvin. And so going back to our definition of entropy, we have the change in entropy is equal to the reversible change in, or the transfer of heat divided by the temperature. And so I can basically just write in the terms that are given in the problem, 100 times 10 to the 3, because I'm going to express this in joules, divided by 273. And so then the answer would be 366 joules per Kelvin. Let's now look at the case of isothermal expansions of gases. Recall for the isothermal, being no change in temperature, expansion of an ideal gas that the work is equal to the negative heat transferred. Since the work is equal to negative nRT times the natural logarithm of the final volume divided by the initial volume for an isothermal reversible expansion, then the change in entropy is equal to n times r times the natural logarithm of the final volume over the initial volume. Note that even though we used a reversible transfer of heat to find this relationship, the change in entropy is a state function, so this result is valid for irreversible changes. Here is a quick example where we're going to examine the change in entropy due to expansions of gases. And so in this case, we're trying to find the change in molar entropy of a gas that it's basically expanding isothermally to twice its initial volume. And we're going to do this in two steps, or in two parts, where we're first going to calculate if this process is reversible, and then we're going to find out what it means if it's irreversible. So in the first case, we're going to talk about reversible changes. We're saying our V final is equal to 2 times our initial volume. And if we go back to our definition of a change in entropy, that's equal to Q reversible over T. As we said in the previous slide, Q reversible is equal to the negative of the work that's performed. And we know that for an isothermal reversible expansion, the work that's performed is negative nRT times the natural logarithm of Vf over Vi. And that's divided by T. So in this case, my minus signs cancel out, my T's cancel out, and what we're left with is this change in entropy term that we had shown in the previous slide, nR times the natural logarithm of Vf over Vi. So if we continue to calculate this value, well, since we're trying to find the molar entropy of this, then that means I can divide both sides by n, because that's what will give me a molar entropy on the left-hand side. And I'm left with now just the gas constant R times the natural logarithm of Vf over Vi. And since I know that Vf is equal to 2 times Vi, I can write 2Vi over Vi. And so now this cancels out my Vi's. And so what I'm left with is 8.3145 times the natural logarithm of 2. And what that's equal to is 5.76 joules per mole Kelvin. How is this different for an irreversible expansion? Well, in this case, since we know that delta S is a state function, what that means is that it's independent of the path that it takes to go from one state to the next. And since its state in this case is defined by the volume, then we know that the molar entropy change for the irreversible process is just going to be 5.76 joules per mole Kelvin. It is expected that the entropy of a system increases with an increase in temperature. To show this, we will start with small changes in entropy, or ds, is equal to small changes in Q reversible, or dq rev, divided by T. And since for small changes in heat transfer, dq is equal to the heat capacity times dt, then we can substitute this in and get ds is equal to C dt over T. Now if we integrate both sides, what we get is delta S is equal to the heat capacity C times the natural logarithm of the final temperature divided by the initial temperature. Note that if the process is performed at constant volume or pressure, it's all right to substitute the corresponding heat capacity term in. Now let's do a quick example where we calculate the change in entropy when we heat up a sample. So in this case, we're going to calculate the change in molar entropy for a gas when it's heated from 20 degrees Celsius to 30 degrees Celsius at a constant volume, where they give us the molar heat capacity at constant volume. So in this case, again, we go back to this term that we just calculated, being delta S is equal to the heat capacity times the natural logarithm of the final temperature over the initial temperature. In this case, delta S is equal to, well, we've got the number of moles times the molar heat capacity at constant volume times the natural logarithm of 30 plus 273.15 divided by 20 plus 273.15, being I'm converting my degrees in Celsius into Kelvin. I then divide both sides by n, so I get a molar heat capacity on the left-hand side, and I can substitute in my molar heat capacity at constant volume, 22.44 times the natural logarithm of 303.15 divided by 293.15. And so what we're left with is 0.75 joules per mole Kelvin. Keep in mind that when the heat capacity cannot be considered a constant, for example solids at very low temperatures, then the starting point is still for infinitesimal changes in entropy, or ds, is equal to the heat capacity C times dt over T. Then a substitution for the function that describes the heat capacity is inserted and integrated between the initial and final temperatures. The figure on the right illustrates this calculation. Another case to consider is what happens at phase boundaries. The entropy of a substance increases when it melts and when it vaporizes. The transfer of energy as heat when the substance is at its melting or boiling point is reversible, and if the pressure is held constant, then the entropy of fusion is equal to the heat of fusion divided by the temperature of fusion, and the entropy of vaporization is equal to the heat of vaporization divided by the temperature at vaporization. Now here's an example where we're going to deal with enthalpy of vaporizations. And in this case, we're looking at a case where we're trying to calculate the entropy of vaporization of water at 25 degrees Celsius, where we're given a heat capacity at constant pressure for liquid water, a heat capacity at constant pressure for gaseous water, and finally we're given the heat of vaporization at 100 degrees Celsius, or 373 Kelvin. And so the process that we're looking at is that if I'm just drawing a plot where temperature is increasing as it goes up, what we're interested in is understanding what is this entropy change as I go from liquid water to gaseous water, or vapor, at 25 degrees. The information that we're given, though, doesn't allow us to do this direct calculation, but instead what we have to do is we have to heat up our liquid water until we get to liquid water at 100 degrees Celsius. We then convert it to water vapor, and then we cool it back down so that we can then get it back at 25 degrees Celsius. And because we have a state function, or because entropy is a state function, going straight across from just liquid to gas at 25 degrees Celsius, well, we can also use this roundabout route where we go up to 100 degrees Celsius to then use the values that are provided and then cool it back down after it does the phase transition to find gaseous water at 25 degrees Celsius. We can use that also to find the change in entropy for this process. So then to calculate this process, we're just going to break this down into 3 steps, where the first step is just going to be this heating process, the second step is just going to be this phase transition, and then the third step is going to be this cooling process. So if we start with step 1, then we're just heating the water. And so then we have our delta S, well that's equal to this integral of Ti to Tf of the heat capacity times dt over T. And in this case, they give us the heat capacity at constant pressure, liquid water, which is a 75.29. And so I can then substitute in N times CPM, since our process is at constant pressure, our Ti and our Tf. That's for our bounds of our integration. And we have dt over T. And in this case, then I can move this N that I have here, divide both sides by N because I'm asking for a molar heat capacity, or a molar entropy. So delta S over N, CPM 75.29. This integral of dt over T is the natural logarithm of T, evaluated between 25 plus 273.15 to 100 plus 273.15, since we always write these things down in Kelvin. And so then once I evaluate this term, what I end up with 16.88 joules per Kelvin mole. The second step in this process, well, that's the phase transition. So we have the change in entropy of vaporization. Well, that's equal to the heat of vaporization at 100 degrees divided by the temperature. And so in that case, what we have is our delta H of vaporization at 373, so that's 40.7 times 10 to the 3, just because I want to express all this stuff into joules. Since it's a molar heat capacity, that I'm going to multiply by N to end up have the total amount, and then I'm going to divide that by 373 since that's the temperature this number is from. And so what I end up with is the entropy of vaporization divided by n, since I divide both sides by n. And when I evaluate the 40.7 times 10 to the 3 divided by 373, I end up with 109.1 joules per mole Kelvin. The final step is the cooling back down step. And so in that case, I go back to calculating this integral again, where I've got the integral over Ti to Tf of the heat capacity times small changes in temperature divided by the temperature. Well, in this case, my heat capacity is a molar heat capacity at constant pressure. So then that's times n times Ti to Tf, the integral of Ti to Tf, dt over T. In this case, I'm going to divide both sides by n to again get a molar entropy. My molar heat capacity at constant pressure is 33.58 for gaseous water, which is what I'm evaluating right now because that's what I'm cooling down. The integral of dt over t is the natural logarithm of t final over t initial, where t final is 25 plus 273.15 divided by 100 plus 273.15. And so what that leaves me with is a molar entropy for cooling down gaseous water being equal to negative 7.53 joules per Kelvin mole. Now all we need to do is just sum up these three values that we've calculated for each of the three steps, where this first step was heating liquid water up to its boiling point. We have the enthalpy, the entropy of vaporization. And then finally we have the molar entropy change as we cool down gaseous water back down to 25 degrees Celsius, so that again we can determine what is this direct pathway, or what is the molar entropy for the transition between liquid water and gaseous water at 25 degrees Celsius. So that just means I'm going to write delta S total divided by n, and that's going to be equal to 16.88 plus 109.1 minus 7.53. And so the total entropy change for this process is 108.4 joules per Kelvin mole. Changes in entropy of the system can also affect the entropy of the surroundings, since heat can be transferred into or out of the surroundings. Using the same definition as before, delta S of the surroundings in contact with the system is delta S surroundings is equal to the reversible heat transfer with the surroundings divided by the temperature. Since the surroundings are so enormous compared to the system, its pressure will not change, so we can write the heat transfer Q as the change in enthalpy of the process, being delta S of the surroundings is equal to the change in enthalpy divided by the temperature. Since the enthalpy is a state function, then it does not matter if the process is reversible or not. As a result, we can write delta S of the surroundings is equal to Q of the surroundings divided by temperature, which is equal to the negative of the heat transfer of the system divided by the temperature, where the minus sign reflects the heat coming into the surroundings represents heat leaving the system, and this is equal to the negative change in enthalpy divided by the temperature. Let's now look at an example which illustrates this point. So what we have is an ideal gas that's expanding isothermally from some initial volume to a final volume, and what we're going to calculate is the molar entropy change in the surroundings if the gas expands, in the first case, reversibly, and then if it expands freely, being that there's no external pressure. So if we look at the reversible case first, well, we know in this case that the work is equal to negative nRT, natural logarithm of Vf over Vi. And we know that in this case the work is equal to the minus of the heat transfer. And this is essentially because this is the first law of thermodynamics we're using, but the first law is the change in internal energy is the work plus the heat. But since it's isothermal, then the internal energy, or the change in internal energy, is equal to 0. So that means the work is equal to the negative of the heat transfer. What this means is that I can now solve for Q, and that means then the heat transfer of the system is just equal to nRT times the natural logarithm of Vf over Vi. Since the heat transfer of the system is the negative of the heat transfer of the surroundings, that means then Q surroundings is equal to negative nRT, natural logarithm of Vf over Vi. And so substituting this into the expression for the change in entropy of the surroundings, well, that's equal to the Q of the surroundings divided by T, and it's the reversible heat, and that's what we have happening. And so then that just means that I have nRT, natural logarithm of VF over VI divided by T, and so I can cancel out my T's, and I forgot a minus sign here. And so what we're left with is negative nR natural logarithm of VF over VI. What if now the expansion happens freely? What that means is that the external pressure is equal to 0. So if I was to calculate the work from this, well, the work by definition is the negative of the initial volume to the final volume, or an integral from the initial volume to the final volume of P external dV. But in this case, P external is equal to 0. So that means that my work is equal to 0. And then following through with this exact same formalism that I just calculated for the reversible process, well, I know that that means then that my heat transfer is also equal to 0, which means that the heat transferred to the surroundings is equal to 0, which therefore means that the delta S of the surroundings, that is also equal to 0. Let's now look at the third law of thermodynamics. It states that the entropies of all perfectly crystalline substances are the same at T is equal to 0 Kelvin. The convention is to set the entropy at 0 Kelvin to be equal to 0, meaning that there is only one arrangement in a perfectly crystalline substance. This is expressed using the definition of entropy where the natural logarithm of 1 is 0, so the entropy at T is equal to 0 Kelvin is also 0. Thus to find the absolute entropy of a substance being S, well, that's equal to the entropy at temperature T minus the entropy at 0 degrees Kelvin, and that's equal to the integral between 0 and T of the heat capacity divided by the temperature times small changes in temperature dt. The figure on the right illustrates the result of this integral, as the change in entropy as a function of temperature is continuous up until phase transitions. At these points, there's a change in entropy that's discontinuous due to the phase change. The third law gives us our reference point to calculate absolute entropies. However, not every substance is perfectly crystalline at 0 degrees Kelvin. For example, vibrational modes are still present. Additionally, there can be different orientations of molecules. For example, carbon monoxide, which is pictured on the slide, may arrange in either direction semi-randomly. The image on the left shows a perfect arrangement where all the CO molecules are arranged in the same direction, while the image on the right has an imperfect arrangement where one of the CO molecules is aligned opposite to all the others. This is just one example of where a perfectly crystalline structure may not exist. The residual entropy is the actual entropy of a substance at 0 degrees Kelvin. So let's now put these two ideas together, and what we're going to do is we're going to find the absolute entropy of carbon monoxide at 16 degrees Kelvin. And to do that, we're going to estimate the residual entropy of this 1 mole of carbon dioxide that we're going to calculate. And from that, then we're then going to be able to calculate the absolute entropy. So first we're going to do the residual entropy. And with that, we're going to start with just the standard entropy expression, Boltzmann's constant times the natural logarithm of the number of microstates. We know that CO has two configurations in its crystalline form at 0 degrees Kelvin. And so if we look at this for one CO molecule, then its entropy is equal to Kb times the natural logarithm of 2. And if we extrapolate this to 1 mole of CO molecules, well, then that entropy is just going to be equal to Kb times the natural logarithm of 2 raised to the power of Na, or Avogadro's number. And so using then the properties of being able to then pull down exponents in front of terms, then we would say its entropy is equal to Avogadro's number times Boltzmann's constant times the natural logarithm of 2. And then if we remember from before, Avogadro's number times Boltzmann's constant is equal to the gas constant. So then I can just write R natural logarithm of 2. And if I start substituting in numbers, I have 8.3145 times the natural logarithm of 2. And so that means then my entropy, or my residual entropy for carbon monoxide for 1 mole of it is 5.76 joules per mole Kelvin. So this is now the residual entropy at 0 Kelvin. And so in order to then find out the entropy at 16 Kelvin, we have to now do that integral where we're basically adding up all the entropy that's gained by the increase in temperature. And so to do that, we're just going to say, well, the entropy is equal to the integral between 0 and 16 Kelvin, and that's of the heat capacity, where I'm jumping ahead of myself here, the heat capacity divided by the temperature times dT. In this case, the heat capacity is equal to N times the molar heat capacity at constant pressure is what we're using. In this case, my N is equal to 1, since I have 1 mole, so it's really going to be CPM as inside that integral between 0 and 16 divided by temperature times dt. And so in this case, since we can see in our hint here that this heat capacity term is a function of temperature, I can't pull it outside of the integral sign. I actually have to substitute it in. So that means then this integral becomes integral of 0 to 16 of 9.5 times 10 to the minus 4 t cubed divided by t times dt. And so in this case, I can cross off terms, and so what I'm really left with is a t squared term. And so what this becomes now is then the integral of t squared, and so I can move out this constant out front, and so I have the integral of t squared times dt. And so the integral of the antiderivative of t squared, well, that's simply going to be equal to, with this constant out front, 9.5 times 10 to the minus 4, I have t cubed over 3, and that's going to be evaluated between 0 and 16. So if I do this fundamental theorem of calculus expression, what I'm going to have is 16 cubed divided by 3 minus 0 cubed divided by 3. And so what that leaves me with in the end is entropy from this integral, 1.3 joules per mole Kelvin. Let's now put this together. So we have basically, in this case, we have our residual entropy, and then we have this integral, so that this raises it to 16 Kelvin from 0 degrees Kelvin, and sort of the entropy that comes from those two parts. And if you remember from the slide where we were talking about absolute entropies, we had the entropy, in this case, we're going to say at entropy at 16 degrees Kelvin, minus the entropy at 0 Kelvin, or entropy naught, and that was equal to this integral of c dt divided by t. This was an expression that was written inside the slide. And so what we found here is we've determined this integral, and that's the number that we can then sub into there. We have our residual entropy, which is the entropy at 0 Kelvin, which is the number that we're going to be substituting into there. So therefore, to find the entropy at 16 degrees Kelvin, what we're doing is we're adding up that residual entropy with the entropy that we found from doing the integral, meaning the entropy that's now added to the system because we changed the temperature. And so what that means is then the entropy at 16 degrees Kelvin is simply going to be 5.76 plus 1.3. And so in the end, then I get an entropy value of 7.06 joules per Kelvin mole, which again is a combination of the fact that we have a residual entropy in the system because the carbon monoxide can be in one of two states, and we have a mole of that. And then also we have ourselves the entropy gain from the temperature change. And again, making a comparison with that slide where we had how the entropy increases with temperature, well, in that slide, that line started at 0, and that assumed that we had a perfectly crystalline system where the entropy at 0 Kelvin is equal to 0. But in our case, in this system, that entropy now starts at 5.76 joules per mole. So it just essentially means that our entropy isn't 0 at 0 Kelvin. It is in a perfectly crystalline system. And so then we're basically then just finding out that number as we extrapolate upwards using how entropy changes with temperature. And that's where basically we get to this 7.06, starting from the residual entropy of 5.76. Here is one reason why it matters that we can calculate absolute entropies. We can use them to quickly calculate if reactions are spontaneous. Similar to the standard molar enthalpy, we can define standard molar entropies, which represent the total entropy at 1 bar. These are absolute entropies typically reported at 298 Kelvin. these values can be used in the same way as the standard molar enthalpy in order to find the change in entropy of a reaction, which is the weighted sum of the standard molar entropies of the products minus the weighted sum of the standard molar entropies of the reactants. Finding the change in the standard total entropy of the reaction indicates if the reaction is spontaneous. So let's now do an example using standard molar entropies to calculate if a reaction is spontaneous. So in this case, what we're looking at is the combustion of hydrogen gas at 298 degrees Kelvin. And the rebalanced chemical reaction is simply 2 hydrogen gas molecules plus 1 oxygen gas molecules reacts and combust to form 2 liquid water molecules. And so the way we're going to break down this problem is into 3 parts. The first is what we're going to do is we're going to calculate the change in the standard entropy of the system. We're then going to calculate the change in the standard entropy of the surroundings. And then what we'll then find out is the total entropy change. And the total entropy change will simply be the summation of the change in entropy of the system and the change of entropy of the surroundings. So let's now find the first part to this problem, which is find the delta, or the change in entropy of the system. And so to find the change in entropy of the system, then we're going to use the standard molar entropies, and that is equal to the weighted sum of the standard molar entropies of the products minus the weighted sum of the standard molar entropies of the reactants. And so here for the products, I have 2 times, or 2 liquid water molecules. So the standard molar entropy is 2 times 69.91. And from that, I'm going to subtract off this weighted sum of the reactants. And so I have 2 times 130.684 plus 1 times 205.138. So the hint very easily gives us all the standard molar entropies that we need for the H2, the O2, and the H2O. But what you'll notice is that for the H2 and the O2, there's actually a standard molar entropy. And remember, this is because we're measuring the uncertainties in terms of the number of microstates that each of these gases can inhabit at room temperature at 298 Kelvin. And so I'm only making note of this because this is in contrast to the standard enthalpy of formation, which is something that we talked about a couple of lectures ago, where the H2 and the O2, well, this was their reference state. And so we defined the standard enthalpy of formation to be 0 for these 2 molecules. Whereas now in this case, when we're talking about standard molar entropies, well, the 0 for these molecules is at 0 degrees Kelvin. Whereas now, because we're looking at 298 Kelvin, even though they're in their reference states, hydrogen gas and oxygen gas, they still have a standard molar entropy because it gained a bunch of entropy as we summed from 0 Kelvin to 298 Kelvin. So moving forward with this calculation, we have 139.82, and from that I'm going to subtract off 466.506. And what I end up in the end is minus 326.7 joules per Kelvin mole. And so now the next thing that you may notice is that I have a minus sign out front, which means that my entropy in this case went down. But that should probably be a little bit surprising because we would expect that for a combustion reaction, where we're basically burning hydrogen and oxygen to form water, we should expect entropy to increase, because it's spontaneous. Or we would expect this reaction to be spontaneous. And so the one thing we have to keep in mind is that when we talk about the second law where we expect entropy to go up, it's for isolated systems. And in this case, our system isn't isolated. And that's why we also need to calculate the surroundings, because the system and the surroundings then produce this isolated system where, again, we would expect entropy to go up, which then we can then use to determine spontaneity. And that's why we're going to calculate delta S total, where we sum the system and the surroundings together. And so it's okay that this number is negative for the system, because what that means is that hopefully then the amount of entropy, or the change in entropy of the surroundings, is going to be a positive number, and it's going to be much bigger than 326.7 joules per Kelvin per mole, so that the total entropy change ends up being a positive number, thereby confirming to ourselves our what our intuition tells us that this reaction should be spontaneous. So then let's calculate the change in entropy of the surroundings. Well, in this case, we're going to use the fact that the heat then that was given off by the system is then the heat that's inputted into the surroundings. And because we're at constant pressure, because this reaction is going to be done in the open air, then we can then say that heat is actually equal to the enthalpy. And so we can actually then use, well, the standard enthalpy change for the reaction to calculate the change in entropy of the surroundings. And so what we would then write is the standard change in enthalpy for the reaction is equal to the weighted sum of the products minus the weighted sum of the standard enthalpies of the reactants. And so for the products, we have 2 times minus 285.8 times 10 to the 3, because this number was given in kilojoules, and so I multiply it by times 10 to the 3 to write it into joules. And then from this, I'm going to subtract off 2 times 0 plus 0. And so here it is with this point that I was making earlier, where we have standard molar entropies of these reference states, but we don't have standard molar enthalpies of these reference states. The standard molar enthalpies of these reference states are 0. And so in this case, then what we have is our change in enthalpy for the reaction is just equal to this 2 times minus 285.8 times 10 to the minus 3. Well, that's then minus 5.716 times 10 to the 5 joules per mole. And so it's this number then I stick back into my change in entropy of the surroundings. Well, I have a minus sign, and then I have minus 5.716 times 10 to the 5. And with that, I'm going to divide by the temperature. In this case, it's 298. And so then that gives me a change in entropy of the surroundings of 1.918 times 10 to the 3 joules per Kelvin mole. All that's left to do now is just to sum up these two numbers so that we can then find the total entropy change. And so from that, we're going to have the system, which is minus 326.7. And to that, I'm going to add 1.918 times 10 to the 3. And it's good that I wrote this in joules per mole for the system, as well as joules per Kelvin per mole for the surroundings. And so both these units are exactly the same. And so then what I get for my entropy change is 1591 joules per Kelvin mole. And in this case now we can see that the entropy in this case went up, which is again what we would expect for a combustion reaction, because we would expect it to be spontaneous. And so therefore our intuition has been confirmed with what we would expect out of this type of reaction in terms of calculating the entropy change for the total being the system and the surroundings. Here's a summary of this lecture. Entropy is defined as the Boltzmann's constant times the natural logarithm of the number of microstates in a given macrostate. A spontaneous process is a process that has a tendency to occur without work needing to be done. This is quantified by entropy since systems tend to evolve to macrostates with more microstates. This idea is encapsulated by the second law of thermodynamics, which states that the entropy of an isolated system tends to increase. The third law of thermodynamics states that the entropies of all perfectly crystalline substances are the same at T is equal to 0 Kelvin. And these two laws of thermodynamics can be used to quantify if a process is spontaneous by calculating the difference in the total entropies of a given temperature of the initial and final states. If the change in the total entropy is positive, then the process is spontaneous. Welcome to Lecture 8. In today's lecture, we will define two new state functions, the Helmholtz free energy and the Gibbs free energy, and we will use the latter to draw phase diagrams of single component systems. This lecture will be broken down into two parts. In the first, we will define two new state functions, the Helmholtz free energy and the Gibbs free energy. In the second part, we will use how the Gibbs free energy varies as a function of pressure and temperature to draw phase diagrams for single component systems. The phase boundaries on these diagrams can be defined using the Clapeyron equation and the Clausius-Clapeyron equation. Always quantifying both the entropy change for the system and the surroundings to determine spontaneity is cumbersome. Instead, it is convenient to write the change in entropy total in terms of the system alone. To accomplish this, let's start by writing that very small changes in the total entropy is equal to very small changes in the entropy of the system and that of the surroundings. For a reversible process, we can write that small changes in the entropy of the surroundings is equal to the negative change in the heat transferred from the system divided by the temperature. We saw this relationship in the lecture on entropy. This heat transferred can be rewritten into two different state functions depending upon the conditions. If the process is at constant volume, then it can be written as a small change in the internal energy. If the process is at constant pressure, then it can be written as a small change in the enthalpy. This slide is broken in half, where the left side is where the process is at constant volume, and the right side is at constant pressure. They will follow an almost identical procedure. In both cases, we will multiply through by negative t to get negative t ds total is equal to du minus t ds system for the constant volume process, and minus t ds total is equal to dh minus t ds system for the constant pressure process. At this point, we will define two new state functions. The Helmholtz free energy is defined as capital A, and it's equal to U minus Ts. The Gibbs free energy is defined as capital G, and it's equal to H minus Ts. If we calculate small isothermal changes in these new state functions, starting with the Helmholtz free energy, we get the infinitesimal change of the free energy minus T times d entropy system minus the entropy of the system times dt. The two terms with temperature and entropy arise from applying the product rule. For the Gibbs free energy, we get the infinitesimal change in the enthalpy times T ds system minus S system times dt. In both cases, the entropy of the system times dt term goes to zero because this is an isothermal process, so there aren't any small changes in temperature, which is what dt represents. What that means is that for both the infinitesimal change of the Helmholtz free energy and the Gibbs free energy is equal to the negative of the entropy of the total for the system. Therefore, quantifying Helmholtz or Gibbs free energies quantifies if a process is spontaneous. Let's now look at the Helmholtz free energy and determine what it represents. First of all, as was just stated, it can be used to determine if a process is spontaneous. Consider a process A plus B is in equilibrium with C plus D. We can calculate the change in internal energy and entropy of a process at a given temperature to find the change in Helmholtz free energy. This will tell us the change in the total entropy for the process times the negative temperature. This is very useful because the terms used to find delta A are all based on the system. The plot on the bottom left illustrates both entropy and Helmholtz free energy as a function of reaction coordinate, and you can see that they are mirror images of each other. As one increases, the other decreases. This is from the negative sign in the relationship between them. So, processes with positive entropy changes are spontaneous. This means that they must have a negative change in the Helmholtz free energy to be spontaneous. If delta A is equal to 0, then the system is at equilibrium. And finally, if delta A is greater than 0, then the reverse process is spontaneous. The change in Helmholtz free energy also quantifies the total work possible by a process. To show this relationship between delta A and work, we will assume that the process is reversible. At constant temperature, dA is equal to du minus T ds. Then, using the first law of thermodynamics, where du is equal to dW plus dQ, means that dA is equal to dW plus dQ minus T ds. Since T ds is equal to dQ, because it's a reversible process, then we can cancel out the dq terms, and that what we see in the end is that dA is equal to dW. Since this relation holds for each infinitesimal step, then delta A is equal to the total work. Let's now look at our first example where we're going to examine this relationship between the change in Helmholtz free energy and the total amount of work that can be extracted from a process. So what we're going to do first is we're going to consider the metabolism of glucose to water and carbon dioxide at 25 degrees Celsius. And because the Helmholtz free energy is a state function, then even though we're talking about something that's going to be metabolized, being the sugar, we can look at just the overall reaction, and since it's path independent, we can still get a calculation of the total amount of work that's possible by metabolizing sucrose. or sorry, glucose in this case. And so what we have here is some calorimetric measurements. We have the change in the reaction of the internal energy of negative 2801.3 kilojoules per mole, and the change in entropy for the reaction is 260.7 joules per Kelvin per mole. And so the question is asking how much energy can be extracted as work. So we'll just start with the definition of the change in Helmholtz free energy. Delta A is equal to the total work, which is equal to the change in internal energy minus T times delta S. Well, we're given a value for the change in internal energy, we're given a value for the change in entropy, and we know the temperature. So we'll just plug in those values. Negative 2801.3 minus 25 degrees Celsius plus 273.15, and that converts it to Kelvin. We're going to write our change in entropy in terms of kilojoules per mole. So that's going to be 260.7 times 10 to the minus 3. If I evaluate that second term, minus 2801.3 minus 77.7, and what we left in the end is minus 2879 kilojoules per mole. The one thing that I want you to notice about this result is that the total work that was calculated here is actually greater than the change in internal energy of the process. And why this is the case is because we have an increase in the entropy of the reaction. And so because of that, this reaction is spontaneous. It actually then helps contribute to being able to do more work than what is actually stored as the internal energy for this process. What about the Gibbs free energy? It can also be used to determine if a process is spontaneous. Consider again a process A plus B that is in equilibrium with C plus D. We can calculate the change in enthalpy and entropy of a process at a given temperature to find the change in Gibbs free energy. This will tell us the change in the total entropy of the process times the negative temperature. Similar to the Helmholtz free energy, this is very useful because the terms used to find delta G are all based on the system. The plot on the bottom left illustrates both entropy and Gibbs free energy as a function of reaction coordinate, and you can see that they are mirror images of each other. As one increases, the other decreases. This is from the negative sign in the relationship between them. So processes with positive entropy changes are spontaneous. This means that they must have negative changes in the Gibbs free energy to be spontaneous. If the change in Gibbs free energy is equal to 0, then the system is at equilibrium. And finally, if changes in Gibbs free energy is greater than 0, then the reverse process is spontaneous. The change in Gibbs free energy also quantifies the non-expansion work possible by a process. To show this relationship between delta G and non-expansion work, we will assume that the process is reversible. At constant temperature, dG is equal to dH plus TdS. Additionally, assuming constant pressure, we can use the definition of enthalpy being dH is equal to du plus pdV to get dG is equal to du plus pdV minus TdS. Then, using the first law of thermodynamics, we get dG is equal to dW plus dQ plus pdV minus dQ, where we can now cancel out like terms. Assuming that there is both expansion and non-expansion type work, denoted as negative pdV, and dW no expansion, meaning that is the portion of the work that is non-expansion type work, we can cancel out the pdV terms and be left with dG is equal to infinitesimally small amounts of non-expansion type work. And since this relationship holds for each infinitesimal step, then we can state that delta G is equal to the non-expansion work. Non-expansion work is any work that doesn't involve an expansion. Examples include electrical work in an electrochemical or biological cell, or other kinds of mechanical work such as winding of a spring or contraction of a muscle. The predominant example used in this course will be electrochemical work. On the right is a diagram of a fuel cell, which is one example of an electrochemical process. The hydrogen-rich fuel reacts at the anode to form protons and electrons. The electrons move through the circuit while the protons move through an electrolyte, where they both react with oxygen to form water at the cathode. The change in Gibbs free energy can be used to determine the amount of energy that can be used to do work from a cell such as this, since work must be done to push the electrons through the circuit. Let's do an example now where we're going to calculate the non-expansion work done by a fuel cell. So in this case, in a fuel cell, we can use natural gases such as methane and it basically does the same redox reaction as a combustion process to produce carbon dioxide and water. And what it does is it generates electricity. And so what we're going to do is we're going to calculate the maximum electrical work that can be obtained from 1 mole of methane at 25 degrees Celsius. So the first thing we should do is we should just write down what the reaction is. So in this case, it's a combustion reaction, as the problem states. And so we've got our methane, which is a gas, plus 2 times O2, which is also a gas. And that's going to then produce CO2, which is a gas, plus 2 times water. And that in this case is going to be a liquid. And we make sure that this is balanced. We have 1 carbon and 1 carbon. We have 4 oxygens and we have 2 oxygens plus 2 oxygens. And then we have 4 hydrogens and we have 2 times 2, so we have 4 hydrogens. To calculate the change in Gibbs free energy, then we're just going to go back to its definition, where we've got delta G is equal to delta H minus T delta S. And so in this case, what we'll do is we'll calculate for this reaction, which is the system in this case, we'll calculate the change in the enthalpy, and we'll calculate the change in the entropy. So starting with the change in the enthalpy of the reaction, delta RH is going to be the weighted sum of the heats of formation of the products minus the weighted sum of the heats of formation of the reactants. And so looking up these values in a table, what we find is that for the products, we have for the carbon dioxide, it's minus 393.509. And with that, we're going to add 2 times the heat of formation of water, which is negative 285.8. And from that, we're going to subtract off minus 74.9, and that's the heat of formation for the methane. And to that we're going to add 2 times 0, because the standard heat of formation of oxygen is going to be 0. We evaluate these two terms, we get minus 965.109, and to that we're going to add 74.9. And so in the end, our delta H for the reaction is negative 890.2 kilojoules per mole. Let's now calculate the change in entropy for the reaction. And we can follow the exact same template. It's a weighted sum of the standard enthalpies of the products minus the weighted sum of the standard enthalpies of the reactants. And so in this case, for the carbon dioxide, the standard enthalpy of formation is 213.6. To that I'm going to add the entropy for the water, which is 2 times 69.9. From that I'm going to subtract off 186.2, which is the entropy of the methane, and to that I'm going to add 2 times 205.0. And remember again, enthalpies for standard states do have values because again the 0 value for entropies is at 0 Kelvin, and since we're at 25 Kelvin then there is certainly an entropy for oxygen. I'm going to sum these two individual terms, 353.4 minus 596.2, which gives me an entropy of negative 242.8 joules per Kelvin per mole. And I just want to point out that these values that I substituted in, these are in joules per Kelvin per mole, whereas the values that are substituted in here for enthalpy, these are in kilojoules per mole. This is an important thing to note because now when we calculate our change in Gibbs free energy, we have to make sure that our enthalpy and our entropy are in similar terms so that we're actually adding apples to apples. And so all that means is that I'm going to use kilojoules per mole as my reference for my energy. So I can directly write in negative 890.2. To that I'm going to be subtracting off the temperature, which is 25 plus 273.15 to translate the 25 degrees Celsius into Kelvin. And then here for my entropy term, I'm going to write negative 242.8 times 10 to the minus 3 so that I can convert it into kilojoules. When I do that evaluation, what I get is negative 817.8 kilojoules per mole. Now, since the question was asking us for what is the work for 1 mole of methane, this number is in kilojoules per mole. So if I were to take negative 817.8 kilojoules per mole, and multiply it by 1 mole since I have 1 mole of methane, then that gives me negative 817.8. And so that's the total non-expansion work that can be extracted from this fuel cell reaction. Now there are 2 points that I want to also elaborate on here. The first of which that you'll notice is that our change in entropy is less than 0. And so what that means is that the work that can be extracted is less than the heat that's actually output, and the heat that we can see outputted is up here with the enthalpy. And basically what that means is that we lost some of the work that was possible through this reaction because we gained more order, and that was expressed here by our lowering of the entropy. The second point that I wanted to make here is that if this were a heat engine, then what that would mean is that the efficiency would be governed by 1 minus T cold over T hot. But in this case, what that would mean is that we would actually have no efficiency since the process is happening at 25 degrees Celsius. And that in reality, because it's an electrochemical cell, we actually get to extract the total amount of work that's calculated based on this electrochemical reaction as predicted by the Gibbs free energy. As for enthalpy, we cannot easily measure the absolute value of Gibbs free energies. We assign a value of 0 to the standard molar Gibbs free energy of formation of an element in its most stable allotropic form at 1 bar and 298 Kelvin. We can calculate standard molar Gibbs free energy of formation for each compound by determining the standard molar enthalpy of formation minus the temperature times the standard molar entropy. If the standard molar Gibbs free energy of formation is known for each component, for instance, they can be found from a table, then the change in standard molar Gibbs free energy for the reaction is equal to the weighted sum of the standard molar Gibbs free energies of formation of the products minus the weighted sum of the standard molar Gibbs free energy of formation for the reactants. We are going to focus on changes in Gibbs free energy in this course. One reason is because we operate in a constant pressure environment, which makes it easier to measure the change in enthalpy of a process, which is a part of the definition of Gibbs free energy. First, we will focus on single component systems. The image presented here is the phase diagram of carbon dioxide. Based on this plot, if you were given a pressure and a temperature, you would be able to determine the phase of carbon dioxide. This figure is based on the Gibbs free energy of the solid, liquid, and gas phases of CO2 as various different pressures and temperatures. When discussing if it is spontaneous for a given phase to form, it would be tempting to use the total Gibbs free energy. For example, for an ice cube floating in a large bath of water at 0 degrees Celsius, the total Gibbs free energy of the ice is smaller than the Gibbs free energy of the water since there is so much more water. However, the water will not freeze since the solid and liquid phase are in equilibrium at 0 degrees Celsius. We must use a quantity that is independent of the total amount of the substance. This issue is solved by using the molar Gibbs free energy. We can still write for a change in Gibbs free energy that the total number of moles times the molar Gibbs free energy of that phase, in this case denoted with a 2, minus the total number of moles times the molar Gibbs free energy of the second phase, in this case denoted with a 1. We can distribute out the number of moles so that the difference is simply between the molar Gibbs free energy. We can conclude that a change in molar Gibbs free energy being less than 0 still indicates a spontaneous process. Here is now an example where we're going to use the difference in molar Gibbs free energy between two phases to predict which phase will spontaneously occur at various temperatures. We're going to assume that we're going to be at ambient pressure, being 1 bar. But basically what we're going to do is we're going to calculate the change in molar Gibbs free energy between water and ice at 0 degrees Celsius, minus 10 degrees Celsius, and 10 degrees Celsius. And what we're going to use to do this calculation to find the difference in molar Gibbs free energy is the molar enthalpy and the entropy of fusion, where we're given the two numbers, the 6.01 kilojoules per mole for the molar enthalpy of fusion, and then we've got the 22.0 joules per Kelvin per mole for the entropy of fusion, basically changing ice to water. So the reaction that we're going to be looking at is H2O solid, being ice, is going to H2O liquid. And the equation we're going to use to describe this process to predict spontaneity is the change in Gibbs free energy. In this case, it's going to be the molar Gibbs free energy is going to be equal to the molar enthalpy minus the temperature times the entropy, or the change in entropy of this process, being the melting of ice. And we already know intuitively what's going to happen at the three temperatures that we've already outlined. At 0 degrees Celsius, the system's going to be at equilibrium, so we expect the change in Gibbs free energy to be 0. At minus 10 degrees Celsius, we expect that it's going to be ice is what's going to spontaneously be formed, so that means then that the reverse reaction is going to be the spontaneous process. And at positive 10 degrees Celsius, we know that liquid water is the expected phase that would be present, and so we would expect then the Gibbs free energy would tell us that the forward reaction is spontaneous. So let's now calculate these values at these three temperatures. So at minus 10 degrees Celsius, we have delta G is equal to, well, using the equation delta H minus TdS, I'm just going to plug in the numbers. The delta H for this process is 6.01. We're going to subtract off minus 10 plus 273.15, multiply that by 22.0 times 10 to the minus 3. And so the reason why I'm choosing to write this times 10 to the minus 3 is because, again, remember the units are given in joules per Kelvin per mole for the entropy, and for the enthalpy of fusion it's kilojoules per mole. And so I'm just making sure that my numbers are in the same units, being kilojoules. And when I evaluate this expression, what I end up with is 0.22 kilojoules per mole. And so just as what was expected, we expect that this tells us that the reverse reaction is the spontaneous reaction, meaning that we expect that ice will be the spontaneous process at negative 10 degrees Celsius. And just taking a second to be reminded of the sign convention, these numbers that are given in the problem, the molar enthalpy of fusion and the entropy of fusion, those are all basically to describe what happens for the forward reaction. And so for a Gibbs free energy for a spontaneous reaction, we would expect to get a negative number, or a number less than 0, to be spontaneous for the forward direction. And so because this is a positive number, then that means then the forward reaction is not spontaneous, it's the reverse direction, which is spontaneous. Now moving on to the second temperature, if we look at this at 0 degrees Celsius, again I'm going to plug in delta G is equal to, and I use the same numbers, 6.01 minus, and in this case it's going to be 0 plus 273.15, and that's going to be times 22.0 times 10 to the minus 3. We end up with a delta G being equal to 0. And again, we know that a delta G being equal to 0 means that we're in equilibrium. And again, this is what we would expect. At 0 degrees Celsius, we have the forward and reverse reaction being the solid and the liquid phase being in equilibrium. So the final temperature we're going to do this calculation at is 10 degrees Celsius. And so again, I'm going to write delta G, that's equal to 6.01 minus 10 plus 273.15 times 22.0 times 10 to the minus 3. And so now I'm going to get a delta G being equal to negative 0.22 kilojoules per mole. And so again, this means that the forward direction is spontaneous. Using this information, we can start to draw phase diagrams. In order to draw phase diagrams more precisely than the sampling method shown in the previous example, we must examine how the Gibbs free energy varies with pressure and temperature for an individual phase. Starting from the definition of Gibbs free energy, being G is equal to H minus Ts, we will substitute in the definition of enthalpy and the first law. So H is equal to W plus Q plus P times V. This means that G is equal to W plus Q plus PV minus Ts. For an infinitesimal process, dG is equal to dW plus dQ plus VdP plus PdV minus TdS minus S dt, where we apply the product rule for the PV and TS terms. Assuming only expansion work and a reversible process means that the infinitesimal change in work, or dW, is equal to minus p dV, and dQ is equal to TdS. And that means that we can cancel out like terms, and what we eventually get is dG is equal to V dP minus S dt. Based on this, we can now quantify how the Gibbs free energy changes as a function of temperature and pressure. Looking first on how the Gibbs free energy of a given phase changes with pressure, we will assume isothermal conditions. This cancels out the second term of our starting expression. If we then divide through by the number of moles, we get the infinitesimal change to the molar Gibbs free energy is equal to the molar volume times dP. We're going to integrate this expression, and by doing so, we have two cases. If the molar volume is essentially the same or is essentially constant during the pressure change, like for a solid or a liquid, then the last term comes out of the integral and we get a change in the molar Gibbs free energy is equal to the total molar volume times the change in pressure. If the molar volume varies significantly, like for a gas, assuming that it behaves ideally, we can substitute the ideal gas law in for the molar volume prior to integrating. This results in the change in molar Gibbs free energy being equal to RT times the natural logarithm of the final pressure divided by the initial pressure. Now let's look at when we vary the temperature. To simplify, we will assume isobaric processes. This means that the change in pressure is equal to 0, so the first term on the right-hand side cancels out. If we divide through by the number of moles, then we have the infinitesimal change in the molar Gibbs free energy is equal to the negative of the molar entropy times the infinitesimal change in temperature. We will assume that the molar entropy is constant so that it comes out of the integral, and therefore we find that the change in molar Gibbs free energy is equal to the negative of the molar entropy times the change in temperature. We can plot both how the Gibbs free energy varies with respect to both temperature and pressure. On the left-hand side of the slide is how the Gibbs free energy varies for the gas, liquid, and solid phase of a substance at a given temperature with respect to pressure. Notice that the solid and liquid parts of the plot are lines, reflecting that the molar volume varies little due to the change in pressure, and that the line representing the gas varies as a ratio of the natural logarithm of the initial and final pressures. On the right-hand side of the slide is how the Gibbs free energy varies for the gas, liquid, and solid phase of a substance at a given pressure with respect to temperature. Here all three plots are lines, since the molar entropy is assumed to be constant over the range of the change in temperature. We can use the information in either plot to determine the most stable phase for a given temperature and pressure by finding which phase is the lowest on the plot. For example, on the left plot, where the pressure varies, the gas phase will spontaneously form at low pressures. As the pressure increases, the gas and liquid lines meet, which represents a phase boundary. As the pressure is increased from this phase boundary, the liquid becomes the most stable phase. As the pressure increases further, the liquid and solid lines meet, which represents another phase boundary. For larger pressures, the solid phase will spontaneously form. Using similar deduction, we can use the plot on the right to predict which phase will spontaneously form as the temperature increases. At low temperatures, this is the solid phase. As the temperature increases, the solid and liquid lines meet, representing a phase boundary, and then the liquid phase will spontaneously form. For higher temperatures, the liquid and gas lines meet, again representing another phase boundary, and finally the gas phase becomes the spontaneously formed phase. The two plots in the previous slide are represented in this phase diagram as the slices drawn over the plot. The vertical cut, denoted as constant temperature, follows the plot on the left where we varied the pressure, where the gas phase was the most stable, then the liquid, and finally the solid phase. The horizontal line denoted as constant pressure represents the plot on the right from the previous slide, where the temperature is varied. At low temperatures, the solid phase is the spontaneously formed phase, then the liquid, and finally the gas at high temperatures. Let's now take what we've just learned so that we can calculate the change in molar Gibbs free energies of the solid and the liquid phases of water, where if we know that these systems begin at equilibrium at 0 degrees Celsius and at 1 bar, what happens when we increase the temperature by 1 degree Celsius? And so what we're going to do is assume that the molar entropy of ice is 37.99 and the molar entropy of water is 69.91 joules per Kelvin per mole. To do this, we're just going to simply calculate what is the change in molar Gibbs free energy as we increase the temperature of each of these phases from 0 degrees Celsius to 1 degree Celsius. And so if we do this for ice, then we know that if we're going to increase the temperature, then it's the negative molar entropy times the change in temperature. In this case, we know that the molar entropy is 37.99, and that's times 1 degree since we do 1 minus 0. And so in the end we get negative 37.99 joules per mole. When we look at it for water, what we end up is the exact same starting point, negative times the molar entropy times the change in temperature. In this case we have minus 69.91 times 1 minus 0. And so in this case then we get 69.91 joules per mole. So the question says to find the difference between these two changes in molar Gibbs free energies due to the increase in temperature. So then we're just simply going to write the molar Gibbs free energy change for the water minus the molar Gibbs free energy change of the ice. And so that's negative 69.91 minus 37.99. And so the difference between these two is negative 31.92 joules per mole. And so what this essentially tells us in the end is that the molar Gibbs free energy of the water is less than the change in molar Gibbs free energy of the ice. And so what we know for that we're trying to minimize Gibbs free energy for various phases, and that's how we predict which one is spontaneously formed. And so in this case we can then say that water is the spontaneously formed phase. And this is something that we expected. If we increase the temperature from 0 to 1 degree Celsius, then we would expect that water would be the spontaneously formed phase. Building phase diagrams can be done by taking slices as previously shown. However, a more efficient method might be to predict the boundaries between phases instead. Any point lying along the phase boundary represents a pressure and a temperature where a dynamic equilibrium exists between two phases where the rate of the forward and the reverse phase change reaction are equal. The YouTube video link shows what this process looks like on the molecular scale. To define a phase boundary analytically, we can use the Clapeyron equation. To derive it, we will start with the assertion that when two phases are in dynamic equilibrium, then the infinitesimal change in the molar Gibbs free energy of one phase is equal to the infinitesimal change in the molar Gibbs free energy of the other phase. For both of these infinitesimal changes in the molar Gibbs free energy, they are equal to the molar volume times dP minus the molar entropy times dt. When we subtract these two equations, we can group together terms and distribute out the dP and the dt. We can also set this subtraction equal to 0, since both values for the infinitesimal change in molar Gibbs free energy is the same. Thus, 0 is equal to the molar volume of the second phase minus the molar volume of the first phase, all times dP minus the molar entropy of the second phase minus the molar entropy of the first phase, all times dt. We will write the difference in molar volume as the change in molar volume for the transition, delta trans V, and the difference in molar entropy as delta Sm. We can also move one of the terms to the right-hand side to the left-hand side, giving change in molar volume for the transition times dP is equal to the change in molar entropy times dt. To continue with this derivation, we will recall that the change in Gibbs free energy is still equal to 0 because we are at a phase boundary. This means that 0 is equal to the change in enthalpy minus the temperature times the change in entropy. As such, the change in entropy is equal to the change in enthalpy divided by the temperature. We can substitute this into our derivation to get the change in molar volume of the transition times dP being equal to the change in enthalpy of the transition divided by the temperature times dt. Dividing both sides by the change in molar volume of the transition gives the Clapeyron equation, which is dP is equal to the change in enthalpy of the transition times dt divided by the temperature times the change in molar volume of the transition. For this result, we will assume that the change in enthalpy of the transition and the change in molar volume of the transition are independent of temperature and pressure over the range we are interested in. So using the Clapeyron equation in example, what we're going to do is we're going to use it to estimate the slope of the solid-liquid phase boundary for water, where we're given the enthalpy of fusion of 6.008 kilojoules per mole, and the densities of ice and water are 0.091671 and 0.99984 grams per centimeters cubed, and those are the densities of ice and water, and we're also given the molar mass. And then once we do that, once we calculate that slope, we're going to then estimate the pressure that's required to lower the melting point of ice by 2 degrees Celsius. And so the one thing I just want to draw or sketch in here first is the phase diagram for water looks something like this, where we have solid, gas, and liquid phases. And so what we're trying to then describe with the Clapeyron equation is this line right here, or at least that's what the question is asking us to figure out, is the slope of that line, because that's the boundary between solid and liquid. And so we're looking at a temperature of around 0 degrees, so that's going to be somewhere right here. And so we're basically sitting somewhere around here on the line, since we'll assume we're at 1 atmosphere, and that we're just trying to figure out the direction of that line, or the slope of that line around that point. So starting with the first problem, and if we start with just writing down explicitly the equation of the Clapeyron equation, which is dP over dt, and that's equal to the enthalpy of the transition divided by the temperature times the change in molar volume of the transition. And so here, when we're talking about trying to find the slope of our line, remember that our axes here are pressure on the y-axis and temperature on the x-axis. So in essence, what it is that we're trying to determine is dP by dt. That's the slope of the line. And so if we can then calculate this enthalpy of transition, we know the temperature, and we know the molar volume of the transition, then that means then we can actually calculate then the slope of this line. For this example, we're actually given two of these numbers already. We know that this is 6.008, and the temperature we're acting at is 273.15 Kelvin, because we're going to be at 0 degrees Celsius. And that's what the problem specifies here and here. So the only thing we need to figure out is what is this molar volume of the transition. And so to do so, we'll expand this term where we'll say the molar volume of the transition, well, that's equal to the molar volume of the liquid minus the molar volume of the solid. And so the one piece of information that they gave us in this example was that they gave us densities of the ice and the water. And so what we can do with the density is that if we take the inverse of the density, well, we know a density is a mass per unit volume, and so if we take the inverse of that, that gives us a volume per unit mass. And if I multiply that number by the molar mass, which is grams per mole, then what I'm left with is volume per mole, which is a molar volume. So all I need to do then is I just need to take these densities, take the inverse of them, and multiply them by the molar mass of water, which is the value that's also given in this problem. So let's do exactly that. So that means we'll look at ice first. I'm going to take the inverse of the density. So in this case, I'm going to have 0.91671 grams over centimeters, or sorry, with centimeters cubed on top. So I have centimeters cubed divided by the 0.91671 grams. I'm going to multiply that by the molar mass, 18.01529 grams per mole. And then finally what I'm going to do is I'm going to convert the centimeters cubed into meters cubed, just so I'm operating in a more distributive of units, being we always want to operate in kilograms, meters, seconds, and so I'm just doing that conversion right here. And so 1 meter cubed is the same thing as 100 centimeters cubed. And so if I do this multiplication and divide out all the correct numbers, I end up canceling out grams, I end up canceling out centimeters cubed. And what I'm left with is a value in meters cubed per mole. In this case for ice, it's 1.965 times 10 to the minus 5 meters cubed per mole. And again, remember what we're trying to calculate in this case what we're finding is the molar volume of the solid, in this case being ice. And here I have a molar volume. I have meters cubed, which is a volume, divided by moles. Let's do this for water now. I'm going to start again. I have my centimeters cubed on top. I have the density, or sorry, the mass on the bottom, 0.99984 grams, times the molar mass of water, 18.01529 grams per mole. I'm going to do the unit conversion again, 1 meter cubed divided by 100 centimeters cubed. And so the result of that operation is 1.802 times 10 to the minus 5 meters cubed per mole. And so again, what we're trying to calculate is this change in molar volume of the transition, which we've defined as the liquid minus the solid. So if I'm going to do that, then I'm going to do delta trans of the molar volume, and the liquid is 1.802 times 10 to the minus 5. From that I'm going to subtract off 1.965 times 10 to the minus 5. And what I'm going to be left with is negative 1.6318 times 10 to the minus 6 meters cubed per mole. Well, now we're pretty much done, because we've now been able to figure out what this value is. And that value is negative 1.6318 times 10 to the minus 6. And so now we can just plug in those three numbers and we're going to get our value. So dp by dt is equal to 6.008, and in this case I'm going to write this in terms of joules, and you'll see why in a second, but that's why I'm writing times 10 to the 3. On the bottom I have 0 degrees Celsius, 273.15 degrees Kelvin, and then I also have my negative 1.6318 times 10 to the minus 6. What that leaves me with is dp by dt is equal to negative 1.348 times 10 to the 7. And on top I had joules. On the bottom I have Kelvin meters cubed. Now you might be asking yourself what happened to the moles. Well, remember the value of the enthalpy of the transition was kilojoules per mole, and that's what a value that I have on top. And then also I had my molar volume had moles, or basically meters cubed per mole, the volume per mole. And that basically canceled itself out. I had mole per mole, and those two terms disappear. The other thing that I want to do here, though, is I'm also just going to move around units just so that we can turn our units, this joules per Kelvin per meter cubed, into something that looks a little bit more applicable to our plot. Because remember, our plot over here, well, it's in a plot of pressure and pressure is in pascals and temperature is in Kelvin. And so what I'm going to do is I'm just going to rewrite this answer, this negative 1.348 times 10 to the 7. Well, I know joules are a Newton meter. And so I'll change the joules to Newton meter. Here's my Kelvin, here's my meters cubed. I can then cancel out a meter and one of the meters on the bottom. And what that leaves me with is meters squared. Well, a meter squared, this is just an area. And if you remember before when we talked about pressure, a pressure is just equal to a force per unit area. And so in reality what we have here is negative 1.348 times 10 to the 7 pascals per Kelvin. And so expressing it in this way, and again this is why I made some choices in terms of units back at the beginning, for instance changing this into meters over here for the molar volume, that's what led us to this final result where we actually have something that's in pascals per Kelvin, which then directly relates to our diagram over here where we can talk about our PT, or our pressure temperature phase diagram. Let's now look at the second problem here, where the problem is asking us to estimate the pressure required to lower the melting point of ice by 2 degrees Celsius. So first we're sitting here at 1 atmosphere and 0 Kelvin, and we're on this line, which represents the equilibrium point. And what the question is asking us is, where do we go on this line so that we can get to the point where we have now decreased our temperature to minus 2 degrees Celsius. And that then represents a new pressure where we have this new dynamic equilibrium. What we have right now is we have a slope. we have this dp by dt, and that's equal to this negative number. And this negative number tells us that the slope is a constant, which is good because we have a line that's on our phase diagram right here. And so if we wanted to then calculate where we're going to go up the slope, well, if we know the slope of the line, then we can just integrate and we end up with our position. And so that's exactly what we're going to do. So I'm going to slide this up. So for problem 2, what we're going to do is we're going to rearrange, and I'm going to then set up my equation. So here I've got the integral of dp, and that's going to be equal to the integral of negative 1.348 times 10 to the 7 dt. And so here all I did was I just multiplied both sides by dt, and then I'm going to integrate. My bounds of my integration, well, I'm starting at 273.15 Kelvin. I want to know what it is when I drop by 2 degrees, so that becomes 271.15 Kelvin. We're at 1 atmosphere of pressure, so that's 101 times 10 to the 5 pascals, because remember this value that we have this is in pascals per Kelvin, so it's important that we write these bounds in terms of those same units, so this needs to be in pascals. And the second part to this, of the above bound, well, this is just that new pressure, the one that we don't know or the one that we're trying to solve for. And so by evaluating these two integrals and then solving for the final pressure, we're then going to know where we're going up the slope of that line. These integrals are very simple to calculate. The integral of dp, well, that's just equal to p, evaluated between pf and 1.01 times 10 to the 5. The integral of some number times dt, well, it's just going to be equal to that number, negative 1.348 times 10 to the 7 times t, evaluated between 273.15 and 271.15. If we evaluate these or utilize the fundamental theorem of calculus, then on the left-hand side I get pf minus 1.01 times 10 to the 5, and that's equal to negative 1.348 times 10 to the 7 times 271.15 minus 273.15. And so in the end, when we rearrange, we get pf is equal to negative 1.348 times 10 to the 7 times negative 2 plus 1.01 times 10 to the 5. And so what that's equal to is 2.706 times 10 to the 7 pascals. Now this number in and of itself probably doesn't mean very much. However, if I were to convert it to atmospheres, so 1 atmosphere, 1.01 times 10 to the 5 pascals, that number is actually 268 atmospheres. So if we were to put a pressure equivalent to 268 times whatever pressure we feel here at sea level, then that is what is required to then change the melting point or the freezing point of water to ice by 2 degrees, or lowering it by 2 degrees. Let's look at what it means for the Clapeyron equation to predict a positive or negative slope for the solid-liquid phase boundary. In the left plot, we have the phase diagram for carbon dioxide. Carbon dioxide is a normal liquid where the phase boundary between the liquid and solid phase has a positive slope. This means that as the pressure increases, liquids will spontaneously turn to solids, which is the intuitive thing to happen. Anomalous liquids are when the slope of the solid-liquid state boundary is negative. As can be seen in the phase diagram for water on the right, the negative slope between ice and water indicates that it is an anomalous liquid. What this means is that as the pressure increases, ice turns to water. Water is the main solvent that supports life. One of the many reasons why this is true is that it remains in the water phase below 0 degrees Celsius at elevated pressures. One example is Lake Vostok, which is the largest of Antarctica's subglacial lakes. 4 kilometers below the ice, researchers have found this pocket of water that has persisted for millions of years. It is theorized that it persists because water is heated by the Earth's core and is insulated from the cold surface temperatures by the ice. However, the water is still calculated to be at negative 3 degrees Celsius and remains liquid due to the high pressure imposed by the weight of the ice above it. It is hypothesized that unusual forms of life could be found in the lake's liquid layer, a fossil water reserve. Lake Vostok contains an environment sealed below the ice for millions of years, in conditions which could resemble those of the ice-covered ocean of Jupiter's moon Europa and Saturn's moon Enceladus. For state changes involving phases with molar volumes that can greatly vary, such as for gases, the Clapeyron equation cannot be used because we cannot assume the volume of the vapor is independent of pressure. So, starting with the Clapeyron equation, where we write out explicitly the change in molar volume of the transition, which gives dP by dt is equal to the change in enthalpy of the transition divided by the temperature times the molar volume of the gas minus the molar volume of the other phase, being solid or liquid. Since the molar volume of the gas is much larger than that of the other phase, we can neglect the molar volume of the other phase, which leaves dP by dt being equal to the change in enthalpy of the transition divided by the temperature times the molar volume of the gas. Assuming that the gas is ideal, we can substitute in the ideal gas law, where the molar volume is equal to the gas constant times the temperature divided by the pressure. The number of moles in this case is included in the molar volume term. This gives dP by dt is equal to the pressure times the change in enthalpy of the transition divided by the gas constant times the temperature squared. Rearranging so that all the pressure terms are on one side and all the temperature terms are on the other, and integrating gives the integral from an initial pressure to a final pressure of dP over P, and that's equal to the integral from an initial temperature to a final temperature of the change in enthalpy of the transition times dt over the gas constant times the temperature squared. Evaluating these integrals gives the natural logarithm of the final pressure over the initial pressure being equal to the change in enthalpy of the transition divided by the gas constant times the inverse of the initial temperature minus the inverse of the final temperature. This is the Clausius-Clapeyron equation. This equation assumes that the molar volume of the gas is much larger than the molar volume of the other phase, that the vapor behaves ideally, and that the change in enthalpy of the transition is independent of the temperature and pressure for the region of interest. The vapor pressure of a substance is the pressure of a vapor in equilibrium with its condensed phase. It is demonstrated by the phase boundary, meaning that the line that denotes the water vapor and solid vapor phase boundaries tells the vapor pressure of the substance for a given external pressure. So, when the vapor pressure matches the external pressure, the substance vaporizes. This is why, for instance, it takes longer to cook things at altitude, since the boiling point of water is lower. For example, the boiling point of water at sea level is 100 degrees Celsius, since the external pressure is about 1 atmosphere. At altitude, say in the Rocky Mountains in Colorado, the external pressure drops. This means that we can only heat up water so much before the pressure matches the lower external pressure and therefore vaporizes. So let's use the Clausius-Clapeyron equation then to predict what is the boiling point of water at altitude. So in this example, we're using Pikes Peak in Colorado, which is about 4,300 meters above sea level. And there we see that the pressure at that point is 0.5836 that of the pressure at sea level. And so the question is asking us, what is the boiling point of water here? And they give us the change in enthalpy of vaporization for water is 40.79 kilojoules per mole. So starting with the Clausius-Clapeyron equation, the natural logarithm of the final pressure over the initial pressure being equal to the change in enthalpy of the transition divided by the gas constant times the inverse of the initial temperature minus the inverse of the final temperature. And here, if we take stock of what we have, the information that we're going to be using, we can draw from a phase diagram for water, which I'll just draw quickly over here. So here we've got the solid phase, the liquid phase, and the gas phase. And in this case, I should probably draw this phase boundary with a negative slope because we are dealing with water and it is an anomalous liquid. And so what we have here is we have typically at 100 Kelvin or 100 degrees Celsius or 373 Kelvin, this is where the typical boiling point of water is at 1 atmosphere, or essentially the pressure at sea level. And what we want to do is we want to go to a slightly lower pressure, which is 0.5836 times the pressure at sea level. And we want to find out what is that temperature at that point. And so what we're going to use then is the information that we know of the boiling point of water at sea level. So we know that in this case the initial temperature we'll say is 373 Kelvin, since that's the boiling point. We know the initial pressure is just the pressure at sea level. The reason why I'm writing it like that is because I can write the final pressure as 0.5836 times the pressure at sea level. And so what we're in the end trying to find is, what is this final temperature? Since we've identified all of this pertinent information, then really this is just an exercise of substituting in these variables into the Clausius-Clapeyron equation and then solving for the final temperature. So if I do just that, I have the natural logarithm of the final pressure, 0.5836 times P, the pressure at sea level, divided by the initial pressure, which is just the pressure at sea level. That's going to be equal to 40.79 times 10 to the 3. And the reason why I'm writing it times 10 to the 3 is because I'm going to convert these kilojoules into joules. The reason why I do that is that my gas constant, 8.3145, is written in joules. And so I want to make sure that my units cancel out appropriately. I have my initial temperature, 1 over 373, minus 1 over T final, which is the variable that I'm trying to solve for. And since I've only got the one unknown, then I can solve for it. Right off the bat, I can cancel out my pressure at sea level. And so I'm just left with the natural logarithm of 0.5836. I'm going to have that multiplied by 8.3145 divided by 40.79 times 10 to the 3. And that's just because I multiplied both sides by the gas constant and also divided both sides by the enthalpy, or the change in enthalpy of vaporization. That's going to be still equal to 1 over 373 minus 1 over T final. I will continue to rearrange. All I'm going to do is I'm going to take this negative 1 over T final, I'll move it to the other side, and I'm going to take all of this and I'm going to move it to the other side. And so by doing so, I'm going to get 1 over T final is equal to 1 over 373 minus the natural logarithm of 0.5836 times 8.3145 divided by 40.79 times 10 to the 3. At this point, I'll actually start substituting or start solving for values. And I'm also going to write out the explicit inverse, because in the end I do have to take the inverse of this 1 over T final. And so all that means is that I'm going to have 1 over 373, which is 0.002681. I'm going to subtract from that, and the natural logarithm of 0.5836 times 8.3145 divided by 40.79 times 10 to the 3. That's going to be equal to negative 0.00011. And all of this is, again, I'm taking the inverse of it because I have to take the inverse of the left-hand side. And so I take the inverse of both sides. And when I evaluate this, then I get a final temperature of 358 Kelvin. And as you can see, the prediction is exactly what we expected. At sea level, we have a temperature of 373 Kelvin, or roughly about 100 degrees Celsius. When we move up to higher altitudes or lower pressures, then the temperature at which the water boils drops, which means it takes longer to cook things since we can't heat it up in water as high of a temperature as we normally could at sea level. The final thing we will cover in this lecture is the phase rule. It is defined as F is equal to C minus P plus 2, where C is the number of substances in the system, P is the number of phases present, and F is the number of variables, being temperature, pressure, or composition, that can be independently chosen without disturbing the number of phases in equilibrium. For example, if we have water vapor, then there is only one substance, H2O, so C is equal to 1. There is only one phase, being the vapor phase, so P is also equal to 1. Therefore, F is equal to 1 minus 1 plus 2, which gives 2. This means that we can select the temperature and pressure independently and still get water vapor. Looking specifically at a phase boundary, let's pretend that our water sample was at the liquid vapor phase boundary. C is still equal to 1 since there is still only H2O in the system. However, now there are two phases present, the liquid and the vapor phase, so P is equal to 2. This means that F is equal to 1 minus 2 plus 2, which gives 1. This means that once the temperature or the pressure is set, the other value must be a specific value in order for the system to be on the phase boundary. Here is a summary of this lecture. Free energies define if a process is spontaneous and does so by only using the thermodynamic properties of the system. A process is spontaneous if it is less than zero. The Helmholtz free energy A quantifies the total work possible by a process, while the Gibbs free energy G quantifies the total non-expansion work that is possible. In single component systems, we can use how the Gibbs free energy varies with respect to temperature and pressure to draw phase diagrams, and the Clapeyron equation can be used to define phase boundaries where the molar volume changes little, while the Clausius-Clapeyron equation should be used when the molar volume changes dramatically across the phase boundary, like between a gas phase and either a liquid or solid phase. Welcome to Lecture 9. In today's lecture, we will define the chemical potential in order to analyze the thermodynamics of multi-component systems to describe what happens in mixtures. This lecture will be divided into 3 parts. First, we will define what is the chemical potential. Then, we will use it to discuss ideal solutions. Finally, since we live in the real world, we will examine how real solutions are described. In the previous lecture, we used the molar Gibbs free energy to define if a process that described a single component system was spontaneous, where the molar Gibbs free energy is simply the Gibbs free energy of the system divided by the number of moles of the substance. If there are multiple species in the system, as illustrated by the different colored dots in the figure on the right, then the contribution to the Gibbs free energy from each component is given by something called the chemical potential. The chemical potential for a component is defined as the partial derivative of the Gibbs free energy with respect to the number of moles of that component while holding the temperature, pressure, and the number of moles of the other components constant. Then, by multiplying the number of moles by the component's chemical potential and summing over all components, we would get the total Gibbs free energy of the system. We previously determined that the molar Gibbs free energy for a pure gas at constant temperature varies with pressure according to the molar Gibbs free energy at some final pressure being equal to the molar Gibbs free energy at an initial pressure plus RT times the natural logarithm of the final pressure over the initial pressure. For our purposes in this lecture, we will set the final pressure, PF, to simply P, being the pressure of interest, and PI to the standard pressure, which is 1 bar. This makes the molar Gibbs free energy at the initial pressure equal to the standard molar Gibbs free energy. Taking all this into account gives the molar Gibbs free energy at some pressure is equal to the standard molar Gibbs free energy plus RT times the natural logarithm of P over the standard pressure. For a mixture of gases, we use the chemical potential to describe gas J's contribution to the total Gibbs free energy. This expression is analogous to the one we just reviewed, but instead of using the molar Gibbs free energy terms, we use chemical potential terms instead. Therefore, the chemical potential of component J is equal to the standard chemical potential of component J plus RT times the natural logarithm of the partial pressure of J divided by the standard pressure. So, the more of gas J that's in the system, the larger its chemical potential and the more potential for that component to contribute chemically. The figure on the right illustrates this fact, that as the partial pressure of the gas increases, so does the chemical potential. It also demonstrates how temperature plays a role in the chemical potential. Let's use the expression for the chemical potential now to describe basically how the chemical potential of a substance changes under varying conditions. So here we have this example where we have the partial pressure of an ideal gas, and that's going from 100 kilopascals to 50 kilopascals as it's consumed in a reaction at 25 degrees Celsius. And the question is, find the change in chemical potential due to this drop in pressure. And so like anything, if we're going to find a change in something, then what that is just the final minus the initial of that thing. So we just have to calculate what is the final chemical potential, what is the initial chemical potential, and then subtract these two terms. So first let's find what the initial chemical potential is. And in this case, we're just going to need to write out first the expression for chemical potential. So the standard chemical potential plus RT times the natural logarithm of, and in this case it's going to be the initial pressure over the standard pressure. And if we substitute in the numbers that we know, I'm going to leave RT written just as RT for now, But this natural logarithm, well, the initial pressure is 100 kilopascals, and the standard pressure is 1 bar, which is also 100 kilopascals. And so in this case, this natural logarithm term, well, I have the natural logarithm of 100 over 100, which is the natural logarithm of 1. And the natural logarithm of 1 is 0. So that means that whole term disappears. And so what that leaves me with is that the initial chemical potential in this case is just equal to the standard chemical potential. Let's now look at the final case. In the final case, again, we're going to start with the same starting point, the standard chemical potential plus RT times the natural logarithm of the final pressure over the standard chemical potential, the standard pressure. In this case, I'm going to leave these numbers unsubstituted quickly for the time being, so I have mu, or the chemical, or the standard chemical potential plus RT. In this case, I have the natural logarithm of 50 divided by 100, again remembering that the standard pressure is 1 bar or 100 kilopascals. So what I have now, if I simplify that expression, I have the standard chemical potential of this component plus RT times the natural logarithm of 1/2. Let's now do this subtraction that I alluded to at the beginning. Because again, we're just trying to find the change in chemical potential. That's equal to the final minus the initial. So if we substitute in those terms, I have the standard chemical potential of this gas plus RT times the natural logarithm of 1/2. And from that, I'm going to subtract off the standard chemical potential for this gas. And so because I have something plus minus the same term, I can cancel it out. And so what I'm left with is RT times the natural logarithm of 1/2. And so if I start now to substitute in numbers, 8.3145 times the temperature, which is 25 plus 273.15 times the natural logarithm of 1/2. Well, the final answer to this then, or the change in chemical potential due to the consumption of this gas, is negative 1.72 times 10 to the 3 joules per mole. Now to be clear, this number that we just calculated, this doesn't tell me if the process itself is spontaneous, because this is only just one part or one component of a mixture of things that are together. And so in order to figure out if the whole process was spontaneous, what we would need to do is find the chemical potentials of all the pieces in the mixture and find out if we get something that's less than 0, simply because a chemical potential is a Gibbs free energy. And if we want to find out if things are spontaneous, then we need to have a change in Gibbs free energy that's less than 0. So let's now look at an example where we're going to do just that. We're going to calculate if something or if a process is spontaneous by examining all the components that have to do with this process. And so in this question, what we have is two gases, and they both start at the same pressure and temperature, and that they're in a box that's separated by an impermeable membrane. And what we're going to show is that they will mix spontaneously when we remove that partition. And so what this looks like is I have a box. This is my initial case. And there's this impermeable membrane. And inside 1/2 of the box, I have one gas. And in the other side of the box, I have a second gas. And that both of these gases, they are going to be at a total pressure of P. And I'm just going to finish labeling these boxes where I have, this is box A and this is box B, and that this has a total number of moles Na, and this has a total number of moles inside this box Nb. The final case, or the case that we want to show is spontaneous, is now we have this box. Inside this box, we have the gas molecules now, and they've mixed. And so this is the final case that we're trying to figure out. And that what we want to show is that the change in Gibbs free energy is less than 0, meaning that it's spontaneous for when we take away this partition, we're going to get complete mixing in the box. And of course, the pressures inside this box now, we will have a partial pressure of A, and we will have a partial pressure of B, but that PA plus PB is going to be equal to that total pressure that we had here a second ago. So this P is the same as these P's. And then just finishing labeling off, I'm going to have inside this box A and B, so they're mixed together, and that the total number of moles, which if we just add this together, we're just going to get total number of moles N. So then let's determine the Gibbs free energy in the initial and the final case, and then we'll subtract the two and we'll find out if the change is less than 0. So the initial Gibbs free energy is equal to the number of moles of A times the chemical potential of A plus the number of moles of B times the chemical potential of B. And again, this is just from the definition of Gibbs free energy, taking into account or writing it as an expression of chemical potentials. And if I substitute in, what we get is number of moles of species A times the standard chemical potential of species A plus RT times the natural logarithm of the pressure P over P standard. And here I've just substituted in P directly because I know the pressure inside the box is P. To that I'm going to add the number of moles of species B times the chemical potential of species B plus RT times the natural logarithm of P over P standard. And again, I'm just substituting in directly because the pressure in that box is just, again, it's P. What about for the final case? So the final Gibbs free energy, I start writing it the same way, the number of moles of A times the chemical potential of A times the number of moles of B times the chemical potential of B. But in this case, I'm going to slightly change what the next step is going to be. I have number of moles of A times the chemical or the standard chemical potential of A plus RT times the natural logarithm of the partial pressure of A over the standard partial pressure. And to that I'm going to add the number of moles of B, and that's going to be multiplied by the standard chemical potential of species B plus RT times the natural logarithm of the partial pressure of B over the standard pressure. Now the one thing that we can write, or what we can do now, is that these partial pressures of A and partial pressures of B, we can apply Dalton's law, where we can say that that partial pressure, well, that's just equal to the mole fraction of A times the total pressure inside the box. And the same thing happens here with the partial pressure of B. That's just equal to the mole fraction of B times the total pressure P. So if I write out those terms with the mole fractions and the total pressures written in instead, I get number of moles of species A times the standard chemical potential of species A plus RT times the natural logarithm of the mole fraction of A times the total pressure divided by the standard pressure. And to that I'm going to add number of moles of species B times the standard chemical potential of species B plus RT times the natural logarithm of the mole fraction of B times the total pressure divided by the standard potential, the standard pressure. The final thing that I'm going to do is I'm just going to invoke natural logarithm rules so that I can split up some of these natural logarithms. And again, if you have natural logarithms that are the multiplication of two terms, so say for instance this one right here, then I can write this as the natural logarithm of, say, the mole fraction of A plus the natural logarithm of the total pressure over the standard pressure, meaning that if things are multiplied together, I can write them as the sum of logarithms, and if they're divided, then I can write them as the difference of natural logarithms. In this case, I want to separate the mole fraction from the pressure terms, and so that's why there's a plus sign in between. So by doing that for both of these natural logarithm terms, what I end up with is the number of moles of A times the standard chemical potential of A plus RT times the natural logarithm of the mole fraction of A plus RT times the natural logarithm of the total pressure over the standard pressure. And to that I'm going to add the total number of moles of B times the standard chemical potential of B plus RT times the natural logarithm of the mole fraction of B plus RT times the natural logarithm of the total pressure divided by the standard pressure. Alright, so now we're ready to determine if this process or if this mixing is spontaneous. And remember again, what we were trying to find out is the change in Gibbs free energy, which is just going to be equal to the final minus the initial, if this is less than 0. And so now what we have is an expression for the final and the initial Gibbs free energy, and so now we just have to take these two terms and subtract them from each other, and then deduce if we're going to have something that's less than 0. So writing this out explicitly, we're going to have the change in Gibbs free energy. Well, the final is just going to be Na, the number of moles of species A, times the standard chemical potential of species A, plus RT times the natural logarithm of the mole fraction of species A, plus RT times the natural logarithm of the total pressure divided by the standard pressure. We have plus the number of moles of species B, and that's going to be multiplied by the standard chemical potential of species B, plus RT times the natural logarithm of the mole fraction of species B, plus RT times the natural logarithm of the total pressure divided by the standard pressure. And from that, I'm going to be subtracting off the number of moles of A times the standard chemical potential of species A, plus RT times the natural logarithm of P over P standard. And from that, I'm going to be adding on within this bracket the number of moles of species B times the mole fraction of species B, or the standard chemical potential of species B, plus RT times the natural logarithm of the total pressure over the standard pressure. My next step here is I'm just going to start crossing out like terms. For instance, I have a total moles of A times the standard chemical potential of A. Here I have that exact same term, and so I can cancel out that mole fraction, that chemical potential, the standard of species A. I have the same thing for the standard chemical potential of species B. I also have this term where I have an RT ln total pressure over the standard pressure, and I have it multiplied by the number of moles of A, and I have it by the number of moles of B. And here again, I have the number of moles of A multiplied with RT times the natural logarithm of the total pressure over the standard pressure, and I have the same thing here. So these two terms also disappear. So the only thing that I have left over is these terms that have to do with the mole fraction of A and the mole fraction of B. And so that's what I'm going to write on my next line. So the change in Gibbs free energy is the number of moles of A times RT times the natural logarithm of the mole fraction of A plus the total moles of B times RT times the natural logarithm of the mole fraction of species B. In order to continue simplifying this, then I just want you to remember that the mole fraction of some species is just equal to the number of moles of that species divided by the total number of moles. And so I can rearrange this so that I can have the number of moles of some species, and that's equal to the mole fraction of that species times the total number of moles. And I'm just going to take that and just substitute that into my expression over here, where I have, again, my change in Gibbs free energy. Well, in this case, the number of moles of species A is equal to the mole fraction of species A times the total number of moles, times RT times the natural logarithm of the mole fraction of A. And to that, I'm going to add, again, I have the number of moles of species B. I'm just going to express that as the mole fraction of species B times the total number of moles in the system, times RT natural logarithm of the mole fraction of species B. And then what I can do is I can distribute out the total number of moles, this R, and this T term. So nRT, that's equal to, or that's going to be times the mole fraction of A times the natural logarithm of the mole fraction of A, plus the mole fraction of B times the natural logarithm of the mole fraction of B. And so we've finally made it to the part where we can actually start to figure out, is this term less than 0, meaning that the mixing of this gas was spontaneous. And so I'm not actually going to give you a number, we're just going to use some reasoning to show that yes, indeed, the Gibbs free energy of this process, the change in Gibbs free energy of this process is indeed less than 0, meaning that it is spontaneous. And so to do that, I'm just going to first remind you that the mole fractions are numbers that are going to be between 0 and 1. And so I'm just writing here 0 is less than the mole fraction of A, which is less than 1, and 0 is less than or equal to the mole fraction of B, which is less than or equal to 1. And so what that means then is that the natural logarithm of a number that's between 0 and 1, so for instance the natural logarithm of the mole fraction of A, that's always going to be less than or equal to 0. And the same thing for the natural logarithm of the mole fraction of B. That's also going to be less than or equal to 0. What that means is that if you have two terms here, if this number, this ln of the mole fraction of A and this natural logarithm of the mole fraction of B, if both of these numbers are going to be less than 0, then that means this whole term that's in the parentheses, this number is going to be negative, because I have a negative number plus a negative number. And so what that means then is that since temperature will always be positive, the gas constant will always be positive, and the number of moles is always going to be positive, then what that means is that my change in Gibbs free energy must be less than 0 or equal to 0, depending upon what the mole fractions are. But what this implies is that if I have any mole fractions that aren't equal to 1, meaning I've only got a single component system, then that means then that I will have mixing, meaning that my Gibbs free energy will be less than 0. Now that we've seen that it is spontaneous for gases to mix, let's now look at solutions. Ideal solutions follow Raoult's law, being the partial vapor pressure of a substance in its liquid mixture is proportional to its mole fraction in the mixture and its vapor pressure when pure. In other words, P sub j is equal to the mole fraction of the jth component times P star j. Let's look at an illustration of Raoult's law. Consider a two-component mixture. These liquid mixtures are going to be in equilibrium with their vapor phase. This means that there is a partial pressure associated with each component. Here are three images that show pure components A and B on the left and right, and a 50-50 mixture by moles in the center. P star is the partial pressure of the gas when it is pure, so on the left the partial pressure of the vapor is P star A, and on the right it is P star B. In the middle, since there is half as much of A and B in the mixture, assuming that the solution is ideal, the partial pressure of both components is 1/2 P star A and 1/2 P star B. Returning to the slide, the plot on the right also illustrates Raoult's law. When each component is pure, meaning that the other is not present, the mole fraction of that component is equal to 1. As the two components are mixed, the mole fraction changes and the partial pressure varies proportionally. For example, if a two-component mixture is mixed 50-50, meaning they both have a mole fraction of 0.5, then the partial pressure of the vapor phase is going to be half what it would have been if that component were pure. Raoult's law also allows us to quantify the chemical potential, mu sub j, of each component of a solution based on their vapor pressure. Starting from pure components, denoted by the asterisk, and assuming that the vapor and liquid phases are at equilibrium, we can say the chemical potential of the pure liquid substance is equal to the chemical potential of the pure gas. This is also equal to the standard chemical potential of the gas times RT times the natural logarithm of the partial pressure of the pure component divided by the standard pressure. Rearranging this to solve for the standard chemical potential for component J gives the standard chemical potential is equal to the chemical potential of the pure liquid minus RT times the natural logarithm of the partial pressure of the pure component divided by the standard pressure. For each component in a binary mixture, as we vary the mole fraction, we get the chemical potential of the pure liquid substance at some defined point in the mixture is equal to the chemical potential of the pure gas. This is also equal to the standard chemical potential of the gas times RT times the natural logarithm of the partial pressure of the pure component divided by the standard pressure. Since the standard chemical potential is the same in both cases, pure and mixed, then we can put them together to get the chemical potential of the jth component in the liquid phase is equal to the chemical potential of the pure liquid of the jth component minus RT times the natural logarithm of the partial pressure of the pure component divided by the standard pressure, plus RT times the natural logarithm of the actual partial pressure of the component divided by the standard pressure. Using logarithm rules to combine the two natural logarithm terms, we can cancel our standard pressures to get the chemical potential of the pure jth component plus RT times the natural logarithm of the actual partial pressure of component J in the mixture divided by the partial pressure of the pure jth component. And so according to Raoult's law, we can also write that the mole fraction of the jth component is equal to the actual partial pressure of component J in the mixture divided by the partial pressure of the jth component when pure. So, doing so, we get the chemical potential of the jth component is equal to the chemical potential of the pure jth component plus RT times the natural logarithm of the mole fraction of component J. Let's now see how this works in practice for solutions. So here we have a simple example where we're trying to find the change in chemical potential. In this case, it's just a benzene at 25 degrees Celsius, where what we've done is we've mixed it with a solute, where that solute is at a mole fraction of 0.1. So what we're assuming here is a binary mixture where we have benzene as our solvent, and it has a mole fraction of 0.9, And then we have some solute where its mole fraction is equal to 0.1. And the question that it's asking is, what is the change in the chemical potential of benzene due to the fact that I've added this solute to my solution? As always, a change in chemical potential or a change in anything is just the final minus the initial. And so let's write that out. I know that in my initial case for the benzene, well, what we had the chemical potential of the pure benzene plus RT times the natural logarithm of the mole fraction. And in this case, in the initial case, the mole fraction is equal to 1. And so if x is equal to 1, then the natural logarithm of 1, that is 0. That just means that in the initial case, I had a pure component, right, a pure benzene solution. And so it's not really a surprise then that the initial chemical potential in this case is equal to the chemical potential of the pure solution, or the pure substance, which in this case is just benzene. In the final case, this is now where we've added in this solute. And so if I write out again just the standard equation, or the full equation for this, well, that's just the chemical potential of the pure component. In this case, this is of the pure benzene. And now I've got RT times the natural logarithm of the mole fraction of benzene. Well, in this case, the mole fraction of benzene has now been dropped to 0.9. But that now is the final chemical potential of my benzene. And so now if I put these two things together in my change in chemical potential of benzene, well, I have my final, which is the standard chemical potential of the pure benzene plus RT times the natural logarithm of 0.9. And to that I'm going to subtract off the chemical potential of pure benzene. So now I can cancel out the chemical potential of pure benzene terms, and I will now substitute in for R, 8.3145 times the temperature, 25 plus 273.15 times the natural logarithm of 0.9. And so in the end what I get is minus 261 joules per mole. So of course this number that we just calculated, this minus 261 joules per mole, this is just the chemical potential of one of two components in this mixture. And so if we wanted to then determine if it's spontaneous for these two things to actually mix together once we combine them, then we're going to have to solve for that explicitly, which is what we're going to do in this second problem, being that we're going to show that the mixing of an ideal solution is in fact spontaneous. And again, what that means is that the change in Gibbs free energy that occurs through the process of actually mixing these two things is going to be less than 0. And so let's just draw our initial and final picture again. So the initial picture is that we have essentially two beakers. One of them has one thing in it and another thing has a second thing in it, and we'll just call this A and B. And then we have a final case where we've mixed these two things together, and that this is just going to be A plus B. And we have all the same rules that we had before, where in this case we have Na plus Nb gives me the total number of moles. And so what we're going to do then is we're going to calculate the initial and the final Gibbs free energy. So here we'll find the initial Gibbs free energy. From this we'll find the final. And then we'll just subtract the two and we'll find out if it's less than equal to 0, then we know that the process of mixing these two things together is spontaneous. So starting with the initial Gibbs free energy, we know that that's just going to be equal to the total number of moles of A times the chemical potential of A plus the number of moles of B plus times the chemical potential of B. So number of moles of A, the chemical potential of A is the chemical potential of the pure substance plus RT times the natural logarithm of the mole fraction of A. To that I'm going to add the number of moles of B times the chemical potential of the pure B component plus RT times the natural logarithm of the mole fraction of B. And in both these cases, since I've got mixtures that are separated from each other, the mole fraction of B in this case is equal to 1, and the mole fraction of A is equal to 1. And we know then that the natural logarithm of 1, well, that goes to 0. And so all we're left with then is number of moles of A times the chemical potential of the pure plus number of moles of B times the chemical potential of the pure B, which isn't necessarily a surprising result since I do have pure separated components all on their own. For the Gibbs free energy of the final case, we start from the same spot, number of moles of A times the chemical potential of A plus the number of moles of B times the chemical potential of B. And in here I'm just going to substitute in for the chemical potentials, so number of moles of A times the chemical potential of the pure A component plus RT times the natural logarithm of the mole fraction of A. And to that I'm going to add the number of moles of B times the chemical potential of B of the pure component plus RT times the natural logarithm of the mole fraction of B. Finally, if I distribute in my number of moles of A and my number of moles of B, I get Na times mu star A plus Na RT natural logarithm of XA plus NB times mu star B plus NB times RT natural logarithm of XB. And so now I have my initial Gibbs free energy, I have my final Gibbs free energy, and so then just to calculate the change in Gibbs free energy, I'm just going to say the final minus the initial. So my final in this case is number of moles of A, chemical potential of the pure component of A, plus Na, the number of moles of A, times RT, natural logarithm of the mole fraction of A, plus number of moles of B times the chemical potential of the pure B component, plus number of moles of B times RT times the natural logarithm of the mole fraction of B. From that I'm going to subtract off number of moles of A times the chemical potential of the A component, the pure A component, plus the number of moles of B times the chemical potential of the pure B component. I'm going to start canceling out like terms. I have number of moles times the standard, or the pure component chemical potential of A, minus number of moles times the chemical potential of the pure component A. Here I have the number of moles of B times the chemical potential of the pure component B, minus number of moles of B times the chemical potential of the pure component B. And so what that leaves me with is just these two terms that I'm outlining here, which are number of moles of A times RT times the natural logarithm of the mole fraction of A, plus the number of moles of B times RT times the natural logarithm of the mole fraction of B. And so just like before, we can express the mole fraction of some component J as being the number of moles of J divided by the total number of moles. And if I rearrange, then we can say number of moles of the jth component is equal to the mole fraction of that component times the total number of moles. Using this substitution here, what I'm going to get is the mole fraction of A times the total number of moles times RT times the natural logarithm of the mole fraction of A, plus the mole fraction of B times the total number of moles times RT times the natural logarithm of the mole fraction of B. And if I distribute out total number of moles, R and T, then I get nRT times the mole fraction of A times the natural logarithm of A, plus the mole fraction of B times the natural logarithm of the mole fraction of B. And so in this case, again, we can see that the mole fractions are going to be numbers between 0 and 1, which means that these natural logarithm terms here are going to be negative numbers, which means that this whole expression is going to be a bunch of positive numbers multiplied by a negative number, which means that this is going to be negative. And so the upshot is that the change in Gibbs free energy, which we were calculating here, is going to be less than 0, which means that when we mix these two things together, they will mix together. Raoult's law is only valid for a small number of mixtures, typically those whose components are very similar. The figure on the right shows the partial pressure of each component of a two-component system as well as the total pressure. The dashed line shows the partial pressure if the two components form an ideal mixture, while the solid lines show the actual partial pressure measured. We are of course concerned with what happens in the real world, so to account for the deviation from ideal conditions, we define something called the activity. The activity of component J is defined as gamma J times the mole fraction of component J, where gamma J is the activity coefficient, meaning it represents the deviation from ideal conditions for component J. We will use activities again and again throughout the course, as well as the activity coefficient, in order to account for deviations from ideal conditions. We can employ Raoult's law to substitute in the partial pressure of component J divided by the partial pressure of the pure component J for the mole fraction of component J. Since Raoult's law is based on the actual partial pressure of the pure component, in real solutions, it is only truly applicable when the mole fraction of J is close to 1, unless there is a good measurement of the activity coefficient. For real solutions, Raoult's law only does well when the mole fraction of the component in question is close to 1. It does not describe very dilute components in real solutions well. A much better quantification of dilute solutions is to use Henry's law, which relates a mole fraction and partial pressure of a mixture together with a constant. The vapor pressure of a volatile solute J is proportional to its mole fraction in a solution, meaning that the partial pressure of component J is equal to the activity of that component J times K sub H, where K sub H is Henry's constant and is characteristic of a solute and chosen so that the straight line predicted by Henry's law is tangent to the experimental curve when the mole fraction is close to 0. Henry's law is similar to Raoult's law in that the actual partial pressure is proportional to the mole fraction of the component. The major difference is that with Henry's law, the partial pressure of the pure component is equal to a value, being Henry's constant, which is simply an extrapolation of a straight line to when the mole fraction is equal to 1. Again, to reiterate, Henry's law is meant to model very dilute solutions, meaning the mole fraction is very small. Using Henry's law at high activities would give unphysical conditions. Let's now use Henry's law to look at an example of a very dilute solution. In this case, we're going to look at a dilute solution of carbon dioxide in water at 298 Kelvin. And what we're going to calculate is the molal solubility, which means moles of carbon dioxide per kilogram of water, assuming that we have a carbon dioxide pressure of 3.3 times 10 to the minus 4 atmospheres, which corresponds to the partial pressure of carbon dioxide in air. What we're going to assume is that our Henry constant is going to be equal to 1.63 times 10 to the 3 atmospheres. So using the definition of Henry's law, what we can write is the partial pressure of CO2 is equal to the activity of CO2 times Henry's constant. And what we saw previously was that the activity of something, in this case of CO2, is going to be equal to the activity constant times the mole fraction of CO2. And in this case, since we're going to assume that we're in ideal dilute conditions, we're going to let this activity coefficient be equal to 1, or at least we're in a region where Henry's law, since we are dealing with a real solution, describes very well the dilute part of this curve, even if it isn't an ideal mixture. From here, what we can write if we're going to try to create something that defines the mole fraction of CO2, well, that's just simply going to be equal to the number of moles of CO2 divided by the number of moles of CO2 plus the number of moles of H2O. What we're going to assume in this problem is that the number of moles of CO2 are going to be much, much less than the number of moles of H2O. And I think this is a pretty intuitive assumption that we can make, because we're basically what we're looking at is how much CO2 is dissolved in water, but water is going to be the huge component. If you have a kilogram of water, a very, very, very small fraction of that water is going to be CO2. And so there's going to be far, far, far many more moles of water than CO2. And so what that means is that then we can state that the mole fraction of CO2 is simply going to be equal to the number of moles of CO2 divided by the number of moles of H2O. And it's just because this addition down here at the bottom, since my moles of H2O is so much bigger, then we can just neglect this number of moles of CO2. So if we start to substitute these terms now into our original definition of Henry's law, we have the partial pressure of CO2. Well, the activity is just the activity coefficient of CO2 times the mole fraction of CO2 times Henry's constant. In this case, we're going to let the activity coefficient be equal to 1, because again, we're assuming the fact that Henry's law describes very well the very dilute part, or the very dilute region we are on our pressure curve, or our partial pressure curve. We're also going to allow our mole fraction to be equal to the number of moles of CO2 divided by the number of moles of H2O times Henry's constant. So what I'm going to do here is I'm just going to rearrange, and I'm just going to write partial pressure of CO2 divided by Henry's constant, and that's going to be equal to the number of moles of CO2 divided by the number of moles of H2O. Now, of course, we haven't defined what is the number of moles of H2O or the number of moles of CO2. However, what we are trying to calculate is the molality of CO2 in this solution given this partial pressure. And what a molality is number of moles of CO2 divided by the kilograms of water in this case. And so what we're going to do then is we're going to then calculate our number of moles of H2O based on as if there was a kilogram of water. And so what that means is that our number of moles of H2O is going to be 1,000 times 1 mole divided by the molar mass, which is 18.01 grams. And so it's going to be, this is what we're going to substitute in for our number of moles of H2O. And in the end, what that'll give us then is a value, once we solve for the number of moles of CO2, we'll essentially be solving for the molality of CO2. So if we substitute that in, I have partial pressure of CO2 divided by Henry's constant. That's going to be equal to the number of moles of CO2, and that's going to be divided by 1,000 times 18.01. And so now I'm just simply going to solve for the number of moles of CO2. And so in the end, what I'm going to get is 1,000, which is part of this number of moles of H2O. I have the partial pressure of CO2, which is 3.3 times 10 to the negative 4. I'm going to divide that by the 18.01, which came from the molar mass of water. And then finally, I have Henry's constant, 1.63 times 10 to the 3. And when I multiply all these numbers together, I'm going to get 1.12 times 10 to the minus 5 moles of CO2. But again, because I used 1 kilogram of water when I was trying to calculate my number of moles of H2O, then what this also ends up being is the molality, or a measure of the molality, meaning moles of CO2 per kilogram of H2O. Now here's the really neat thing about Henry's law, is that this constant, this Henry's law constant, doesn't have to be defined just in terms of relating mole fraction to partial pressure. We can actually also use it to relate the partial pressure to the molality directly. And it just takes a different Henry's constant, one that's been calibrated to do this exact operation. And so instead of going through all of this effort to convert mole fraction into number of moles and then be able to use that to then reason out the molality of something, we can just use a different Henry's constant and we end up with a relationship between the molality directly and then this partial pressure. And so in this case, what we're going to do is just have a different Henry's law constant, which does exactly this. And so that's why I'm calling it K prime of H. And in this case, it's just going to be 29.3 atmospheres kilograms per mole is the units that goes with this type of Henry's constant. And so then if I substitute these numbers in directly, will I get partial pressure of CO2 divided by this new Henry's constant that's calibrated to calculate directly the molality of, in this case, CO2. And so then the molality of CO2, again, it's the same partial pressure, 3.3 times 10 to the minus 4, divided by 29.3. And I get the 1.12 times 10 to the minus 5 moles of CO2 divided by kilograms of my solvent, being in this case H2O. In either of these cases, all these Henry's constants that I'm going to be drawing from, these things are just coming from tables. They're just the kind of thing that you pull from backs of textbooks or from Google. So as long as you have a reputable source and you can find an appropriate Henry's law constant, then you can jump either between molality or mole fraction in terms of trying to calculate from or trying to relate the partial pressure to whatever your solution is, the dilute component of whatever solution is. When talking about chemical reactions in solution, the components that will be doing the chemistry will be the minority component. For example, for aqueous solutions, anything dissolved in water will be the minority component. It is important to know the chemical potential of these minority components in solutions so that we can calculate what processes are spontaneous. Henry's law allows us to quantify the chemical potential of the dilute component of a solution based on the vapor pressure. Starting from pure components, this time denoted by a dagger, and assuming that the vapor and liquid phase are at equilibrium, then the chemical potential of component J in the liquid phase is equal to the chemical potential of the component J in the gaseous phase, and that's equal to the standard chemical potential of component J in the gaseous phase plus RT times the natural logarithm of Henry's constant of component J divided by the standard partial pressure. Recall that previously the natural logarithm term here had the partial pressure of the pure component when we were talking about Raoult's law. Now, since we're talking about dilute solutes, the pure component has a partial pressure equal to Henry's constant, and that's why it's written in here now. Rearranging this to solve for the standard chemical potential gives the standard chemical potential of component J is equal to the chemical potential of the pure component J as a liquid minus RT times the natural logarithm of Henry's constant of component J divided by the standard partial pressure. Now for each component in a binary mixture, as we vary the mole fraction, then the chemical potential of component J of the liquid is equal to the chemical potential of component J of the gas, and that's equal to the standard chemical potential of component J in the gas phase plus RT times the natural logarithm of the partial pressure of J divided by the standard pressure. And in this case, we use the partial pressure of J because we were measuring the actual partial pressure at a specific mole fraction. Since the standard chemical potential is the same in both cases, for the pure and mixed case, we can then substitute it together to get the chemical potential of component J in the liquid phase is equal to the chemical potential of component J of the pure liquid phase minus RT times the natural logarithm of Henry's constant of component J divided by the standard pressure plus RT times the natural logarithm of the partial pressure of component J divided by the standard pressure. According to Henry's law, we can then substitute in for the partial pressure of component J is equal to the activity of component J times Henry's constant for component J. Substituting in Henry's law for the partial pressure of component J gives the chemical potential of component J of the liquid phase is equal to the chemical potential of component J of the pure liquid minus RT times the natural logarithm of Henry's constant for component J divided by the standard pressure plus RT times the natural logarithm of the activity of component J times Henry's constant of component J divided by the standard partial pressure. What we can then do is we can separate the second natural logarithm term into two terms, and then we can cancel out the equivalent terms, being the RT times the natural logarithm of Henry's constant of component J divided by the standard partial pressure. And what that gives in the end is the chemical potential of component J of the liquid phase is equal to the chemical potential of component J of the pure liquid phase plus RT times the natural logarithm of the activity of component J. We've now introduced two definitions of the chemical potential of pure component J, mu star and mu dagger. The figure on the left is an illustration meant to show the difference between mu star and mu dagger. Mu star is the chemical potential that assumes that the pressure of the pure component is P star, which is the actual partial pressure of the pure substance. Looking at component B as an example, the dashed line represents Raoult's law, which uses the partial pressure of B star as its reference. The dashed line only follows the black line, the actual partial pressure, for high mole fractions of B. Mu dagger is the chemical potential that assumes that Henry's law constant is the pressure of the pure component. This is an unphysical value. However, the point is that Henry's law fits the filled-in black curve when B is the minority component. Since the standard state simply represents the value for a different set of conditions, it's all right to have Raoult's law standard state and a Henry's law standard state. Moving forward, we will write the standard chemical potential in reference to the Henry's law standard chemical potential for dilute components. This means that the chemical potential of component J in the liquid phase is equal to the standard chemical potential of component J in the liquid phase plus RT times the natural logarithm of the activity of component J. Since this standard state is defined with Henry's law constants, we can use the constant that relates partial pressure to molality instead of mole fraction. It is convenient to define the activity using molality since that is much more convenient and relatable when discussing dilute components in aqueous solutions. So the activity of component J can be expressed as the activity coefficient times the molality divided by the standard molality being equal to 1 kilogram per mole. Here is a summary of this lecture. The molar Gibbs free energy of each component of a multi-component system is quantified by the chemical potential mu. When calculating the chemical potential under certain conditions, we calculate the deviation from a reference or standard chemical potential of that component. Raoult's law defines the partial pressure of components in ideal mixtures as the partial pressure of component J is equal to the mole fraction of component J times the partial pressure of the pure component J. And Henry's law defines the partial pressure of dilute components in real mixtures as the partial pressure of component J is equal to the mole fraction of component J times Henry's constant. Since both Raoult's law and Henry's law are linear extrapolations in pure and dilute situations, to account for the real nature of mixtures, we use activities instead of mole fractions, and this is defined as the activity of component J is equal to the activity coefficient of component J times the mole fraction of component J. And for dilute components, the Henry's law constant that relates molality to partial pressure means that the chemical potential can be defined using activities where the activity of component J is equal to the activity coefficient times the molality divided by the standard molality. Welcome to Lecture 10. In this lecture, we will examine equilibrium conditions between phases and rates of diffusion in order to derive expressions that we can use to predict collective or colligative properties of mixtures. This lecture will be divided into 3 parts, each looking at a specific equilibrium condition. In Part 1, we will look at the vapor-liquid phase boundary in order to draw phase diagrams for volatile mixtures and use it to discuss fractional distillation. In the second part, we will look at the solid-liquid and liquid-vapor phase boundaries to predict how the melting point lowers and the boiling point rises in mixtures. Finally, in the third part, we will look at the diffusion of a solvent through a semi-permeable membrane at equilibrium to predict the osmotic pressure that arises. Before we get started, we will first review how the chemical potential changes as a function of pressure and temperature. The chemical potential of a component in a mixture changes the same way as previously defined for the Gibbs free energy of a single component system, or small changes in chemical potential is equal to small changes in the molar Gibbs free energy, and that's equal to the molar volume times dP minus the molar entropy times dt. So, at constant temperature, the dt term is 0, and we are left with the small change in chemical potential being equal to the molar volume times dP. And at constant pressure, the dP term is 0, so we are left with small changes in the chemical potential is equal to the negative of the molar entropy times dt. We will use both of these relationships later in this lecture. The first topic in this lecture involved fractional distillation, which is used to separate 2 volatile liquids. Typically, the components to be separated have boiling points that differ by less than 25 degrees Celsius at 1 atmosphere. Otherwise, simple distillation would be used. A mixture in the round bottom flask is heated so the components of the mixture it contains vaporizes. As we will see, the mole fraction of the more volatile component will be higher in the vapor phase, which allows for the separation of one component for the other. This process is commonly used in petrochemical refining and air separation to produce liquid oxygen, liquid nitrogen, and argon. To understand how this works, we will first examine pressure composition phase diagrams of 2-component mixtures. An example of this type of phase diagram is illustrated on the right with an indicated pathway for fractional distillation. This is a pressure mole fraction phase diagram. Notice that there are 3 phases, a liquid phase, a mixed liquid vapor phase, and a vapor phase. At high pressures, only the liquid phase exists. As the pressure drops, the vapor phase can form over the liquid. Finally, as the pressure drops further, the mixture completely vaporizes. There are 2 phase boundaries, and we will now discuss how both are drawn. For this discussion, we will assume we are using ideal mixtures, say a benzene-toluene mixture. As a result, we can use Raoult's law. For the benzene, the partial pressure of the benzene is equal to the mole fraction of the benzene times the pressure of pure benzene, and for the toluene, the partial pressure is equal to the mole fraction of toluene times the partial pressure of pure toluene. To draw the phase boundary between the liquid and the liquid vapor phases, we need to describe the pressure of vapor that the liquid mixture produces. We will do this as a function of mole fraction for one of the components, in this case benzene, so that we can get a pressure versus mole fraction diagram. The total pressure due to the liquid is the sum of the partial pressures of the benzene and the toluene. Using Raoult's law, we can write the partial pressure as the mole fraction of benzene times the partial pressure of pure benzene plus the mole fraction of toluene times the partial pressure of pure toluene. Since the mole fractions of both components of a two-component mixture must also add to 1, then the mole fraction of toluene equals 1 minus the mole fraction of benzene. Rearranging gives the total pressure being equal to the partial pressure of pure toluene plus the partial pressure of pure benzene minus the partial pressure of pure toluene times the mole fraction of benzene. Note that the partial pressures of the pure components are constants, so only the mole fraction of benzene varies in this equation. This equation defines the liquid and liquid-vapor phase boundary. The curved line, being the liquid-vapor phase boundary, is drawn using the total pressure as a function of the mole fraction of the vapor. Before we can derive this expression, we will need to derive an expression that links the mole fraction of benzene in the liquid to benzene in the vapor phase using only constants. To do this, we will first use Dalton's law to write the mole fraction of benzene being equal to the partial pressure of benzene divided by the total pressure. Then using Raoult's law, the partial pressure of benzene is written as the mole fraction of benzene in the liquid times the partial pressure of pure benzene. The total pressure comes from the relationship we just determined, being equal to the partial pressures of pure toluene plus the partial pressure of pure benzene minus the partial pressure of pure toluene times the mole fraction of benzene. Rearranging this to solve for the mole fraction of benzene in the liquid gives the mole fraction of benzene in the vapor times the partial pressure of pure toluene divided by the partial pressure of pure benzene minus the mole fraction of benzene in the vapor phase times the partial pressure of pure benzene minus the partial pressure of pure toluene. Now that we have this expression for the mole fraction of the liquid, we return to Dalton's law and Raoult's law to get an expression for total pressure. So, the partial pressure of benzene is equal to the mole fraction of benzene in the vapor phase times the total pressure, which is also equal to the mole fraction of benzene in the liquid phase times the partial pressure of pure benzene. Rearranging gives the total pressure being equal to the mole fraction of benzene in the liquid phase times the partial pressure of pure benzene divided by the mole fraction of benzene in the vapor phase. Substituting in the previously derived expression for the mole fraction of benzene in the liquid phase means that the total pressure is equal to the partial pressure of pure toluene times the partial pressure of pure benzene divided by the partial pressure of pure benzene minus the mole fraction of benzene in the vapor phase times the partial pressure of pure benzene minus the partial pressure of pure toluene. This expression divides the liquid-vapor phase from the vapor phase for the mixture. Revisiting the phase diagram, the first expression being the total pressure being equal to the partial pressure of pure toluene plus the partial pressure of pure benzene minus the partial pressure of pure toluene times the mole fraction of benzene is the straight blue line that links the partial pressure of pure toluene to the partial pressure of pure benzene and separates the liquid phase from the liquid vapor phase. It is essentially Raoult's law expressed as a function of the mole fraction of one of the components. The second expression being the total pressure is equal to the partial pressure of pure toluene times the partial pressure of pure benzene divided by the partial pressure of pure benzene minus the mole fraction of benzene in the vapor phase times the partial pressure of pure benzene minus the partial pressure of pure toluene is the curved green line that links the partial pressure of pure toluene to the partial pressure of pure benzene and separates the liquid vapor phase from the vapor phase. To understand this phase diagram, let's trace down from A to E and discuss what happens at each letter. At A, the mixture is all liquid. As we lower the pressure to B and the system reaches the phase boundary, then vapor will then begin to form. If we lower the pressure to C, then both the liquid and the vapor continue to exist. The composition of the vapor is given by the mole fraction calculated at point G, whereas the composition of the liquid is given by the mole fraction calculated at point F. If we continue to lower the pressure to D, then we hit the next phase boundary. And if we continue to lower the pressure, say to E, then at this point only the vapor phase exists. So let's now use the properties that we just calculated to solve a couple of questions that have to do with phase diagrams. In this case, what we're going to look at is an ideal solution that is 5 moles of benzene and 3.25 moles of toluene, and that basically we put them in a piston and cylinder assembly. which just means that we're able to vary the pressure inside the chamber that we place toluene and benzene in. And so then at 298 Kelvin, we know that the partial pressures of the pure substances are 12.85 kilopascals for the benzene and 3.85 kilopascals for the toluene. And so the question starts as, if the pressure starts at 101.3 kilopascals, when does the vapor phase first appear? And the second question is, what is the composition of the vapor phase when it does first appear? So the picture of what this looks like is if we were to draw a pressure vapor phase diagram or a pressure mole fraction phase diagram, and I'm going to draw it in terms of benzene, then what we have here is we start at a point where we're at 101.3 kilopascals, and that if we were to then continue to draw this phase diagram, we have mole fraction of 1, mole fraction of 0, we're going to have the partial pressure of toluene, we're going to have the partial pressure of pure benzene, and then we can draw our phase diagram lines to look something like this. And so like I said before, we're starting up here at 101.3 kilopascals, and that I've just drawn the x in an arbitrary spot. We don't actually know what this number is just yet. We could calculate it, but we don't know it just right off the bat. But the first question is asking, what happens when we lower the pressure until we hit this first phase boundary? Because at this first phase boundary is when we have, or when we'll start to see vapor, because that's when we see the liquid vapor phase. When we start, we're only in the liquid phase. And then in the second part of the problem, what it's asking us is, what is the composition of the vapor phase? And we get that by basically drawing a straight line across, and we see that we get this second point right here, and that'll then tell us what the vapor phase is of the benzene, which then we can use to calculate both phases. So for the first problem, it wants us to find what is this pressure, and then for the second part, it wants us to find what is this mole fraction of the vapor of the benzene. So starting with problem 1, we know that this liquid vapor phase boundary is drawn as the total pressure being equal to, in this case, the partial pressure of pure toluene plus the partial pressure of pure benzene minus the partial pressure of pure toluene times the mole fraction of benzene in the liquid. And the mole fraction of the benzene in the liquid, well, that's just equal to the number of moles of benzene in the liquid divided by the number of moles of benzene in the liquid plus the number of moles of toluene in the liquid. And those numbers are given to us in the problem. So that's 5.00 divided by 5.00 plus 3.25. And so then the mole fraction of the original liquid is 0.606. So we can take that number and plug that back into this original expression. P total is equal to, well, the partial pressure of pure toluene, that's 3.85. And that's going to be plus the partial pressure of pure benzene, 12.85 minus 3.85 times 0.606. The total pressure then is going to be equal to 3.85 plus 5.45. So the total pressure is equal to 9.3 kilopascals. And so this number right here, this 9.3 kilopascals, that's the number that we are finding right here. That's the pressure as we lower down from 101.3 kilopascals, as we lower it down to 9.3 kilopascals, that's when we then will start to see the vapor start to form, because we've now hit this phase boundary. Now that we've found this pressure, we can now start to figure out what is this composition of the mole fraction of benzene in the vapor phase, because that's found at when this pressure that we just calculated, this 9.3 kilopascals, basically meets this liquid vapor phase boundary. And so the equation that we use to draw that liquid vapor phase boundary is P total is equal to the partial pressure of pure toluene times the partial pressure of pure benzene, and that's divided by the partial pressure of pure benzene minus the partial pressure of pure benzene minus the partial pressure of pure toluene, all times the mole fraction of benzene in the vapor phase. Substituting in numbers, we've got 9.3 being the total pressure, partial pressure of pure toluene is 3.85 times 12.85, and that's going to be divided by 12.85 minus 12.85 minus 3.85, all times the mole fraction of benzene in the vapor phase. If I continue to simplify, 9.3 is equal to 49.5 divided by 12.85 minus 9 times the mole fraction of benzene in the vapor phase. I'm going to continue to simplify. I'm going to basically multiply both sides by 12.85 minus 9 times the mole fraction of benzene in the vapor phase and divide both sides by 9.3. So 12.85 minus 9 times the mole fraction of benzene in the vapor phase is equal to 49.5 divided by 9.3. I'm then going to continue to rearrange. I'm going to move my 49.5 divided by 9.3 to the left-hand side, and my minus 9 times the mole fraction of benzene in the vapor phase to the right-hand side. And so I'm going to get 12.85 minus 5.32 when I do that division, and that's going to be equal to 9 times the mole fraction of benzene in the vapor phase. If I subtract 12.85 minus 5.32, I get 7.53. And to that, if I divide both sides by 9, then I get that equal to the mole fraction of benzene in the vapor phase. And so what that means is that my mole fraction of benzene in the vapor phase is equal to 0.836. And if I wanted to know the mole fraction of toluene in the vapor phase, well, that's just 1 minus 0.836, since I've only got a two-component mixture. And that means my mole fraction of toluene in the vapor phase is 0.164. And you can actually see here, just in this first quick calculation, that I started with a mole fraction in the liquid of 0.606, and then by dropping the pressure, I've created a vapor that has a mole fraction of benzene of 0.836. And so by simply just dropping the pressure, like I showed in the problem, that I create a vapor that has a mole fraction that's actually higher than the mole fraction of benzene. And so you can start to appreciate that this is how you can then start to separate the two mixtures, because if I were to take this vapor that I have here of just the toluene and the benzene, and I were to condense this to a liquid and then revaporize it again, I would then increase again the mole fraction inside that vapor. And it's through this process that I would continually separate these two volatile liquids. In that previous example, we just saw how fractional distillation occurs in practice. Through a series of pressure changes, one component of a volatile mixture can be separated from the other. So at constant temperature, we vary the pressure to separate the components. Starting at A, where the mixture is only a liquid, we drop the pressure to the liquid-vapor phase boundary. This means that the mole fraction of the vapor for one component, in this case benzene, is determined at point B, while the composition of toluene is found by taking 1 minus the mole fraction of benzene. What can be seen is that the mole fraction of benzene in the liquid is roughly 0.2, but in the vapor phase it's about 0.5. So if we separate the vapor from the liquid and raise the pressure on the vapor to condense it, point C, we now have a liquid with a much higher benzene concentration, roughly about 0.5. The vapor of this separated liquid has an even higher mole fraction of benzene, found at point D, roughly about 0.8. Therefore, through a series of steps where the vapor is separated from the liquid and condensed, the resulting solution become more and more concentrated with one of the two components. This is how fractional distillation works. A temperature mole fraction phase diagram can also be created. In the temperature mole fraction diagram, the lower region is the liquid, the mid region is the liquid vapor, and the top region is the vapor phase. Starting at A1, we heat the mixture to the liquid vapor phase boundary at A2. This creates a vapor where the mole fraction of component A is much larger than the liquid, found at A2'. Cooling the separated vapor, A3, condenses it, where the vapor from this condensed liquid has an even higher mole fraction of component A, found at A3'. By continuing these separation cooling steps, we can also separate two components of a mixture. The second topic in this lecture is what happens to the freezing point and boiling point of a solvent when a non-volatile solute is added to make a solution. We know that mixtures have lower chemical potentials than pure substances, and this shifts the phase boundaries to lower pressures as illustrated in the phase diagram on the right. So, for a given pressure, this shifts the freezing point to lower temperatures and the boiling point to higher temperatures. What we will see is that these colligative properties do not depend on the type of solute, but only on the concentration of this solute. To derive the changes to the phase diagram with respect to the mole fraction of the solute, we need to calculate something called the Gibbs-Helmholtz equation. We start with applying the product rule to the Gibbs free energy divided by the temperature. So, the derivative with respect to temperature at constant pressure of the Gibbs free energy divided by the temperature is equal to 1 over T times the partial derivative of the Gibbs free energy with respect to temperature at constant pressure, plus the Gibbs free energy times the derivative of 1 over T, which gives negative 1 over T squared. Recall, as was reviewed at the start of the lecture, that the partial derivative of the Gibbs free energy as a function of temperature at constant pressure is the negative entropy. So, substituting that into the above equation gives negative S over T minus G over T squared. Creating a common denominator, being T squared, and distributing out the minus sign gives G plus Ts over T squared, all times negative 1. Using the definition of Gibbs free energy means that G plus Ts is equal to the enthalpy, H. Therefore, the derivative with respect to temperature at constant pressure of the Gibbs free energy divided by the temperature is equal to negative H over T squared. We will use this a little later to simplify an expression. Let's now look at the melting point reduction. To do so, we will start at the equilibrium condition, being that the chemical potential of the pure solid is equal to the chemical potential of the solution. When these are equal to each other, we are at a phase boundary, where both the solution and the solid exists. To find the chemical potential of the solution, we know that it is equal to the chemical potential of the pure solvent plus RT times the natural logarithm of the mole fraction of the solvent. Solving for the natural logarithm of the mole fraction of the solvent gives the chemical potential of the pure solid minus the chemical potential of the pure solvent, all divided by RT. The difference in chemical potentials is simply the negative of the Gibbs free energy of fusion. The minus sign is due to the fact that the positive direction for this process is solid to liquid. The difference written here is written as a process going from liquid to solid. So, the natural logarithm of the mole fraction of the solvent is equal to the negative of the Gibbs free energy of fusion over RT. Since we are interested in melting point reduction as a function of the mole fraction of the solvent at constant pressure, expressed as the partial derivative of the temperature with respect to mole fraction of the solvent at constant pressure, we will differentiate with respect to mole fraction. This means the partial derivative with respect to mole fraction of the solvent of the natural logarithm of the mole fraction of the solvent is equal to 1 over the mole fraction of the solvent. On the right-hand side, we apply the chain rule, so the partial derivative with respect to mole fraction of the solvent of the negative of the Gibbs free energy of fusion over RT is equal to minus 1 over R times the partial derivative with respect to the temperature of the Gibbs free energy of fusion over temperature at constant pressure times the partial derivative of temperature with respect to mole fraction of the solvent at constant pressure. The first partial derivative on the right-hand side is simplified using the Gibbs-Helmholtz equation, giving 1 over the mole fraction of the solvent is equal to the enthalpy of fusion divided by RT squared times the partial derivative of temperature with respect to the mole fraction of the solvent at constant pressure. Rearranging this expression to separate the variables gives d mole fraction of the solvent over the mole fraction of the solvent being equal to the enthalpy of fusion divided by RT squared times dt. We will now integrate this expression where the bounds of integration are indicative of the process. On the left-hand side, the pure solvent has a mole fraction of 1, and it is diluted to some mole fraction after the addition of the solute. On the right-hand side, the pure solvent has a melting point of T fusion, and that changes to T as the solute is added. Upon integration, we get the natural logarithm of the mole fraction of the solvent is equal to the enthalpy of fusion divided by R times 1 over the original melting point minus 1 over the new melting point. Rearranging gives 1 over the new melting point is equal to 1 over the pure solvent melting point minus R times the natural logarithm of the mole fraction of the solvent divided by the enthalpy of fusion. This expression tells us that the lowering of the melting point does not depend on what was added to the solvent. The only thing that the solute changes is the mole fraction of the solvent, which is what ultimately lowers the melting point. It is more convenient to state this result with respect to the molal concentration of the solute. This can be written as the change in the melting temperature is equal to R times the molar mass of the solvent times the melting temperature squared times the molal concentration of the solute divided by the enthalpy of fusion times -1. All of the constants, being R, molar mass of the solvent, temperature of fusion squared, and the enthalpy of fusion, can be bundled together in a constant, K sub F. This is the freezing point constant, and they are known for many solvents. A similar derivation can be done also for the boiling point elevation. It leads to a similar expression. The change in boiling point is equal to R times the molar mass of the solvent times the boiling temperature squared times the molal concentration of the solute divided by the enthalpy of fusion. The constants in this expression can also be bundled together in a constant called K sub B. This is the standard boiling point constant. Let's now use what we have just learned to solve a problem that deals with raising of the boiling point and lowering of the melting point of a substance. In this case, we're adding 4.5 grams of something into 125 grams of carbon chloride. And so what we measure is that we have a boiling point elevation of 0.650 Kelvin. And what we want to find is the freezing point depression and the molar mass of the substance. And we're given various properties of the carbon tetrachloride. In this case, the normal freezing temperature, the standard freezing constant, the boiling temperature, and the standard boiling constant. So then to find the amount of freezing point depression, what I'm first going to do is we're going to make a relationship between the two expressions we just saw, being the change in freezing point is equal to the negative of the freezing point constant times the molality of the solute. And we also saw that the change in boiling temperature is equal to the boiling point constant times the molality of the solute. Now the common factor between these two equations is that they both share this molality of solute. And so what I'm going to do is I'm going to then rewrite both these expressions and solve for molality of the solute. So I have change in the freezing point divided by the freezing point constant. That's equal to the molality of the solute. And that's also equal to the change in the boiling point divided by the boiling point constant. And so what we're trying to solve for in this first problem is we're trying to solve for this change in freezing point. So I can solve for that change in freezing point with this relationship that I've just written, where I can say change in freezing point is equal to the change in boiling point times the negative of the freezing point constant divided by the boiling point constant. And so if I start to substitute in numbers that we have in the problem, then we have minus 30 times 0.65, all divided by 4.95. And that gives me then a freezing point depression of 3.9 Kelvin. To solve for the molar mass of the substance, I'm going to go back to looking at the change in boiling point being equal to the boiling point constant times the molality of the solute. What we know, or what I can write for this molality of the solute, is that that's equal to the mass of the solute divided by the molar mass of the solute, denoted by this capital M, times the mass of the solvent. And I'm explicitly writing out mass solute, mass solvent so that it doesn't get confused with the little m that I'm using for molal concentration. But what that basically means is that I can substitute in some of the numbers that I have inside this in this question. And the units I'm going to use here is that the mass of the solute I'm going to keep in grams, and the reason is because I'm going to use for the molar mass grams per mole, which means that this massive solvent has to be in kilograms. And this is just because when we do a molal concentration, this is typically in moles of solute divided by kilograms of solvent. And so in this way, by assigning these units, I'm going to have the correct units for my molality. So substituting numbers in, I have my change in my boiling point, which is 0.65. That's equal to my boiling point constant, which is 4.95. And my molality of my solute, well, my mass of my solute is 4.5 grams divided by the molar mass of the solute times the mass of the solvent in kilograms, 0.125. And so now I just need to solve for the molar mass of the solute. And that just means I multiply both sides by the molar mass of the solute and I divide both sides by 0.65. So I have 4.95 times 4.50. That's divided by 0.65 times 0.125. And so I get a molar mass of my solute being equal to 274.2 grams per mole. The process by which a solvent passing through a semi-permeable membrane and dilutes a solution is known as osmosis. The diagram below shows a U-shaped container where sugar is added to one side, and as a result, the water moves to the side with the sugar. The important part to the U-shaped container which makes this possible is the semi-permeable membrane. By semi-permeable, what is meant is that only certain components can pass through. Typically, this is the solvent that can flow freely. So in this case, water can pass through, while the solute, being the sugar, cannot. Osmosis can be thought of as an entropic process, where concentrated components tend to mix. So on the left side, there is sugar, and therefore water moves through the membrane to mix with it. The water level rises on the left side as a result, because the sugar cannot move to the right side, where it would normally do so if the semi-permeable membrane did not exist. The change in height of the solvent is typically quantified as an increase in pressure on the dilute mixture side relative to the pure solvent side. It is typically denoted with the symbol pi. To derive the added pressure, we again start with the equilibrium condition, where the chemical potential of the solution at the raised pressure is equal to the chemical potential of the pure solvent, and apply Raoult's law to express the concentration dependence of the chemical potential of the solvent in the solution side of the semi-permeable membrane. So, the chemical potential of the pure solvent at some temperature and pressure is equal to the chemical potential of the solvent in the solution at the same temperature but at an increased pressure, P plus pi, with a specified solvent mole fraction. Using Raoult's law, we can re-express the right-hand side as the chemical potential of the pure solvent at temperature T and pressure P plus pi plus RT times the natural logarithm of the mole fraction of the solvent. Rearranging gives minus 1 times RT times the natural logarithm of the mole fraction of the solvent being equal to the chemical potential of the pure solvent at temperature T and pressure P plus pi minus the chemical potential of the pure solvent at temperature T and pressure P. The right-hand side is the change in chemical potential as the pressure is raised from P to P plus pi. Recall that the change in molar Gibbs free energy with respect to pressure at constant temperature is the molar volume times dP. So this difference can be expressed as the integral from P to P plus pi of the molar volume of the pure solvent times dP, which is simply the molar volume of the pure solvent times pi. This assumes that the molar volume of the pure solvent does not change significantly over the pressure difference. This means that minus RT times the natural logarithm of the mole fraction of the solvent is equal to the molar volume of the pure solvent times pi. We will now make a few assumptions to simplify this expression. We will use a Taylor expansion of the natural logarithm, which is almost exact for very small values of the argument. This means that we can approximate the natural logarithm of the mole fraction of the solvent as minus 1 times the mole fraction of the solute. We will assume that the solution remains dilute, meaning that the number of moles of the solvent will be much larger than the number of moles of the solute. This means that the negative of the mole fraction of the solute is approximately equal to the number of moles of the solute divided by the moles of the solvent. Substituting this into the top equation gives RT times the number of moles of the solute divided by the number of moles of the solvent, and is equal to the molar volume of the pure solvent times pi. We can solve for pi, the increased pressure due to osmosis, and find that it's equal to the number of moles of the solute times RT divided by the volume of the solution. We will assume that the volume of the solvent and the volume of the solution are approximately the same. This result is called the Van 't Hoff equation, and note how similar it looks to the ideal gas law. Let's now do a quick example where we're going to calculate the osmotic pressure pi at 298 Kelvin, where if we put a cell, which has a concentration of 0.5 of some solute, and we're going to immerse this cell in pure water. And we're going to assume that the cell wall is permeable to water molecules, but is not permeable to the solute molecules. And so to do this, we're going to start with the Van 't Hoff equation. So pi being the osmotic pressure is equal to N solute times RT divided by the volume. And in this case, what we know, or what we have here in this example, is we have a concentration of the solute being equal to 0.5 moles per liter. And that's precisely what this part of the expression is telling us. This N solute is the number of moles per solute per unit volume. And that's exactly what we have right here. So we're going to substitute in that 0.5 for the N solute divided by the volume. And then R and T are going to be typically the values what we normally use. So 0.5 times 8.3145 being the gas constant times the temperature, 298. And in the end, what we get is 1,239 kilopascals. Or if we convert this into atmospheres, we have 12.2 atmospheres. So let's take a second and actually think about what we just calculated and what this 12.2 atmospheres of additional pressure means. So let's pretend here I've got my beaker, and then I drop my cell inside of it. So inside my beaker I've got water. And inside my cell, I'm going to have this solute mixture. And since there's this semi-permeable membrane, then we know that the water is going to then rush into my cell, and it's going to cause an additional pressure. Where outside here I have my pressure P, but inside here I'm going to have P plus pi. And what that means is that if we're talking about just normal atmospheric pressure, this is just 1 atmosphere. But by putting this cell inside this solution or inside this water, what we've done is that we've added an extra 12 atmospheres of pressure to this column. And you can imagine then that if we're not careful with this, there's an amazing amount of pressure that was just generated. And so this is one of those reasons why you have to be careful in biological systems when dealing with osmotic pressure, because it's very easy to generate very large pressures. So for example, you don't actually want to give hospital patients pure water in an IV, because what that does is that then generates a huge osmotic pressure inside blood cells, which can cause them to rupture. In this lecture, we saw that using equilibrium conditions of mixtures defined by the chemical potential can predict colligative properties. One example of this process is fractional distillation, where the separation of volatile liquids occurs through cycling pressure or temperature of the mixture and condensing the vapor at each cycle. A second example predicts the lowering of the freezing point or raising of the boiling point in a mixture. These two changes can be predicted using delta Tf is equal to negative Kf times the molality of the solute, and delta Tb is equal to Kb times the molality of the solute. The final example in this lecture is the osmotic pressure, which is the additional pressure generated on the solution side of a semi-permeable membrane, and is predicted using the Van 't Hoff equation, being pi is equal to the number of moles of the solute times R times T divided by V. Welcome to Lecture 11. In this lecture, we will show that minimizing the Gibbs free energy of a mixture undergoing a chemical reaction can determine equilibrium concentrations of the components and derive how shifts in conditions affect this equilibrium. This lecture will be broken down into 2 parts. In the first part, we will define the equilibrium constant K from first principles, and in the second part, we will examine how K, and by extension, the equilibrium concentrations, change when the conditions are modified. At constant temperature and pressure, A reaction mixture tends to adjust its composition until its Gibbs free energy is at a minimum. This adjustment not only is a function of mixing, but also based on the composition of the mixture given a chemical reaction that links the components together. The parabolic plots in the figure below shows the Gibbs free energy versus the reaction coordinate. Each colored line represents a reaction that favors some combination of reactants and products. This is indicated by where the minimum Gibbs free energy is located, as systems will tend to move towards minimizing the Gibbs free energy, as that is the spontaneous process. For example, the blue line has its minimum close to the pure reactant side of the composition spectrum. This indicates that the reaction characterized by the blue line favors the reactants. Conversely, the green line's minimum is close to the pure product side of the x-axis. Therefore, the reaction characterized by the green line favors the products. Finally, the red curve, with the minimum in the middle, indicates that the equal mixture of reactants and products will spontaneously result. At each of these minima, the system is said to be in equilibrium. A generic chemical reaction can be expressed as some amount of A of species A in the gas phase reacting to form some amount of species B in the gas phase. The change in Gibbs free energy can be expressed as dG is equal to the chemical potential of A times the change in moles of A plus the chemical potential of B times the change in moles of B. Since the change in each component, dN, can be different for each species, we will instead use a common term, dC, to denote the infinitesimal extent of the reaction. This means that each term has to now be weighted by their stoichiometric coefficient. Thus, dG is equal to negative A times the chemical potential of A times dC plus B times the chemical potential of B times dC, where we explicitly give the reactants a negative sign in this case to denote that they are being consumed. Dividing both sides by dC and assuming constant temperature and pressure gives d by dC of the Gibbs free energy at constant temperature and pressure is equal to B times the chemical potential of B minus A times the chemical potential of A. The derivative of the Gibbs free energy with respect to the reaction coordinate at constant temperature and pressure is simply the change in Gibbs free energy for the reaction. Therefore, we can make some generalizations. If the chemical potential of the reactants is greater than the chemical potential of the products, then delta G of the reaction is less than 0, and the forward reaction is spontaneous. If the chemical potential of the reactants is equal to the chemical potential of the products, then delta G of the reaction is equal to 0, and the system is at equilibrium. And finally, if the chemical potential of the reactants is less than the chemical potential of the products, then delta G of the reaction is greater than 0, and the reverse reaction is spontaneous. For substances, we have seen that the chemical potential can be written as the chemical potential of some component J is equal to the standard chemical potential of that component J plus RT times the natural logarithm of A sub J, where A sub J is the activity of the substance. Recall that activities are dimensionless quantities where the reference chemical potential is in the standard state and gamma indicates the deviation from ideal conditions. In the table below are the activities for various substances in their standard state and what we will use for their activity. Note that for a pure liquid and solid we will use an activity equal to 1, meaning that they are already in their standard state. This is because we will assume that a pure solid and a pure liquid are not mixed and cannot mix with another substance, so their chemical potential is not altered from the standard state. The remaining three substances, gas, solute, and solvent, are all easily mixed, and we have discussed their mixing in a previous lecture. In these cases, the activity is gamma times the ideal quantity divided by the standard state, and is a unitless quantity. Gamma represents the deviation from ideal conditions. So using the previous example of some gas A reacting to form some gas B, we can substitute in our expression for the chemical potential into our change in Gibbs free energy of the reaction expression to write the change in Gibbs free energy of the reaction is equal to B times the standard chemical potential of B plus RT times the natural logarithm of the activity of B, all minus A times the standard chemical potential of A plus RT times the natural logarithm of A. And that since we know that the change in Gibbs free energy, or the standard Gibbs free energy of the reaction, is equal to B times the standard chemical potential of B minus A times the standard chemical potential of A, and if we arrange the natural logarithm terms,
what we can get is the change in Gibbs free energy of the reaction is equal to the standard change in Gibbs free energy of the reaction plus RT times the natural logarithm of the activity of B raised to the power of B divided by the activity of A raised by its stoichiometric coefficient A. What we will do now is we will define something called the reaction quotient as that ratio of activities, meaning that it's equal to, in this case, the activity of B raised to the power of its stoichiometric coefficient B divided by the activity of A raised to its power of its stoichiometric coefficient A. And in the end, once we make the substitution for the reaction coefficient into the expression above, what we get is the change in the Gibbs free energy of the reaction is equal to the change of the standard Gibbs free energy of the reaction plus RT times the natural logarithm of the reaction quotient. When the system is at equilibrium, meaning that the change in Gibbs free energy of the reaction is equal to 0, a special case for the reaction quotient occurs. In this case, we will define that at equilibrium, Q is equal to K, and our expression becomes 0 is equal to the standard change in Gibbs free energy of the reaction plus RT times the natural logarithm of K. And when we rearrange this expression, we get the standard change in Gibbs free energy of the reaction is equal to negative RT times the natural logarithm of K. K is the equilibrium constant. This expression is a very important relationship since 1. The thermodynamic properties of the constituent parts can predict the equilibrium concentration of the mixture, and 2. The measurement of K allows for the quantification of the standard change in Gibbs free energy for the reaction.
We're now going to look at some examples in the context of equilibrium, and we're going to use the Haber-Bosch process as the main chemical reaction that we're going to use to examine equilibrium. And so the Haber-Bosch process is this reaction where we're combining nitrogen and hydrogen to form ammonia. And what it has been credited with is essentially the continued explosive growth of the human population during the 20th century. And so leading up to this point, where in about 1913 in Germany, when this was first industrially produced, and if I were to mark it on my little plot right here, which is a plot of the population of the Earth as a function of time, we had growth of the human population, and it continues going up exponentially. But during this time that we had, right around the turn of the 20th century, the nitrogen that was being used in fertilizer was being mined. And it wasn't necessarily clear where a continued renewed supply of this fixated nitrogen could be found to ensure the continued exponential growth of the human population. Not to mention that this fixated nitrogen was also used in munitions. And so that's why Germany was a country that was very concerned about creating a process, because they had to mine it externally, and because of embargoes during World War I, they needed to find a separate source. Hence, Professor Haber and Professor Bosch, who were both German physicists, they then industrially produced this process and won the Nobel Prize for it. But to put this in the context of how important then the fertilizer aspect to this industrial process is that annually today we create about 450 million tons of fertilizer produced from this process, and that the Haber-Bosch process consumes about 1 to 2% of the total annual world energy budget, which is an amazing amount of energy focused on just one very simple chemical reaction. But the output from this is that it has essentially quadrupled the productivity of all the agricultural land on Earth, which means that if we didn't have this process, we would have to use 4 times as much agricultural land to produce the equal or the food necessary to feed the 7 to 8 billion people that we currently have on Earth. Now, what is truly neat about this process is that we can use these concepts in equilibrium and shifts in equilibrium to understand completely why the industrial process is set up the way it is. And so that's what we're going to start to do right now in this example, and then as we move through the lecture. So the first step that we're going to accomplish is we're going to just simply find the change in Gibbs free energy of this reaction. And we're going to find the standard change, where basically we're going to do this at 298 Kelvin. And we're going to do this so that we can then determine the K for this process, the equilibrium constant, so that if we were to then just throw nitrogen and hydrogen into a reaction vessel and just let it go for enough time, that then we'd be able to predict what is the equilibrium concentration of the reactants and the products. And that's essentially what we're going to do in number 3, is that we're going to have a bar of nitrogen and 3 bars of hydrogen, and then since now we know K, we can then find out the equilibrium concentration of all the reactants and products. So starting with the first problem, where we're just going to find out what the change in the standard Gibbs free energy of the reaction is, well, that's just what we've discovered a couple of lectures ago. The change in the standard Gibbs free energy of the reaction is just the weighted sum of the products minus the weighted sum of the reactants. And I'm just going to be pulling these numbers from tables. And so for our products, we have 2 times ammonia, and the standard Gibbs free energy of ammonia is negative 16,450 joules per mole. And I put the 2 in front of it because I have a stoichiometric coefficient of 2 as a part of the balanced equation. And then for my reactants, I have nitrogen and hydrogen in their standard states. And so then I'm going to have 0 plus 0, because the Gibbs free energy of formation of standard states is equal to 0. And so what that means is that my changing the standard Gibbs free energy for the reaction is minus 32,900 joules per mole. Let's now find K. We just saw a second ago that this change in Gibbs free energy, or the standard change in Gibbs free energy of the reaction, well, that's also equal to negative RT times the natural logarithm of K. And so in this case now we're going to take this number that we just calculated a second ago and then solve for K. So minus 32,900, that's equal to minus 8.3145, so that's the gas constant R, times the temperature, we're at 298 Kelvin, times the natural logarithm of K. And just as a side note, the reason why I chose to express my Gibbs free energy in joules per mole instead of kilojoules per mole is that my R value is also expressed in joules. And so I wanted to make sure that both of these values had the same order of magnitude for this unit of energy. And that's why I made that choice there. But if I rearrange so that I divide both sides by R and T and the negative sign, then on the left-hand side I'm going to get 13.3 is equal to the natural logarithm of K, which means then my K is equal to 5.84 times 10 to the 5. So taking a brief step back and thinking about what this number means, this K value, this equilibrium constant value, well, we also just saw that the equilibrium constant can be expressed as the activities. And so I have the activity of ammonia raised to the power of 2, and I have that divided by the activity of nitrogen, and then I have the activity of hydrogen raised to the power of 3. And because I have this number that is very, very, very big, this 5.84 times 10 to the 5, what that means is that in this case the numerator is then going to be some big number, and that's going to be divided by a relatively smaller number. And so this says then that if I'm going to put a bunch of reactants in a vessel, that then over time these are going to tend to form ammonia all on its own, simply because this is what the equilibrium constant is telling us, and that the direction of spontaneity, the direction of the Gibbs free energy, tells us that it's going to move towards products, which is great for this process because that's what we want. We want to take nitrogen and hydrogen and form ammonia so we can use it in a relevant application like fertilizer production. So let's then do the third part to this problem, where we're actually going to then calculate, based on throwing in 3 bars of hydrogen and 1 bar of nitrogen, what are then the equilibrium concentrations that come out of this. And so if I'm going to substitute in numbers here, I'm going to write 5.84 times 10 to the 5, because that's what my value of K is. Over here on my left-hand side, I have my activities, and so I'm going to substitute in directly for the pressures. Since that's what I have here, is I have gases in my chamber. So I have the partial pressure of ammonia squared divided by the partial pressure of nitrogen times the partial pressure of hydrogen cubed. And in this case, all 3 of these partial pressures are divided by the standard pressure, which is just 1 bar. Now the one thing that you have to do here in this case is that we have to use an ice table to basically determine what is the equilibrium concentrations, because that's what these pressures represent, is the pressure of these gases at equilibrium. And so we know what they are initially, and so then to find the change, then that's where the ice table comes in. So I have my H2, my N2, and my ammonia, and I have initial, change, and then at equilibrium. And so initially I have 3 bars of hydrogen, I have 1 bar of nitrogen, and I have 0 bars of the product, which is ammonia. The change that happens is going to be 3 times H, since that's the stoichiometric coefficient in front of hydrogen. The nitrogen, I just subtract X. And then finally with the nitrogen, I am going to be adding 2 times X, because again, the stoichiometric coefficient instead of in front of the nitrogen, or sorry, in front of the ammonia is 2. So that means then at equilibrium, I start with 3 and I'm going to subtract 3x for the hydrogen. I start at 1 and I subtract x for the nitrogen. And then here I start at 0 and I'm going to add 2x for the ammonia. So I can now take these expressions and I can put them back into my relationship between K and the activities over on this side. So if I'm going to write in my K again, I have 5.84 times 10 to the 5. I have in this expression for my partial pressure of ammonia, for that I'm going to write in 2x squared. On the bottom I'm going to have 1 minus x, and that I'm going to have multiplied by 3 minus 3x raised to the power of 3. What I can do is I can start to simplify this expression, so I'm going to have 5.84 times 10 to the 5, and that's equal to, well, on top if I evaluate the square, I'd have 4x squared. On the bottom I have 1 minus x, and then here I've got 3 minus 3x, so I can distribute out a 3, and then that 3 also goes to the power of 3. So I'm going to have a 27, because 3 times 3 times 3 is 27, and then I have 1 minus x times 1 minus x cubed, which gives me 1 minus x raised to the power of 4. Here I can simplify one more time, so I'm going to have 5.84 times 10 to the 5 on my left-hand side. I'm going to have a 4 over 27 because I just take that numerator and denominator out. And then I am left with an x squared over a 1 minus x raised to the power of 4. And the equivalent statement to that is to say, well, that's just x over 1 minus x squared, all squared. Because if that thing gets basically multiplied by itself, then I get x squared is over 1 minus x raised to the power of 4. Now I'm doing all this work because now I can start moving some of these terms to the left-hand side and simplifying again what's going on the right-hand side. So if I do multiply by 27, divide by 4, and take the square root, so if I multiply by 27 and divide by 4 times 5.84 times 10 to the 5, then what I get is 3.94 times 10 to the 6, and then I can take the square root of that, and what that leaves me on the right-hand side is x over 1 minus x squared. That number, the square root of 3.94 times 10 to the 6, well, that's just going to be equal to 1986. And that I'm going to multiply, and now I'm going to multiply both sides by 1 minus x squared, or 1 minus x all squared, but I'm also going to expand it by using first outside, inside, last. And so that gives me 1 minus 2x plus x squared. And on the right-hand side, I'm still left with x. If I distribute in the 1986 into this polynomial, I'm going to get 1986 minus 3972x plus 1986 squared, or x squared. And if I move this x to the other side, I subtract both sides by x, then I get a minus x here, and that's going to be equal to 0. And then finally, if I subtract the two terms that just have an x associated with it and rearrange, I'll have 1986 times x squared. I'm going to have minus 3973x, because I have 3972 minus x. And to that I'm going to add the 1986, and that's equal to 0. And so what we have here is a polynomial that we can solve using the quadratic formula. And some of you might be thinking, well, why couldn't before we just cross off the x in the denominator and simplify? And the reason is because this k value is super big. This is a very big k value, and whenever you did that, the k values were very small, and so then the changes would be very small. But in this case, because k is very big, then that means that this x that we have here is also going to be very big, so we can't cross it off. And so what that means is that we have to go through this solution process where we actually have to solve for x using all the terms, and what that leads us to, as I've said before, is that this polynomial, which we will now solve using the quadratic formula. So the quadratic formula is written as x is equal to minus b plus or minus b squared minus 4ac all square root divided by 2 times a, where again the way that these polynomials are written is ax squared plus b times x plus c is equal to 0. So in this case, my a is this 1986, my b is the negative 3973, and my c is 1986. And so if I substitute those numbers in, I get x is equal to 3973 plus or minus 3973 squared minus 4 times 1986 times 1986. I take the square root of everything after the plus minus, and then I'm going to divide that by 2 times 1986. If I start to simplify these expressions, then what I'm going to end up with is 3973 plus or minus the square root of 7945, and that's divided by 3972. And so if I evaluate this using the plus and the minus, so in one way I'm going to evaluate it with the plus, and that's going to give me 1.023. Or if I do it with the minus, then I'm going to get 0.978. And so we end up with two solutions, and that should be expected. We should get usually two roots out of the quadratic equation. And so how do we know which one to choose? And so this is where we go back to our ice table and we pull out, well, what were supposed to be the concentrations at equilibrium? And we said, well, the pressure of hydrogen, that was going to be 3 minus 3x. And the pressure of nitrogen, well, that's supposed to be 1 minus x. And the pressure of the ammonia, that was supposed to be 2 times x. And what we just found is these two values of x. So if we were to take the 1.023 and we were going to plug that into x, what we would get as a value is 3 times 1.023, and that number is going to be then bigger than 3, so we would end up with a negative number. And we would do the same thing here for the nitrogen, 1.023, well, that x into here, well, that's going to be then bigger than 1, and that also gives us a negative number. And negative pressures make 0 sense. And so because of that, we can then logically deduce that we're not going to be using this 1.023 value. Conversely, if we use this 0.978 and we plug that into these x values, then I'm going to get positive numbers in the end. And in fact, if I do that for my pressure of hydrogen, I'm going to get 0.067 bar. Down here with my nitrogen, I'm going to get 0.022 bar. And then finally, for my pressure of my ammonia, I get 1.96 bar. Now again, let's just take a quick step back and let's just do one last quick calculation. And what I want to calculate is what is the mole fraction of ammonia at the equilibrium conditions. And so the mole fraction is just simply going to be the partial pressure of the ammonia divided by the total partial pressure, or the total pressure in the vessel. And so the partial pressure of ammonia is 1.96, which we just calculated a second ago, and the total pressure is 1.96 plus 0.022 plus 0.067, which is 2.049, and what that gives us is 0.96. And this is actually fairly remarkable because what this value tells us, this 0.96, says that when we started at the beginning we had 0 mole fraction of ammonia. We put in some hydrogen and some nitrogen into a vessel, and that over time when it moves towards equilibrium we ended up with an amount, or in terms of mole fraction, 96% of it is going to be then ammonia. Now here's the rub with this, is that when we talk about spontaneity, and that's what we talk about when we look at Gibbs free energy and changes in Gibbs free energy, we don't talk about reaction rates. It doesn't tell us a single thing about how fast the reaction goes. And in fact, in this case, this reaction has a super high activation energy. And so there are certain things that we have to do then to overcome that, and then that'll shift the equilibrium. And that's something that then we're going to start to discuss next. Before we can move on with the discussion regarding the Haber-Bosch process, we will need to define Le Chatelier's principle. It is defined as, when a system at equilibrium is subjected to a disturbance, the composition of the system adjusts so as to tend to minimize the effect of the disturbance. This is a qualitative rule of thumb, where a disturbance causes the reaction to shift in order to return to the equilibrium constant K. The only way that K itself is modified is through changes in temperature, since temperature is the only variable in the definition of K. Now let's apply Le Chatelier's principle to various conditions. First, the effect of a catalyst. Recall that equilibrium occurs when the forward and reverse reaction rates are equal. A A catalyst increases both reaction rates by changing the pathway the reaction follows, as illustrated in the figure on the bottom right. This figure shows two reaction pathways, where the parabolic pathway isn't catalyzed and the multi-step pathway is catalyzed. However, this does not affect the equilibrium concentrations of the reaction since the change in reaction rate is equivalent to both directions. If we look at this in the context of the Gibbs free energy, recall that the standard Gibbs free energy of the reaction plus RT times ln K is equal to 0, and since the standard Gibbs free energy of the reaction is a state function, the pathway that the reaction takes is irrelevant to K. The change in Gibbs free energy is the same for both pathways. Therefore, adding a catalyst does not affect the equilibrium concentrations. What about changes in temperature? Returning to the Haber-Bosch process, which converts nitrogen and hydrogen gas to ammonia, we calculated that the heat of the reaction is negative 91.6 kilojoules per mole. How would an increase in temperature change the composition of the equilibrium? Well, Le Chatelier's principle tells us that by increasing the temperature, and as a consequence heat, the equilibrium will shift left to consume the added heat and favor more reactants. This can be visualized by thinking that heat is a product in this reaction, and the increase in temperature adds heat to the system, which must be consumed, therefore shifting the equilibrium towards the reactants. We've said that changing the temperature is the only way to change K for a given reaction. So, let's quantify how K changes with varying temperature. Recall the Gibbs-Helmholtz equation, which is the partial differential with respect to temperature at constant pressure of the standard change in Gibbs free energy of the reaction divided by the temperature is equal to the negative of the standard change in enthalpy of the reaction divided by the temperature squared. If we substitute in the equilibrium expression, then we get the partial differential with respect to temperature at constant pressure of negative RT ln K divided by T is still equal to the negative of the change in standard enthalpy of the reaction divided by T squared. On the left-hand side, the T's cancel out, and we can take out a negative R and move it to the right-hand side in order to get the partial differential with respect to temperature at constant pressure of the natural logarithm of the equilibrium constant is equal to the change in standard enthalpy of the reaction divided by RT squared. This equation has also been called the Van 't Hoff equation. If we can assume that the standard enthalpy of the reaction does not change significantly over the change in temperature, then we can integrate both sides, meaning that we have an integral from one equilibrium constant K1 to the second equilibrium constant K2 of d ln K is equal to the integral from T1 to T2 of the standard change in the enthalpy of the reaction divided by RT squared times dt. The result of this integral is that we get ln K being evaluated between K1 and K2, and that's equal to the change in the standard enthalpy of the reaction divided by R times negative 1 over T, which is evaluated between T1 and T2. And then applying the fundamental theorem of calculus leads to the natural logarithm of K2 minus the natural logarithm of K1 being equal to the change in standard enthalpy of the reaction divided by R times 1 over T1 minus 1 over T2. This equation is how we can quantify changes to the equilibrium constant K with changes in temperature. Let's return to the Haber-Bosch process, which is this reaction where we convert nitrogen and hydrogen into ammonia, which is used to make fertilizer. And what we saw before was that at room temperature and pressure, we saw that by putting the reactants into a chamber, the equilibrium is in such a way that the reaction moves almost all the way to completion and that we form ammonia, which is great. However, the reaction is very slow, and so what equilibrium concepts tells us is where things go, but it doesn't tell us how long the process takes. And so in order to speed up the reaction, what we do is that we add a catalyst and we increase the temperature. And so what we need to do now is figure out, let's predict what happens with this change in temperature and how this affects our equilibrium. So the first thing that we're going to do is we have to recalculate what our K is, because we've just discussed that when we increase the temperature, we're going to then be changing our equilibrium constant K. That's essentially what this first question is asking us, is we're going to calculate the equilibrium constant K when we've increased the temperature now to 463 Kelvin. So recall when we did this problem previously and we calculated K, we saw that at 298 Kelvin, we had an equilibrium constant that was equal to 5.84 times 10 to the 5. And so based on this result that we had from before, we're going to now calculate what is the equilibrium constant at 463 Kelvin, this elevated temperature, so that we can increase the reaction rate. So using the expression that we just figured out before, we just calculated previously, the natural logarithm of K2 minus the natural logarithm of K1, and that's equal to the standard enthalpy of the reaction divided by the gas constant R, and that's multiplied by 1 over T1 minus 1 over T2. I'm just going to move my natural logarithm of K1 to the other side to isolate for the natural logarithm of K2. So I have natural logarithm of K2 is equal to the change in the standard enthalpy of the reaction divided by R times 1 over T1 minus 1 over T2. And to that I'm going to add plus the natural logarithm of K1. At this point I'll start substituting in numbers the natural logarithm of K2, and that's equal to negative 91.6 times 10 to the 3 joules. And that's I get from my standard heat of the reaction, which was just provided up here. My gas constant is in joules, 8.3145. My T1, well, that's going to be the values that I have already. So this is at 298, and this 5.84 times 10 to the 5. So I have 1 over T1, 1 over 298. From that I'm going to subtract off T2, which is at this elevated temperature, the 463. So 1 over 463. And to that I'm going to add the natural logarithm of 5.84 times 10 to the 5. When I evaluate both these expressions, I still get the natural logarithm of K2. That's equal to minus 13.175 plus 13.278. When I add these two numbers together, I get the natural logarithm of K2 being equal to 0.1027. The inverse of a natural logarithm is an exponent, so I take e to the power of to both sides, which means I get K2 is equal to e to the power of 0.1027. When I evaluate that, I get 1.11. And so the really important thing that we should see here is that this value for K is much smaller than it was before. And so we know just intuitively that as we decrease the rate or the equilibrium constant K, what we're going to do is that the concentrations at equilibrium are now going to be more balanced between reactants and products than they were before. Since before we had this really huge K that was times 10 to the 5, and now we've dropped 5 orders of magnitude and we're now at times 10 to the 0. So let's now see what our new equilibrium concentrations are based on what we've just calculated. So in this problem, we're still going to start with the same 1 bar of nitrogen and 3 bars of hydrogen gas, and we're going to determine the equilibrium concentrations of the reactions and products at this new elevated temperature. And so to do so then, we start with, again, our equilibrium constant is equal to the activity of the ammonia squared divided by the activity of the nitrogen times the activity of the hydrogen cubed. And we do these things basically to these powers because these powers again come from the balanced chemical reaction, which we would write as N2 plus 3H2 is in equilibrium with 2NH2, or NH3 I should say. And so if we build our ice table again, where we would say we start with 1, 3, and 0 for the ammonia, we're going to lose 1x of the nitrogen, we're going to lose 3x of the hydrogen, and then we're going to add 2x of the ammonia. And so what that means then at equilibrium, we're going to have 1 minus x, we're going to have 3 minus 3x, and we're going to have 2x. And so these are the values, and then we're going to substitute in for our activities because we assume that these gases behave ideally. So we have our equilibrium constant, which we've just calculated, 1.11, and that's going to be equal to 2x squared divided by 1 minus x times 3 minus 3x cubed. This equilibrium coefficient or constant is still quite large, and so we probably can't do any approximations. We'll just solve this analytically. And so what that means is that I can distribute out certain quantities. I have the 1.11 on the left. I have a 2 squared on top, so that gives me 4x squared. On the bottom I have 1 minus x. And inside the second part of the denominator I have a 3 which I can factor out. And that 3 then I also take to the power of 3 when I factor it outside, which 3 times 3 times 3 is 27. And that leaves me with 1 minus x raised to the power of 3. If I then
move these terms to the other side, what I get is 7.48, and that gives me an x squared divided by 1 minus x raised to the power of 4. And so what I can do now is I can take the square root of both sides, the square root of 7.48, the square root of x squared over 1 minus x raised to the power of 4. And what that gives me is 2.735 being equal to x divided by 1 minus x squared. And so then in this case now we can actually write this in terms of a quadratic. And so if I move this denominator, this 1 minus x squared, over to the left-hand side, I multiply both sides by it, I get 2.735, and that's going to be equal to 1 minus x squared being equal to x. I'll now apply FOIL, first outside, inside, last, to the 1 minus x squared term. So 2.735, 1 minus 2x plus x squared, that's still equal to x. I'm going to distribute in the 2.735, so I'm going to get 2.735 x squared minus 5.47 times x. To that I'm going to add 2.735, and I'm going to move my x to the other side, so I'm going to have a minus x, and that's equal to 0. And what this finally gives me in terms of a quadratic is 2.735 x squared minus 6.47 x plus 2.735 being equal to 0. I'm going to take these terms and put it into the quadratic equation. X is equal to 6.47 plus or minus 6.47 all squared minus 4 times 2.735 times 2.735. All of that is inside a square root. That I'm going to divide by 2 times 2.735. Now if I simplify, what I get is x being equal to 6.47 plus or minus 3.46 divided by 5.47. And so if I apply this, where if I do the plus and the minus cases, what I get is an x being equal to 0.55 or 1.82. And if we look back at our ICE table, what we can see is that we have 1 minus x squared, 3 minus 3x, and that basically helps us choose which one of these two answers we can take. Because if I were to take an x of 1.82, then this number would be a negative number, and this number would also be a negative number, which is something that is impossible. So we would immediately then cross off the 1.82, and we would select the 0.55 as our answer. And so if we were to then calculate what the final pressures are at equilibrium, we have a pressure of the nitrogen being equal to 1 minus 0.55, and that gives us an answer of 0.45 bar. We have our pressure of hydrogen, and that's equal to 3 minus 3 times 0.55, and that gives us an equilibrium pressure of 1.35 bar. And we have our pressure of ammonia, and that's equal to 2 times 0.55, and that's equal to 1.1. And so then if we calculate the mole fraction of ammonia, like we did last time, we found that this has actually now dropped to 0.38. And this isn't great, at least not for our reaction, because remember, we're trying to produce ammonia so that we can make fertilizer, and if we do this at an industrial scale, we want it to be a very efficient process. But the reason why we had to do this was that we wanted to increase the temperature so that we can increase the reaction rate. But this has the negative consequence of lowering our output of our reaction. We're going to be forming less products. The story doesn't end here, though, for the industrial Haber-Bosch process. We can still apply another type of stress to the system to help counteract the effect of the increase in temperature. Let's see how an increase in pressure affects the composition of the gas phase equilibrium. Le Chatelier's principle tells us that by increasing the pressure of a component, the system will shift to consume it. If all the partial pressures are changed through changing the volume of the container, the equilibrium will then favor the side of the reaction with the fewer number of moles of gas. In the case of the Haber-Bosch process, by using a smaller container, which increases the partial pressure of all components, this exchange will shift the equilibrium to the right, since there are fewer moles of ammonia in the right-hand side of the reaction.
How do we quantify changes due to varying pressures? Well, we will note that the natural logarithm of the equilibrium constant is proportional to the standard change in Gibbs free energy of the reaction. This is defined at 1 bar, so changes in pressure do not affect K. Even though K doesn't change, the equilibrium concentration is affected by changes in pressure. These are calculated using an equilibrium expression. Returning one final time to the Haber-Bosch process, where we were examining how stresses that are applied to the system are basically used to drive forward this industrial process into what we see today. What we saw previously was that we increased the temperature so that we can increase the rate of the reaction. But what that also did was shifted the equilibrium towards the reactants, which is something that was not very good in terms of trying to produce ammonia from this reaction. And so what we're going to explore now is the effect of pressure changes on the equilibrium. And so what we're going to do is we're going to calculate the same thing where we're going to do it now at 4 times the pressure, still at 463 Kelvin. And we're going to predict the equilibrium composition of the mixture. We will start from the same starting point where we're going to say K is equal to the activity of the ammonia over the activity of the nitrogen times the activity of the hydrogen. And we're going to still write our same ice table where we have nitrogen plus 3 hydrogens in equilibrium with ammonia, and we have 2 ammonias. And in this case, in every other problem we started with 1 bar of nitrogen and 3 bars of hydrogen. In this case we're going to quadruple that, so we've got 4 and 12. We still have 0 in terms of the ammonia. The change in this case is still going to be minus x, this is still minus 3x, this is still plus 2x for the change in each of these components, which means that at equilibrium the nitrogen is going to have 4 minus x, the hydrogen is going to be 12 minus 3x, and the ammonia is going to be at 2x. So substituting these values into the equilibrium expression, we've got 1.11, which is our equilibrium constant at 463 Kelvin. On the top we have 2x all squared, divided by 4 minus x times 12 minus 3x raised to the power of 3. I can make the same distribution or distribute out the same terms as I did before. So on top I've got 4x squared. On the bottom I'm still going to have 4x. Here because I've got 12 minus 3, well I can factor out 3. And then raised to the power of 3, I've got 3 times 3 times 3, gives me 27 again on the bottom. And then 12 divided by 3 is 4, 3 divided by 3 is 1, so I get 4x, or 4 minus x, raised to the power of 3. I can then move the 27 and the 4 over to the left-hand side, and so what I get is 7.4925 is equal to x squared divided by 4 minus x, raised to the power of 4. And so what I'll do at this point is I'll take the square root of both sides. That leaves me with 2.737 is equal to x over 4 minus x all squared. I can then move this denominator over to the left-hand side, where I'm going to get 2.737 times 4 minus x squared is equal to x. And then finally what I'll do is I'll FOIL, the 4 minus x squared. So I get 2.737. And what I end up with is 16 minus 8x plus x squared. And that's still equal to x. I'm going to distribute in the 2.737, and I'm going to move this x over to the left-hand side. And so what I'll get is 43.792 minus 21.896x plus 2.373x squared minus x, and that's equal to 0. Finally, my expression here is going to ultimately be 2.737x squared minus 22.896x plus 43.792, and that's equal to 0. So I'm going to take this expression and then I'm going to plug in the respective values into the quadratic formula. X is equal to 22.896 plus or minus 22.896 squared minus 4 times 2.737 times 43.792. All of this part is inside a square root, and all of this is divided by 2 times 2.737. So if I simplify these two expressions, or this expression I should say, these two parts of this expression, I've got 22.896 plus or minus 6.697, and that's going to be divided by 5.474. And so when I solve for the plus minus and I solve for x, what that gives me is an x that's equal to 2.96 or 5.406. And again, I go back up to my starting point again. Here I've got 4 minus x as the equilibrium concentration for, or pressure, sorry, for the nitrogen gas. And if I were to choose the answer 5.406, then I would get a negative number. And that means that I can immediately then go cross off that value, and I'm going to then use the 2.96. And so ultimately what I'm going to get is a nitrogen pressure at equilibrium to be equal to 4 minus 2.96. And what that gives me then is a value of 1.04 bar. I have a partial pressure of hydrogen gas, which is equal to 12 minus 3 times 2.96, which gives me a value of 3.12 bar. And my partial pressure of ammonia, that's going to just be equal to 2 times 2.96, which gives me then a partial pressure of 5.92. And if we do this quick analysis again, where we find out, well, what is the mole fraction of ammonia in this equilibrium mixture, we find that it's now equal to 0.59. And so this value is certainly better than the value that we had before when we didn't apply higher pressures. And so what we've basically determined by going through all these different equilibria steps is that we found that at the beginning, at a low temperature and pressure, we would get lots of products. But we found that the reaction went really slowly. So to alleviate that, we raised the temperature and added a catalyst, which then shifted the equilibrium back towards the reactants, and we formed much less products. But then also what we then did was we increased the pressure a lot, and that again caused then a stress that would then force the reaction to produce more products again. And this mirrors exactly what happens industrially. We have a high temperature catalytic process that's done at high pressures. And that's how most of the ammonia, which is then ultimately converted into fertilizer, is produced on an industrial scale today. Chemical reactions, like mixtures, minimize their chemical potential until equilibrium is established. The equilibrium constant can be calculated according to the change in standard Gibbs free energy of the reaction being equal to the minus RT times the natural logarithm of the equilibrium constant. Le Chatelier's principle states that when a system is at equilibrium and it is subjected to a disturbance, the composition of the system adjusts so as to tend to minimize the effect of the disturbance. Only temperature modifies the equilibrium constant, and it modifies it according to the natural logarithm of K2 minus the natural logarithm of K1 is equal to the change in the standard enthalpy of the reaction divided by the gas constant R times 1 over T1 minus 1 over T2. Welcome to Lecture 12. In today's lecture, we will quantify the activity coefficient for ionic solutions and apply it to sparingly soluble salts in order to describe the process of salting in and salting out. This lecture will be broken down into 3 parts. In the first part, we will define the activity coefficient, gamma, for ions in solutions. In the second part, we will use 2 versions of the Debye-Huckel laws to calculate the activity coefficient for ionic solutions, and then apply it in the third part to see how the activity coefficient affects the solubility of ions. Electrolyte solutions, meaning solutions composed of molecules that break down into charged ions when in solution, deviate from ideal conditions at low concentrations. This is because of the Coulombic forces between ions that act over a long range. Therefore, we have to treat ionic systems as real solutions. Like all real solutions, we will write their activities to include an activity coefficient, meaning that the activity of component J is equal to the activity coefficient of component J times the mole concentration of component J divided by the standard mole concentration, where we use the standard molality being 1 mole per kilogram. And in this case, we will use molality instead of molarity because molality is temperature independent. Gamma sub J is the activity coefficient. This quantifies the deviation from ideal conditions for the solute. Just as Henry's law would predict, as the molality of component J goes to 0, then the activity coefficient of component J goes to 1. In real terms, as the system is diluted, the closer it returns to ideal conditions. Having defined the activity of the solute, we can write the chemical potential of component J as the chemical potential of component J being equal to the standard chemical potential of component J plus R times T times the natural logarithm of the activity of component J. Now, consider the dissociation of table salt in water, being NaCl being deposited in liquid H2O, and that's in equilibrium with the Na plus aqueous and the Cl minus aqueous ions. And the activities for this process include the activity for the sodium ion being gamma plus times the molality of the sodium ion divided by the standard molality, and the activity for the chlorine ion is equal to gamma minus times the molality of the chlorine ion divided by the standard molality. So in order to calculate the activities, we need to know the concentration and the activity coefficients. However, no procedure currently exists to measure gamma plus or gamma minus, since separating the effect of the cation from the anion is not possible. They both occur simultaneously and are not easily separated. So, we need a method to calculate the activity coefficients for both ions. This method won't directly involve using the individual activity coefficients. Consider instead a salt M nu plus, X nu minus, where M forms the positive ion and X forms the negative ion, while nu plus and nu minus are the number of M and X in the salt. The Gibbs free energy for the salt is N plus being the number of moles of the positive ion times the chemical potential of the positive ion, plus N minus being the number of moles of the negative ion times the chemical potential of the negative ion. Using the definition of the chemical potential for non-ideal dilute solutions, meaning the chemical potential of component J is equal to the standard chemical potential of component J plus RT times the natural logarithm of the activity of component J, where the activity of component J is equal to the activity coefficient of component J times the molal concentration of component J divided by the standard molality. And knowing this, it can be shown that the average activity coefficient, being something that is defined as gamma plus minus, can be defined as gamma plus minus raised to the power of nu plus plus nu minus is equal to gamma plus raised to the power of nu plus times gamma minus raised to the power of nu minus. And when we define this average activity coefficient, we can actually include that into our expression of Gibbs free energy, where the average activity coefficient is now used as the activity coefficient for both ions, meaning that we can write the total Gibbs free energy as N plus times the standard chemical potential of the positive ion plus RT times the natural logarithm of gamma plus minus times the molal concentration of the positive ion divided by the standard molal concentration, and that's all plus N minus times the standard chemical potential of the negative ion plus RT times the natural logarithm of gamma plus minus times the molality of the negative ion divided by the standard molal concentration. Let's now do a quick calculation in order to calculate an average activity coefficient, where in this problem we're going to take some Na2SO4 and we're going to dissolve it in water to form a 0.01 moles per kilogram solution. And let's pretend that we could actually calculate the activity coefficients for the sodium plus ion and the SO4 2 minus ion being equal to 0.98 and 0.84 respectively. And so what we're going to do in this problem is that we're going to calculate the average activity coefficient, and then we're just going to calculate the activities for each ion using the average activity coefficient. So my first step here is just to write down the balanced chemical reaction. So we have the Na2SO4, which is a solid, and to that we're throwing it into water, H2O, which is a liquid. This is an equilibrium where we're going to have two Na plus aqueous ions, and we're going to have one SO4 2 minus aqueous ion. And so based on this, we can actually then start to write down our average activity coefficient expression, which is this gamma plus minus raised to the power of nu plus plus nu minus, and that's going to be equal to gamma plus raised to the power of nu plus times gamma minus raised to the power of nu minus. And so the values that I'm going to be plugging in here is on this left-hand side, I've got gamma plus minus. Well, nu plus, in this case, that's just going to be equal to the stoichiometric coefficient here, and that's equal to 2, since there's two Na pluses. So I'm going to have 2 plus, and the stoichiometric coefficient in front of the SO4 2 minus is just a 1, so it's 2 plus 1. And that's going to be equal to the gamma plus, where in this problem we define gamma plus as 0.98, so I'm going to have 0.98 raised to the power of 2, since again I have two sodium ions, and then that's going to be multiplied by, I have the 0.84 for the SO4 2 minus ion, 0.84, and that's going to be raised to the power of 1, because I've only got one SO4 2 minus. And so if I evaluate the left-hand side and the right-hand side, what I get is gamma plus minus raised to the power of 3, and that's going to be equal to 0.807. And so at this point then I'm just going to take the cube root of both sides, and once that's done I can say gamma plus minus is equal to 0.931. So that's part 1 finished. So let's now do part 2, where it says calculate the activities of each ion. So I'm going to have the activity of Na plus, and that's just going to be equal to gamma plus minus times the mole concentration of the sodium ion divided by the standard mole concentration. And so when I start substituting in numbers, what I'm going to get is the activity of the sodium ion is equal to gamma plus minus, which we just calculated, 0.931. The concentration of the sodium ion, well, we start off with a concentration of the salt as 0.01 moles per kilogram, and since there's two sodium ions for every 1 mole of the salt itself, then that means I'm going to have 2 times 0.01 as my mole concentration of sodium. And that I'm just going to divide it by 1 kilogram or 1 mole per kilogram, which is the standard mole concentration. And so at the end of the day, when I multiply these numbers together, I'm going to get 0.019 moles per kilogram. Looking forward now, if I calculate then the activity of the SO4 2 minus, that's just going to be equal to gamma plus minus times the mole concentration of the SO4 2 minus divided by the standard mole concentration. Activity of SO4 2 minus, well again, this average activity coefficient is just 0.931, and then since for every 1 mole of salt I put in, I get 1 mole of SO4 2 minus, then it's just going to be 0.01 divided by 1. And so when I multiply these numbers together, I'm going to get 0.0093 as the activity for the SO4 2 minus. We just covered that we cannot directly calculate individual ionic activity coefficients, so using them to calculate an average activity coefficient is also not a good strategy. However, Peter Debye and Debye-Huckel developed a theory to determine the average activity coefficient. Central to their theory, they assumed that each charge was surrounded by a cloud of opposite charge, which lowers the potential energy of the system. This results in the average activity coefficient being less than 1. One could imagine that at low concentrations, the oppositely charged ions could surround each other without interfering with similarly charged ions. However, as the concentration of ions increases, similarly charged ions will start to interact with each other in a significant way. Therefore, the Debye-Huckel law becomes valid as the concentration of the ions approaches 0. In the opposite extreme, when the concentration of ions in the solution is large, empirical modifications should be employed. For small ionic concentrations, we can employ the Debye-Huckel limiting law to calculate the average activity coefficient, since it is equal to the log of the average activity coefficient is equal to negative a times the absolute value of z plus times z minus times I raised to the power of 1/2, where a is a constant. For water at 25 degrees Celsius, a is equal to 0.509. Z plus and Z minus is the charge of the positive and negative ions respectively, and I is something called the ionic strength of the solution, and it is defined in terms of the molalities of all ions in the solution, where I can be calculated as 1/2 times the sum over I, being all the charged particles in the system, and the sum goes over Zi squared, being the charge squared, times the mole concentration of species I divided by the standard mole concentration. Let's now use the Debye-Huckel limiting law in the context of a problem so that we can get a better idea as to where the values one would put into it come from. And so what we ultimately want to do with the Debye-Huckel limiting law is calculate a mean activity coefficient. And so in this case, we're going to calculate one for ions where we have a total concentration of 0.001 moles per kilogram of Na2SO4 aqueous at 25 degrees Celsius. And so the first thing that we need to do whenever we calculate the mean activity coefficient in this way is that we need to calculate the ionic strength, which is this expression that's equal to 1/2 times the sum over I of Zi squared times the molar concentration of component I divided by the standard molar concentration. Recall for this dissociation of Na2SO4, what we had was this Na2SO4 solid going and being added to water, which is a liquid, and this is in equilibrium so that we have 2Na plus aqueous plus SO4 2 minus aqueous. And so in this case, this will help us inform what values we're going to put into this ionic strength expression. Because in this case, I'm going to write I is equal to 1/2. And in this case, I'm going to write this sum. So for the first part of this sum, I'm going to use the sodium plus ions. And so in this case, the Zi is the charge on the sodium atom. In this case, that's 1. So I'm going to write 1 squared. The molar concentration of the sodium plus ions is 0.001 times 2, since that's the total concentration of sodium ions, since the original concentration was 0.001 moles of Na2SO4 per kilo of water. So that's why I'm writing 2 times 0.001. And then the standard molar concentration is 1, which I'm going to write as the denominator. And because this is a sum, then that means I'm going to write the second part of this sum, which is now the SO4 2 minus. And in this case, the charge on the SO4 2 minus, that's the Zi term, is -2. So we have -2 squared times its concentration. It's a 1-to-1 mole ratio between Na2SO4 and SO4 2 minus. So I just write 0.001. And to that I'm going to then divide it by 1, the standard molar concentration. So if I evaluate this expression, or I simplify, I get I is equal to 1/2 times 0.002 plus 0.004. And what this leaves me with is an ionic strength of 0.003. So now that we have the ionic strength, we can now use the Debye-Huckel limiting law to calculate the average activity coefficient. And so in this case, we would write then the logarithm of the average activity coefficient is equal to -a times the absolute value of Z plus times Z minus times the square root of the ionic strength. And so again, on the left-hand side, I'm going to have the logarithm of the average activity coefficient. A in this case, because I'm at water with 25 degrees Celsius, is just going to be equal to 0.509. The charge on the sodium, which is the plus or the positive ion, is 1. The charge on the negative ion is -2, the SO4 2 minus, absolute value. And then I have the square root of 0.003. And so if I evaluate all of these terms, I get the log of the average activity coefficient, and that's equal to -0.056. And finally, if I do the inverse of a natural logarithm, of a logarithm base 10, then that would mean that I'm going to take 10 to the power of whatever value it is. So I'm going to have then the average activity coefficient is equal to -0.0, or 10 raised to the power of -0.056, which makes it equal to 0.88. As we have said previously, the Debye-Huckel limiting law is only valid for dilute solutions, meaning low ionic strength, since we are assuming that like charges are distant enough not to interact with each other significantly. The more concentrated the ions in solution, the further the activity coefficient deviates from the Debye-Huckel limiting law. In these cases of high ionic strength, we must use empirical corrections to fit the data. One such empirical expression is called the Davies equation. It is expressed as the logarithm of the average activity coefficient is equal to -0.509 times the absolute value of Z plus times Z minus times the square root of the ionic strength divided by 1 plus the square root of the ionic strength
minus 0.3 times the ionic strength. And as the ionic strength decreases, the Davies equation approaches the Debye-Huckel limiting law. In the figure on the right, there is a plot of the logarithm of the average activity coefficient versus the square root of the ionic strength. There is a blue line and a parabolic red curve, where the decreasing blue line illustrates the Debye-Huckel limiting law, and the red curve illustrates the Davies equation. These two curves deviate when the square root of the ionic strength is greater than 0.2. We will use this value as the threshold to shift from using the limiting law to the Davies equation. Given the empirical relationship between the activity coefficient and the ionic strength, as approximated by the Davies equation, adding ions to the solution will at first have a beneficial effect and then a negative effect on the solubility of the ions in solution. This arises from the fact that at low ionic concentrations, ions of opposite charge will associate with one another and not each other, which lowers the potential energy of the system, leading to a higher affinity for the solution to dissolve a higher concentration of ions. However, as more ions are introduced, like charges will interact with each other more strongly, raising the potential energy of the system and reduce the affinity for the solution to dissolve ions. Therefore, the ionic strength of a solution can directly affect the solubility of a substance. This is called salting in and salting out. We're now going to do an example which illustrates this phenomena of salting in and salting out, where we're going to use a sparingly soluble compound, in this case magnesium fluoride, which is going to dissolve into water to form magnesium ions and fluoride ions with an equilibrium constant of 6.4 times 10 to the minus 9. And we're going to examine three different cases for this. The first case, which is what we're going to look at in number 1, is if we were to just throw in magnesium fluoride salt into water, what is the equilibrium concentration of the ions? So what would we expect in terms of just the solubility of these ions just by themselves in the solution? In the second question, what we're going to do is we're going to then, at equilibrium, we're going to add in 0.01 molar of potassium nitrite salt, which is a very soluble salt, so we're going to assume that it dissociates completely. And we're going to see what happens with the concentration of the dissolved magnesium fluoride ions. And the upshot to this is that we expect that because this is a small concentration, that we're going to increase the concentration of these ions, and this is salting in. And then finally, in this final question, question 3, we're going to add in a lot of this KNO3 salt. And what we're going to do is calculate now the new concentration of the dissolved ions. And what we'll see is that as we greatly increase the concentration of this salt, we're going to decrease then the solubility of the magnesium fluoride, and that this is then going to be called salting out. So, starting with question 1, since we're dealing with an equilibrium expression, we're simply going to start by writing our ice table. We have our MgF2, which is a solid, plus H2O, which is a liquid, and that's going to be in some equilibrium with Mg2 plus 2F minus. And if I write my ice table, ICE, well, because we've got a solid and we've got a liquid, then those two things don't matter. And at the starting point, we have 0, 0, plus x plus 2x. And so that at equilibrium, we're going to have x and 2x as our equilibrium concentrations of our two ions. And then from there, we just start by writing our equilibrium expression, KSP. That's going to be equal to the activity of magnesium 2 plus times the activity of fluorine minus raised to the power of 2. And if we substitute in for these activities, then what we end up with is KSP is equal to gamma plus minus times the molality of magnesium 2 plus divided by the standard molality times gamma plus minus times the molality of the fluoride ion divided by the standard molality, all squared. So we're now in a bit of a chicken and an egg problem, because to calculate these equilibrium concentrations, we need to know what these gammas are. We need to know what these average activity coefficients are. But to calculate these average activity coefficients, we need to know the ionic strength, which, to know the ionic strength, which I'm writing down the expression over here, which is equal to 1/2 times the sum over all the ions, times, which is the charge of all the ions squared, times the concentration of all the ions divided by the standard concentration. Well, we need to know what the concentration of ions in solution before we can calculate the gamma plus minus, the average activity coefficient. So the solution to this problem
is that we will take an iterative approach where for this first round, before we actually solve for the equilibrium concentration, taking into account the ionic strength, we will just assume that the ions are not important, at least for this first time through. And this is so that we can get a first estimate as to the concentration of ions in solution, so that then we can then calculate an ionic strength to then calculate a new average activity coefficient to then find out what is actually the concentration of ions in solution. And so that's the strategy that we're going to follow right now. And so if I was to write out that strategy, that what we're going to do, we're going to first assume that gamma plus minus is equal to 1, meaning the ions have no effect. We're going to calculate the concentration of the ions. Based on this, we can actually then calculate an ionic strength. From that, we can then calculate what is actually the gamma plus minus, or at least a better estimate of the gamma plus minus. And then we're going to then find out what is the concentration of ions, taking into account this new gamma plus minus. Let's now put this plan into action. And so what that means then is I'm going to set these average activity coefficients to be equal to 1. And then if I start substituting in numbers, I can get 6.4 times 10 to the minus 9. The concentration of the magnesium ions, well, I have that over here from X, so that's going to be equal to X. I have the concentration of fluoride ions, which is just going to be 2x, so I have 2x all squared. And then I know that these standard mole concentrations, they're just equal to 1 mole per kilogram, so I can just set those to 1. This then makes a fairly straightforward solution to find what x is. And so if I take the 4 and divide both sides by 4, I'm going to get 6.4 times 10 to the minus 9 divided by 4 is equal to x cubed. And I'm just going to take the cube root of both sides. And so what I'm going to get when I solve for x is going to be equal to 1.17 times 10 to the minus 3. And what that means then is that my concentration of my magnesium ions is going to be equal to 1.17 times 10 to the minus 3. And my concentration of fluoride ions is going to be equal to 2.34 times 10 to the minus 3, because it's equal to 2 times x. So 2 times 1.17 times 10 to the minus 3 is equal to 2.34 times 10 to the minus 3. So that's the first two steps of this plan. The next step is to calculate the ionic strength. And so now I actually have a concentration of, at least a first iterative knowledge of the concentration of ions in solution. So now I can calculate I. So in this case, I'm going to have I is equal to 1/2, and this is the sum over all these terms. So the first term is going to be 2 squared, since I'm talking about the magnesium. And the concentration of the magnesium is 1.17 times 10 to the minus 3. And that's going to be divided by 1, since that's the standard mole concentration. And to that I'm going to add minus 1, because now I'm talking about the fluorine. So minus 1 squared times 2.34 times 10 to the minus 3. And that's going to be divided by 1 as well. My ionic strength then is equal to 1/2 times 4.68 times 10 to the minus 3 plus 2.34 times 10 to the minus 3, which means that my ionic strength is going to be equal to 3.51 times 10 to the minus 3. And so if we're trying to decide now if we're going to use the Debye limiting law, if we're going to use the Davies equation, that test that we were going to use, or the choice we make, is if we say if the square root of I is greater than or less than 0.2, and in this case the square root of 3.51 times 10 to the minus 3 is less than 0.2. And so then we'll use the limited law to calculate our average activity coefficient. And that's what is our next step on this. So we've just done number 3 here. We've calculated the ionic strength. And so our next thing now is to do the average activity coefficient. So to calculate that, we use the Debye-Huckel limiting law, which, as we saw before, it's the logarithm of the average activity coefficient being equal to negative 0.509 times the absolute value of Z plus times Z minus, which is the charge on the positive and negative ion, times the square root of I. The log of the average activity coefficient is equal to negative 0.509 times 2 times minus 1 absolute value, and that's times the square root of 3.51 times 10 to the minus 3, which was the ionic strength that we just calculated a second ago. We have the log of the average activity coefficient then is equal to negative 6.03 times 10 to the minus 2, which then means that our average activity coefficient is equal to 0.87. And so this was now step 4 that's completed, where we've now calculated the average activity coefficient given that we have some concentration of ions in solution. So our last thing now is then to calculate what is the concentration of ions in our solution, given that now we are actually quantifying the effect of the ions on the solution. And so to do that, then we just go back to our equilibrium expression. So we have Ksp is equal to the activity of the magnesium ions times the activity of the fluoride ions squared. I'm going to do the exact same substitution. I have Ksp is equal to gamma plus minus times the molality of the magnesium ions divided by the standard molality, and that's going to be times the average activity coefficient times the molality of the fluoride ions divided by the standard molality, and that's raised to the power of 2. And so in this case now, instead of setting my average activity coefficient to 1, which assumes that the ions have no effect, we know that the ions do have an effect. We are dealing with a real solution, and we've actually now calculated an average activity coefficient for this system. And so that means that I'm going to keep my gamma plus minuses. What I will do is I can immediately cross off these standard mole concentrations because they're both just 1. And so if I start to substitute in numbers, I'm going to get 6.4 times 10 to the minus 9, and that's going to be equal to 0.87 cubed. And where I get that from is I get 1 from the activity of magnesium, and I get 2 from the activity of fluoride because of the fact that it's squared. And then I get times x, which is from the concentration of magnesium, and then I have 2x all squared, which is with the concentration of the fluoride ion. And so then in this case I then rearrange 6.4 times 10 to the minus 9 divided by 4 times 0.87 cubed. And that's going to be equal to x cubed. And so I'm going to just take the cubed root of both these numbers. And what that leaves me with is an x that's equal to 1.34 times 10 to the minus 3. And so what we can see here is that the difference between this x, this 1.34 times 10 to the minus 3, and the x that we calculated before, which was this 1.17 times 10 to the minus 3, that illustrates to us that there really is a difference when we take into account the fact that the solution is real. That the average activity coefficient does mean that there is a different solubility that'd be calculated from between the two cases of where we assume that the ions have no effect on each other to when the ions do have an effect on each other. And in the end what we have is a concentration then of the magnesium ions being equal to 1.34 times 10 to the minus 3, and the concentration of the fluoride ions is double that. So that means it has a concentration of 2.68 times 10 to the minus 3. So I'm now just going to reiterate this process that we just went through, where when we're solving these problems, we start our equilibrium expression and we assume that the ions have no effect. So we set our average activity coefficient to 1. Based on that, then we can now calculate the concentration of the ions using this assumption. Once we know that, we can then calculate the ionic strength. Once we know an ionic strength, we can now recalculate an average activity coefficient that takes into account the fact that we do have ions in solution. And then finally, we can then calculate the concentration of ions that we have based on this average activity coefficient. And what we would do actually at this point, if we wanted to be ultra precise on these concentrations of ions that we have in solution, in this case the magnesium and the fluoride, is that we would then repeat 4 and 5 again. And we would continue to repeat those things until these concentrations don't change very much, meaning that this iterative process that we would go through to find out these concentrations, we would keep cycling through doing 4 and 5 over and over again until these numbers don't change. For the purposes of this course, though, we're only going to just do 1 through 5, just so that we don't have an onerous amount of work to do whenever we solve one of these on an examination. So let's now take stock of where we are. We just finished problem 1,
or part 1 of this problem, where we were just finding out what is the concentration or the equilibrium concentration of the ions in solution. And so now that we know this, we're going to now attempt number 2, where now that at equilibrium, we're now going to add this very soluble salt, and we're going to find out how does this shift then the equilibrium, or how does this change the concentration of our magnesium and fluoride ions in our solution. So now that we have this concentration of magnesium and fluoride at equilibrium, we actually know already then many of the pieces. We don't have to go through all 5 of these steps again. We're actually at the step, if I back up here, we've just finished essentially step 2 by calculating these equilibrium values. And so where we're going to jump in this process is here at step 3, where we're going to calculate the ionic strength of our solution. And so that means then is that we have our ionic strength calculation, which is equal to 1/2 times the sum over all the ions in the solution, times the charge, times the concentration of the ion, times the standard mole concentration. Our next step is just to substitute in the values for this sum. So I is equal to 1/2 times, and I'm going to start again with my magnesium. So I've got 2 squared times the concentration, which is what we just calculated a second ago, 1.34 times 10 to the minus 3, divided by 1, the standard mole concentration. We have our fluoride ions, so I've got minus 1 times, or squared, times that concentration we calculated, 2.68 times 10 to the minus 3. That's going to be divided by 1. We now have our sodium ion, and so that has a +1 charge. That's going to be squared, and we said that the concentration was 0.01, because we assumed that it dissociates completely. And that's going to be over 1. And then finally we have our NO3 ions, which has a charge of -1, which is going to be squared, times 0.01 divided by 1. So if we calculate this ionic strength, what we end up with is 1/2 times 5.36 times 10 to the minus 3, plus 2.68 times 10 to the minus 3, plus 0.01, plus 0.01. I keep simplifying. My ionic strength is equal to 1/2 times 0.02804, which leaves me with an ionic strength of 0.01402. And again, we're doing this decision whether or not we're going to use the limiting or the Davies equation. And we can find that the square root of the ionic strength is going to be less than 0.2. And so we're going to use then the limiting law. So let's calculate our average activity coefficient. The logarithm of the average activity coefficient is equal to negative 0.509 times the absolute value of Z plus times Z minus times the square root of the ionic strength. The logarithm of the average activity coefficient is equal to negative 0.509 times 2 times minus 1 times the square root of 0.01402. This means that the logarithm of the average activity coefficient is equal to negative 0.1205, which means then that our average activity coefficient is equal to 0.7576. And now that we have this average activity coefficient, we go right back to our equilibrium expression. So again, we have our magnesium fluoride salt plus H2O water is in equilibrium with the magnesium 2 plus aqueous plus 2F minus aqueous. And if we write our ice table, ICE, we have our salt and our liquid, they don't matter. And we started with a concentration of 0.00134. And we started for the fluorine, we started with 0.00268. The change in this case is still plus x, and it's still plus 2x for the fluoride ion, which means that our equilibrium concentration after adding this extra salt is going to be 0.00134 plus x and 0.00268 plus 2x. And then we go back to our equilibrium expression. KSP is equal to the activity of the magnesium salt times the activity of the fluoride ion, and the magnesium ion. We continue to write KSP is equal to gamma plus minus times the molality of the magnesium ion over the standard mole concentration. times the average activity coefficient times the molality of the fluoride ion divided by the average activity, or sorry, the standard molar concentration, all squared. And so then next is I'm just going to start substituting in numbers. I'm going to have 6.4 times 10 to the minus 9. I'm going to have that equal to, again, my gamma is going to be cubed, so I'm going to have 0.7576 raised to the power of 3. My concentration of magnesium ions at equilibrium is 0.00134 plus x. And then my concentration of fluoride ions at equilibrium is 0.00268 plus 2x, all squared. If I continue to simplify, I'm going to have 6.4 times 10 to the minus 9 divided by 0.7576 cubed. And then over here on this side, on the right-hand side, I have 0.00134 times, or plus x. And in this case, I have 0.00268 plus 2x. And so what I can do is I can factor out a 2. And if I do that, I'm actually having to square it once I factor it out. So I'm actually factoring out a 4. But what that does is that means I now have 0.00134 plus x all squared. And so by doing so now I have two terms that look exactly the same, which means that I can multiply them together to simplify this expression. So here I have 6.4 times 10 to the minus 9. That's divided by 4 times 0.7576 cubed, and that's equal to 0.00134 plus x raised to the power of 3, because I have 1 plus 2. And so then at this point I can just take the cubed root of both sides. And so what I'll get on the left-hand side once I do that is I get 1.544 times 10 to the minus 3, and that's going to be equal to 0.00134 plus x. And what that leaves me then is my x is going to be equal to 2.038 times 10 to the minus 4. Now this doesn't seem like a very big number, but remember we're comparing it to a number that's times 10 to the minus 3, so this actually has a significant, or it'll make a significant change to our concentration of ions just by adding in this extra salt. And so if we actually calculate that, we have our concentration of our magnesium 2 plus ions. Well, that was 0.00134. In this case, I'm going to add x, which is 2.038 times 10 to the minus 4, which gives me 1.54 times 10 to the minus 3. And if we look at my concentration of fluoride ions, this is equal to 0.00268 plus 2 times 2.038 times 10 to the minus 4, and that's going to be equal to 3.09 times 10 to the minus 3. So we can see here that by simply adding in 0.01 molar KNO3, what we've done is that we've increased the solubility of this sparingly soluble salt, where we went for the magnesium from 0.00134 to 1.54 times 10 to the minus 3, so we've changed that by about 15%. And the same thing down here, we had 2.68 times 10 to the minus 3 going to 3.09 times 10 to the minus 3. And so this phenomena is called salting in, where we add a salt so that we can make something more soluble. And so now going back to our original problem that we were looking at, we've now finished number 2, where we've looked at what happens when we add 0.01 molar of this KNO3. The second thing we're going to do, or sorry, the last thing that we're going to do is we're going to look at question 3, and we're going to see what happens if instead of adding 0.01, we're going to add in 2.0 moles of KNO3. And so in order to solve this, we're going to follow the exact same procedure that we just followed a second ago, only we just now have a different concentration of the salt that we added. So we're going to start with our ionic strength. I is equal to 1/2 times the sum over all the ions, which is the sum is over the charge of each ion squared times the mole concentration of each ion divided by the standard mole concentration. The ionic strength is equal to 1/2, and so now I'm going to write out this sum. I have the magnesium ion first, 2 squared, times 1.34 times 10 to the minus 3 divided by 1,
plus negative 1 squared times 2.68 times 10 to the minus 3 divided by 1. Now I've got the sodium ion, which is 1 squared times 2 divided by 1, and then I have my nitrate ion, which is negative 1 times, or squared, times 2 divided by 1. And remember, this problem is framed so that we're starting from the equilibrium concentration again before we added any sodium nitrate salt. And so that's where I have this 1.34 times 10 to the minus 3 and 2.68 times 10 to the minus 3 coming from. And again, in this case now, instead of it being 0.01 like I did in the last problem, it's now 2 molar, which is why I've got 2's written right there. So when I simplify this expression, what I get is an ionic strength that's essentially equal to 2. And what we can see here is that the square root of this ionic strength, the square root of 2, well, that's going to be much bigger than 0.2. And so in this case, we have to use the Davy's equation if we want to get somewhat close to what is empirically true for the ionic strength, or sorry, the average activity coefficient for this system. And so that's what we're going to employ next. That means then that the log of the average activity coefficient is going to be equal to negative 0.509 times the absolute value of Z plus times Z minus, and that's going to be all times the square root of the ionic strength divided by 1 plus the square root of the ionic strength minus 0.3 times the ionic strength. And so if we start to substitute in numbers, we get the logarithm of the average activity coefficient being equal to negative 0.509 times the absolute value of 2 times minus 1. And then I have the square root of 2 divided by 1 plus the square root of 2 minus 0.3 times 2. And so if I simplify this expression on the right, I get the logarithm of the average activity coefficient being equal to 0.01447, which means that my average activity coefficient is now equal to 1.034. And what you'll notice right now is that our average activity coefficient is now greater than 1. And so this is one of those predictors that helps you identify whether or not the solubility of your salt will go up or down. And you can do this based on looking at your average activity coefficient. So let's now take this average activity coefficient and plug it into our equilibrium expression. We're going to use the same one as before. So KSP is equal to the activity of the magnesium ion times the activity of the fluoride ion squared. We start substituting in numbers. 6.4 times 10 to the minus 9 is equal to, and I have my average activity coefficient, 1.034 times 0.00134 plus x times 1.034 times 0.00268 plus 2x, all squared. And where this expression is coming from is that we're using the exact same equilibrium expression that we used before. And so hence we can just plug that right in. The only difference from what we had in question 2 versus now is that the average activity coefficient has just been replaced with the one that fits for the ionic strength of the solution we're talking about. But that means when I simplify this, I get a similar expression that we had before. 6.4 times 10 to the minus 9, that's going to be divided by 4 times 1.034 cubed, and that's equal to 0.00134 plus x, and this value is raised to the power of 3, and I'm going to take the cubed root of both sides, and so what I'm left with is 0.001131 being equal to 0.00134 plus x. And so if I solve for x, in this case I actually get a negative number. I get negative 2.1 times 10 to the minus 4. And so again, this is another one of those indicators that says that we're starting to salt out, or that we're going to start to decrease our concentration of ions in solution. And if I calculate the concentration of ions in solution, I have magnesium 2 plus, and how I calculated that would be the 0.00134 plus x. X in this case is negative 2.1 times 10 to the minus 4. And so what I end up with is 1.13 times 10 to the minus 3. The concentration of my fluoride ions Well, that's equal to 0.00268 plus 2x. In this case, x is a negative number, so I'm going to say minus 2 times 2.1 times 10 to the minus 4. And that's equal to 2.26 times 10 to the minus 3. And so as you can see, I have now, by adding in a large concentration of sodium nitrate, I've gone from an equilibrium concentration before was added of 0.00134 and 0.00268 to a smaller concentration, 1.13 times 10 to the minus 3, 2.26 times 10 to the minus 3. And so this is the phenomenon of salting out, where when we add an extra salt to the solution, we add more ions to the solution, eventually we're going to come to the point where the ions interact with each other of similar charge, which then means that we're going to try to push out ions out of the solution. And the part where that happens in this case is part of this equilibrium expression where we can push out some of these magnesium and fluoride ions. So now I just want to summarize this process one last time because it's a long process and it's sometimes a lot of things to keep in mind. But what we did was we ended up first solving for our equilibrium concentration of our ions without taking into account the fact that they were ions. We assumed that it was an ideal solution. And so to do that, we just said, well, our average activity coefficient is equal to 1, meaning that this is an ideal solution, that the ions have no effect on each other. Once we did that, we were able to then calculate our concentration of our ions. And so in this case, this is our concentration of magnesium 2 plus and our concentration of fluoride minus, assuming that our gamma plus minus was equal to 1. Once we had that, then we actually now can have an estimation of these ions in solution. We knew that it wasn't going to be perfect, but it gives us then an ability to calculate for a first iteration what our ionic strength was going to be. And then from that, once we knew our ionic strength, we can now recalculate what is our average activity coefficient, because again, we realize that this isn't an ideal solution, this is a real solution, that we have ions interacting with each other in the solution, and that has an effect on their solubility. And once we have this updated average activity coefficient, we can then calculate the concentration of our magnesium and our fluoride ions given this new average activity coefficient. That is essentially how we ended up solving problem 1. And then once we had solved problem 1 and we knew our equilibrium concentrations of magnesium and fluoride, and we started adding in extra salt, then what that meant was that we could actually start at step 3, where we were just then needing to recalculate our ionic strength, so then we can then calculate an updated average activity coefficient, which then would give us an updated concentration of our magnesium ions and our fluoride ions, given this updated average activity coefficient. And so, again, the only reason why I bring this up is that we have these cases where when you start from scratch, so when we started in problem 1, we had this issue where we needed to find, or we needed to know, a concentration in order to then be able to solve for an ionic strength, which is then going to give us an average activity coefficient, which then would give us our concentration. And so because we didn't know this concentration to then calculate our ionic strength, we had to then make an assumption where we would say, well, we're going to just set this equal to 1, and then that starts this chain. But once we can actually get into this chain, then we can start inserting ourselves along it to then start recalculating values and setting up this iterative loop where we can get better and better representations of what our concentration is just by doing this loop over and over again until our concentrations don't change anymore. Ions in solution deviate the properties of mixtures from ideal conditions. This deviation is quantified using the average activity coefficient. It can be calculated using the Debye-Huckel limiting law, a theoretically determined expression designed for low ionic strength solutions. Alternatively, for higher ionic strength solutions, we must use empirically determined expressions, such as the Davies equation. Welcome to Lecture 13. In today's lecture, we will apply activity coefficients for ionic solutions to acid-base equilibria. This lecture will be presented in 2 parts. In the first part, we will review some acid-base equilibria concepts and then include ion effects which are governed by the average activity coefficient. In the second part, we will continue applying average activity coefficients in the context of buffer systems. Consider the following generic acid equilibrium reaction, being that HA in aqueous solution is plus H2O liquid,
is in equilibrium with A minus aqueous plus H3O plus aqueous. If we were to write an equilibrium expression based on this chemical reaction, we would write that the equilibrium constant Ka is equal to the activity of A minus times the activity of H3O plus divided by the activity of HA, which would be equal to gamma plus minus times the molality of A minus over the standard molality times gamma plus minus times the molality of H3O plus divided by the standard molality, all divided by the molality of HA divided by the standard molality. The percent ionization of the acid could be calculated by the molality of H3O plus at equilibrium divided by the molality of HA of the original point times 100%. And then finally, after the activity of H3O plus at equilibrium was determined, the predicted pH of the solution would be found by taking the negative log of the activity of H3O plus.
Let's take these concepts and then let's now do a refresher on how we would calculate the pH and percent ionization of an acid with an acid equilibrium constant of 1 times 10 to the minus 3. Now in this case what we're going to do is we're going to have 0.1 mole of some generic acid HA mixed into 1 kilogram of water, meaning that we're going to have 0.1 mole of this, and that in this case we're going to assume ideal conditions to start off with, where we're going to say our gamma plus minus is going to be equal to 1. Things first is that we'll write down our balanced chemical reactions. We have HA plus H2O, which is a liquid, DHA is aqueous, and that's in equilibrium with our conjugate base A minus aqueous plus H3O plus, also aqueous. And then if we write our ice table, ICE, we would say, well, our starting acid concentration, we already said, is 0.1 mole. We have nothing in terms of the conjugate base and nothing in terms of the H3O plus. Because the H2O is a liquid, it won't count in our equilibrium expression because its activity will always be equal to 1. The change in this case for our acid, we're going to subtract x. Because it's a 1-to-1 mole ratio, we're going to add x to both of these, which leaves me with 0.1 minus x at equilibrium. For my conjugate base, it's going to be x, and for my H3O plus, it's also going to be x. This means that I'm going to write my equilibrium expression to be equal to Ka is being equal to the activities of the products, so that's the activity of A minus times the activity of H3O plus divided by the activity of the acid, HA. And so if I start to substitute in numbers, I'm going to have 1 times 10 to the minus 3, and that's equal to gamma plus minus times x, gamma plus minus times x, and that's going to be divided by 0.1 minus x. So in the lecture where I did ions in solution, I ended up solving this expression using the quadratic formula. In this case, what I'm going to assume is that x is going to be very, very small. So meaning it's going to be much, much less than 0.1. And so what this does is this means that this term that's on the bottom, this 0.1 minus x, is just going to be equal to 0.1 because a subtraction is going to make it very little difference in terms of the 0.1 concentration. And then what we'll do is we'll then do a successive approximation to make sure that this value or this assumption is actually true. However, for this case, I'm going to show you how to solve it in this manner. The other thing that I'm going to do right away is I'm just going to cross off my average activity coefficients because we said that we're going to assume that it's going to be equal to 1, that we're operating under ideal conditions. And so in this case, I can simplify then this expression to be 1 times 10 to the minus 3 on the left-hand side times 0.1, and that's going to be equal to x squared. So if I take the square root of both of these sides, then what I get for my x is going to be equal to 0.01. We can now go back and we can actually gauge the validity of our approximation where we assumed that x was going to be much, much smaller than 0.1. And what we can do is just do a quick ratio where we would say 0.1 divided by 0.1, where this is equal to whatever x is divided by the original acid. And we can see that what we have is that this value is about 10%. If I multiply this by 100% right here. And generally what we would say is that if this value that we get, if this x over the original acid is less than about 5%, then we can just assume that our small value approximation is valid. In this case, though, it isn't less than 5%, it's about 10%, and so what that means is that we have to do a successive approximation. But all that means then is that we just take this
this expression that we just wrote a second ago, this equilibrium expression, which I've now denoted with a 1, and we're just going to do it, or we're going to keep doing it until we get the same number over and over again for x. And so in practice what that means is that I'm going to just write again 1 times 10 to the minus 3, that's going to be equal to x squared, and on the bottom here I'm going to have my 0.1 minus 0.01. So I'm now actually explicitly writing in what is the x that I had before, so I can actually get a more accurate value for my denominator. That means what I'm going to have is 1 times 10 to the minus 3 times 0.09, and that's equal to x squared. And so if I take the square root of both sides, what I'm going to get is an x being equal to 0.0095. And so we can see that we now have a slightly different number, which is fine, because again, we're still doing successive approximations, and we're going to keep doing this until we get the exact same number over again. 1 times 10 to the minus 3 is equal to x squared divided by 0.1 minus 0.0095. I'm going to get then 1 times 10 to the minus 3, and that's going to be multiplied by 0.0905, and that's going to be equal to x squared. I take the square root of both sides. I get an x that's equal to 0.0095. And so now, because I've gotten the same number twice in a row, then that means then I'm going to settle on this value and say that my x is equal to 0.0095. Now if I'd done this using the quadratic equation, then I would have solved the quadratic and I would have gotten this exact same number. So it doesn't matter which method you choose to use, it's just that if you end up doing successive approximations, you might end up doing multiple steps with this, whereas the quadratic solver might just take you to the answer immediately. Generally though, what we could say is that if the equilibrium constant is much less than the initial concentration of whatever it is that's doing the hydrolysis, in this case this is the acid, then we can use then the small x approximation and be fairly confident that it's going to be valid in the first attempt. It's just in this case, because our equilibrium constant Ka was on the same order of magnitude, or at least very close to our initial concentration of acid, it meant that a lot of the acid then would dissociate, which means that the x is going to be comparable to the initial concentration. But if Ka was some number like 1 times 10 to the minus 7, then we would have had something that was much less than 0.1. And then we probably would have even only had to do one iteration of the successive approximation, because we would have been far less than 5%, which is this threshold that we can typically use to say that a single approximation would be valid. Moving forward now, let's finish solving the problem where the problem asks us to find the pH and the percent hydrolysis. So in this case, the pH is equal to the negative log of the activity of H3O+. And so when I substitute in the activity, what I'm going to have is the average activity coefficient times the molality at equilibrium of the H3O+ divided by the standard molality, which is equal to 1. In this case, then I can then substitute in for these numbers. We said we're operating in ideal conditions, so I'm letting my gamma plus minus equal to 1. The molality was 0.0095 divided by 1. And so this gives us a pH of 2.022. And that if I were to calculate the percent ionization, then that's the molality at equilibrium divided by the original molality of what was in solution. In this case, it was the acid. I'm going to multiply that by 100%. And so when I substitute in the numbers, I get 0.0095 divided by 0.1 times 100%. And so what we're left with is 9.5%. Of course, acid-base equilibria are ionic solutions, so our assumption of the average activity coefficient being equal to 1 is not valid. Recall that in order to calculate the average activity coefficient, we can use the Debye-Huckel limiting law or the Davies equation, depending upon the ionic strength of the solution. If the square root of the ionic strength is below 0.2, then we can use the simpler limiting law. However, if the square root of the ionic strength is larger than 0.2, then we will use the Davies equation, as it offers a better empirical fit to the activity coefficient. Alright, so now that we remember that we have a way to quantify the average activity coefficient, let's now recalculate the same problem, taking the average activity coefficient into account. And so we still have the exact same chemical reaction, where we have some acid in solution added to water, which is a liquid, is in equilibrium with its conjugate acid or base in an aqueous solution, plus hydronium, H3O plus, aqueous. And then if we write our ice table, we have the exact same scenario that we had before. We start with 0.1 mole. We have nothing in terms of conjugate base or H3O plus. We're going to subtract x plus x plus x for our products. And so at equilibrium for our acid, we have 0.1 minus x, and then we have x and x for our conjugate base and H3O plus. And in this case, because the water is a liquid, then its activity is going to be 1 the whole time. What we also found previously was that the x that we had calculated under ideal conditions was 0.0095. And so if we go back to our list of things that we needed to accomplish while we were doing the sparingly soluble, which is something we're going to apply here as well, is that the first 2 steps was to calculate the concentration of ions in an ideal case where we assume that the gamma plus minus is equal to 1. And so we've actually done those 2 things already with the previous problem. And so we're now actually on to step 3, where we're going to calculate the ionic strength. We're then going to determine what our gamma plus minus is, our average activity coefficient, and then we're going to calculate the concentration of the ions, given that we have a real solution, meaning that we have calculated our gamma plus minus. And like I said in the previous problem, we've actually already done these 2 steps. We know the concentration of ions in the ideal scenario where we assume that gamma plus minus is equal to 1. And so then our next 2 steps that we're going to do is then calculate the ionic strength and our average activity coefficient, so that then we can then redetermine what our ions or our concentration of ions are, given that they are in a real solution. So starting first with calculating our ionic strength, that's equal to 1/2 times the sum over all the ions of the charge of the ions squared times the molality of the ions divided by the standard molality. And so if I were to write that out, I would have 1/2 times, and I would have 1 squared times the concentration of the H3O plus divided by the standard mole concentration. And to that I'm going to add minus 1 squared times the concentration of the conjugate base divided by the standard mole concentration. And so when I substitute in numbers, I get 1/2 times 1 times 0.0095 divided by 1 plus 1 times 0.0095 divided by 1. And so in the end, when I do this calculation, I'm going to get I is equal to 0.0095. And so what we can see here is that the square root of this number is going to be less than 0.2. And so that means then we can use then the Debye-Huckel limiting law. Using the Debye-Huckel limiting law to calculate our average activity coefficient means that my log of my average activity coefficient is equal to negative 0.509 times the charge of the positive ion times the charge of the negative ion, or at least I'm going to take the magnitude of that product, and that is going to be multiplied the square root of the ionic strength. So that means then the logarithm of the average activity coefficient is equal to negative 0.509, and that's going to be times 1 times negative 1. I'm going to take the magnitude of that product, and then I'm going to take the square root of 0.0095. And when I do that multiplication, then I'm going to get the log of the average activity coefficient is equal to negative 0.0496, which means that my average activity coefficient is equal to 10 raised to the power of negative 0.0496, and that's going to be equal to 0.892. Alright, so then we've now calculated our ionic strength, we've calculated our average activity coefficient, so our last step now is just to calculate what is the concentration of ions in this real solution. And so to do that, we just go back to our equilibrium expression. The equilibrium constant Ka is equal to the activity of the conjugate base A minus times the activity of hydronium divided by the activity of my acid. And in this case, I'm going to use the successive approximations method to calculate x, which is why I've labeled this as number 1, because I'm going to do this a couple of times. But substituting in numbers, I've got 1 times 10 to the minus 3, and that's equal to gamma plus minus times x I'm going to have, again, gamma plus minus times x for the activity of hydronium, and then that's going to be divided by 0.1 minus x. Since none of these values have changed, the only thing that's now changed is that I actually have a value for this gamma plus minus now, which we just determined a second ago, which was this 8.892. So, substituting in those numbers, what I'm going to get is 1 times 10 to the minus 3. I'm going to use my small value approximation, so that means my x is then going to be very little compared to 0.1, and so then I'm going to then multiply both sides by 0.1, and what that's equal to is gamma plus minus times x, and this value is all squared. So if I take the square root of both sides, then what I'm left with is 0.01 is equal to 0.892 times x, which leaves me an x being equal to 0.0112. I'm now going to do this a second time to test to see if I get the same number over again. So I get Ka is equal to the activity of my conjugate base times my activity of H3O plus divided by my activity of my acid. 1 times 10 to the minus 3 is equal to my gamma plus minus x all squared, and my denominator in this time, now I can actually plug in my x from my last time, so 0.1 minus 0.0112. That gives me then, on my left-hand side, if I multiply both sides by this denominator, 1 times 10 to the minus 3 times 0.0888 when I do that subtraction, and that's equal to 0.892 times x all squared. I'm going to take the square root of both sides. What I'm left with is 9.423 times 10 to the minus 3 being equal to 0.892 times x. And so when I solve for x, what I'm left with is 0.0106. And so because these two numbers are not the same, then that means that I have to do a third step, or a third successive approximation. Again, I have my acid coefficient, and that's equal to, or my activity coefficient I should say, and that's equal to my activity of my conjugate base, activity of hydronium divided by my activity of my acid. 1 times 10 to the minus 3, that's equal to gamma plus minus x all squared divided by 0.1 minus 0.0106. On my left-hand side, I have 1 times 10 to the minus 3, and that's going to be multiplied by 0.0894, and that's equal to 0.892 times x. This value is all squared, so if I take the square root of both sides, I'm left with 9.455 times 10 to the minus 3. That's equal to 0.892 times x. And if I solve for x, then what I'm left with is 0.0106. And so now, because these two values are the same, then that means then I can stop this process and I can say that my x is equal to 0.0106. Let's now finish this problem, because the problem was asking what is the pH and what is the percent hydrolysis. So the pH is equal to the negative log of the activity of hydronium, H3O+, negative log of, well, the activity is equal to gamma plus minus times the molality of H3O+. That means I have the negative log of 0.892 times 0.0106. And so when I evaluate this, I get 2.024. And if I calculate my percent ionization, well, that's just equal to the molality of H3O+ divided by the molality of the original acid, or the original concentration of the acid times 100%. And so that's 0.0106 divided by 0.1 times 100%, which leaves me with 10.6%. So here's the neat thing that we actually just calculated. Recall from before that we had our percent ionization in the ideal case was 9.5%. And in this case now that we have our real system, we have a slightly higher
percent hydrolysis, meaning that we have slightly more H3O plus in solution. And that's because we have ions in solution, which then shields the ions from each other, which then allows for a greater solubility of these ions in solution. And so we actually, in reality, have a slightly higher concentration of H3O plus. But over here, when we calculate the pH, remember our pH in the ideal case, that was equal to 2.022. And now that we have our value based on the fact that we have ions in solution, our pH actually went up, meaning that this solution is actually less acidic than what we would have predicted in the ideal case. And the reason for that is that because it's based on not the concentration of H3O plus, but it's actually based on the activity of H3O plus, then what that means is that even though the concentration of H3O plus got higher because of the ions in solution, its effective concentration, meaning its activity, got lower because the ions that were in solution, the H3O plus, is partially shielded by the other ions in solution, meaning that their effect is diminished. And that's what gives us then this pH that's actually higher, meaning more neutral, than what we got in the ideal scenario, which is what we calculated at the beginning of this problem. In light of this, let's actually draw a quick table. Where in this table, what I'm going to have is we'll have 4 cases. We'll have the ideal case that we calculated as the initial problem in this lecture. We have the real case, which is what we just calculated a second ago. If we were to do this in 0.6 molar sodium chloride solution, which is about what seawater is, the concentration of salt in seawater, and then a more concentrated salt solution, 2.5 molar NaCl. And I'm only doing this just so that we can compare basically what the concentration of the hydronium is in the solution, what is our average activity coefficient, our percent ionization, and finally, what is the pH that we predict to measure for these solutions. And I can fill in the top 2 rows because we've just calculated these numbers, 0.0095, the gamma plus minus was 1 because we said it was ideal. This had a percent ionization of 9.5%, and the pH that we expect to measure would be 2.022. In the real solution, we calculated the concentration of hydronium to be 0.0106. Our gamma plus minus, our average activity coefficient, is 8.92. Our percent hydrolysis is 10.6%, so it's slightly more soluble. And then we have a pH of 2.024, a slightly higher pH because the effective concentration due to the average activity coefficient reduces the effect of the ions. Finally, if we did calculate it for the 0.6 and the 0.25 molar, what we would get for our X is 0.0126. We would get an activity coefficient of 0.741. Our percent hydrolysis would be 12.6%. And our pH that we would calculate for this case is even higher, 2.030. And finally, if we had a very strong salt solution, our concentration of hydronium is 0.008136. Our average activity coefficient is above 1 now, 1.178. We have a percent hydrolysis of 8.14%. And finally, our pH that we would calculate from these numbers is 2.018. And so looking at these numbers, we can actually see 2 trends. Or at least I want you to take away 2 trends from this. The first one is that we can see the salting in and salting out of the hydronium. And we can see this in terms of both looking at the concentration of H3O plus, which is what this X essentially is referring to, and we can see it here in our percent ionization, where as we increase the concentration of ions in solution, and that's basically what happens as we go down this table, we have our ions become more soluble. And this is from the screening that we saw in the previous lecture, where we have positive charges being surrounded by negative charges, and what that means is that then screens them all the like charges from each other, which means more can be dissolved in the solution. However, as we continue to increase the number of ions in solution, we can see that the solubility of the ions goes down, and this is because we have so many like charges that they cannot be screened by the opposite charge as well anymore, which makes them less soluble. The second thing that we can see is that the pH in this case moves in a not intuitive way, meaning that as we get a higher amount of
ions in solution, of H3O plus in solution, our pH actually goes up instead of down, which is what we would expect intuitively, is that if we increase the amount of H3O plus in solution, then our pH should go down. But if what we calculate is that our pH actually goes up. And this is because, again, we're multiplying this concentration by the average activity coefficient to get an effective concentration. And what that means is that our pHs then move in a different direction than what we would expect. And that this even continues that when we have supersaturated solutions with a salt, the pH then even goes down when our percent ionization has also gone down, which again is not intuitive. However, the key takeaway that I want you to take away from this is that the values that we have here for our pH are not significantly different from each other, at least not in a meaningful way. And so that's the second point I want you to take away, is that the pHs only change very little when we account for real solutions. Buffers are solutions that can resist changes to its pH when acids or bases are added. They occur when an equivalent amount of weak acid exists with its conjugate base. When equal amounts of weak acid and conjugate base are in the system, then the pH of the buffer is the acid's pKa. This allows for a convenient way to measure the equilibrium constant of an acid by simply determining the pH at the half equivalence point. To calculate the expected pH of a buffer, we will use the Henderson-Hasselbalch equation. It is derived from the standard equilibrium expression, meaning that the equilibrium constant for the acid is equal to the activity of the conjugate base times the activity of hydronium divided by the activity of the acid. And this is equal to the average activity coefficient of the molality of the conjugate base at equilibrium divided by the standard molality times the activity of hydronium divided by the molality of the acid at equilibrium divided by the standard molality. And here I've left the activity of hydronium as is to make it simpler a little bit later on in the derivation. Now if I take the negative log of both sides and simplify, what I get is the negative log of the acid coefficient is equal to the pKa, and so that's what I have on the left-hand side. And on the right-hand side I can split apart all the terms within the logarithm using logarithm rules so that I get the negative log of the average activity coefficient minus the log of the molality of the conjugate base at equilibrium divided by the molality of the acid at equilibrium minus the log of the activity of H3O plus. And so then if I rearrange and move two of the terms to the left-hand side, what I get is the logarithm of the average activity coefficient plus the logarithm of the concentration of the conjugate base divided by the concentration of the acid plus pKa, and that's equal to the pH, because the pH is the negative log of the activity of a substance, in this case of H3O plus. This is the modified Henderson-Hasselbalch equation. The equation for ideal solutions, when the average activity coefficient is equal to 1, well, this part is highlighted in blue, being that the pH is equal to the pKa plus the logarithm of the concentration of the conjugate base divided by the concentration of the acid. And that when we're including the effect that there are ions in the solution, then we add then the log of the average activity coefficient. To calculate the average activity coefficient, we still use the Debye-Huckel limiting law or the Davies equation, depending upon the ionic strength. So a couple of things to keep in mind with the Henderson-Hasselbalch equation is that it is most effective when the log of the ratio of the concentration of the conjugate base to the conjugate acid is between -1 and 1, and that the concentration of the buffer should be at least 100 times higher than the acid equilibrium constant. And this is because the Henderson-Hasselbalch equation assumes that the amount of dissociation that occurs is very small, and so that the concentrations of the acid and the base are not significantly different from the amount originally added to the solution. Let's now use the Henderson-Hasselbalch equation to calculate the expected pH of a buffer. So in this case we've got a 0.1 mole solution of acetic acid and 0.09 mole of its conjugate base. And so in this case what we're going to do is calculate the pH for this buffer, where the acid coefficient is, or the acid equilibrium coefficient is equal to 1.76 times 10 to the minus 5. And so if we were going to do this without our average activity coefficient, then we would have then pH is equal to pKa plus the logarithm of the concentration of the conjugate base divided by the concentration of the acid. This means that our pH is equal to the negative log of 1.76 times 10 to the minus 5 plus the log of 0.09 divided by 0.1. And so that gives us then a pH of equal to 4.709. But in this case, the question is asking us what is the pH of the buffer, and that we know how to calculate this gamma plus minus. And so what we're going to do then is we're going to determine the gamma plus minus. We're going to then calculate then what is the pH of this buffer, employing or taking into account the fact that it's a real solution. And so to do that, then the first step is always, well, we have to find out what is our ionic strength. And so that's again 1/2 times the summation of the charge squared times the concentration divided by the standard concentration. And in this case, I'm only going to have ions that come from the conjugate base, and so that I'm only going to have the Na plus and the CH3COO minus. And so those are the two terms that go into this ionic strength calculation. So I'm going to have, for the sodium plus, I have 1 squared times the concentration of the sodium divided by the standard concentration plus 1 minus squared times the concentration of the CH3COO minus divided by the standard concentration. My I then is going to be equal to 1/2 times 0.09 plus 0.09, since that's the concentration of both, because we have a 0.09 mole solution to start off with, and so it's a 1-to-1 mole ratio, so I get 0.9 plus 0.9, and so what that gives me then is an ionic strength of 0.09. Now this ionic strength, if I take the square root of it, that is going to be greater than 0.2, and so in this case we're going to employ the Davies equation. The Davies equation tells us that the log of the average activity coefficient is equal to negative 0.509 times the absolute value of the charge on the positive ion, the charge on the negative ion, and then we have the square root of the ionic strength divided by 1 plus the square root of the ionic strength minus 0.3 times the ionic strength. And so substituting in numbers, I get the logarithm of gamma plus minus equal to negative 0.509, magnitude of 1 times negative 1, and I'm going to have the square root of 0.09 divided by 1 plus the square root of 0.09 minus 0.3 times 0.09. Let me just correct that mistake there. The logarithm of my gamma plus minus is equal to minus 0.509 times 0.20377. What this means is that my log of gamma plus minus and my average activity coefficient is equal to negative 0.1037. And I'm going to leave it in this form, this natural logarithm of the average activity coefficient, because when I take that into account in my Henderson-Hasselbalch equation to get my modified Henderson-Hasselbalch equation, well, that's equal to the pH of pKa plus the logarithm of the concentration of the conjugate base divided by the concentration of the acid. And to that I'm adding the logarithm of gamma plus minus. And so in this case I can then directly take this number that I've just calculated using the Davies equation and stick that right into my modified Henderson-Hasselbalch equation. That means then that my pH is equal to 4.709, because I had this number from before when I calculated without my gamma plus minus, and from that I'm going to subtract 0.1037, which leaves me with a pH equal to 4.605. And so what we can see here is that when we don't include the effect of the ions in solution relative to when we do take into account the average activity coefficient, we actually get a much more significant difference between these two. And so what we can conclude then from this is that when we look at buffer solutions, it becomes important to take into account the average activity coefficient, so that then we can get a much more reliable value for our expected pH of our buffer. Acid-base equilibria include ions in solution, which deviate properties of mixtures from ideal conditions. The deviation is quantified by the average activity coefficient, which can be calculated using the Debye-Huckel limiting law at low ionic strength and the Davies equation at high ionic strength. The average activity coefficient, when incorporated into the Henderson-Hasselbalch equation in order to predict the pH of buffers, means that the pH is quantified as the pKa plus the logarithm of the concentration of the conjugate base over the conjugate acid, plus the logarithm of the average activity coefficient.
Welcome to Lecture 15. In this lecture, we will define basic rate law expressions in order to derive integrated rate law expressions. This lecture will be divided into 3 parts. In Part 1, we will define how reaction rates are quantified. In Part 2, we will define what is a reaction order. And finally, in Part 3, we will derive integrated rate law expressions. Up to this point, we have been using thermodynamics to inform if a process is spontaneous. Thermodynamics' state functions provide a convenient overview of a process, where only the beginning and ending reagents are necessary to get important big-picture information. They quantify which direction a reaction will progress and what should be observed at equilibrium. However, they do not give any indication about how fast a process will take to reach equilibrium. The role of chemical kinetics is to inform how fast a process takes to occur. Given that a given process involves multiple steps, proper kinetic analysis requires examining individual reaction mechanisms to gain an overall grasp of a chemical reaction. Kinetics can also quantify equilibrium constants. We will now examine these pathways between products and reactants and the rate at which the conversion occurs in order to give us time-resolved information about the process. In order to discuss reaction kinetics, we must first define how the amount of a substance varies as a reaction progresses. To do so, let's first define a generic chemical process. A moles of A plus B moles of B gives C moles of C plus D moles of D. The number of moles of a species I at a given time, denoted as N sub I, will vary according to Ni naught plus nu I plus zeta, where Ni naught is the initial number of moles for species I, nu I is the stoichiometric coefficient of species I, and zeta is the advancement of the reaction. If we were to take the derivative of Ni with respect to time, then we get dNi by dt is equal to nu I times d zeta by dt. d zeta by dt is the speed or the rate at which the reaction progresses. Therefore, if we solve for the rate, we get d zeta by dt is equal to 1 over nu sub I times dni by dt. We can now write an expression for the rate of change of the amount of all 4 components in the reaction and relate them together, since they all share the same reaction rate. This means that the rate of the reaction is equal to negative 1 over A dNA over dt, which is also equal to negative 1 over B dNB over dt, which is equal to 1 over C times dNC over dt, and that's equal to 1 over D dND over dt. In this case, the negative signs we add in explicitly because the reaction as written is a forward reaction, so A and B are being consumed while C and D are being produced. If instead we want to express these reagent amounts as concentrations instead of with moles, we would then divide through the general expression using the volume of the solution. Still considering the same generalized reaction, the rate at which the concentration of one of the species decreasing, for example A, is governed by the product of the concentrations of all the species that A interacts with raised to some power. This means that the rate is equal to the concentration of A raised to some power x times the concentration of B raised to some power y times some constant of proportionality, in this case K sub f. K sub f is called the rate constant. The order of each component is the power that each concentration is raised by. In this example, the order of A is x and the order of B is y. The overall order of the reaction is the sum of all the powers. So for this example, it is x plus y. This final point is an important one. The orders are not related to the stoichiometric coefficients in the balanced equation. Keep in mind that there may be many reaction steps the reaction takes to go from reactants to products. Some steps are faster than others. The slow steps will dictate the overall rate, and it may not be captured in the overall rate law expression. So, predicting the order based on stoichiometric coefficients is generally problematic.
Rate laws are empirical relationships, and so the orders must be verified empirically. Let's now look at a couple of examples in reading the order from some rate law expressions. In this first example, we can simply read the order from the expression. Component A has an order of 2, and component B has an order of 1. The total order is 3. In the second example, we can again read the orders from the expression. Component A has an order of 1/2, and component B has an order of 3. The order of a reaction need not be whole integers, so the total order is 7/2. Number 3 is a bit more complicated. Component E has an order of 1, however, component S has an undefined order, and the total order is also undefined. However, if the amount of S is a lot larger than Km, then the denominator simply becomes the concentration of S. This cancels out the factor of S in the numerator, and the total order becomes effectively equal to 1. Conversely, if S is much smaller than Km, then the denominator will simply be Km. This means that the order of S is effectively equal to 1, and the total order is effectively equal to 2. This final example shows that the order need not be a static value, and the importance of each reagent may change as their concentration changes. Consider this simplified reaction. We start with reactants A and it goes to products P with a rate constant of Kf. If we know the order of a reaction and the initial conditions, we can integrate the rate law expression and predict the concentration of reagents at any time. This integral is written at the bottom of the slide, where the variable x is replaced with the order A. Once we integrate, we can then draw plots as illustrated on the right, where we can see how the concentration of each reagent changes as a function of time. By doing this, we start to answer the question, how long does a given process take? So let's evaluate these integrals and start to determine what are integrated rate law expressions depending upon what order of the reaction we're looking at. So let's assume that the order of A is 0, which means that if we were to write our rate law expression, we would get minus d concentration of A by dt is equal to Kf times the concentration of A raised to the 0th power, which leaves us with just Kf, because something raised to the power of 0 is just equal to 1. What we would do is we would rearrange and we'd separate our variables so that we can then integrate easily, which means that I'm going to leave the d concentration of A on the left-hand side. I'm going to write minus Kf dt on the right-hand side. And then I'm going to integrate this. On the left-hand side, I'm going to integrate from my starting concentration A0 to my concentration at time t, which is just the concentration of A. On my right-hand side, I'm going to evaluate this integral between 0, because at t is equal to 0, I have A0 as my concentration, up until time t, where now my concentration of A is just that, the concentration of A. If I evaluate the integral on the left-hand side, I have dA. Well, that just becomes the integrand at both parts, which means that I'm going to evaluate my fundamental theorem of calculus, which just gives me concentration of A minus concentration of A0. On the right-hand side, I'm going to have my minus Kf, which is a constant. dt just becomes t. I evaluate the fundamental theorem of calculus, and I just get t minus 0. And so what I end up with here is I have concentration of A is equal to minus Kf times t. And to that, I'm going to move my minus A0 to the other side, so I'm just going to say plus A0. And so this is the integrated rate law expression if I have a 0th order reagent. Now what if the order of our reaction was a first order reaction? So in this case, we would write our rate law expression as minus d concentration of A by dt is equal to our rate constant Kf, and then our concentration of A had an order of 1, which means now we actually have to include it in our expression. In this case, I'm going to follow the exact same procedure. I'm going to separate my variables. So I'm going to have d concentration of A over concentration of A, and that's going to be equal to minus Kf dt. I'm going to integrate both sides again. I'm going to integrate from my initial concentration of A to my concentration of A at some time t. And that means then on my right-hand side, my integral goes from 0, since my initial condition where my system starts at t is equal to 0, and then evolves to t at some time later t. And when I evaluate this integral, what I end up with is
the natural logarithm of concentration of A minus the natural logarithm of the concentration of A naught, because I have dA divided by A, and so the integral of that is just the natural logarithm of A, and now I've just evaluated it with the fundamental theorem of calculus. On my right hand side I have minus kf, and then dt just becomes t, evaluated between t and 0 means I've got t minus 0. And then finally, when I finish writing this out, or I can basically simplify this expression, I get natural logarithm of the concentration of A over the concentration of A naught equal to minus kf t. I take e, or I take the exponent of both sides, which leaves me with the concentration of A over the concentration of A naught is equal to e to the negative kf t. And then finally, my concentration of A is equal to the concentration of A naught, e to the minus kf t. And so here is my integrated rate law expression for a first order type reaction, where I only have one component in my rate law expression, and that basically this again tells me my concentration of A as a function of time. Finally, we'll do this again assuming that the concentration of A has an order of 2, so we're going to have a second order rate law expression in this case. So this is again writing my rate law, minus dA by dt is equal to kf concentration of A squared this time, because now it's of order 2. I again separate my variables. D concentration of A by concentration of A squared is equal to minus kf dt. I'm going to again evaluate my integral, or I'm going to set up my integral, where I'm going to go from A naught to A on the left hand side. I'm going to go from 0 to t on the right hand side. I evaluate this integral. This is essentially saying the integral of 1 over A squared, which is just going to be negative 1 over A. And if I evaluate the integral, then I have negative 1 over the concentration of A minus minus, so I have a plus 1 over concentration of A naught, and that's equal to minus kf, and evaluate my integral with the fundamental theorem of calculus, I get t minus 0. And so in this case now I'm just going to rearrange. I'm going to move my minus kf times t over to the left hand side, my minus 1 over A to the right hand side. So I'm going to have 1 over A naught plus kf t. And I'll write that a little bit better. kft, and that's equal to 1 over the concentration of A. And so here is my integrated rate law expression for a second order process, where I can now plot out my concentration of A as a function of time, knowing my initial concentration. So for all three of these reactions, we had this very simple reaction scheme. This reactant A goes to product P, and then we just assumed that A was a 0th order, a first order, and a second order, and we were able to get integrated rate law expressions again that predict the concentration of A as a function of time. But not every reaction is going to be this simple, and so let's do one that's slightly more complicated, where we're going to think of this process now where we have two reactants, A plus B, that go to some product P, and we're going to assume that both A and B are both of order 1. And so then we're going to determine the integrated rate law expression so that we can predict the concentrations of A and B at any time t. So the first thing that we're going to do is just write out our rate law expression. And we're going to write this in terms of the rate of change of A. So we've got minus dA by dt, and that's equal to my rate law expression, kf times the concentration of A raised to the power of 1 times the concentration of B raised to the power of 1. And so right away I have two variables that change in time. I have my B and my A. And so what I need to do then is I need to write this in terms of only one variable so that I can do this integral very easily. And so what we're going to do then is we're going to let the concentration of A be equal to the concentration of A naught, meaning our initial concentration, and this value is static, it's a constant. And we're going to subtract off some value x, meaning it's going to be some amount as time goes on, x is going to get bigger, which means our A is going to get smaller, and that makes sense because we're consuming A. We're also going to let B be equal to some initial concentration B naught, which is something that we know, and we're going to subtract off the same x. And so this x, again, it represents basically the progress of the reaction, and since in our expression here, the moles of A, like 1 mole of A plus 1 mole of B gives you a mole of P, then I can basically subtract off X from both these expressions, and I'm going to get an effective way to measure the concentration where I now only have one variable, where I only have this X that's changing in time, because these other two values, the A naught and the B naught, these things are constant. So if I plug those things back into my rate law expression here, I'm going to have minus D. I have a concentration of A, so this is the concentration of A naught now, minus X by dt. And on the right-hand side, I'm going to have Kf times A naught minus X, concentration of B naught minus X. On my left-hand side, well, if I take the derivative of A naught minus X with respect to time, well, A naught is a constant, so what I end up with is just dx by dt. My minuses cancel out on this side. And on my right-hand side, I'm going to get Kf, concentration of A naught minus X, concentration of B naught minus X. And so now you can see that by doing this change of variables where I now write things in terms of X, I now have an expression, which is this guy right here, that is only in terms of one variable. It's only in terms of X, which means that now I have a single variable differential equation or a single variable expression that now I can then just integrate simply. So now let's follow the same process that we followed before, where we're going to separate our variables, meaning that we're going to try to group together like variables on the same side of the equation. That means that on my left-hand side, I'm going to have dx. I'm going to move all these terms with x to the left-hand side. So I'm going to have in the denominator A naught minus x times B naught minus x. And on my right-hand side, I'm going to have Kf times dt. And so now here on my left-hand side, I have this expression where I have the product of two polynomials. And instead of multiplying them together, I'm going to use a slightly different approach where I'm going to try to simplify this expression into easier integrals to do by doing something called a common fraction. And all this means is that I'm just going to try to separate this denominator in such a way that I get only one of these polynomials in the denominator. And I'm going to have a summation of these two terms. And what that looks like essentially is that if I have some expression, let's say x times y, or 1 over x times y, then I can come up with something where I would have some expression that looks like this, where I have some number on top divided by x plus some number on top divided by y. And again, this is just a way to separate this denominator out so that I have a simpler expression to integrate. So the way we do this is we're going to write out an expression where we're going to say concentration of A naught minus x, concentration of B naught minus x. We're going to have the 1 over it because we're not going to include the dx on top, because that'll just multiply against whatever we determine here. And that's going to be equal to something where we have some number on top divided by the concentration of A naught minus x times the concentration of B naught minus x over the concentration of B naught minus x. And to that we're going to add some value y, which we'll determine over the concentration of B naught minus x, and that we have multiplied by the concentration of A naught minus x divided by the concentration of A naught minus x. And so you can see that in this case I have on both these terms on my right-hand side, I have A naught minus x times B naught minus x, which gives us our exact same denominator here. And it's just on top, what we need to determine if we want to split these two things up is we just need to figure out what is w and what is y. And so to do this, we're going to then just simply write out two equations and two unknowns. We're going to write out a couple of expressions that we can then easily solve. What we can see here for the denominators, again, all the denominators are the same, but all the numerators, that's where things are going to be different. And so we can write then one of our two expressions to just be simply 1 is equal to w times the concentration of B naught minus x plus y times the concentration of A naught minus x. And what we can do then is we can actually start to distribute in this w and this y, which again are just values that we're going to have that are going to be the numerators for our separated fractions. We're going to have w times the concentration of B naught minus wx plus y concentration of A naught minus yx. And if I group together some of my terms again, my x terms at least, I have 1 is equal to w concentration of B naught plus y times the concentration of A naught. From that I can subtract off x, and I'm going to get w plus y. And so this is where I'm going to essentially get my two equations and to be able to solve for these two unknowns. In this first case, we can see here that on my left-hand side, if I were to write it out explicitly, I have 0 times x plus 1, meaning I have no terms in x and I have some value 1. On my right-hand side here, I have an expression that has to deal with x. And for the left-hand side to equal the right-hand side, that means this expression that has x in it has to be equal to 0, meaning that w plus y must equal to 0. So this is our first expression. W plus y is equal to 0. My second equation I'm going to get from here comes from the first part of this equation, where on my right-hand side I only have the value of 1, which means that this w times b naught plus y times a naught has to equal 1. And so that becomes my second expression. W times b naught plus y times a naught, that has to equal to 1. And so that's the only way that this whole expression that we're looking at from before, that's the only way that this will be consistent with the original expression that we had in our integrated rate law expression that we're trying to solve. So then let's now solve for w and y. That means what I'm going to start with is, with equation 1, I'm going to solve for y. So here I've got w plus y is equal to 0. If I solve for y, then what I get is that it's equal to negative w. I can then go to my second expression, and I can plug in now for y, I'm going to write minus w, which means that the original expression, w times b naught plus y times a naught is equal to 1. Well, in this case, again, I'm going to substitute in any time I see y, I'm going to write in minus w. So there I've got w times b naught minus w times a naught. And that's still, sorry, I'm writing it equal to 0. This should be equal to 1. I can distribute out a w. So I'm going to have w is equal to concentration of b naught, or w times the concentration of b naught minus the concentration of a naught, is equal to 1. That means my w is equal to 1 over the concentration of b naught minus the concentration of a naught. And so what that then allows me to do is to go back to my equation 1, and I can substitute this back in, and that then tells me that my y in this case is equal to negative 1 over the concentration of b naught minus the concentration of a naught. So let's refresh why we did all this. We had this expression that was up here that we had solved to at this point, and that we were going to see that this integral, because our next step at this point is to integrate this expression, would be somewhat challenging because we have this denominator that has this polynomial. We have this a naught minus x times b naught minus x. That would be challenging. And so what we decided to do was to split it up into two pieces, so that we would then have a slightly simpler set of denominators to have, or slightly simpler integrals to be able to evaluate. And that's what we ended up doing here, is that we then determined what the common fractions were, so that we can write up this separated expression. So if we start at that one expression that we had that we're trying to separate, we have this dx, the concentration of a naught minus x times the concentration of b naught minus x, and that's equal to kf dt. Well, now that we have this y and this w, meaning for these separated terms, we can now write a separated fraction for this, where what we would have is 1 over concentration of b naught minus the concentration of a naught, and that I'm going to multiply with 1 over a naught minus x. From that I'm going to subtract off 1 over b naught minus a naught times 1 over b naught minus x. All of this is multiplied by dt, and that's still equal to kf dt. And so you can start to see now I have these terms on the left-hand side where I have a constant and a constant, and now I just have some term, one of these terms, a naught minus x and b naught minus x, now in separate terms, so that when I integrate this, I can now integrate it, or like when I integrate both sides, I now have two very simple integrals because I just have 1 over a naught minus x and then a second integral 1 over b naught minus x. And so when I go to do those integrals, what I simply get is 1 over b naught minus a naught, and that's just equal to the natural logarithm of a naught minus x times minus 1. And in this case, I'm going to have a plus to get the minus 1 out from the integral. B naught minus a naught, natural logarithm of b naught minus x. And on my right-hand side, I have the integral of kf dt. This is just kf times t. This is on the left-hand side, or on the right-hand side, evaluated between 0 and t. On the right-hand side, this is evaluated between 0 and x. What I'm going to do is I'm just going to retroactively write in these bounds of these integrals back up here. But what we have is now our integrated expression. Let's evaluate it using the fundamental theorem of calculus. What that means is that over here on my left-hand side, I'm going to have minus 1 over b naught minus a naught, the natural logarithm of a naught minus x, plus 1 over b naught a naught, natural logarithm of b naught minus x. And from that I'm going to be subtracting off minus 1 over b naught minus a naught times the natural logarithm of a naught, because now this is where x is equal to 0. And to that I'm going to add 1 over b naught minus a naught, natural logarithm of b naught, because then again this is where my x is equal to 0. And that's just going to be equal to kf t minus 0, me evaluating the integral on the right-hand side, doing the fundamental theorem of calculus there. So here what I'm going to do is I'm going to start to multiply through my minus sign, so that becomes a plus, this becomes a minus. And so what I have now is 4 terms that are exactly the same out front, this 1 over b naught minus a naught, so that I'm going to distribute out. So I'm going to have 1 over b naught minus a naught, and then I'm just going to start just writing out all my terms again. I have the natural logarithm of a naught minus x plus the natural logarithm of b naught minus x. And from that I'm going to add the natural logarithm of a naught. And from that I'm going to subtract off the natural logarithm of b naught. Continuing on, writing down the right-hand side, I just have kf times t. So then the next thing I'm going to do is I'm going to now substitute back in the concentration of A and the concentration of B. And so what I want you to recall was that we made this substitution where we said the concentration of A is equal to the concentration of A naught minus X, the concentration of B is equal to the concentration of B naught minus X. And this was again just so that we can evaluate this integral, so it was only a single variable integral. But now that we've done the integral, we can now convert back, and we can actually write in now the concentration of A and the concentration of B directly back into this expression. And so that just means now my left-hand side is 1 over concentration of B naught minus the concentration of A naught, and now I just have the natural logarithm of the concentration of A. And I'm just going to correct something real quick here because I forgot to carry through a minus sign. But now I'm just moving forward. I have the natural logarithm of, and I've got b naught minus x up here, and so that again, that's just b. Just like over here, this concentration of A naught minus X, that was the concentration of A. So here I have the natural logarithm of the concentration of B plus the natural logarithm of the concentration of A naught minus the natural logarithm of the concentration of B naught, and that's equal to KFT. Finally, what I'm going to do is I'm just going to group together these natural logarithm terms using, if I'm subtracting, then they become denominators. If they're adding, they become numerators. So I have 1 over the concentration of B naught minus the concentration of A naught, and that's going to be then multiplied by the natural logarithm of all the positive ones. Well, I have a positive one here, and I have a positive one here, so on top I'm going to get concentration of B times the concentration of A naught. And then I've got a negative term here and a negative term here. And so that I'm going to then divide by the concentration of A times the concentration of B naught. And that's still equal to KFT. So what we've just seen is that if we start with something that on the surface it looks deceptively simple, where we're just trying to find, we're using a rate law expression to predict the concentrations of our reagents in some chemical reaction. In this case, our chemical reaction was just products or reactants A plus B gives us some product P. And then we had this simple rate law expression that when we integrated it so that we can then determine or predict the concentrations at the end, it took this very long process with multiple steps in order to get to this ending point where we can now take this expression and start to use it to then predict what are our concentrations of A and B as a function of time. What you can see now, or what you can now begin to appreciate, is that it's important to devise strategies to be able to simplify these rate law expressions so that then we can go back to doing the simple integrals that I showed you when we just had single component systems where I was just doing 0, first, and second order rate law expressions. So here is one strategy to simplify a rate law expression. Consider the reaction CH3COCl plus H2O gives you CH3COOH plus HCl. And the rate is going to be governed by a second order expression, being the negative rate of change of CH3COCl by dt is equal to Kf times the concentration of CH3COCl and the concentration of H2O. And you could solve this expression as the second order rate law expression that we just completed, that complicated expression that we just finished. Frequently, however, and this is the strategy you can use to simplify that process, is that you can change your experimental conditions such that if you use a large excess of water in this case, then that water, that amount of water, that concentration of water isn't going to change as the reaction progresses. And so because of that, you can then write a revised rate law expression such that you have the negative d of the concentration of CH3COCl by dt is equal to some new rate constant K prime F times the concentration of CH3COCl, where in this case the K prime F is equal to the original rate constant Kf times the concentration of water. And that both these values are now constants because we used a lot of water in the system, so the concentration doesn't change. This is called flooding. But the result of this is that we can now solve this rate law expression as if it was just a simple first order rate law expression, making the math that much simpler. All of this analysis that we've just completed assumes a specific reaction order to solve the expressions. Now that we have these solutions, we can use empirical data as well as rate law and integrated rate law expressions to determine the order of components in a given reaction. Here are 4 strategies one can follow to use the previous expressions to empirically find the order of a given reagent. The first is the isolation method, or, as I've just called it, flooding. And this is where we keep all the concentrations of the reactants constant except one, which simplifies the rate law to a single component, and we can focus on the single component to determine its order. The integration method, where we measure the concentration of the components at various times and evaluate the data with each rate law. This method is typically not very accurate. The third method is the differential method, where we start with the rate law expression instead and take the logarithm of both sides and solve for the orders. And finally, fourth, we have the half-life method, where we measure how long it takes for half of the concentration of a given component to remain.
and this is dependent upon the order of the reaction. We will now do an example of the differential method and the half-life method.
So in this example where we're going to use the differential method, we're going to consider the following reaction where we have two reactants A plus B and it gives us some product C. And what we're going to do is we're going to determine the order of A and B as well as the rate constant K for the reaction, where we have a set of data here where we have at some initial time we have our concentration of A, we have our concentration of B, and we have the initial rate of our reaction. And so what you'll notice here is that we have two of the runs. We have the concentration of B, where we've designed this experiment such that they're exactly the same. And so we're going to exploit that to be able to start this problem, as what we can do is we can cancel out one of these components so we can then isolate for one of the orders. So let me show you what I mean by that. So in general, the rate is going to be equal to the rate constant K times the concentration of A raised to some power X times the concentration of B, also raised to some power. In this case, I'm going to label it as Y, because they're going to be independent of each other. And so what we want to do then is, or what we can do is we can say, well, the rate in a specific run, in this case we'll say the rate in run 2, and if we divide it by the rate in run 3, my K is still going to be the same. This is A in run 2, B in run 2, this is A in run 3, B in run 3. Well, in this case, when I substitute in the numbers, I'm going to have the rate at run 2, which is this 4.2 times 10 to the minus 2. The rate in run 3 is 1.68 times 10 to the minus 2. That's equal to K over K. My A in run 2 is 4.6 times 10 to the minus 4. And that's going to be raised to the power of X. My concentration of A in run 3 is 9.2 times 10 to the minus 4. This is also raised to the power of X. My concentration of B in run 2, 6.2 times 10 to the minus 5, divided by 6.2 times 10 to the minus 5. These are both raised to the power of Y. But again, because this concentration of B is the same in both of these runs, then they cancel out. And so what I've done here is I've eliminated one of my unknowns. My unknown in this case was Y, because it ends up canceling out with the value on the top and the bottom. By doing this division as well, I also cancel out the second of my three unknowns, being the rate constant K. And so what I'm left with then is just this expression that only has one unknown, this value X. And so now we actually can go and solve for this value. So if I do this division, what I end up with is 0.25, and that's equal to 0.5 raised to the power of X. Here's where we take the logarithm of both sides. So I have the log of 0.25 is equal to, well, the log of 0.5 raised to the power of X. I can bring the X down, so that's just X log 0.5. I can solve for X. X is equal to the log of 0.25 divided by the log of 0.5. And that means then my X is equal to 2. I can employ a similar strategy in order to find the order of B, which is Y. In this case, I'm going to take runs 1 and 2 because I don't want my concentration of B to cancel in this time, so I won't take 2 and 3 again. But I could just as easily have taken 1 and 3. But like I said, in this case, I'm just going to take 1 and 2. That means my expression is going to be, I've got rate is equal to K times A squared times B raised to the power of Y. So that means I'm going to write 5.25 times 10 to the minus 4, which is my rate. From that, I'm going to divide it by 4.2 times 10 to the minus 3. This is the rate of run 2. I have my K over my K. I have my concentration of A in run 1, 2.3 times 10 to the minus 4. This is squared. That I'm going to then divide by 4.6 times 10 to the minus 4, and that's also squared. Here I'm going to have 3.1 times 10 to the minus 5. This is raised to the power of Y, my unknown. I'm going to have this divided by 6.2 times 10 to the minus 5. This is also raised to the power of Y. And so again, I now only have two unknowns because now I know my X. My K's, because I'm doing this division strategy, they cancel right out, so I'm only left with one unknown, which in this case is my Y. when I do this division, when I move things around, what I end up with is 0.5 is equal to 0.5 raised to the power of y. I can take the logarithm of both sides. Log 0.5 is equal to y log 0.5. And what this means is that my y is equal to 1. So for this expression, this rate law expression, my total order is going to be equal to 3, since it's just going to be 1 plus 2. The final thing to solve for in this problem is simply just to find what is the rate constant k. And so I'm just going to make myself a little bit more space. But to do this, I can go straight back to the original rate law expression where I just got rate is equal to my rate constant k times the concentration of A, and I know that's now raised to the power of 2. Concentration of B raised to the power of 1, so I only have one unknown. I just don't know what k is. And so I'm just going to substitute in this case, the data for run number 3, but I could use any of the 3 runs. And I get 1.68 times 10 to the minus 2, and that's equal to k times, in this case, 9.2 times 10 to the minus 4 squared times 6.2 times 10 to the minus 5. And what that leaves me with then when I solve for k to be equal to 3.2 times 10 to the 8 per molar squared per second. Where these units come from that I've just written in for my k, I mean, they're just used just so that they can balance out, so that on the left-hand side here, my rate law expression, I'm going to get molar per second. And in each of these concentrations, these are all going to be moles. But in this case, because I've got a squared written here, then in this expression, I'm going to get moles squared times moles. And what that means then is that my k, to turn these moles cubed, being mole squared moles, into moles per second, or sorry, concentration per second, then I have to divide by 2 of the concentration units, and then I also have to divide by seconds. And so that's where my units of m to the minus 2 per second come from. The second example we're going to cover here is using the half-life method to determine the order of a reaction. And so in this case, our reaction is just a simple, I have reactant A that turns to product B, and then what we do is that we change the concentration of A from 1.2 to 0.6 molar. And what that did is that it increased the half-life from 2 minutes to 4 minutes at 25 degrees Celsius. And so then the question is, what is the order of the reaction? And so to do this, the strategy that we're going to utilize is that we're going to calculate using these expressions that determine the half-life of a reaction depending upon its order, and that we're going to calculate based on the data that's provided what is the rate constant k. And if the rate constant k is consistent across these two data sets, meaning we've got this 0.1 or 1.2 molar, so there's our first data set, and then we have our second data set, our 2 or 0.6 molar with our 4 minutes, and if our k is constant, then that then becomes the order of the reaction. Where do these half-life expressions come from? Well, let's just do the 0th real quick. So for the 0th order, what we would have is we would start with our integrated rate law expression, which again, if you remember, was the concentration of A is equal to negative kft plus the concentration of A naught. And then what we're trying to do is we're trying to find the concentration or the time at which it takes for the concentration to drop from A naught to 1/2 A naught. So T1/2 basically says is the time such that A naught goes to A naught over 2. And that just means that in this integrated rate law expression that I have right here, all I'm going to substitute in is for my concentration of A, I'm just going to write concentration of A naught over 2 minus Kf. And the time that it happens at is just T1/2. And at this point, I'm just going to rearrange. So I have A naught over 2. I'm going to move my A naught to the other side. So I'm going to have A naught over 2 minus A naught. And that gives me minus Kf T1/2. And then finally, I'm just going to do the subtraction. So I get negative A naught over 2. And to that, I'm going to divide by Kf. So I'm going to have a minus Kf over here on the left-hand side, on the denominator. And what that leaves me then is A naught over 2 times Kf is equal to my half-life time. And we would follow the exact same strategy to find out
this value, this expression I got for a first order, and again for the simple second order rate law expression that we calculated previously. So now that we know where these expressions come from, let's employ our strategy. Remember, we're calculating K's based on the data that's provided. So we have our 1.2 molar. If we assume a 0th order expression, then I've got T1/2 is equal to 1.2 over 2K. My T1/2 in this case is 2 times 60, meaning 2 minutes times 60 seconds. It's always good to work in standard units, meaning kilograms, meters, seconds. So 2 times 60 is what I'm writing in for my T1/2. When I solve for K, my K is simply going to be equal to 0.005. Now if I do this again for the 0.6 molar, again this is for the 0th order, I have a T1/2, and that's equal to 0.6 divided by 2K. I'm going to substitute in my 4 times 60 because now it's 4 minutes it takes for that reaction to happen, 0.6 over 2K. And so what that means is then my K ends up being equal to 0.00125. And so because these two numbers are not the same, then we would say this isn't a 0th order reaction. Let's do this for the first order reaction. So in this case, I've got T1/2 is equal to the natural logarithm of 2 divided by K. I'm going to substitute in the same 2 times 60 ln 2 over K. That means in this case, my K is equal to 0.0058. I do it for the 0.6 molar. I have T1/2 is equal to natural logarithm of 2 over K. I'm going to still write in this case, again, this is the 4 times 60. And that's equal to the natural logarithm of 2 over K. In this case, my K for my first order case is going to be equal to 0.0029. Again, these two numbers are not the same, and the K needs to be the same no matter what the initial conditions are. And so that means then that this is probably not a first order reaction. And so now that we've eliminated the 0th order process and the first order process, let's do it now for the second order process. And so for that one, we have a T1/2 that's equal to 1 over the concentration times K. In this case, we had T1/2, so we're going to still have that 2 times 60 in the case where we have the 1.2 molar times K. In this case, my K is equal to 0.0069. And then for the 0.6 molar case, we have, again, I use the same expression, T1/2 is equal to 1 over A naught times K. I'm going to have now 4 times 60, since it takes 4 minutes for this process to happen, or at least lose half its value. I have 0.6 times K, and when I solve for this, my K is equal to 0.0069. And so in this case now, because these two numbers are the same, then that means then that this reaction operates as if it was a second order reaction. So we would say that this process that we just looked at where A goes to B, we would say then it's second order. Or at least A at least operates in a second order where K is equal to 0.0069. Here is a summary of what was covered in this lecture. Rate laws are empirical expressions used to describe how components in a reaction change with time. When they are integrated, these integrated rate law expressions can be used to predict the concentration of each component at a given time. These expressions can also be used to determine the order of a reagent, which quantifies how influential a given component is to the overall reaction. The order also determines the component's half-life, the time it takes for half of the original amount of the component to be left. Welcome to Lecture 16. In today's lecture, we will discuss how rate constants vary with temperature according to the Arrhenius equation and determine the physical underpinnings of this empirically derived equation. This lecture will be broken down into 4 parts. In the first part, we will introduce the Arrhenius equation. In the following 2 parts, we will discuss 2 theories used to describe how to quantify reactions, collision theory and transition state theory, and relate them to the Arrhenius equation. Finally, we will calculate how the rate constant varies with temperature according to the Arrhenius equation. In the 19th century, the Swedish chemist Svante Arrhenius remarked that there was a linear relationship between the natural logarithm of the rate constant of a given reaction and the inverse of its temperature.
This relationship is commonly known as the Arrhenius equation, and when written in its more common form, it reads the rate constant Kf is equal to A times e raised to the power of negative Ea over RT, where A is a constant of proportionality and Ea is the activation energy. The activation energy is the energy required to overcome a barrier which separates the reactants and the products. It is illustrated in the figure on the right as the hill that the reactants A and B overcome in energy to become products C and D. The physical meaning behind the exponential prefactor A is more nuanced. We will now examine two theories, collision theory and transition state theory, and we will find that they produce relationships that are Arrhenius in nature. By doing so, we will start to elucidate the physical meaning behind the terms in the Arrhenius equation. Let's start first with collision theory. Collision theory is based on the premise that molecules must collide with the correct orientation and sufficient energy along their line of approach for a reaction to occur. The figure on the right illustrates the second point. In both images, the particles have a high velocity. However, in image A on top, the component of their velocities that lie along the direction which leads them to collide, or their line of approach, is very small. This means the likelihood of a reaction occurring upon impact is also small. In image B, on the bottom, the particle on the left has a very high velocity aligned along the particle's line of approach. Therefore, there is a higher probability of the reaction occurring since there is more energy directed into the collision. Let's start collecting the terms necessary to quantify if a reaction will go to completion. The first thing we need to know is the number of collisions that occur. It is intuitive to relate the frequency of collisions to the concentration of the reactants. The greater the concentration of reactants, the more often reactants will collide. We can also quantify the fraction of these collisions with sufficient energy to overcome the activation energy. This is equal to e raised to the power of negative 1 times the activation energy divided by RT. This factor is Maxwell-Boltzmann in nature and is related to the partition function. The illustration on the bottom right shows two Maxwell-Boltzmann distributions, one at 300 Kelvin and the other at 500 Kelvin, with the shaded regions which indicate the fraction of particles that have an energy that are higher than the activation energy. The exponential factor quantifies this shaded region. In order to find a direct relationship between the rate and the product of the collision frequency and the fraction of collisions with energy equal to the activation energy, we will need to quantify more precisely the collision frequency. In order to quantify more precisely the collision frequency, we will first review the collision cross-section. The collision cross-section of a particle, denoted as sigma, is the area that if the geometric center of a second particle enters, there will be a collision between the two particles. This is illustrated by the yellow circle in the figure on the left. Once the geometric center of the second particle enters the yellow circle, the two particles have collided. This value changes for different molecules, but it should certainly be included in a formulation of the rate at which particles collide. Now that we have an expression of the cross-sectional area that a particle occupies, we can now determine the volume that a given particle occupies over a given time frame. This is illustrated by the cylinder with cross-sectional area sigma, and its length is dependent on the average speed of the particle times a given time interval. Using the kinetic model of gases, we can determine the average velocity of a particle, denoted as v in the angled brackets. The multiplication of this length by sigma gives the volume that a particle occupies. If another particle enters this volume during the specified time interval, then the two particles will collide. This is illustrated by the cylinder where any red particle, which are those that have their geometric center inside the cylinder, has an opportunity to collide with the blue particle. Those outside the cylinder, shaded in green, will not collide with the blue particle in the specified time interval. Now, of course, all the particles are moving, and not just the blue one. To account for this, the square root of 2 times the average velocity gives the relative average velocity between the particles. Therefore, the cylinder has a volume of the square root of 2 times the average velocity times delta t times sigma. Let's assume that our reaction involves two particles, particle A and particle B. To determine a collision frequency between A and B, we multiply this collision volume we just determined by the density of particles, denoted as the concentration. Remember that concentrations are simply particles per unit volume, which is a quantification of density. If we divide this by the same time interval, delta t,
then we now have the number of collisions per second. The extra value of 1/2 is simply to eliminate double counting of collisions. We can then eliminate the factors of time and substitute in the average velocity from the kinetic model of gases to get sigma times the square root of 2 times the concentration of A times the concentration of B divided by 2, and all this is times the square root of 8 times the Boltzmann constant times the temperature divided by pi times mu. And in this case, mu is the reduced mass, which is equal to the mass of particle A times the mass of particle B divided by the mass of particle A plus the mass of particle B. This expression assumes that every collision will lead to a successful reaction if the particle has sufficient energy. However, this is not the case. One additional factor must be included, the steric factor P. This quantifies how often the molecules are in the correct geometry to react when they collide. In this image, there are 3 collisions. The top 2 are an effective collision since the NO is hitting the ozone in the middle oxygen. It would be hard to pull the middle oxygen out of the ozone, so these reactions do not occur. However, if the NO were to hit the ozone at a different angle of approach, with this nitrogen atom facing one of the side oxygens, like in the bottom image, then it can remove that oxygen, resulting in a successful reaction. This is what the steric factor quantifies. An interesting note is that the value of P is only restricted to be greater than or equal to 0. Since a collision can result in multiple products being formed from the reactants, P can actually be greater than 1. So, for a reaction being A plus B goes to the products P with rate constant Kf, this second order rate law can be written as being equal to Kf times the concentration of A times the concentration of B. This is also equal to the collision frequency times the fraction of particles with sufficient energy to react, those with an energy equal or greater than the activation energy. If we were to cancel out the concentration of A and concentration of B, we were left with the rate constant Kf being equal to the steric factor times the collision cross-section times the square root of 2 times the square root of 8 kBt over pi times mu, divided by 2 times e raised to the power of minus 1 times the activation energy over RT. Comparing this expression to the Arrhenius equation implies that the pre-exponential factor A in the Arrhenius equation can be interpreted as the collision frequency between the molecules. Let's now move on to the second theory, which tries to describe reaction processes. Transition state theory is a more general theory which borrows from the notation of equilibrium. Consider the reaction where A plus B is in equilibrium with C double dagger, where C double dagger is an activated complex. Think of the activated complex as the moment that A and B are fused together and could react either way, meaning that it could return to the reactants A and B or form the products. We can write an equilibrium expression for this reaction as K double dagger being equal to the concentration of C double dagger over the concentration of A times the concentration of B. From this equilibrium, it is possible to estimate the rate constant using the Eyring equation, which states that the rate constant K is equal to kappa times the Boltzmann constant times T divided by Planck's constant H times the equilibrium constant capital K, where in this case kappa is the transmission coefficient, which is the fraction of activated complexes that actually go to products. Unless otherwise stated, always assume that it is equal to 1. This equation is based on the idea that the thermal energy is equivalent to the vibrational energy along the direction that the activated complex would vibrate and break apart to form a product. Since we are using a thermodynamic framework to describe the rate constant, we can then relate the equilibrium constant to the Gibbs free energy. Recall that at equilibrium, minus RT times the natural logarithm of the equilibrium constant is equal to the change in the standard Gibbs free energy of the reaction. Since we are now talking about an equilibrium between the reactants and an activated complex, we are discussing something called the activation Gibbs free energy, denoted as delta G double dagger. When this is substituted into the above relationship and then solved for the equilibrium constant K double dagger, what we get is the equilibrium constant being equal to e raised to the power of the negative of the activation Gibbs free energy over RT. We can also express the activation Gibbs free energy in this equation as the activation enthalpy minus the temperature times the activation entropy. So the Eyring equation can be rewritten as the rate constant K being equal to kappa times the Boltzmann's constant times T divided by Planck's constant times E raised to the power of the activation entropy over R, all times E raised to the power of the negative of the activation enthalpy over RT. This is an interesting result because we again have an Arrhenius relationship, where this time the prefactor A is now related to the thermal energy of the system and the activation entropy. And the activation energy is simply the difference in enthalpy between the reactants and the activated complex. Here are the ways that the rate constant is quantified according to both transition state theory and collision theory. The Arrhenius relationship is also provided below. It is remarkable that the complex series of events that both collision theory and transition state theory try to quantify both display Arrhenius-like behavior. Based on the assumptions that are used to formulate both collision theory and transition state theory can be more broadly applied, since it uses general thermodynamic principles to quantify the rate constant. Collision theory explicitly uses the kinetic theory of gases to quantify the rate constant, so it reliably can only be applied to ideal gases. Now that we have a good idea as to what the Arrhenius parameters represent, let's now use the Arrhenius equation to determine the activation energy and exponential prefactor of a process. In this example, we will examine the decomposition of methyl orange, a pH indicator, in an acid tin solution. It is a third-order process according to the rate being equal to the rate constant times the concentration of methyl orange times the concentration of tin ions times the concentration of hydronium. We can flood this reaction with tin and acid to make it a pseudo-first-order reaction where only the concentration of methyl orange matters. And then by varying the initial concentrations of the acid and tin in solution, we can also fit for the order of tin and hydronium and determine the rate constant for the reaction. The following temperature-dependent data and rate constants are measured and fitted according to the Arrhenius equation, rearranged in order to plot a linear expression. In this case, the natural logarithm of the rate constant is the dependent variable, and the inverse of the temperature in Kelvin is the independent variable. According to the equation of our line, the natural logarithm of A is the y-intercept, and the negative of the activation energy over R is the slope. The linear plot on the right illustrates a fit of the data according to the Arrhenius equation expressed as a line. So now that we have this data, and we have this fit to this line, which is this y is equal to minus 3234.5 x plus 10.91, what our job is that we're going to now determine what is the activation energy and the pre-exponential factor based on this information. And how we're going to do that is, again, we're just going to state that this natural logarithm of kf, that's our dependent variable. Our natural logarithm of a, this is our y-intercept. Our negative EA over r, that's going to be our slope. And in this case, this 1 over temperature, that's going to be our dependent variable. And so using this way of parsing up this equation, this Arrhenius equation that we have, using the fit that we have written down over here of our data, we're going to be able to put together what is our activation energy and what is our pre-exponential factor. So starting first with our y-intercept, we're going to write down then that our natural logarithm of a, which is our y-intercept, and over here our y-intercept is equal to 10.91. And so that just means that when I solve for a over here, I'm going to have a being equal to e raised to the power of 10.91, which means that my exponential prefactor in this case is 54,720.8. Finding the slope is also very straightforward. In this case, I can just write slope, and that's going to be equal to negative 3234.5, because again, it's just this value that I have right here from my equation. And I know that my slope is equal to the negative of the activation energy divided by R. And so in this case, since I'm trying to solve for the activation energy, I can cancel out the minuses on both sides, and I can then write, well, the activation energy is equal to 3234.5 times the gas constant, 8.3145, and so that leaves me with an activation energy of 26,893 joules per mole. And again, the one thing that I'm going to point out here is that if you ever get an activation energy that's negative, then you would know that immediately that that must
be incorrect because you cannot have an activation energy that's negative.
Once the activation energy and the rate constant at one temperature is known, the rate constant can be found at a different temperature. Let's start by writing the Arrhenius equation at two different temperatures, denoting one of the two temperatures with a Kf prime and a temperature prime. We can then subtract the first from the second, giving natural logarithm of Kf prime minus the natural logarithm of Kf, and that's equal to the negative of the activation energy over RT prime plus the activation energy over RT. And if we distribute out the activation energy and the gas constant and rearrange, what we get is the natural logarithm of Kf prime minus the natural logarithm of Kf, and that's equal to the activation energy over R times 1 over T minus 1 over T prime. And using this relationship, we can find the rate constant at a different temperature once it's known at a given temperature.
So let's now do a quick example where we actually calculate the rate constant at a different temperature. So in this example, we wanted to determine the rate of decomposition of methyl orange in your stomach. And this is just in case if you were to actually accidentally ingest some of this pH indicator in your stomach, and you would know, well, how fast would this actually decompose potentially into something that's more benign, or would you have to induce vomiting to get it out of your system before it actually caused any toxic reaction? So if we were to assume that it follows the same decomposition route, meaning that its activation energy in your stomach is 26.9 kilojoules per mole, then we're going to determine what is the rate constant at typical body temperature, which is 37 degrees Celsius. And this is assuming that we'd already measured the rate constant at 296, which is somewhere a little above room temperature, and that being equal to 1.004 being the rate constant at that temperature. So we would start with the expression that we just written out a second ago, this natural logarithm of K prime minus the natural logarithm of K, and that's equal to the activation energy over the gas constant times 1 over T minus 1 over T prime, where again, these are rate constants, these aren't equilibrium constants, so that's why I usually denote them with an F. My next step is I'm going to rearrange a little bit, so I have the natural logarithm of the rate constant, the primed rate constant, and that's equal to the activation energy over the gas constant, 1 over T minus 1 over T prime. And to that I'm going to add the natural logarithm of the original rate constant, the one that I already know. Now I'm going to substitute in numbers the natural logarithm of the rate constant prime, the activation energy, 26.9, and I'm adding times 10 to the 3 because I have to write it in joules per mole. And that's because my gas constant, 8.3145, is in joules per mole per Kelvin. Over here, I'm going to write in my temperatures. This is my original temperature, my T, 296.65. And from that, I'm going to subtract 1 over 37 plus 273.15, being the conversion from Celsius to Kelvin. And to that, I'm going to add the natural logarithm of the rate constant that I already know, 1.004. And so I start to calculate these numbers, the natural logarithm of K prime, that's equal to 0.4747 plus 0.00399, which means that my rate constant, my new rate constant, my Kf prime, that's equal to the exponent raised to the power of 0.4787, which means that my new rate constant at 37 degrees is 1.614. And so now using this updated rate constant, where this is the rate constant at 37 degrees Celsius, we would then be able to then predict, if we know the integrated rate law expression, how long it takes for methyl orange to decay if it was inside a biological system.
The Arrhenius equation is an empirical relationship relating the rate constant to the temperature according to the rate constant Kf being equal to an exponential prefactor A times e raised to the power of the negative of the activation energy divided by RT. The pre-exponential factor A can be interpreted as the frequency at which reactants collide with the correct orientation in order for a reaction to occur. This can also be interpreted as being dependent on the thermal energy of the system and the change in entropy between the reactants and the activated complex. The activation energy, EA, is the difference in energy between the reactants and the activated complex. Once the activation energy and the rate constant are known at one temperature, the rate constant at another temperature can be found according to the natural logarithm of K prime minus the natural logarithm of K being equal to the activation energy divided by R
times 1 over t minus 1 over t prime. Welcome to lecture 17. In today's lecture we will quantify how long it takes for a reaction to reach equilibrium. This lecture will be broken down into two parts. In the first part we will introduce equilibria into rate law expressions and solve the integrated rate law expression to quantify how long it takes for a system to reach equilibrium. In the second part, we will quantify how long it takes for a reaction to return to equilibrium after a temperature change is applied to the system. All forward reactions are accompanied with backward reactions. Consider the following reaction where A is in equilibrium with B, where the rate constant for the forward direction is Kf and the rate constant in the reverse direction is Kr. The rate law expression for the forward direction is equal to Kf times the concentration of A, while for the reverse direction it is equal to Kr times the concentration of B. Since the consumption of A is dependent upon the concentration of A, and the formation of A is dependent upon the concentration of B, we can write the net change in the concentration of A as being equal to Kr times the concentration of B minus Kf times the concentration of A. Now that we have this rate law expression, let's use it to then start to examine what this system is doing as a function of time. Meaning, let's start looking at how these two components, component A and component B, which are in equilibrium, how they change as we approach equilibrium. And so this is going to be a multi-step type problem where the first step is just simply we have this rate law expression here that we saw in the previous slide. And then what we're going to do is we're going to determine the integrated rate law expression for both the concentration A and the concentration of B. And what we're going to assume is that the initial concentration of B is going to be equal to 0. And that's to simplify this problem. But then once we know the integrated rate law expressions, we can then plot these two concentrations as a function of time. And we can start to examine how long it takes for these systems to get to equilibrium. Starting first with the integrated rate law expression, I'm just going to start by writing down just the rate law. So we have the rate of change of the concentration of A as a function of time, and that's equal to the rate constant in the reverse direction times the concentration of B minus the rate constant in the forward direction times the concentration of A. And like it says in the setup for the problem, since we're going to set up our system such that the initial concentration of B is equal to 0, then what that means is that our concentration of B as a function of time is simply going to be the concentration or the initial concentration of A minus whatever the concentration of A is at any given time. And that's just because in our equilibrium expression we have a 1-to-1 mole ratio. So for every 1 mole of A that's consumed, we get 1 mole of B that's produced. And so what that allows us to do is to write this expression here where we can write the concentration of B simply as a function of the concentration of A. So if we plug that into our rate law expression, we have the rate of change of the concentration of A, and that's equal to the reverse rate constant, and then I'm going to multiply by the initial concentration of A minus the concentration of A. From that I'm still going to subtract the rate constant in the forward direction times the concentration of A. If I distribute in my rate constant, my reverse rate constant, change in concentration of A by the change in time, and that's equal to the reverse rate constant times the concentration of, or the initial concentration of A, minus the rate constant in the reverse direction times the concentration of A. And from that I'm still going to subtract off the rate constant in the forward direction times the concentration of A. And then finally what I'm going to do is I'm going to distribute out this concentration of A term, and what that leaves me with is the rate of change of the concentration of A being equal to the reverse rate constant times the initial concentration of A minus the concentration of A times the reverse rate constant plus the forward rate constant. At this stage we can actually set up our integrals now. And so what I'm going to do is I'm going to start by saying I'm going to start isolating my variables. So here I've got d concentration of A, and I'm going to multiply so that my right hand side is going to have my dt. And so all that means is that I'm just taking my dt term and I'm just going to multiply both sides by dt, so I have it on my right hand side. Because I've got this whole portion here that has to do with the concentration of A, well, I need to move all of it to the left hand side because I can't actually isolate for my concentration of A at all. So what that means is that I'm going to have here in my denominator Kr times the concentration of A naught minus the concentration of A times Kr plus Kf. And then I'm just going to take the integral of both sides. My right-hand integral, well, that's just from 0 to t, and my left-hand integral, that's just going to be from the concentration of A naught, so my initial concentration, to whatever my concentration is at any given time t. And now to evaluate this integral on the left-hand side, I'm going to use integration by substitution. So what I'm going to do is I'm going to let u be equal to Kr times the concentration of A naught minus the concentration of A times Kr plus Kf. So basically everything here in my denominator, I'm just going to let that equal to u. My du by d concentration of A, well, that's just going to be equal to, in my first term here, I can see that there's no function of concentration of A, so that's just basically equal to 0. And from that, I'm going to be subtracting off. Well, here I've got a concentration of A times a constant. So what that leaves me with when I take the derivative with respect to the concentration of A is just Kr plus Kf. And so what this means in the end then is when I rearrange to find what is my small change in concentration of A, when I rearrange, it's just equal to du divided by the negative of Kr plus Kf. And so it is these two terms where the first one is u and the second one is this term that has to deal with deconcentration of A that I'm going to stick back into my expression here on the left-hand side. And this is again just to simplify this integral that we're about to do. So let's now apply this substitution and let's start to evaluate this integral. By applying this substitution, I'm also going to be changing my bounds of integration on my left-hand side integral. And so I'm going to write them in terms of u, which means that I'm basically just going to be substituting in the concentration of A naught anytime I see the concentration of A inside my substitution, because that's my independent variable in this integral. And so that means that my integral starts from Kr times the concentration of A naught minus the concentration of A naught times Kr plus Kf. And that on the upper bound of my integral, I'm now just going to substitute in the concentration of A into my u term wherever I see concentration of A. So meaning I'm just going to write in that exact same expression. Kr times the concentration of A naught minus the concentration of A times Kr plus Kf. And then I'm going to make my substitutions, meaning that since this whole denominator here in this term, that's what I set equal to u. So I'm just going to write 1 over u. And I have my dA and my numerator here. Well, my d times the concentration of A is just going to be equal to du times du over minus Kr plus Kf. And that's still going to be equal to this integral from 0 to t of dt. This integral now is actually pretty trivial because what I have is essentially an integral of du over u. And since the minus Kr plus Kf is a constant, then that can come straight out in front. And so that's why I'm going to write it straight out in front, since it's just two constants and they don't play anything in the integral. And like I said, the integral of du over u, well, that's just the integral or the natural logarithm of u. And since I'm writing this in terms of this substituted coordinates, then I'm just going to just write in my bounds using the same coordinate system, Kr times the concentration of A naught minus the concentration of A naught, Kr plus Kf, and on top my upper bound is Kr times the concentration of A naught minus the concentration of A naught, Kr plus Kf. And what that's equal to here on my right hand side, well, my integral of dt is just simply equal to t, and that's evaluated between 0 and t. So now if I apply my fundamental theorem of calculus, what we end up with is 1 over the negative Kr plus Kf, and I have my natural logarithm of, well, I have my upper bound, which is Kr times the concentration of A naught minus the concentration of A times Kr plus Kf. And from that I'm going to subtract off the natural logarithm of Kr times the concentration of A naught minus the concentration of A naught times Kr plus Kf. And on my right hand side, I have t minus 0 when I evaluate the fundamental theorem of calculus for that term. Now all we have to do is just simplify this expression. And so my first step in this simplification is I'm just going to group together my natural logarithm terms. 1 over the negative of Kr plus Kf. And I can write this natural logarithm term, or this difference in natural logarithm terms, as the division of the two pieces, meaning the natural logarithm of Kr concentration of A naught
minus the concentration of A times Kr plus Kf divided by Kr concentration of A naught minus the concentration of A naught times Kr plus Kf, and that's going to be equal to T. My next thing I'm going to do is I'm going to now start to simplify some of these terms and move some stuff around. First of all, I'm going to multiply both sides by negative Kr plus Kf, and so what that leaves me with is minus Kr plus Kf times T on my right-hand side. What I'm also going to do is I'm also going to distribute in this concentration of A naught into my denominator, and then I'm going to factor it out. So what that means is I'm going to have the natural logarithm of Kr, concentration of A naught, minus the concentration of A, Kr plus Kf, and that's going to be over the concentration of A naught, and since I've distributed it out, I'm just left with Kr minus Kf, since I'm now also distributing in this minus sign, so that goes into both of these terms here. What that leaves me to do then is I'm able to cross off these Krs on the bottom. And so what I'm left with here on the bottom is natural logarithm of Kr, concentration of A naught, minus the concentration of A times Kr plus Kf, divided by the negative of Kf times the concentration of A naught. And that's equal to the negative of Kr plus Kf times T. It's always more convenient to be able to solve for these expressions in terms of the concentration of the thing that you're trying to find, in this case the concentration of A, and that way then we can easily then see how does the concentration of A vary in time. So I'm going to continue to work on this to solve for this concentration of A. That means my next step is to take the exponent of both sides, and so the exponent of a natural logarithm just cancels out both of those terms, which means I have Kr times the concentration of A naught minus the concentration of A times Kr plus Kf, and that's divided by negative Kf over the concentration of A naught. And since I have to apply the exponent onto the right-hand side, then that means I get e raised to the power of negative Kr plus Kf times time. And then after that, I'm just going to start to rearrange and simplify. What that means is then I'm going to multiply both sides by negative Kf over A naught, which means I have Kr times the concentration of A naught minus the concentration of A times Kr plus Kf, and that's equal to negative Kf concentration of A naught e raised to the power of negative Kr plus Kf times time. Continuing along on this, what I'm going to do is I'm going to subtract both sides by Kr times A naught, and then I'm going to multiply through by minus 1. What that leaves me with is the concentration of A times Kr plus Kf being equal to Kr times A naught plus Kf times A naught e raised to the power of negative Kr plus Kf times T. And for my final step, I'm going to do two things. The first thing is I'm going to distribute out this concentration of A naught. And the second thing is that I'm going to divide both sides by Kr plus Kf. And so what that leaves me with is my concentration of A being equal to my concentration of A naught over Kr plus Kf. And that is going to be all multiplied by Kr plus Kf times e raised to the power of negative and then Kr plus Kf times T. So now that we have the concentration of A at any given time T, and that's given by this integrated rate law expression, we can now determine the concentration of B at any time T. Because if you recall, the concentration of B was equal to the concentration of A naught minus the concentration of A. And this was again based on this assumption that we had before, where we said in our system that the concentration of B naught was equal to 0, which means that B only comes from A. Well, now that we have this expression for the concentration of A, we can substitute that directly into this expression. So the concentration of B is equal to the concentration of A naught, and from that I'm going to subtract off the concentration of A naught divided by Kr plus Kf all times Kr plus Kf times e raised to the power of negative kr plus kf times t. And I've left this huge gap here because what I'm going to do to help simplify this expression is that I'm going to multiply the first half of this term by kr plus kf over kr plus kf. And so essentially what this is I'm multiplying the first part of this term by 1. But what it really does is it allows me to subtract these two terms from each other because I have this common fraction, being this kr plus kf term. And so what that then lets me do is it lets me then write my concentration of B being equal to, and I can actually distribute out a concentration of A naught over Kr plus Kf, so basically the concentration of A naught and the denominator. But what that leaves me with is being able to write down all the numerators, which is Kr plus Kf, and then I'm going to distribute in this minus sign, so that goes in front of both of these terms, which means I get minus Kr minus Kf e raised to the power of Kr plus Kf t. And so now I can start to cancel out like terms, and I can even distribute out a few more, which means that I have a Kr here, subtract off Kr, and I actually have then left over a Kf and a Kf, which means I can distribute out that term, which means that my concentration of B is equal to Kf times the concentration of A naught over Kr plus Kf, and that's going to be multiplied by 1 minus e raised to the power of negative Kr plus Kf times t. Well, this is now great, because what we have now is integrated rate law expressions for the concentration of A and an integrated rate law expression for the concentration of B. And so now we can actually plot, and we can start to play around with the idea of how long does it take for this system to reach equilibrium. Now, of course, before we do that, let's look at two extreme cases. And so what I'm going to do is I'm just going to rewrite these two expressions side by side just to make it easier to see this stuff. So here's the integrated rate law expression for the concentration of A, which is equal to the concentration of A naught divided by Kr plus Kf, and that's going to be multiplied by Kr plus Kf times e raised to the negative Kr plus Kf times t, and we have the concentration of B being equal to Kf times the concentration of A naught divided by Kr plus Kf, and that's going to be multiplied by 1 minus e raised to the negative Kr plus Kf times t. The first thing that probably would be good to test is just to see if we regain our initial conditions from these expressions, meaning what happens when we set t is equal to 0. Well, in this case, our concentration of A, that's going to be equal to our concentration of A naught over Kr plus Kf. We have our expression here, Kr plus Kf, e raised to the power of 0. Because if I set t is equal to 0, then I have e raised to the power of 0. E raised to the 0, well, that goes to 1. So what we're left with here is Kr plus Kf divided by Kr plus Kf, which means that my concentration of A is equal to A naught at t is equal to 0. Also, if I do the same thing here with my concentration of B, I have that being equal to Kf times the concentration of A naught over Kr plus Kf, 1 minus e raised to the power of 0. What we can do is we can do the same thing, e raised to the power of 0 is equal to 1, but that means then that I have 1 minus 1, which makes this whole expression equal to 0. And what that says to us then is that my concentration of B is equal to 0, which is what we set it to be at the beginning of the problem. We said we didn't have any B starting in the system, and that's what we regain here. What about if we wanted to figure out what our equilibrium concentrations were? Well, in that case, we would let our T go for a very long time. And in this case, we're going to let T be such a big number, we're going to say that T is infinitely large. And so what does that do for our expressions? Well, we would say our concentration of A is equal to our concentration of A naught times Kr plus Kf, and that is then multiplied by Kr plus Kf, e raised to the power of negative infinity. And what we can say about the power e raised to the power of negative infinity is that if I have e being basically 1 over e and raised to the power of a very, very, very large number, then that means that number then goes to 0, which means that that whole portion goes to 0.
And what we're left with is the concentration of A being equal to Kr times the concentration of A naught divided by Kr plus Kf. If we do the same thing for the concentration of B, we would again be able to write Kf, concentration of A naught, all over Kr plus Kf. We have 1 minus e raised to the power of negative infinity. And again, in this case, since we have this value, that ends up going to 0. And again, this is because 1 over e raised to the power of a very, very large number, that number tends to go to 0. Or that number will end up essentially being equal to 0. What that leaves us with then is that our equilibrium concentration of B is equal to Kf times the concentration of A naught divided by Kr plus Kf. I'm just going to denote my concentration of A as an equilibrium concentration as well, just to be explicit and uniform. And so as we start to answer the question, how long does it take to get to equilibrium, we can see that in both these examples, the major thing that changes is this exponential term, at least when we look at these two extremes, t is equal to 0 and as t goes to infinity. And so if we want to start talking about how long processes take, it seems like it's this scaling factor that we multiply the t by in the exponential that then starts to quantify how long it takes to go from, say, t is equal to 0 to t is equal to infinity. Just because as we go from this case where we have e raised to the power of 0 to this case where we have e raised to the power of negative infinity, it's this exponential term that is going to be the major component that then modifies whatever our concentration of A is and our concentration of B is. And on an intuitive level, this should make a lot of sense. Because again, we're basically moving between this regime where this exponential is equal to 1 to where this exponential is equal to 0. And that if the reaction rate is very, very, very fast in both directions, then that means then this summation that we're looking at here will then scale this exponential faster so that we go from this case where we're going from 1 to 0. And if my reaction rates are very small, meaning my rate constants are very small, then the scaling of time will then happen much slower. And so then this transition from 1 to 0 will also happen very slowly. So let's just ask one final question before moving on. Let's say if we actually were to write down some rate constants and we wanted to actually calculate what our equilibrium concentration is. So let's say, what if our forward rate constant was equal to 2 times our reverse rate constant? What would that mean for our equilibrium concentrations? Well, that would mean that we would just be substituting in directly into these expressions that we just wrote. And so for our equilibrium concentration for A, then I would still write it equal to Kr times the concentration of A naught divided by Kr plus 2Kr, because I'm essentially just substituting in for Kf into this part of the denominator. And in this case, I can actually then just cross off all the Krs since I have a common term. And what that leaves me with is my concentration of A at equilibrium being equal to the concentration of A naught divided by 3, because I have 1 on top and I have 1 plus 2 on the bottom. I can do the same thing with my concentration of B at equilibrium. And so then here I get, in this case, I'm going to again substitute in my Kf into this expression on top in my numerator. So that means I get 2 times Kr times the concentration of A naught divided by Kr plus 2 times Kr. And so then my concentration of B at equilibrium, well, that's equal to, and again, I can cross off all my Krs. And so now I have 2 on top. And I have 1 plus 2 on the bottom, so I have 3 on the bottom. And this result should feel intuitive, and it should feel intuitive for 2 reasons. The first one is that if our forward rate is occurring at twice the rate of the reverse reaction, then what that says is that we should have more of B than we should have of A in the end, because we're producing B at twice the rate that we're producing A. And that's what falls out of these equilibrium expressions. I have twice as much B as I do A. The other thing also here is that both of these terms, these equilibrium expressions, should be scaled as a function of the original concentration of A naught. Because remember, we said that at t is equal to 0, we have the concentration of A being equal to the concentration of A naught, meaning we have some initial amount of A in our system, but we also said our concentration of B is equal to 0. And since we have a 1-to-1 mole ratio, then that means then that
everything is going to be scaled as a concentration of A naught, because that is all we had in our system to begin with. And so again, because we've got twice the reaction rate going in the forward direction than the reverse direction, it shouldn't be terribly surprising that we get a result in the end where we have twice as much B as we do A in the system at equilibrium. And in fact, if we plot these integrated rate law expressions, where again this blue line is then the concentration of A as a function of time, and this red line is the concentration of B as a function of time, and we use the rate law expressions, or the relationship between the rate constants that we had before, then we end up with what we just predicted a second ago, where we have here our concentration of B at equilibrium being equal to 2 times the concentration of A naught over 3, and we have our concentration of A at equilibrium being equal to 1/3 of the initial concentration of A naught. Since we are talking about systems at equilibrium, we can also quantify this process using thermodynamic expressions. So, the equilibrium expression for A in equilibrium with B is expressed as capital K, being the equilibrium constant, being equal to the concentration of B at equilibrium over the concentration of A at equilibrium. An equilibrium expression can also be calculated starting from the rate law expression. At equilibrium, the rate of change of A is 0, which is still equal to Kr times the equilibrium of the concentration of B minus Kf times the concentration of A at equilibrium. If we rearrange this expression, we get Kf over Kr being equal to the concentration of B at equilibrium over the concentration of A at equilibrium. Since both the equilibrium constant K and the ratio of the rate constants Kf over Kr is equal to the concentration of B at equilibrium over the concentration of A at equilibrium, we can relate the rate constants to the equilibrium constant, resulting in the equilibrium constant being equal to Kf over Kr. This means that to understand how the equilibrium will change as a function of temperature, we can use both the Van 't Hoff equation to modify the equilibrium constant, or we can use the Arrhenius equation to modify both rate constants. Let's now verify this fact that if we were to change the equilibrium constant as a function of temperature, like using here with the Van 't Hoff equation, that we would actually get the exact same change based on the fact that we actually have the Arrhenius equation modifying both rate constants, and that the modification of both these rate constants gives us the exact same equilibrium constant after the reaction or after the temperature change has occurred. Now here I've written my Van 't Hoff equation up here, which is just the standard Van 't Hoff equation where I'm modifying my equilibrium constant, and that's relative to the change in the enthalpy of the reaction, which I have illustrated right here. And then I have my two Arrhenius equations where I've got my forward reaction rate constant change based on the activation energy, which is what I have illustrated right here. And for the forward direction, it is just labeled as just EA, since it's just this little barrier that we have to overcome. For the reverse rate, which is what I have written down right here, we can see that I have this special relationship, or at least this more involved one, where I have EA minus delta R for the reaction, the change in enthalpy for the reaction. And that's just because we have in our expression here that our change in enthalpy is a negative number. And so what that means is that if I want to find out what the total distance or the total amount of energy that the products have to do to get back over the hump, well, I'm going to be writing that, or express that as the activation energy minus this enthalpy, and that's strictly because, as I said before, this is a negative number. And so when I do that negative negative, then I end up with a total positive barrier that the products have to overcome to come back to the reactants. And so the strategy that I'm going to employ to show that both these methods, Van 't Hoff and Arrhenius, will give us the exact same thing is I'm just going to show that, or what we already know is that the equilibrium constant K is equal to Kf over Kr. And so what we're going to show then is that this modified equilibrium constant K prime is going to be equal to Kf prime over Kr prime. And we're going to use the Van 't Hoff and the Arrhenius equations to define what the equilibrium constant K prime is, the rate constant Kf prime,
and the rate constant Kr prime r. And so the first thing I'm going to do is I'm just going to simplify my Van 't Hoff equation for my equilibrium constant. And so all I'm going to do is I'm just going to apply e to the power of to both sides. And so what that does is that gets rid of the natural logarithm on the left-hand side, and that gives me then on the right-hand side e raised to the power of the enthalpy of the reaction divided by r times 1 over t minus 1 over t prime. And if I solve for k prime, then I'm left with the original rate constant before the temperature shift times e raised to the power of the enthalpy of the reaction divided by r times 1 over t minus 1 over t prime. I can do the same thing down here for the Arrhenius equations. I'm going to apply e to the power of just on both sides. That eliminates the natural logarithm, so I'm left with the rate constant kf prime times kf, or divided by kf I should say, and that's equal to e raised to the power of the activation energy over r times 1 over t minus 1 over t prime. And finally I get kf prime is equal to kf times e raised to the power of the activation energy divided by r, 1 over t minus 1 over t prime. And then finally for the reverse rate constant, I'm going to take e to the power of, again, to both sides. That eliminates my natural logarithm, so I get kr prime divided by kr, and that's equal to e raised to the power of the activation energy minus the enthalpy of the reaction divided by r times 1 over t minus 1 over t prime. And then if I solve for kr prime, then that's equal to kr times e raised to the power of the activation energy minus the enthalpy of the reaction divided by r times 1 over t minus 1 over t prime. And so like I said before, my strategy is I'm just going to take my kf prime and I'm going to divide it by my kr prime. And in the end, if I end up with k prime, like I have up here, then we know that yes, indeed, the Arrhenius equation can predict the change in the rate constants such that whatever the changes in this ratio of the forward and the reverse reaction will still give us the same change that we should expect if we use the Van 't Hoff equation to basically predict what is the change in our equilibrium constant. So let's do just that. So that means then I'm going to write kf prime over kr prime, which means I'm writing kf e raised to the power of the activation energy over r times 1 over t minus 1 over t prime, and that's divided by kr times e raised to the power of the activation energy minus the heat of the reaction divided by r, 1 over t minus 1 over t prime. And so in this denominator, because I have this difference that's in this exponential, then what I can do is I can separate that exponential into two pieces. So on the top I still have kf times e raised to the power of the activation energy divided by r, 1 over t minus 1 over t prime. And on the bottom what I get is kr times e raised to the power of ea over r times 1 over t minus 1 over t prime. And that's multiplied by e raised to the power of the negative of the heat of the reaction divided by r times 1 over t minus 1 over t prime. And now I can start to cross off terms. I have an e raised to the ea over r times 1 over t minus 1 over t prime on top, and I have one of those on the bottom. And so then what I can continue to do here is I can then say, well, here I've got e raised to the power of negative of an exponent, which is the same thing as saying it's the positive. So I can move it to the top and I can say that's the equivalent of saying kf times e raised to the power of positive the heat of the reaction divided by r times 1 over t minus 1 over t prime divided by kr. And so we know still that kf over kr is equal to capital K, our equilibrium constant. So I have capital K, our equilibrium constant, is equal to e raised to the power of the heat of the reaction divided by r times 1 over t minus 1 over t prime. And then finally, as my last step, if we look at this relationship that I've just written down, and I'm just going to scroll back up, because we can see that that is the exact same relationship that I have written down up here for how our equilibrium constant changes using the Van 't Hoff equation. And so what I can write then immediately is that I can say, well, kf prime over kr prime is equal to my equilibrium constant at the new temperature. And so again, all this verifies is that the Van 't Hoff equation can be used to describe changes to our equilibrium constant, and that we can use Arrhenius to describe our changes to our two rate constants, and that the way that Arrhenius modifies these two rate constants, the ratio of those two rate constants still equal whatever the Van 't Hoff equation describes what our change to our equilibrium constant would be. Ultimately, what this demonstrates is that there's a pretty fundamental link between the thermodynamics of a system as described by the equilibrium constant and the kinetics of the system as described by the rate constants. Let's now determine how long it takes for a reaction to re-establish equilibrium after a shift in temperature. First, we will define some terms. Continuing to work with the reaction where A is in equilibrium with B, and the rate constant for the forward direction is Kf, and the rate constant for the reverse direction is Kr. Before the temperature shift, the net rate of change of the concentration of A is given by Kr initial times the concentration of B minus Kf initial times the concentration of A, where we're denoting the rate constants before the temperature shift with the I subscript. And when the system achieves equilibrium before any change in temperature, we can write Kr initial times the concentration of B at equilibrium in this initial frame being equal to Kf initial times the concentration of A at equilibrium in this initial frame, where now the concentration of A and B have the I subscript to denote that no temperature change has been applied. Finally, after the temperature shifts, we drop the I subscript to express the modified rate constants in equilibrium concentrations, such that we now have an expression that is expressed as Kf being equal to the concentration of A at equilibrium is equal to Kr times the concentration of B at equilibrium. So now that we've defined all these different positions for equilibrium, at least for the concentration of A and the concentration of B, we're now going to answer a pretty fundamental question about kinetics, which is if we have some sort of equilibrium shift, how long does it take for the system to reestablish equilibrium? Problem we solved where we had this previously established equilibrium where we had at equilibrium our concentration of A was 3 and our concentration of B was equal to 2A naught over 3, and that in this example what we're going to have happen is that the temperature is going to suddenly shift, and so now it's going to shift in such a way that our equilibrium constant will now be equal 1, meaning that at this new equilibrium constant, because of the temperature shift, will change so that whatever number it was before is becoming 1. And what we're going to do is we're going to calculate how much time it takes to reestablish equilibrium. And the quantification of this time is going to be centered in this time constant tau. And that what we'll also discover is what is the new equilibrium concentrations of the two species, which is something we already know how to do, but we're going to do it now in the context of kinetics, and also in conjunction with finding out what is this time constant, which I'll introduce a little bit later, meaning how long will it take for this equilibrium to be reestablished. So again, our goal in this case is to basically determine how long to find out what is the concentration of A at equilibrium, so this is the concentration of A at the new equilibrium, and the concentration of B at the new equilibrium. And so before we get into that, let's again write down what our starting parameters are. So to start, and this is before the temperature change occurs, we had our concentration of A being equal to the concentration of A at the initial equilibrium. So this is where I've got EQ, I, and I. And as the problem states, that's at A naught over 3. My concentration of B, that's equal to this concentration of B equilibrium at the initial frame. So before the temperature changed, and this was again the 2 A naught over 3. And so in the previous problem we also had our values of our rate constants, where we saw that our forward rate constant was equal 2 times the reverse rate constant. And if I wanted to know what is my equilibrium constant in this initial frame, well, that's just the concentration of the products. In this case, it's my concentration of B at this initial equilibrium divided by the concentration of A, the reactant, at this initial equilibrium. And so if I were to continue to write that out, the concentration of B at the equilibrium was 2 A naught over 3 divided by the concentration of A naught at this initial equilibrium. So then I can write that as 3 over the concentration of A naught. And so then I can start to cross off various terms. And so what I get is my value of K, my equilibrium constant, being equal to 2. And so what we find is that at this new equilibrium, the K is changed such that after the temperature shift occurs, then our equilibrium constant is now equal to 1. And so what that means is that for my equilibrium constant to go from 2 to 1, that must mean that my concentration of A is then going to go up, and my concentration of B is going to go down in order to reestablish equilibrium. And now if I write my rate law expression, I'm going to write the concentration of A, or the change in concentration A, which is a function of time, is equal to the reverse rate constant times the concentration of B minus the forward rate constant times the concentration of A. And again, this is the expression that still governs how my concentration of A and B change. However, I want to simplify this expression because, again, I start with a certain equilibrium, that's what I have here, and then I'm doing a change which then changes my equilibrium constant such that I now realize that my concentration of A is going to go up and my concentration of B is going to go down. And so I want to look at my rate law expression and I want to turn this into an expression that only has one variable so that then I can actually do this integral and be able to see how both A and B shift at the same time. And that's because my reaction is A is in equilibrium with B. So basically A turns into B or B turns into A, and that's my shift in equilibrium. So I'm going to use this trick again, this progress of the reaction, where I'm going to write down that my concentration of A is equal to the concentration of A at the new equilibrium, and for this I'm going to subtract this progress value, which I'm going to denote as X, and I'm going to say my concentration of B is equal to the concentration of B at the new equilibrium plus X. And again, X is basically this term that is this progress of the reaction. It's going to be, the way that this progress is going to be measured though is that it's going to be backwards from what intuitively you might have thought before, where in this case I'm going to have some value x naught being some number, and that's going to be at t is equal to 0, where at t is equal to 0 is when the temperature suddenly changes, and that as t increases, so as t goes to infinity, my x naught, or my x rather, my progress is going to go to 0. Meaning that as these values change, so as x goes to 0 in both these terms, then my concentration of A will then become my equilibrium, my new equilibrium concentration, and my concentration of B will become my new equilibrium concentration. The reason why I wrote minus sign here for the A part and plus sign for the B part is that if x naught is some finite value, and it essentially represents how far away each of these components are from the new equilibrium, well, since I know that I'm going to be increasing A, then that means that if when x is x naught, then I've subtracted amount from the new equilibrium, and that's where I'm sitting at some time t, which means that as the system, or as time increases, as the reaction progresses, and we reestablish equilibrium, then my concentration of A will rise as my x term gets smaller. And the same thing can be said for the B. In essence, the picture that this is trying to plot is one that looks like this, where if I have my time here on my x-axis and I have my concentrations on my y-axis, again, B is something that's going to be up here, my A is something that's down here that we found before because my concentration of A at equilibrium was less than my concentration of B. It's this 2/3, 1/3 values that I have over here. Suddenly, and this is at this spot where I'm going to say at t is equal to 0, because that's where we're going to say that our shift happened in our equilibrium. And as we saw down here when we said our k nu is equal to 1, which means our A goes up and our B goes down, then we have our new equilibriums that form. So there's my B going down, and here is my A going up. And they both move up and down at a certain amount, and that amount that they move up and down, this is my x naught. And so this is where these values then, or where these expressions come from, is that here I've got B equilibrium, or the concentration of B at the new equilibrium, and here is where I've got the concentration of A at the new equilibrium, and that at t is equal to 0 for the B equilibrium, I'm going to be adding x, which means that to get back to the original case, that's how I'm going to get to the original amount I had before at t is equal to 0. And the converse happens here. I have to subtract from the A equilibrium by x naught to get back to the original A. And that the progress of the reaction is basically watching the decay of x naught go to 0 as the time increases. So my next step that I'm going to do here is I'm essentially going to take these values, this concentration of A and this concentration of B, and I'm just going to plug this in to my rate law expression, because now I have terms that basically describe how far away from this new equilibrium, and I have an expression that talks about how things change in terms of time. I'm just going to put those two things together, and I'm going to write down my new rate law expression. And so that means then I'm going to have a term that says, well, here's my rate of change of time. That concentration of A, well, I said that that's the concentration of A at the new equilibrium minus x, and that's going to be equal to my reverse rate constant, and this was my concentration of B, which I'm going to write as the concentration of B at the new equilibrium plus x, and from that I'm going to subtract off my forward rate constant, and that this was the concentration of A, which I'm now going to write as the concentration of A at the new equilibrium minus x. So for here, I'm just going to apply my differential on the left-hand side and distribute out terms on the right-hand side. So d by dt applied to the equilibrium of A, well, that's a constant, so really I just have dx by dt, and I have to carry through the minus sign. And on my right-hand side, I'm just going to have kr times the concentration of B at the new equilibrium plus my reverse rate constant kr times x, minus my forward rate constant kf times the concentration of A at the new equilibrium, plus my forward rate constant kf times x. And so I can start to group together like terms. I still have my left-hand side negative dx by dt. I'm going to have kr, concentration of B at the new equilibrium, minus kf times the concentration of A at the new equilibrium. And then I'm going to have plus krx plus kfx. And so one thing that we saw previously was that when we were at equilibrium, and so if I were to write my rate law expression out again, I'd have dA by dt is equal to kr concentration of B minus kf times the concentration of A. And at equilibrium, then I can say, well, the rate of change of A is going to be 0. I'm going to write kr concentration of B at equilibrium minus kf times the concentration of A at equilibrium. But what this means then, if I move my minus kf concentration of A at equilibrium to the left-hand side, I get kf times the concentration of A at equilibrium is equal to kr times the concentration of B at equilibrium. What that means then is that in this term right here where I've got, say, kf times the concentration of A at equilibrium, I can actually write that as kr times the concentration of B at equilibrium. What that means then is that I now have concentration of B at equilibrium times kr minus kr times the concentration of B at equilibrium. And so those two terms essentially cancel out. I can also, on the other two terms on my right-hand side, I have a factor of x that I can factor out. And so what I'm going to be left with here is I've got negative dx by dt, and that's going to be equal to x times kr plus kf. And all I'm going to do now is just multiply both sides by minus 1, so that in the end I'm going to get dx by dt is equal to negative x times kr plus kf. Just to reiterate, again, we're trying to figure out how x changes in time, because then that'll help tell us how long it takes for us to reestablish our new equilibrium from the old equilibrium. So I'm going to then do my separation of variables. I'm going to divide both sides by x, and I'm going to multiply both sides by dt. And so all I'm doing is just shifting around my x and my dt. So I've got dx over x is equal to negative kr plus kf dt. And then at this case, now I'm just going to integrate. My bounds of my integration is simply I start at x naught, and I'm going to go to sum x, and that's when I start at t is equal to 0, moving to some time t. So then on my left-hand side, I have 1 over x as my thing I'm integrating, which then results in natural logarithm of x, applied between x naught and x. And on my right-hand side, I have minus kr plus kf. The integral of dt is just t, a value between 0 and t. I apply my fundamental theorem of calculus, natural logarithm of x minus the natural logarithm of x naught, and that's equal to minus kr plus kf times t minus 0. I keep moving through. I get the natural logarithm of x over x naught, and that's equal to minus kr plus kf times t. I apply e to the power of, so I take the exponential of both sides. X over x naught is equal to e raised to the power of negative kr plus kf t. And then finally, my x, how it changes in time, is basically equal to x naught times e raised to the power of negative kr plus kf t. So what does this tell us? This tells us that we have our rate of our reaction, or our progress of reaction x, and we know that as a function of time. And what this tells us is that if we know x naught, where x naught is just the difference in concentration between the old equilibrium and the new equilibrium, then we can actually plot out how these two concentrations, in our case A and B, vary in time. And again, this is an exponential decay is how they both vary in time. So how long it takes for this new equilibrium to be established, that's something that I'm going to quantify by defining a new term. And so what I'm going to do is I'm going to define a term called tau. And in this case, this tau, that's going to be equal to 1 over kr plus kf. And so what that means then in my expression that I have written down in terms of how my x changes with time, and if I rewrite that using this tau, what I get is x is equal to x naught e to the negative t over tau. And so what has this done for us now? Well, what this means is that the tau represents how long it takes for a reaction to progress from x naught to about 1/3 of what x naught was. And how do I know that? Well, let's do the thought experiment. Let's let t, like the time, equal to tau. And so what that does here then is I would say, well, x is equal to x naught, e is equal to negative tau over tau, which means that my x is equal to x naught e raised to the power of negative 1. And e is, if we're going to approximate to a really simple number, we're going to round up to the nearest whole number, then e is roughly equal to 3. So what that means is that at that time tau, we basically have 1/3 of x naught, meaning that we've progressed this reaction to about 2/3 the time to completion. And so that's essentially what tau is trying to quantify. And this would be the value that you would quote as to how long it takes for something to reach equilibrium. You would basically give this time constant as that value. And the reason why we say until we get to this point where we only go 2/3 of the way to completion, and I'll illustrate it using the same plot that I had before. Here's my concentration of B. Here's my concentration of A. Here's when the temperature shift happens at T is equal to 0. And then what we would say is that these concentrations, they move forward and they move towards an asymptote, but it would take a very long time for it to actually hit whatever equilibrium expression or equilibrium value that we say it does. And so whenever we do these calculations using integrated rate law expressions, we set t as t goes to infinity. But of course we don't have that long to wait. And so instead we just quote, how long does it take until we get to, basically it's gone 2/3 of the way to get to this value, to this equilibrium value. And so we started at x naught. We're trying to find the value that it gets to x naught over 3. And so then this is then what tau represents, is this time to go between
these two values, and I could draw the exact same thing down here, where here I've got the value of x naught, I have my value of x naught over 3, and so then my tau is then equal to this time frame. That then tells me, or gives an indication as to how long this reaction takes to go back to equilibrium. And so you can imagine that if my rate constants were very, very, very large, then my tau is going to be a very small number, meaning that if the reactions goes very fast in both directions, then I'm going to reestablish equilibrium very quickly. And if my rate constants are very, very, very small, then my tau is going to be then much larger, and it's going to take far longer for the system to re-achieve equilibrium. Alright, so now that we have an expression for the time constant, which represents then how long it takes for the system to reestablish equilibrium, let's now actually calculate what are the new equilibrium concentrations and also calculate what is that time constant tau. So here I've actually got a plot of what this equilibrium does to after it hits the temperature shift, which is basically happening right here. This is when T is equal to 0, and then after that, what we saw, or what we talked about before in the setup of the problem, was that that's when my equilibrium constant K, that's when it goes from 2 to 1. And so let's now calculate what is our new equilibrium concentrations. And so in that case, this just involves writing an ice table. So I've got an equilibrium between A and B. So I'll write ICE, representing the ice. Concentration of A naught over 3 is my initial concentration of A. 2A naught over 3 was my initial concentration of B. Both of these, the A we know gains x naught, the B is going to subtract x naught. And so at equilibrium we have A naught over 3 plus x naught, and for B it's concentration of A naught, or 2A naught over 3 minus x naught. And that's something, again, that's plotted here on the right-hand side, or sorry, on the left-hand side, where in red I've got my concentration of B, and in blue I have my concentration of A. And we can see that my B decreases and my A increases, which is reflected in my equilibrium constant, capital K, going from 2 to 1, meaning that we expect the reactants to get bigger and the products to get smaller as my rate constant decreases. And again, where my x naught fits into all of this is, again, the x naught is the difference between the two equilibria. So there's my x naught there, and this is, again, here is my x naught here, which represents the distance between my initial, which is what I have written down here, and my final, which is just denoted here in my change, which is what I have written down here, and I'll add the naught into that case. So my next step then is just to apply standard equilibrium values. So here's my equilibrium, or my equilibrium constant at the new equilibrium, and that's equal to the concentration of B at the new equilibrium divided by the concentration of A at the new equilibrium. So my K at this new equilibrium is equal to 1, and that's equal to, well, my concentration of B at the new equilibrium is just 2 times A naught over 3 minus x naught, and that's divided by concentration of A naught over 3 plus x naught. I multiply both sides by this denominator, and so what I get is concentration of A naught over 3 plus x naught, and that's equal to 2 A naught over 3 minus x naught. I then continue and solve. I'm going to move this minus x naught on the right hand side to the left hand side, this A naught over 3 over to the right hand side. So I'm going to get 2x naught is equal to 2 A naught over 3 minus A naught over 3, which means I have x naught is equal to A naught over 6. And so this value, this A naught over 6, this should start to make a little bit more sense with how I've drawn the figure here, which gives you the basic answer as to what is going on. Because if I continue and I just say, well, the actual equilibrium value here, well, now I can write A naught over 3 plus A naught over 6, and what that gives me then is equal to A naught over 2. And my 2A naught over 3 minus A naught over 6, well, that's also equal to A naught over 2. And that should make perfect sense in intuitively as well, because we've set our equilibrium expression such that my K is equal to 1, which means my concentration of B has to be equal to my concentration of A. And so that's why then both of these lines here that I've got on my plot, like they both beat each other. My concentration of B decreases until it meets the concentration of A as it increases. And so then the next question that we could ask is how long does this process take? How do we quantify how long this process takes to achieve this new equilibrium? And so in this case then, this is where we'll bring tau back in. And so we can then say, well, our rate constant K, our equilibrium constant K, well, this is equal to Kf over Kr. And we need to start quantifying what our rate constants are so we can calculate tau. And so we know that's equal to 1. And so that tells us then that Kf is equal to Kr after this temperature change happens at T is equal to 0. And so if we were to calculate our tau, then remember our tau is equal to the inverse of Kr plus Kf. And so then since we know Kf is equal to Kr, we can say our tau is then equal to Kr plus Kr, which means that our tau is equal to 1 over 2 Kr. And so where does that fit onto this plot? Well, if you notice down here, I've multiplied my time, or my scale of my time is Kr times T, which means that on this plot, if I want to take this tau, this time constant, and actually plot on this plot, to get a time out of it, then I'm actually going to multiply it by Kr, which means that my tau on this plot is equal to 1/2. And so where that puts me here is, here's my 1/2. So there's my spot on this plot where I'm saying that's where the value with which I've gone from x0 to x0 divided by roughly about 3. Really it's about by e, but we can just say by 3. And so then that time then is, or that tau then represents this time, how long it takes to go from t is equal to 0 to get to this point where I've gone to about x0 over e. Or if you want to think in terms of a number, then it's just over 3. And again, that's how we would quantify how long it takes for this process to occur, to go from one equilibrium to another once we shift our temperature such that our equilibrium constant moved, in this case, from 2 to 1. In summary, many processes must take into account both backwards and forwards reactions. Both should be included in the rate law expression. Furthermore, the equilibrium constant K can be related to the rate constants for a process. And finally, as systems move to equilibrium, one metric that quantifies the time it takes to reach equilibrium is the time constant, denoted as tau, which depends on the rate constants for the reaction. Welcome to Lecture 18. In this lecture, we will quantify integrated rate law expressions for multi-step reactions. This lecture will be divided into 2 parts. In the first part, we will introduce what is a multi-step reaction. We will define what is an elementary reaction and calculate integrated rate law expressions for multi-step reactions. We will also introduce the rate-determining step. Next, we will demonstrate 2 common approximations used to simplify multi-step reaction mechanisms. The first is when equilibrium are involved, and the second is called the steady state approximation. The overall chemical reaction for a given process is typically written as some set of reactants, denoted here as A, which produces some set of products, P. However, many chemical reactions occur in a series of steps. A reaction mechanism is a collection of individual steps that transforms reactants to products. For example, the above reaction may in fact involve an intermediate, I, where the reactants A first turn into this intermediate before reacting again to become the product P. Since a reaction seldom takes place according to the balanced chemical reaction, the challenge is to identify the individual steps. Consider the decomposition of hydrogen peroxide, where 2 hydrogen peroxide molecules decompose into 2 water molecules and an oxygen molecule. When the reaction is catalyzed by iodide ions, the rate law is expressed as the rate being equal to a rate constant K times the concentration of hydrogen peroxide times the concentration of the iodide ions. The reaction mechanism potentially follows these 2 steps. The first involves a reaction between hydrogen peroxide and an iodide ion to form water and IO-. And in the second part, the second hydrogen peroxide molecule reacts with the IO- formed in the previous step and results in a second water molecule, the oxygen molecule, and regenerates the iodine ion. In the correct reaction mechanism, each step is an elementary reaction. An elementary reaction is one that follows what actually happens at the molecular level, with no intermediates. For elementary reactions, the order of each component in the rate law expression follows the stoichiometry of the balanced reaction. Recall that it was previously stated that the order cannot be determined from stoichiometry. The certainty of this previous statement is now being amended, since we were talking then about overall reaction mechanisms. The stoichiometry indicating the order of a component is only true for elementary reactions. Using our peroxide decomposition reaction example, assuming we have the correct mechanism and they are elementary reactions, we can then write the rate law expressions using the stoichiometry of the balanced chemical reactions. So, for the first step, the rate law expression can be given as the rate being equal to a rate constant times the concentration of hydrogen peroxide times the concentration of iodide ions. And for the second step, the rate law expression can be expressed as the rate being equal to a rate constant times the concentration of hydrogen peroxide times the concentration of IO-. Now that we have this basic understanding of what is a multi-step reaction and what is an elementary reaction, let's now use that understanding to calculate integrated rate law expressions for a simple two-step reaction. And so in this case, what we have is this restriction enzyme, EcoRI, and what it does is catalyzes the cleavage of DNA. And so what we start with is some supercoiled DNA, and then that becomes this open circle DNA, which then finally results in linear DNA. And so what we're going to do then is we want to calculate the integrated rate law expressions for these three components. And to do so, what we're going to do is, for this example, we're going to assume that each of these steps are elementary reactions and that the reverse reactions are very slow. And that if we start with some initial conditions, in this case if we start with only the supercoiled DNA and then we have no open circle or linear DNA, we're going to then determine the integrated rate law expressions for these three components. Our strategy for this will involve solving for two of the rate law expressions, and then using these initial conditions, we're then going to be able to solve for the third one. And so, just to do with the setup, all three of these integrated rate law expressions look like this. We have the rate of change of our supercoiled DNA with respect to time, and what that equals to is the negative of the first rate constant times the concentration of the supercoiled DNA. For a second rate law expression, this has to do with the open circle DNA, and this one is going to be a combination of, we have it coming in from the supercoiled DNA, and so we have some rate constant, the Kf1 times the supercoiled DNA, and from that I'm going to subtract off, this is the consumption of the open circle DNA to linear DNA, and so that's the second rate constant times the open circle DNA. And then finally I have the rate of change of the linear DNA with respect to time, and that's simply equal to the second rate constant times the concentration of the open circle DNA, because this is then the consumption of the open circle to become the linear DNA. The final thing that we can actually write about this is that we can say that in our system we have a total amount of stuff in the system, and that's basically determined by the amount of the supercoiled DNA that we start with. And so at all times in the system, then we have the concentration of the supercoiled plus the concentration of the open circle plus the concentration of the linear DNA must equal to this initial amount of supercoiled DNA that we started with in the system. And so now we have this series of four equations that we can use, and we're really just trying to solve for what is this concentration of sup, this concentration of open circle, and this concentration of linear. And so the strategy that we're going to employ is that we're going to solve two of these differential equations, namely this first one and the second one, because once we do, then in this fourth equation that we have down here, we can actually solve for the linear DNA by just saying, well, that's just the original amount of the supercoiled DNA minus the supercoiled DNA at any given time t minus the concentration of the open circle DNA at time t. And we find both of these, like the supercoiled at any time t and the open circle at any time t, by basically just solving for equation 1 and equation 2. So this is the strategy that we're going to employ to solve for the three integrated rate law expressions, one for each of these components. So let's put this strategy into practice. Let's solve the integrated rate law expression for this first equation, where we're going to find this concentration of the supercoiled DNA. So that's d concentration of supercoiled by dt, and that's equal to the negative of the first rate constant times the concentration of the supercoiled DNA at any given time t. I'm going to divide both sides by the concentration of the supercoiled DNA and multiply both sides by dt. And what that gives me is the d concentration of supercoiled divided by the concentration of supercoiled, and that's equal to the negative of the first rate constant times dt. And if I integrate both sides, on my right hand side I'm going to integrate between 0 and t. On my left hand side I'm going to integrate between the initial concentration of the supercoiled DNA, and then the upper bound is my concentration of my supercoiled DNA at a given time t. And what that leaves me with is, on the left hand side, the natural logarithm of supercoiled DNA evaluated between the initial concentration of supercoiled DNA and the concentration of supercoiled DNA at a given time t. And on my right hand side I have negative of the first rate constant times t, and this will be evaluated between 0 and t. After I apply my fundamental theorem of calculus, what I get is my natural logarithm of my supercoiled DNA minus the natural logarithm of my initial amount of supercoiled DNA. And on my right hand side I have the negative of the first rate constant times t minus 0. I continue to simplify. On my left hand side I have the natural logarithm of the supercoiled DNA divided by the initial concentration of the supercoiled DNA, and that's equal to, on the left hand side, the negative of the first rate constant times t. Finally, I can then solve for the concentration of supercoiled DNA by taking the exponent on both sides. That eliminates my natural logarithm, so I have my concentration of supercoiled DNA, and that's equal to e raised to the power of the negative of the first rate constant times t. And then if I multiply both sides by the concentration, or the initial concentration of my supercoiled DNA, then I get the concentration of the supercoiled DNA being equal to the initial concentration times e raised to the power of negative kf1 times t. So we've now solved for this first one. We're now going to do this second one. And so to solve for this one, I'm going to employ a slightly different strategy than we've been using before to solve integrated rate law expressions. And I'll show you that in a second. First of all, let's just write out our differential equation, where we have the rate of change of the open circle DNA with respect to time, and that's equal to the first rate constant times the supercoiled DNA minus the second rate constant times the open circle DNA. And what I'm going to do is I'm going to move this second term, the whole thing, I'm just going to add that term to both sides. And so what that leaves me with is I've got my rate of change of my open circle DNA with respect to time, and to that I'm going to add the second rate constant times the concentration of open circle DNA, and that's equal to the first rate constant times the concentration of the supercoiled DNA. Now the first substitution I'm going to do is that we actually have a solution already for this concentration for supercoiled DNA for all time t. And so I'm actually just going to plug that right in. So I've got on my left hand side my concentration of my open circle DNA, the derivative with respect to time, plus the second rate constant times the concentration of open circle DNA, and that's equal to the first rate constant times my initial concentration of supercoiled DNA times e raised to the power of the negative of the first rate constant times time. The second substitution I'm going to make is that I'm going to multiply both sides by a factor of e raised to the power of the second rate constant times time. And the reason why I'm doing this is so that I can very easily solve for the integral here on the left-hand side. And so let me demonstrate how that's going to be true. So let's pretend that the answer to that integral, once I eventually do it to the left-hand side, well, that's equal to the concentration of open circle DNA times e raised to the power of the second rate constant times time. And so then to test this, if this is actually the antiderivative, then let's take the derivative of this thing with respect to time. What does that give me? Well, I would have to apply the product rule to this because both these factors, they are both varying in time. So I would have to say the first times the derivative of the second, so the first is the concentration of open circle DNA, times the derivative of the second, so I get a factor of the second rate constant pulled down, and that's times e to the raised to the power of the second rate constant times time. And to that I'm going to add the second times the derivative of the first. So the second is e raised to the power of the second rate constant times time, and that's times the derivative with respect to time of the first term, so d concentration of open circle DNA by dt. Well, these two terms that I have over here that I've just written out, these two terms are exactly what I have written down over here on the left-hand side after I distribute in this factor of e raised to the power of the second rate constant times time. And so what I can actually do then at this point is I can say that this left-hand side, well, that's equal to d by dt applied to the concentration of open circle DNA times e raised to the power of kf2 times time. On my right-hand side, I would still write the concentration of supercoiled DNA, or the initial concentration of supercoiled DNA, times the first rate constant times e raised to the power of the second rate constant minus the first rate constant, because all I'm doing is that I'm just joining together these two exponential terms, and when I multiply two exponential terms, then it's the same as summing or subtracting their exponents, and that's going to be multiplied by time. And then at this point, this is now where I'm going to apply that integral. I'm going to do the integration. And so on my left-hand side, I have an integral. On my left-hand side, or my right-hand side, I'm going to be applying an integral from 0 to t, and I do the same thing on my left-hand side. However, this integral on the left-hand side is now very straightforward, because what I'm doing is I'm applying an integral to a differential term. I have my integral term, and then I'm going to immediately be doing a differential to it. And that's the same thing as saying I'm going to add some value, and then I'm going to subtract that same value from it. Whatever integration does, differentiation undoes. And so essentially what I have on my left-hand side is then just the concentration of open circle DNA raised, or e raised to the power of the second rate constant times time, is what the result of that integration and then immediate differentiation is. On my right-hand side, I would evaluate this integral as I normally would. And so I'm going to have concentration of supercoiled DNA, or at least the initial concentration, times the first rate constant. And really where this integral applies is to this exponential term. And the antiderivative to this exponential term means that I have a factor of the second rate constant minus the first rate constant in the denominator of this fraction. And then I have e raised to the power of the second rate constant minus the first rate constant times time. And this is going to be evaluated between 0 and t. I will now apply the fundamental theorem of calculus to my right-hand side. And so what that gives me is my initial concentration of supercoiled DNA times the first rate constant divided by the second rate constant minus the first rate constant. And then here is where the application of the fundamental theorem of calculus will be done. I have e raised to the power of the second rate constant minus the first rate constant times t minus e raised to the power of 0. And of course, still on my left-hand side, I have my concentration of open circle DNA. And what I'll do at this point is I'll also just divide both sides. So I'll isolate from my concentration of open circle DNA, which means that I'll divide both sides by e raised to the power of the second rate constant times time, which means that on my right-hand side, I get e raised to the power of negative of the second rate constant times time. What I'm also going to do is I can also just immediately cross off this e raised to the power of 0, and I know that that's going to be equal to 1. And what that means is that then solving for my concentration of open circle DNA, that's now equal to my original concentration of supercoiled DNA times the first rate constant divided by the second rate constant minus the first rate constant times e raised to the power of the second rate constant minus the first rate constant times time minus 1, and that's multiplied by e raised to the power of the second, or the negative of the second rate constant times time. I'm going to do one more simplification step here on the right hand side, where I'm going to multiply in this exponential term that's outside the parentheses. And so what that leaves me with is the concentration of supercoiled DNA, or at least the initial concentration, times the first rate constant divided by the second rate constant minus the first rate constant. And then when I multiply in this term into both of these terms, when I distribute it in, well, at least for this first exponential term, because I have minus kf2 times time, and here I have a kf2 times time, then what that does is that basically cancels out that term, because when you multiply two exponentials together, in this case I'm going to subtract those two terms from each other. What that leaves me with is then that first term is just simply going to be e raised to the power of the negative of the first rate constant times time. Completing the application of the distributive principle simply means that I'm just going to subtract off e raised to the power of the negative of the second rate constant times time. So taking stock, we've now just finished calculating the concentration of the open circle DNA at any given time t. So if we go back to our strategy that we had before, we have now done this first step and we've now done this second step. And when we said that the third part of our strategy was that as soon as we've calculated the concentration of open circle DNA for all time t and the concentration of supercoiled DNA for all time t, we can then use this expression, meaning using the initial conditions of our system, where we know that we only have supercoiled DNA, or at least the total amount of moles in the system is based on the initial amount of supercoiled DNA. And so now that we know the concentration of supercoiled DNA at all time t, we know the concentration of open circle DNA for all time t, and that this concentration, or this initial concentration of supercoiled DNA is a constant, then we can solve for the concentration of linear DNA. So let's now make those substitutions and simplify. So what that means then is that I'm going to have my concentration of linear DNA, and that's equal to the initial concentration of my supercoiled DNA. From that I'm going to subtract off the concentration of supercoiled DNA, and from that I'm also going to subtract off the concentration of open circle DNA. That means then my concentration of linear DNA is equal to the initial concentration of supercoiled DNA, and now I can make those substitutions where I know the concentration of supercoiled DNA for all time t is the initial concentration of supercoiled DNA times e raised to the power of the negative of the first rate constant times time. And then from that I can also then subtract off the concentration of the open circle DNA at all time t, which is just equal to the initial concentration of supercoiled DNA times the first rate constant divided by the second rate constant minus the first rate constant. And all that is times e raised to the power of negative of the first rate constant times time minus e raised to the power, or the negative power, of the second rate constant times time. The first simplification that I'm going to make in order to solve for the concentration of linear DNA is that I'm going to distribute out all of these initial concentrations of supercoiled DNA, since there's one at the beginning of each of these terms. So I'm going to have the concentration of supercoiled DNA sitting out here in the front, and then I have all my remaining terms. I'm going to have 1 minus, and then I've got e raised to the power of negative of the first rate constant times time, and from that I'm going to subtract off the first rate constant divided by the second rate constant minus the first rate constant, and that's all times e raised to the negative of the first rate constant times time minus e raised to the power of the negative of the second rate constant times time. You notice that I've inserted this huge gap, and so what I'm going to do also in this, and this is a part of the second simplification I'm going to make, or ultimately make, is that I'm going to multiply in this spot here a term that's the second rate constant minus the first rate constant divided by the second rate constant minus the first rate constant. So I'm essentially multiplying that second term by 1, even though I have the second rate constant minus the first rate constant divided by itself. But the reason why I'm doing that is because I'm trying to create a common denominator. So I have this denominator here and I have this denominator here. And it's so that I can now join together the second and the third terms. My next simplification step will then therefore be to distribute in these rate constant terms. So my left-hand side is still my concentration of my linear DNA, and that's equal to my original concentration of supercoiled DNA. I still have 1. In this case, now I'm going to be distributing these rate constant terms. So I'm going to have minus the second rate constant divided by the second rate constant minus the first rate constant times e raised to the power of the negative of the first rate constant times time. Because I'm distributing in this minus sign, I have minus here, but then I have minus minus, which gives me a plus. So I'm going to have plus. In this case, I'm going to have the first rate constant divided by the second rate constant minus the first rate constant. And this again is equal to e raised to the power of the negative of the first rate constant times time. With this next term, again, I'm going to be distributing in all of these rate constants and the minus sign. So for the first term, I have minus kf1 divided by the second rate constant minus the first rate constant, and that's multiplied by e raised to the power of the negative of the first rate constant times time. And then again, because I'm going to be distributing in this minus sign, I have minus minus here, which gives me a plus. Then I have my first rate constant divided by my second rate constant minus my first rate constant times e raised to the power of the negative of the second rate constant times time. We can simplify this expression that I've just written out now because I have a positive first rate constant and here I have a negative of the first rate constant. These exponentials in these two terms, they're both the same and they're both divided by the same denominator. And I have a plus and a minus. And so what that means is that they cancel each other out. And so the final expression that I'll write out here for my concentration of my linear DNA is equal to my initial concentration of my supercoiled DNA, and that's going to be equal to 1, and I'll write it as a plus because what I'll start with is the furthermost right-hand term, which is just the first rate constant, e raised to the power of the negative of the second rate constant times time, and that is going to be subtracted from the second rate constant times e raised to the power of the negative of the first rate constant divided by, or times time, and all that is then divided by the second rate constant minus the first rate constant. And what you may have already noticed here with this denominator is that if we had our two rate constants and if they were equal, then that implies that this denominator then, or that would result in this denominator then being equal to 0. And in fact, actually, this top part, if both our rate constants were the same, this top part would actually also be equal to 0. And so what we end up with this is this unphysical solution with our result because the second term then ends up being 0 over 0. And so we would probably then set a restriction on the solutions to this since we don't want an unphysical result, or we don't want to handle unphysical results with this, is that we would have to then state that our two rate constants cannot be equal in order to get a valid solution out of this derivation for the concentration of the linear DNA, or for our product. With this restriction in mind on the values of our two rate constants, let's now look at a plot of these integrated rate law expressions where we've set the rate constants to be close to being equal to each other. And what we see in this plot is pretty much what we would expect to see, where we have our supercoiled DNA, that's going to be in blue, our open circle DNA, that's going to be shown in red, and then finally our linear DNA, that's shown in green, and that's what we've plotted over here. We've got linear, we've got open circle, and we've got our supercoiled. And it's essentially exactly what we would expect to see, or would look like something that we would imagine we would see, where since the supercoiled is the first part and it's going to be just consumed, and as it turns into open circle, then we see this exponential decay, which is this term that we see right here. We see that we start with some amount, and there's some exponential decay that happens. In terms of the open circle DNA, we had that because it's our intermediate, we have it being produced from the supercoil as it's converted, and then it's also consumed. And so we would expect that at short times t, which is what I'm trying to indicate here, so this is small t,
then what we would see is that we would see this growth in this intermediate because we don't have very much of the open circle DNA to convert into the linear DNA, and so the rate of the growth is just dependent upon how much supercoiled has turned into the open circle. But then after a while, so any time that's now moving out from this maxima, which is then going to occur right here, then what happens is that since the supercoiled has now been consumed, then that means there's no more open circle that's now coming into play. And so then now it's just open circle that's being consumed. And so we get then this decay that happens as it's converted into the linear DNA. And then of course for the linear DNA, the growth of it starts out to be very small, which is what we can see right here. So it's not exponential growth that immediately matches the supercoiled because there's the intermediate that it has to move through first. But eventually it does move into exponential growth, and that at large times t, which is basically these times that are out here, we see that since everything is converted into the linear DNA, then it basically is all that's left inside our system. All the supercoiled is converted into open circle, and then it's all converted into linear DNA. In that two-step example, we can see that initially the production of the intermediate was faster than its consumption, so the concentration of the intermediate grew. Eventually, as the amount of the reactants decreased, so does the rate of production of that intermediate. Therefore, over time, the consumption of the intermediate outgrows the rate of its production, and therefore its concentration will then begin to decrease. This trend means that there is a time at which there would be a maximum amount of the intermediate that will exist in the system. It is useful to be able to determine the time at which that maximum concentration occurs. If the integrated rate law expression is known, then setting its derivative with respect to time to be equal to 0 will give when the concentration of the intermediate will be at a maximum. So, given that we can use the first derivative test to find local extrema, let's then apply that concept to determine the maxima for our intermediate. So returning again to our example where we're looking at our reaction where we start with supercoiled DNA that turns into some intermediate, which in this case is open circle DNA, that then converts into linear DNA. Our question then is how long after the initialization of the reaction should we, say, extract the open circle DNA to get a maximum amount? And so the premise behind this question is that once you initiate this reaction, you start with supercoiled DNA. What you want in the end is to have the open circle DNA. You don't really need the linear DNA in the end at all. And so the question is then asking, after you initialize, at what point do you then stop the reaction, or what point do you do your extraction so that you can then get out the maximum amount of the component that you actually want, this open circle DNA. Then let's apply our first derivative test. What that means is that I'm going to set the rate of change of the open circle DNA with respect to time to be equal to 0. And since I know my integrated rate law expression for my concentration of open circle DNA, I'm just going to plug that in. So d by dt of the first rate constant divided by the second rate constant minus the first rate constant, and that's going to be times the exponent raised to the power of negative of the first rate constant times time minus the exponent of the negative of the second rate constant times time, and that again is going to be equal to 0. Applying the differential to this expression, well, I can basically take out the constants, which is just these rate constants, the kf1 divided by kf2 minus kf1. And so then I can then apply my differential to the first term. I have an exponent raised to some power, so I can take down then the constant in that power. So I'm going to get minus the times the first rate constant times e raised to the power of the negative of the first rate constant times time. I get the same thing. I get e raised to some exponential, and so that I can get the constant and then exponential coming down, which means that in this case I have minus minus, which gives me plus the second rate constant, e raised to the power of the negative of the second rate constant times time. And again, that's all equal to 0. And so in this case, what I can do is I can divide both sides by the first rate constant. I can multiply both sides by the second rate constant minus the first rate constant. And so I can essentially then just cross off these two terms because they're going to be multiplied by 0 on the other side. And so I can then rearrange where I can move then this negative term
and I can move it to the right-hand side. And so what that leaves me with is the second rate constant times e raised to the power of the negative of the second rate constant times time, and that's equal to the first rate constant times e raised to the power of the negative of the first rate constant times time. I'm going to continue to simplify, so I'm going to divide both sides by the second rate constant, and I'm also going to divide both sides by e raised to the power of negative kf1t. And so essentially what I'm trying to do is move this term over to the left-hand side, and I'm going to move this term over to the right-hand side. And so what I'm left with is e raised to the power of the negative of the second rate constant times time times e raised to the power of this first rate constant times time. And the reason why there's no negative sign here is that when I divide both sides by e to the negative of kf1t, well, 1 over e raised to the power of a negative of an exponent is just e raised to the power of the positive of that exponent. On my right-hand side, I get kf1 divided by kf2. I continue to simplify. I have these two exponent terms on the left, and so it's the same as essentially taking, when I multiply them together, then I can add together their exponents. So I get e raised to the power of kf1 minus kf2 through the distributive principle, and that's multiplied by t. And on my right-hand side, I still get kf1 over kf2. Now I can take the natural logarithm of both sides, and so what I get on my left-hand side is kf1 minus kf2. I'll re-add in my terms up here, and that's still times t. And over here I have the natural logarithm of kf1 divided by kf2. Finally, I'm going to solve for t. And so what that means then is that my t max, because that's what I've always been solving for here since I set my derivative to be equal to 0. But my t max is then equal to 1 over kf1 minus kf2 times the natural logarithm of the first rate constant divided by the second rate constant. Now let's apply this result to our plot here to see if we get something that's consistent. So when I drew this plot, I said that the relationship between the two rate constants is such that the second rate constant is about 99% of the first rate constant. And so what that means for our expression here, I'll do this in blue, is that when I substitute in for t max, then I'm going to say, well, 1 over, and I'm still going to have the first rate constant, but from that I'm going to subtract off 0.99 k1, or the first rate constant, just to substitute in for the second rate constant to simplify this. And the same thing with our natural logarithm. I'm going to have the natural logarithm of the first rate constant divided by 0.99 times the first rate constant, meaning I'm substituting that in for the second rate constant. In that case, I can then cross off my first rate constant here, and I'm going to distribute out, or I'm going to basically do the math there for that term underneath. So I'm going to have t max is equal to 1 over 0.01 times the first rate constant times the natural logarithm of 1 over 0.99. And in the end, what I'm going to get is my t max is going to be equal to 1.005 divided by the first rate constant. And if we go and look up at our plot, we can see that our x-axis is denominated in units of kf1 times time. And this was just so that I can do a trick like this, where I can just set a relationship between the two rate constants so I can plot these diagrams. But I can then just write my solution here as that first rate constant times t max, and that's equal to 1.005. And if we look at our plot here, well, our maximum is going to be right here of this intermediate, which again is the open circle DNA. And if I draw this down to the line, well, that's approximately equal to 1, which is what our answer is. And so based on the solution, we can see the consistency from the solution that we got for the integrated rate law expression for the concentration of open circle DNA, leading us back to our solution here, that if we knew our forward rate constant and the relationship between the two rate constants, we would be able to determine what is this maximum, or what is the time at which we would have a maximum amount of